everyone, welcome to Simplilearn's YouTube channel. Today, we bring you the Data Science Full Course, a comprehensive learning journey designed to take you from core data concept to advanced data science applications used in real-world businesses environments. Now, data science is the practice of turning raw data into meaningful insights using statistics, programming, and machine learning. It is widely used across industries such as technology, finance, healthcare, retail, and marketing to predict outcomes, optimize processes, and support strategic decision-making. What makes data science powerful is its ability to combine data analysis with predictive modeling, helping organizations move from descriptive reporting to forward-looking insights. In this course, we start with the fundamentals, understanding data, statistics, and programming, and gradually moving on to advanced topics such as machine learning, model evaluation, and real-world use cases. You won't just learn theory. You will learn how to apply data science concept practically using tools and workflows that are commonly expected in data science and analytics roles. And by the end of this course, you will be able to clean and analyze data sets, build and evaluate machine learning models, visualize insights, and communicate results effectively to both technical and non-technical stakeholders. Having said that, let's take a look at the agenda for this course. We will be having a total of 12 modules in this full course. We will start off this course with the first module as an introduction to data science. Here, we will learn the basics on what is data science, how it works, and the foundations on which the entire ecosystem is laid on. Next, we move on to module 2 about the programming fundamentals for data science. Now, once we have a key understanding of the fundamentals, we'll move on to our next module, which is Python Foundations for Data Science. Now, here, we will focus on building strong programming basics using Python, which is the primary language used across data science, analytics, and machine learning workflows. Now, with Python fundamentals in place, we will transition into next module, which is data handling with NumPy and Pandas. Now, in this module, you will learn how to work with real data sets, loading data, cleaning it, transforming it, and preparing it for analysis using industry standard libraries. After that, we will move on to our next module, which is exploratory data analysis or EDA. Now, this is where data starts telling a story. You will analyze patterns, trends, and outliers using statistics and visualizations to understand what the data is actually saying. Now, once you're comfortable exploring data, we will strengthen your analytical foundation with statistics and probability for data science. Here, you will learn the statistical concepts that power data-driven decisions, including probability, distributions, and hypothesis testing. With a strong base in data and statistics, then we will step into machine learning fundamentals. Here, you will understand what machine learning is, how models learn from data, and how the overall machine learning workflow is structured. Building on those fundamentals, we will move into supervised learning algorithms. Here, you will work with models that learn from labeled data, such as regression and classification techniques, used widely in real-world business problems. Next, we'll transition into unsupervised learning algorithms, where you will explore techniques that identify hidden patterns in data, such as clustering, dimensionality reduction, without predefined label. After learning about how to build models, it's important to know how well they perform. That brings us to model evaluation and optimization, where you will learn how to measure model performance, compare models, fine-tune them, and achieve better accuracy and reliability. With evaluation techniques covered, we will then move on to advanced topics in data science, where you will be introduced to advanced and emerging areas such as time series analysis, natural language processing, and ethical consideration in data science. Now, once the technical concepts are in place, we will apply everything you have learned in real-world data science use cases, where you will solve practical business problems across domains like marketing, finance, and customer analytics, bridging theory with real-world applications. And finally, we will conclude with tools, deployment, and career readiness, where you will learn about data science tool ecosystem, basic deployments concept, and interview preparation to help you transition confidently into a data science role. Now, if these are the type of videos you would like to watch, then hit that subscribe button with the bell icon to get notified whenever we host. The question is, which of the following best describes the primary goal of data science? Your options are writing complex code using Python, storing large amounts of data, extracting insights and making predictions from data, or creating dashboards only. Let me know your answers in the comment section below.
Do you know how Netflix decides which movies suit your taste better? Or how Google Maps can provide routes with low traffic at given moment in seconds? This is all possible thanks to data science. The popularity of data science exploded in the 2010s, causing an approximate 15% year-on-year growth in the job market and is expected to grow even higher in the coming decade. Now, what exactly is data science? Data science is the field of study that works with massive amounts of data, utilizing relevant tools and techniques to derive valuable data. The day-to-day work of a data scientist involves collecting, analyzing, and interpreting this data to help businesses achieve their goals. Companies across various industries generate vast amounts of data, so its application range all the way from education, healthcare, and entertainment to finance and marketing. When it comes to the subfields of data science, it comprises many technologies like artificial intelligence, machine learning, natural language processing, and deep learning. Each of them fulfilling different purposes and having varied functionalities. The role of a data scientist was voted the sexiest job of the 21st century, and it is for a good reason. The demand for professionals who can make sense of vast amount of data is more than ever in this day and age. Companies like Microsoft, Google, and Amazon hire data scientists as they deal with problem-solving models involving massive amounts of data daily. This is why data science professionals are in high demand, with average salaries going as high as $1,864 per annum. With 2.5 million terabytes of data being transferred over the internet on a daily basis, the data science industry is slated to grow even higher, promoting further innovation and job opportunities.
Hello all, welcome to another informative video from Simplilearn. Imagine this, you are scrolling through job listings and you keep seeing two roles everywhere, data analyst and data scientist. They both sound similar, both deal with data and both seems to be in high demand. So what's the difference? And more importantly, which one is right for you? That's where things get confusing. Many people think a data scientist is just an advanced version of data analyst. But the reality is, these roles have very different responsibilities, required skills and salary potential. And choosing the right one can shape your entire career. So let's understand the difference between them through a simple example. Let's take the example of Netflix. Here, data analysts and data scientists play different but equally important roles. A data analyst looks at past viewing trends, identifying which shows are popular, when people watch the most, and how long they stay on the platform. So their insights help Netflix decide which shows to promote on the homepage or in trending lists. Meanwhile, a data scientist takes it a step further by building the recommendation systems itself. They create predictive models that analyze your watch history and preferences to suggest shows you're most likely to enjoy. So in simple terms, data analysts focus on understanding past behavior, while data scientists predict and shape future experiences. In this video, we'll break down the key differences between data analysts and data scientists, covering what each role does, the tools and technologies they use. We'll compare their skills, educational paths, and career growth opportunities. We'll also look at salary compensations in the US and India to see who earns more and why. So let's start with, what does a data analyst do? Number one is collecting data. So a data analyst's first task is gathering information from different sources. This could be company databases, customer feedback, market research, or even publicly available data. And the goal is to get a complete picture of what's happening. Now next is processing and cleaning data. So raw data can be messy. Analysts spend time organizing it, fixing errors, and removing any irrelevant information. So this step is crucial because bad data leads to bad insights. After processing and cleaning data comes analyzing data. So once the data is ready, the real work begins. Analysts use statistical methods to spot trends, patterns, and relationships in the numbers. This might include forecasting future trends or running predictive models to see what could happen next. After that comes visualizing and reporting. So data alone isn't useful unless it's easy to understand. That's why analysts create charts, graphs, and dashboards to present their findings in a way that makes sense. So well-designed visualization can help businesses quickly grasp key insights. After that comes making recommendations. So data analysts don't just crunch numbers, they provide actionable advice, whether it's improving a marketing campaign optimizing business operations, or cutting costs. Their insights help companies make data-driven decisions. And then comes using powerful tools. So data analysts use a range of tools to get the job done. SQL helps them manage databases. Excel is great for handling spreadsheets, and programming languages like Python or R come in handy for advanced analysis. Also, visualization tools like Tableau or Power BI help turn raw data into meaningful stories. And finally comes working with teams. So data analysts don't work in isolation. Analysts collaborate with marketing, finance, operations, and other teams to ensure their insights align with business goals. So their findings influence everything from budget planning to customer strategies. Now let's see, what does a data scientist do? So again, just like data analysts, data scientists gather data from various sources. But here's the twist. They often work with huge and complex data sets, including unstructured data like text, images, or even videos. They also design and manage data storage systems, ensuring data is easily accessible and secure. After that comes advanced data analysis. So data scientists take analysis to the next level. Instead of just identifying trends, they use machine learning and statistical modeling to predict future outcomes. So if you want to know which customers are likely to leave your service, a data scientist can build a predictive model for you. After that comes building algorithms and models. So this is where the magic happens. Data scientists create and fine-tune algorithms to process massive amounts of data quickly. So these models help businesses automate processes, personalize recommendations, and make data-driven decisions. So as already discussed, how does Netflix recommend movies? It's a data scientist's work in action. After that comes data visualization and communication. So data scientists don't just build models, they also need to explain their findings to non-technical stakeholders. So their visualizations are often more complex and interactive, designed to demonstrate machine learning results and reveal deep insights. Then comes driving product development. So data scientists are crucial in shaping business strategies. So they work with product teams to integrate AI and analytics into products, whether it's improving a search engine, optimizing ad placements, or creating recommendation systems for e-commerce platforms. After that comes mastering machine learning and AI. So unlike data analysts, data scientists are deeply involved in AI-driven solutions. They work on natural language processing, image recognition, fraud detection, and even self-learning systems. So these technologies power innovations across industries, from healthcare diagnostics to self-driving cars. Research and experimentation. So data science is an evolving field, and experimentation is key. Scientists constantly test hypotheses, explore new machine learning techniques, and refine models to improve accuracy and efficiency. And finally, collaboration with teams. So data scientists don't work alone. They team up with engineers, marketing teams, business strategies, and senior leadership to ensure their models are effectively integrated into business operations. So whether it's fine-tuning a chatbot or predicting market trends, cross-functional teamwork is very essential. Now that you know the role of a data scientist and a data analyst, let's move on to the educational requirements for these roles. So we'll start with data analysts. So for data analysts, a bachelor's degree in statistics, mathematics, and computer science or economics is usually enough to land a job. Their coursework typically covers statistics, data management, and basic programming. So most analysts are expected to be proficient in Excel and SQL with some knowledge of Python or R to handle data more effectively. Now for data scientists, this role often requires an advanced degree like master's or PhD, especially for technical or research-focused positions. So data scientists dive deeper into machine learning, artificial intelligence, and advanced programming. Their studies include advanced statistics, data management, and AI-related topics. So proficiency in programming languages like Python, R, or Scala, along with experience in big data tools like Hadoop and Spark, is crucial. So if you enjoy working with data but don't want to spend years in academics, becoming a data analyst might be the right choice. A bachelor's degree plus technical skills like SQL, Excel, and Python can help you land a great job. But if you're passionate about AI, machine learning, and predictive modeling, a data science career could be worth the extra years of study. A master's or PhD will give you the expertise needed for high-level problem solving and algorithm development. So now let's move on to the skills a data analyst and a data scientist needs. So a data analyst is all about understanding past trends and presenting data in a way that helps businesses make decisions. So here's what they need to excel. Number one is statistical analysis and mathematics. So solid foundation in statistics and mathematics is key to interpreting data accurately and drawing meaningful conclusions. Then comes data visualization. So analysts use tools like Tableau, Power BI, or advanced Excel functions to create compelling dashboards and reports. Data manipulation and analysis tools. Now, SQL is a must for querying databases. Excel is used for organizing and analyzing data, and some analysts use Python or R for deeper statistical analysis. After that comes reporting and communication. So it's not just about numbers. Analysts must prepare detailed reports and presentations that clearly explain their findings to stakeholders. Business acumen. Knowing what data matters and how it can solve business problems is crucial for making insights actionable, and also clear communication. So since they often work with non-technical teams also, analysts need to translate data insights into simple business-friendly language. Now let's see the skills needed for a data scientist. So a data scientist, on the other hand, focuses on predicting future trends and building AI-driven models to automate decisions. So their skill set is more technical and research-driven. Number one is advanced statistics and mathematics. So since they create predictive models and algorithms, data scientists need a deeper understanding of probability, linear algebra, and statistical modeling. Machine learning and AI. Now, data scientists build machine learning models to classify data, detect patterns, and make predictions. They work on applications like fraud detection, recommendation engines, and customer churn prediction. So to excel in this, focus on topics such as supervised and unsupervised learning, deep learning, natural language processing, neural networks, and model evaluation techniques. Next comes programming languages. So Python and R are the go-to languages for data science, but Java or Scala can also be used when handling big data. Next, you must be proficient with big data technologies. So as you know, data scientists work with massive data sets that require tools like Hadoop, Spark, and distributed computing to process efficiently. Next comes AI and deep learning. So as AI continues to evolve, many data scientists specialize in neural networks, NLP, natural language processing, and computer vision. Also, data scientists often create new techniques to analyze data in ways that weren't possible before. So their job is more experimental and research-oriented compared to analysts. Also, like analysts, data scientists must present their findings, but they also influence high-level strategic decisions and product innovations. Now let's talk about the salaries. In the United States, data analysts earn an average salary of $81,000 per year, while data scientists command significantly higher pay with an average base salary of $125,000. In India, data analysts earn an average annual salary of 6 LPA, whereas data scientists make approximately 14 LPA. Salaries in both roles vary based on experience, industry, location, and skills, with tech, finance, and healthcare sectors offering the highest pay. So data scientists earn more due to their expertise in machine learning, AI, and big data, whereas data analysts focus on reporting, visualization, and business insights. So that's a wrap, guys. Now you know the key differences between data analysts and data scientists, what they do, the skills they need, and how much they earn. So whether you're drawn to analyzing past trends or building AI-powered models for the future, both careers offer amazing opportunities.
Hello and welcome to this session on data science. My name is Mohan and today we are going to take a look at what this buzz is all about. So now let's talk about the life cycle of a data science project. Okay, the first step is the concept study. In this step, it involves understanding the business problem, asking questions, get a good understanding of the business model, meet up with all the stakeholders, understand what kind of data is available, and all that is a part of the first step. So here are a few examples. We want to see what are the various specifications and then what is the end goal, what is the budget, is there an example of this kind of a problem that has been maybe solved earlier. So all this is a part of the concept study. And another example could be a very specific one to predict the price of a 1.35 carat diamond. And there may be relevant information, inputs that are available, and we want to predict the price. The next step in this process is data preparation, data gathering and data preparation, also known as data munging, or sometimes it is also known as data manipulation. So what happens here is the raw data that is available may not be usable in its current format for various reasons. So that is why in this step, a data scientist would explore the data, he will take a look at some sample data, maybe pick, if there are millions of records, pick a few thousand records and see how the data is looking. Are there any gaps? Is the structure appropriate to be fed into the system? Are there some columns which are probably not adding value, may not be required for the analysis? Very often these are like names of the customers. They will probably not add any value or much value from an analysis perspective. The structure of the data, maybe the data is coming from multiple data sources and the structures may not be matching. What are the other problems? There may be gaps in the data. So the data, all the columns, all the cells are not filled. If you're talking about structured data, there are several blank records or blank columns. So if you use that data directly, you'll get errors or you'll get inaccurate results. So how do you either get rid of that data or how do you fill these gaps with something meaningful? So all that is a part of data munging or data manipulation. So these are some additional subtopics within that. So data integration is one of them. If there are any conflicts in the data, data may be redundant. Yeah, data redundancy is another issue. There may be, you have, let's say, data coming from two different systems and both of them have customer table, for example, customer information. So when you merge them, there is a duplication issue. So how do we resolve that? So that is one. Data transformation. As I said, there will be situations where data is coming from multiple sources and then when we merge them together, they may not be matching. So we need to do some transformations to make sure everything is similar. We may have to do some data reduction. If the data size is too big, you may have to come up with ways to reduce it meaningfully without losing information. Then data cleaning. So there will be either wrong values or null values or there are missing values. So how do you handle all of that? A few examples of very specific stuff. So if there are missing values, how do you handle missing values or null values? Here in this particular slide, we are seeing three types of issues. One is missing value. Then you have null value. You see the difference between the two, right? So in the missing value, there is nothing, blank. Null value, it says null. Now, the system cannot handle if there are null values. Similarly, there is improper data. So it's supposed to be numeric value, but there is a string or a non-numeric value. So how do we clean and prepare the data so that our system can work flawlessly? So there are multiple ways and there is no one common way of doing this. It can vary from project to project. It can vary from what exactly is the problem we are trying to solve. It can vary from data scientist to data scientist, organization to organization. So these are like some standard practices people come up with. And of course, there will be a lot of trial and error. Somebody would have tried out something and it worked and will continue to use that mechanism. So that's how we need to take care of data cleaning. Now, what are the various ways of doing, if values are missing? How do you take care of that? Now, if the data is too large and only a few records have some missing values, then it is okay to just get rid of those entire rows, for example. So if you have 1,000,000 records and out of which 100 records don't have full data, so there are some missing values in about 100 records. So it's absolutely fine because it's a small percentage of the data. So you can get rid of the entire records which have missing values. But that's not a very common situation. Very often you will have multiple or at least a large number of a data set. For example, out of 1,000,000 records, you may have 50,000 records which are like having missing values. Now, that's a significant amount. You cannot get rid of all those records. Your analysis will be inaccurate. So how do you handle such situations? So there are again multiple ways of doing it. One is you can probably, if a particular values are missing in a particular column, you can probably take the mean value for that particular column and fill all the missing values with the mean value, so that first of all you don't get errors because of missing values, and second, you don't get results that are way off because these values are completely different from what is there. So that is one way. Then a few other could be either taking the median value or depending on what kind of data we are talking about. So something meaningful we will have put in there. If we are doing some machine learning activity, then obviously as a part of data preparation, you need to split the data into training and test data set. The reason being, if you try to test with a data set which the system has already seen as a part of training, then it will tend to give reasonably accurate results because it has already seen that data, and that is not a good measure of the accuracy of the system. So typically you take the entire data set, the input data set, and split it into two parts. And again, the ratio can vary from person to person, individual preferences. Some people like to split it into 50-50. Some people like it as 63.33 and 33.3 is basically 2/3 and 1/3. And some people do it as 80-20. 80 for training and 20 for testing. So you split the data, perform the training with the 80%, and then use the remaining 20% for testing. All right. So that is one more data preparation activity that needs to be done before you start analyzing or applying the data or putting the data through the model. Then the next step is model planning. Now these models can be statistical models, this could be machine learning models. So you need to decide what kind of models you're going to use. Again, it depends on what is the problem you're trying to solve. If it is a regression problem, you need to think of a regression algorithm and come up with a regression model. So it could be linear regression. Or if you're talking about classification, then you need to pick up an appropriate classification algorithm like logistic regression or decision tree or SVM, and then you need to train that particular model. So that is the model building or model planning process, and the cleaned up data has to be fed into the model. And apart from cleaning, you may also have to, in order to determine what kind of model you will use, you have to perform some exploratory data analysis to understand the relationship between the various variables and see if the data is appropriate and so on, right? So that is the additional preparatory step that needs to be done. So a little bit of details about exploratory data analysis. So what exactly is exploratory data analysis? It's basically to, as the name suggests, you're just exploring. You just receive the data and you're trying to explore and find out what are the data types and what is the data clean in each of the columns. What is the maximum minimum value? So for example, there are out of the box functionality available in tools like R. So if you just ask for a summary of the table, it will tell you for each column, it will give some details as to what is the mean value, what is the maximum value, and so on and so forth. So this exercise or this exploratory analysis is to get an understanding of your data. And then you can take steps to, during this process, you find there are a lot of missing values. You need to take steps to fix those. You will also get an idea about what kind of model to be used and so on and so forth. What are the various techniques used for exploratory data analysis? Typically, these would be visualization techniques, like you use histograms, you can use box plots, you can use scatter plots. So these are very quick ways of identifying the patterns or a few of the trends of the data and so on. And then once your data is ready, you've decided on the model, what kind of algorithm you're going to use. If you're trying to do machine learning, you need to pass your 80% the training data, or rather you use that training data to train your model. And the training process itself is iterative. So the training process you may have to perform multiple times. And once the training is done and you feel it is giving good accuracy, then you move on to test. So you take the remaining 20% of the data. Remember, we split the data into training and test. So the test data is now used to check the accuracy or how well our model is performing. And if there are further issues, let's say, and model is still, during testing, if the accuracy is not good, then you may want to retrain your model or use a different model. So this whole thing again can be iterative. But if the test process is passed, or if the model passes the test, then it can go into production and it will be deployed. All right. So what are the various tools that we use for model planning? R is an excellent tool in a lot of ways, whether you're doing regular statistical analysis or machine learning or any of these activities. R, along with R Studio, provides a very powerful environment to do data analysis, including visualization. It has a very good integrated visualization or plot mechanism, which can be used for doing exploratory data analysis and then later on to do analysis, detailed analysis, and machine learning, and so on and so forth. Then, of course, you can write Python programs. Python offers a rich library for performing data analysis and machine learning and so on. Matlab is a very popular tool as well, especially during education. So this is a very easy to learn tool. So Matlab is another tool that can be used. And then last but not least, SAS. SAS is again very powerful. It is a proprietary tool and it has all the components that are required to perform very good statistical analysis or perform data science. So those are the various tools that would be required for or that can be used for model building. And so the next step is model building. So we have done the planning part. We said, okay, what is the algorithm we are going to use? What kind of model we are going to use? Now we need to actually train this model or build the model rather so that it can then be deployed. So what are the various ways or what are the various types of model building activities? So it could be, let's say in this particular example that we have taken, you want to find out the price of 1.35 carat diamond. So this is, let's say, a linear regression problem. You have data for various carats of diamond and you use that information, you pass it through a linear regression model or you create a linear regression model which can then predict your price for 1.35 carat. So this is one example of model building. And then a little bit details of how linear regression works. So linear regression is basically coming up with a relation between an independent variable and a dependent variable. So it is pretty much like coming up with equation of a straight line which is the best fit for the given data. So like for example here, y is equal to mx plus c. So y is the dependent variable and x is the independent variable. We need to determine the values of m and c for our given data. So that is what the training process of this model does. At the end of the training process, you have a certain value of m and c, and that is used for predicting the values of any new data that comes. All right, so the way it works is we use the training and the test data set to train the model and then validate whether the model is working fine or not using test data. And if it is working fine, then it is taken to the next level, which is put in production. If not, the model has to be retrained. If the accuracy is not good enough, then the model is retrained, maybe with more data, or you come up with a newer model or algorithm and then repeat that process. So it is an iterative process. Once the training is completed, training and test, then this model is deployed and we can use this particular model to determine what is the price of 1.35 carat diamond. Remember, that was our problem statement. So now that we have the best fit for this given data, we have the price of 1.35 carat diamond, which is 10,000. So this is one example of how this whole process works. Now, how do we build the model? There are multiple ways. You can use Python, for example, and use libraries like Pandas or NumPy to build the model and implement it. This will be available as a separate tutorial, a separate video in this playlist. So stay tuned for that. Moving on, once we have the results, the next step is to communicate these results to the appropriate stakeholders. So which is basically taking this results and preparing like a presentation or a dashboard and communicating these results to the concerned people. So finishing or getting the results of the analysis is not the last step, but you need to, as a data scientist, take these results and present it to the team that has given you this problem in the first place and explain your findings, explain the findings of this exercise and recommend maybe what steps they need to take in order to overcome this problem or solve this problem. So that is the pretty much once that is accepted, and the last step is to operationalize. So if everything is fine, your data scientist presentations are accepted, then they put it into practice and thereby they will be able to improve or solve the problem that they stated in step 1. Okay, so quick summary of the life cycle. You have a concept study, which is basically understanding the problem, asking the right questions, and trying to see if there is enough data to solve this problem. And then even maybe gather the data. Then data preparation, the raw data needs to be manipulated. You need to do data munging so that you have the data in a certain proper format to be used by the model or our analytics system. And then you need to do the model planning, what kind of a model, what algorithm you will use for a given problem, and then the model building. So the exact execution of that model happens in step 4, and you implement and execute that model and put the data through the analysis in this step, and then you get the results. These results are then communicated, packaged and presented and communicated to the stakeholders, and once that is accepted, that is operationalized. So that is the final step.
Everyone, and welcome to this module, and we will be discussing on use cases of mathematics in data science. Then we have Bayesian inference. So Bayesian inference is used widely in different verticals. It's a popular data science technique used for businesses, especially for pricing decisions. So businesses, they can determine the prices for products based on field information like retail and wholesale prices, the size of the market, and the market share. So it can be used for new product development as a whole. Maybe one would look at the different risks by being uncertainties and determining if the project is worth it or not. But again, when it comes down to the Bayesian inference and the business decisions, the most common application relates to the product ranking. So many systems they have been developed to help customers have an ideal and customized shopping experiences. So online shopping giants like Amazon uses it to make ratings appear natural when searching for a product as opposed to displaying rankings in the order, the default option. It is used in terms of marketing, so again, we use it to look at previous campaigns and marketing information to improvise the existing campaigns or make new ones. Hypothesis testing. Then we have hypothesis testing. So hypothesis testing is used in different scenarios. First of all, it is used in clinical trials as well. So many pharmacists and doctors, they use hypothesis testing for clinical trials. So the impact of a new clinical method, medicine, or procedure, or the condition of the patient is analyzed through hypothesis testing. For example, a pharmacist believes that the new medicine is resulting in the rise of blood pressure in diabetic patients. Now, to test this assumption, the researcher has to measure the blood pressure of the sample patients before and after the intake of new medicine for nearly a particular period, let's say 1 month. So then there can be 2 scenarios. We have the null hypothesis, like the average blood pressure is the same after and before the conception of medicine. And then we can have alternative hypothesis, where the average blood pressure after the consumption of the medicine is less than the average blood pressure before the consumption of medicine. So the p-value of hypothesis test is less than the significance value, then null hypothesis is going to be rejected. It is also used widely in testing the effectiveness of the fertilizers on plants. So nowadays, it is highly used by farmers, by those in the agricultural vertical. So suppose, let's say, a researcher wants to check their assumption that a particular fertilizer may result in faster growth of the plant in a month than its usual growth than what is observed, I suppose, in a couple of plants. Now, to verify this assumption, we will consistently give the fertilizer to the plant for nearly a month, and then it can be further divided into 2 hypotheses, null and alternative, where null will be like fertilizer does not have any influence on the growth, and alternative can be the fertilizer results in a faster growth of the plant. And it is also used highly in manufacturing sector as well. So it is used in finding the defects in any kind of manufactured product. For example, let's say manufacturing plant X decides to verify that the particular method results in an increase in the defective products per quarter. Let's say the number can be 200. Now to verify this, we can calculate the mean of numbers of defective products produced before the start and end of the quarter. So again, we can divide them into two different scenarios, null and alternative. When null can be the average number of defective products and alternative can be the average number of defective products before and after the implementation of the new method, and then we can see which one fits into our current criteria. Then we have image and signal processing. So we have a number of use cases for image processing, and it is highly used in different verticals, including insurance, retail, banking, in pharmaceutical, especially in the healthcare community as well. So basically it is used in reverse image search for different purposes. So for example, if we have any image that we want to search the web page, if we use this image for performing a search, we can drag and drop search, and then any search engine will be able to use this image as a base and give us all the relevant links where we can find image or whatever is present in the image. So this is called as a reverse image search. So we can search by an image and find out the relevant details about it. So it uses the artificial intelligence software and image recognition techniques to identify image content, and then compare them with billions of images indexed on the web. So the image recognition algorithms they help out find out similar images, the origin of the image, and information about the owner of the image websites using the same image, image plagiarism, and all other relevant information. In the past, reverse image was only used for finding the similar images on the web, but today we can use it for multiple other requirements as well. Then we talk about linear regression. So linear regression is basically a technique through which we can model the relationship between different data pointers, and one of the most widely used use case is the weight loss reduction. So the problem of predicting the weight reduction in the form of number of kilos reduced hypothetically could depend upon the input features that we have: age, height, the weight of the person, and the time spent on exercises. So weight reduction is going to be the function of age, height, weight, and time spent on exercises. So that's why we have a shoe size, which is going to be based on the height, weight, age to time on exercise. So as a part of creating the above model, the goal will be to find the value of B1, B2, B3, B4, and B0, which would minimize the objective function. So the objective function would be the summation of mean squared error, which is nothing but the sum of the square of actual value and the predicted value for different values of age, height, weight, and time spent on exercises. That's how it's going to be. It is also used for forecasting the performance of students based on the marks, based on the number of hours they have put in. Let's consider the problem of predicting the marks of a student based on number of hours he or she puts into the preparation. Although at the outside it may look like a problem that can be modeled using simple linear regression, it could turn out to be a multiple linear regression problem, depending upon multiple input features. And alternatively, it can also look like a problem that can be modeled using simple linear regression, but it can be a multiple linear regression problem. So let's assume for the sake of understanding that the marks of student M depends upon the number of hours he or she puts for the preparation. So this is going to be the formula that can represent this model marks, where M multiplied by the hours plus the constant. So the best way to determine whether it is simple linear regression problem will be to do a plot of marks versus hours. A plot is going to be completely diagonal, and again, it is going to be a good fit for linear regression setup. So we have predicted modeling, which is basically used to model the probability distribution of variables in a given data set. So there are multiple use cases. First of all, we have churn prevention. So when a business loses a customer, it has to replace a loss of revenue by bringing a new customer. So it proves to be expensive as the cost of acquiring a new customer is much higher than retaining the existing customer. So predictive analytics model, they help us in preventing the churn in our customer base by analyzing the dissatisfaction among our current customers and then identifying the customer segments at most risk for leaving. Our businesses can make the necessary modifications using predictive data to keep customers happy and satisfied, eventually protecting their revenue. And then it is also used for customer segmentation. So it allows us to group the customers by shared traits in different businesses. They define the market differently, depending upon the aspects that offer the most value to the company products or services. So profound use of this analysis technique allows us to target the markets based on accurate insight and indicators, and then we can analyze these segments of those most interested in what our company offers. So there are multiple verticals like banking, pharmaceutical, retail, insurance, automotive sector. They all make use of customer segmentation. And then in terms of quality assurance, so ineffective quality control will affect our customer satisfaction scale and ultimately impact the revenue and market share. Also leads to more customer support calls, warranty issues, repairs for inefficient manufacturing, and so on. So, using predictive analytics, we can help identify high-risk modules in our application where we can prioritize the critical areas. We can reduce the time to market through shift-left testing. And by using this, we are going to get a better quality, and we will be able to tame customers for long and different verticals like pharmaceutical, manufacturing, automotive, logistic transportation. They all make use of this to keep on improvising their current business models. And as we discussed earlier, there are multiple use cases of these in healthcare. Like we use that in creating some kind of prediction modeling. So all the data sets from the demographics, clinical measurements, medical history, mathematics, they all are used to create models so that we can make an accurate prediction. How the same data set is going to behave for any future references, how we can find the most probable condition before it actually happens. So they use to analyze large data sets of health-related information so that we can prevent the disease before they happen, like we have the image scanning for lung. So based on the previous lung cancer patients, we know what exactly is a pattern or development of cancer cells. And based on the current scanning, which has already been completed, we can let the patient know if they are having a probability of developing the same lung cancer or not, so that since they will be having enough amount of time, we can make the right decision at the right time so that the prevention of cancer can get started before it spreads. Then we have some clinical files like we discussed. So mathematics play a crucial role in the design and analysis of clinical trials, so we can make use of the models. We can make use of the hypothesis testing to see if a given drug is effective or not, and then we can carry on with other hypothesis scenarios. It is used for medical imaging, so that we can know how exactly we can identify tumors. We can identify cells. We can identify some kind of cancer cells before they actually start in the blood, so that we can analyze thousands of previous scans done, and based on the pattern seen in the actual patients, we can cross-verify that by using the current scan and simply get the best probability of developing a cancer and so on. These all things can be easily verified there. And it is also used in precision medicine to ensure that we are able to give and use the right amount of medicine, so that the possibility of them getting an overdose or getting less than what will be effective for their treatment can be avoided. So these things are all done by using machine learning.
I'll take you through this lesson on statistical analysis and business applications. In this lesson, you'll learn to define statistics and differentiate between statistical and non-statistical analysis. You'll also learn about the two major categories of statistical analysis, namely descriptive and inferential analysis, and their differences. You'll also be able to describe the statistical analysis process and calculate mean, median, mode, and percentile. You'll also be able to represent data distribution using various methods such as histogram, bell curve, and kurtosis. You'll also learn about hypothesis testing, chi-square test, types of frequencies, and correlation matrix. Let's begin this lesson by defining the term statistics. Statistics is the study of the collection, analysis, interpretation, presentation, and organization of data. It's widely used to understand the complex problems of the real world and simplify them to make well-informed decisions. Several statistical principles, functions, and algorithms can be used to analyze primary data, build a statistical model, and predict the future outcome. There are two major categories of statistics: descriptive analytics and inferential analytics. Descriptive analytics helps organize the data and focuses on the main characteristics of the data. It provides a concise summary of the data. You can summarize data numerically or graphically. For example, you can collect all the data about the visitors to your website for a week and summarize the data. Inferential analytics generalizes the larger data set and applies the probability theory to draw a conclusion. In this approach, a random sample of data is taken from a population to describe and make inferences about the population. Inferential statistics is valuable when it is not convenient or possible to examine each member of an entire population. Let's understand both categories better through an example. Suppose you want to study the height of a person in an entire population. You can do this in two ways. Were you to record the height of each person in the population, it would be a tedious process. Instead, if you categorize height as tall, medium, and small, and then take only a sample from the population, this is an inferential analysis. In the descriptive analysis method, you would record the height of every person in the population and then provide the data for the maximum height, minimum height, and average height of the population. Let's understand population and sample through the visual. Population consists of various samples. A sample is the part or piece drawn from the large population for statistical analysis. It can be treated as a subset of the population. A sample should be random to help ensure that it has all the characteristics of the population and is also representative of the population. Let's understand the terms statistics and parameters, which we'll be using throughout this lesson. Statistics are quantitative values calculated from the sample. Parameters are the characteristics of the population. Suppose you have x0, x1, x2, and so on until xn, a sample from a population, and you want to know some vital information such as average, most occurring characteristic, and so on. These are calculated using formulas displayed on the screen. Mean is the average, a typical value present in the distribution, and is calculated by summing the values and dividing them by the number of values. Variance measures the sample variability. Standard deviation explains how spread out the data is from the mean. The greater the standard deviation, the greater the spread in the data. It's measured in the same units as the mean. Certain terms are used in statistical analysis to understand the data and gain insight into it. Some of these terms are as follows. Search. Search is typically used to find unusual data. Unusual data refers to those data that doesn't meet the parameters set at the beginning. Inspect. Inspect refers to studying the shape of the dataset and determining how spread out it is. Characterize. Characterize determines the central tendency of the data. Conclusion. Based on the understanding of search, inspect, and characterize, we can draw some preliminary or high-level conclusions about the data. Data distribution is the collection of data values that are arranged in order along with their relative frequency or occurrences. To understand any kind of problem, It's important to describe the data in terms of its spread and shape using graphical techniques. Range of the data indicates the quantitative values, minimum and maximum. Frequency of the data indicates the number of occurrences of any particular data value in the given dataset. Central tendency indicates whether the data values accumulate in the middle of distribution or toward the end. Following are the measures of central tendency. Mean, the sum of all the values in the dataset divided by the number of values. Median, the data value right in the middle of the dataset or the 50th percentile. Mode, the data value which is the most common or frequent. Let's understand percentile in data distribution. A percentile or a centile is a measure used in statistics indicating the value below which a given percentage of observation in a group of observations falls. For example, the 20th percentile is the value or score below which 20% of the observations may be found. Usually, we report percentiles as below. The 25th percentile is called the first quartile. The 50th percentile is called the median or second quartile. The 75th percentile is called the third quartile. Histogram is a graphical representation of data distribution first introduced by Carl Pearson. To construct a histogram, the first step is to bin the range of values. That is, divide the entire range of values into a series of intervals, and then count how many values fall into each interval. The bins are usually specified as consecutive, non-overlapping intervals of a variable. The bins must be adjacent and are usually of equal size. In the graphical representation, each bar represents a group of values, also called bin. The height of the bar represents the frequency of the values in the bin. Histograms help assess the probability distribution of a given variable by depicting the frequencies of the observations occurring in a certain range of values. A normal distribution is the most commonly used distribution in statistics. It is characterized by its bell shape and its two parameters, mean and standard deviation. A bell curve or normal distribution, it's symmetric around the mean. If you draw a line at the center, you'll get the symmetric shapes on both sides. The mean, median, and mode of a normal distribution are equal. Normal distributions are denser in the center and less dense in the tails or sides. Normal distributions are defined by two parameters, the mean and the standard deviation. The bell curve is also known as the Gaussian curve. Let's understand the bell curve better. The bell curve is divided into three parts to understand the data distribution better. Peak. It's where most of the observations occur. Generally, the peak is within one standard deviation from the mean. Flanks. They are the areas beyond the peak, but between 1 and 2 standard deviations from the mean. Tails. They refer to the area far from the center of the distribution and considered to be beyond 2 standard deviations from the mean. Usually, 5% or less data falls under this. Skewed data distribution indicates that the tendency of data distribution is to be more spread out on one side than the other. In this graphical representation, the data is left skewed. Mean is less than median. The distribution is negatively skewed or represents negative statistics. Left tail contains large distributions. In this graphical representation, the data is right skewed or positively skewed distribution. Mean is greater than median. Right tail contains large distributions. Let's now learn about kurtosis, another popular measure of data distribution. In a similar way to the concept of skewness, kurtosis is a descriptor of the shape of a probability distribution, and just as there are for skewness, There are different ways of quantifying it for a theoretical distribution and corresponding ways of estimating it from a sample of a population. Depending on the particular measure of kurtosis that is used, there are various interpretations of kurtosis. Kurtosis measures the tendency of the data towards the center or towards the tail. Platykurtic is negative statistics or negative kurtosis. Mesokurtic represents a normal distribution curve. Leptokurtic is positive statistics or positive kurtosis. Hypothesis testing is an inferential statistical technique to determine whether a certain condition is true for the entire population. For example, in a manufacturing company, the hypothesis is that every dress manufactured has no defect. A study of each dress manufactured and noting the defects as they occur will prove or disprove the hypothesis that every dress is flawless. A hypothesis test studies two opposing hypotheses about a population, the null hypothesis and the alternative hypothesis. The null hypothesis is the statement that has to be tested. Usually, the null hypothesis is a statement of no effect or no difference. The alternative hypothesis is the statement that has to be concluded as true. To quickly summarize, alternative hypothesis. It's a research hypothesis. It needs a significant level of evidence to support the initial hypothesis or assumption. If the alternative hypothesis garners strong evidence, reject the null hypothesis. Null hypothesis, it's the logical opposite of the alternative hypothesis. It indicates that the alternative hypothesis is incorrect. Weak evidence of alternative hypothesis indicates that the null hypothesis cannot be rejected. The table explains how a decision can be made based upon the hypothesis testing. Type 1 error rejects the null hypothesis when it is true. The probability of making type 1 error is represented by alpha. Type 2 error fails to reject the null hypothesis when it is false. The probability of making type 2 error is represented by beta. Probability value. The probability of observing extreme values or more extreme than the one observed. Calculated from collected data. Let's understand the process of hypothesis testing. The first step is to set the hypothesis. The hypothesis could be null or alternative. The null hypothesis, or H0, states that a population parameter is equal to a value. The alternative hypothesis, or H1, states that the population parameter is different than the value of the population parameter in the null hypothesis. The alternative hypothesis is what is believed to be true or is to be proven true. The next step is to set alpha, or choose the significant level for the population. The third step is to collect the sample from the population, which represents the characteristics of the population. The final step is to compare the p-value and alpha. You reject the null hypothesis if p-value is less than alpha, and fail to reject the null hypothesis if p-value is greater than or equal to alpha. This example shows how clinical trials can be analyzed. Suppose a pharmaceutical company wants to compare a medicine it manufactures with that of a competitor's medicine. Then, hypothesis testing can be the method it adopts. The null hypothesis would be that both the medicines are equally effective. The alternative hypothesis would be that the two medicines are not equally effective. There are three types of data on which you can perform hypothesis testing. Continuous data. Evaluate the mean, median, standard deviation, or variance. If you take the same example to test the efficacy of medicine, take the temperature of every person in the sample after 3 hours of administering the medicine. This would be referred to as continuous data. Binomial data. Evaluate the percentage general classification of data. When data is divided into two categories, you obtain binomial data. Supposing the same population were asked if their fever had subsided and the answers could be yes or no, then the percentage who said yes should match the null hypothesis. Poisson data. Evaluate rate of occurrence of frequency. If the sample is asked about how many times in a month they use the medicine, and the rate of frequency is recorded and is then compared to the null hypothesis, where the rate should be less than a certain number. Let's understand the different types of variables to analyze categorical data. Nominal variables have values with no logical ordering. They are independent of each other, and the sequence does not matter. For example, in a restaurant, you can order burgers, soda, and coffee in any order. Ordinal variables have values in logical order. However, the relative distance between the two data values is not clear. For example, large, medium, and small coffee sizes. Association indicates that two variables are associated or independent of each other. For example, in the first dataset, weather does not affect the train schedule, but in the second dataset, it does. Variables have dependencies, and one changes if the other changes. Chi-square test is a hypothesis test that compares the observation distribution of your data to an expected distribution of data. The test is applied usually when there are two categorical variables from a single population. It's used to determine whether there is a significant association between the two variables. Chi-square test is used to test the independence or association between categorical variables. Determine whether a statistical model fits the data adequately. Let's understand the chi-square test through an example. We have a data set of male purchasers and female purchasers. Let's assess whether probability of females purchasing items of $500 or more, or 0.45, is significantly different from the probability of males purchasing items of $500 or more, or 0.25. Null hypothesis. There is no association between gender and purchase. The probability of purchase does not change for $500 or more, whether female or male. Alternative hypothesis. There is association between gender and purchase. The probability of purchase over $500 is different for female and male. Let's look at the types of frequencies. Expected frequencies, or FE. The cell frequencies that are expected in a bivariate table if the two tables are statistically independent. Observed frequencies, or FO. There is association between gender and purchase. The probability of purchase behavior over $500 is different for female and male. If there is no association between gender and purchase, then the observed frequency would be equal to the expected frequency. If there was an association between gender and purchase behavior, then the observed frequency will not be equal to the expected frequency. The formula for calculating them using chi-square method is shown here. Chi-square is calculated using the formula shown on the screen. Chi-square is the sum of the squared difference between the observed frequency and the expected frequency data, or the deviation, divided by the expected frequency data in all possible categories. Expected and observed frequencies require no assumption of the underlying population. Both the frequencies demand random sampling. Let's understand the correlation matrix. A simple matrix can be visualized as an Excel document with 3 rows and 3 columns. A correlation matrix is always a square matrix. That is, it has the same number of rows and columns, but it's a larger set. A correlation matrix is expressed in the form of NXN matrix when we compare n variables. The covariance is calculated by getting the sample variance between the variables in question. A correlation coefficient measures the extent to which two variables tend to change together. The coefficient describes both the strength and the direction of the relationship. Pearson product moment correlation. The Pearson correlation evaluates the linear relationship between two continuous variables. A relationship is linear when a change in one variable is associated with a proportional change in the other variable. Spearman rank order correlation. Also called Spearman's row, the Spearman correlation evaluates the monotonic relationship between two continuous or ordinal variables. In a monotonic relationship, the variables tend to change together, though not necessarily at a constant rate. The Spearman correlation coefficient is based on the ranked values for each variable rather than the raw data. Here is the example of a correlation matrix calculated for the stock market. We can choose the data variables and calculate the correlation matrix to demonstrate the short, medium, and long-term relationships between them. Now you can see why a correlation matrix would prove useful for traders. We already know that inferential statistics uses a random sample from the data to make inferences about the population. This is a valuable method when each and every member of the population cannot be studied. Inferential statistics can be used only under the following conditions. You have a complete list of the members of the population. You draw a random sample from this population. Using a pre-established formula, you determine that your sample size is large enough. Inferential statistics can be used even if your data does not meet these criteria. Inferential statistics can help determine the strength of the relationship with your sample. If it's very difficult to obtain a population list and/or draw a random sample, then you do the best you can with what you have. Inferential statistics is an effective forecasting tool widely used in businesses. For example, companies use it to predict their finances for future quarters. Using current data, future patterns can be inferred. Let's now quickly recap what we've learned in the lesson. Statistics is the study of the collection, analysis, interpretation, presentation, and organization of data. Statistical analysis is more reliable, as it is based on numbers and scientific analysis when compared to non-statistical analysis. Descriptive and inferential are the two major categories of statistics. Descriptive takes into account all the members of the population, while inferential uses only a sample. Mean, median, and mode are measures of central tendency, while variance and standard deviation measure the spread of data. The spread of distribution is called dispersion and is graphically represented by a histogram and a bell curve. The shape of the dispersion is represented as left-skewed, right-skewed, and kurtosis. Hypothesis testing is an inferential statistical technique that is useful for forecasting future patterns. Chi-square test is a hypothesis test that compares observed distribution to an expected distribution. The correlation coefficient or covariance measured with the help of correlation matrix measures the extent to which two variables tend to change together.
So first, let us understand why is 2026 a game changer for data science. Now, data science is evolving at lightning speed. A few years ago, it was all about looking back at data to make sense of the past. But now it's about predicting the future, helping businesses make smarter decisions in real time, and even creating personalized experiences for customers. For example, think about the way your shopping experience is tailored online. That's data science in action. And in 2026, data scientists will take this to new heights, making predictions faster and more accurately than ever before. The demand for data scientists is growing rapidly. According to the US Bureau of Labor Statistics, the job market of data scientists is expected to grow at 35% between 2021 and 2031, much faster than the average of other jobs. The world is becoming more data-driven every day, and businesses need skilled professionals to help them make sense of it. So what has changed this year, and why should you pursue it now? In 2026, data science is no longer about analyzing data. It's all about making data work for you. Technologies like generative AI, real-time analytics, and machine learning are shaping the future. Businesses need data scientists who can use AI to create new ideas, products, and even content. Plus, AI ethics has become a key focus, and companies are looking for experts to help them use AI responsibly. And the best part is the opportunities are growing globally. A report by Glassdoor ranks data science as one of the top 5 in-demand jobs for the coming years. And the need for professionals who can work with AI and machine learning is expected to increase even further. So now that you have understood why 2026 is a game changer for data scientists, let's dive into the core foundations that will help you build a strong base in data science. The first one is Python mastery with Pandas and NumPy. Now, when you're starting out as a data scientist, Python is your best friend. Why? Because it's simple to learn and powerful enough to handle complex data sets. But just knowing Python isn't enough. You'll need to get comfortable with Pandas and NumPy, two important libraries in Python that will help you work with data. What is Pandas? Well, you can think of Pandas as a tool that makes working with data in Python easy. Imagine you have a spreadsheet full of data. Pandas will help you read, clean, and organize that data without much hassle. Let's say, for example, if you have a table of customer orders, you can use Pandas to sort, filter, and analyze that data in just a few lines of code. Talking about NumPy, NumPy on the other hand is all about handling numbers and mathematical operations. If you're calculating average sales or finding out how the weather impacts your business, NumPy would help you do the math quickly and efficiently. It's great for working with large amounts of numerical data. So to put it simply, Pandas is just like a toolbox for managing and analyzing data, whereas NumPy is your calculator for fast and easy mathematical operations. Mastering these two tools in Python will make you a data manipulation wizard. Let's move on to our second skill, which is SQL for data querying and analysis. Let's talk about SQL, which is structured query language. This is one of the most important skills for data scientists. Imagine you have a giant database filled with information. How do you get the specific data you need? That's where SQL comes in. SQL is a language which is used to communicate with databases. It allows you to ask questions called queries to get the data you need. For example, if you want to know how many products were sold in the last week, you could write a SQL query that pulls the data from your sales database. So let's take an example. Imagine you have a customer database with tables for customer information, sales transaction, and products. If you want to find out which product sold the most last month, you would use SQL to query the sales transactions table and group the data by product. With just a simple query, SQL gives you the answers you need. Learning SQL is crucial for analyzing big data, filtering out the noise, and getting the precise information you need to make decisions. It's like being able to ask the database questions and get the answers you want in a flash. The third one is statistics for data-driven decision making. So now that you know Python and SQL, you need to understand how to make sense of the data you're working with. This is where statistics comes in. It's the science of collecting, analyzing, and interpreting data to help you make decisions based on numbers, not just guesses. So why is statistics important? You can think of statistics as your toolkit for understanding patterns in data. Let's say you're working on a project to analyze customer behavior. You want to know if there's a pattern in how customers buy certain products. Now, using descriptive statistics like averages, percentages, and distributions, you can summarize what's happening in the data. Let's suppose you run a bakery and you want to know if there's a particular time of day when you sell the most cupcakes. You would collect data on the number of cupcakes sold at different times and use statistics to calculate things like an average number of cupcakes sold per hour. Now, this will help you make data-driven decisions about when to bake more cupcakes and when to adjust your marketing. So using statistics, it will help you answer questions like what's the average sales of each day of the week? What's the probability of a customer buying a specific product? Are there any patterns or trends we should be aware of? So basically, by mastering statistics, it will help you make smarter decisions and analyze data like a pro. Fourth one on our list is problem solving and analytical thinking. Lastly, we come to most important skill of all, problem solving and analytical thinking. Being a data scientist isn't just about using tools and coding. It's all about thinking critically and approaching problems in a structured way. So what does a problem solving look like in a data science? Now, when a business presents a challenge, it's up to you, the data scientist, to break down the problem, figure out what data you need, and find the best way to solve it. Let's suppose a company might ask, how can we predict which customers are most likely to buy a new product? So here's where your problem solving skills kick in. You would understand the question and break it down. Collect and clean the necessary data using Python, Pandas, and SQL. Analyze the data to find patterns. Build a model using machine learning to predict the likelihood of each customer buying the product. And finally, present your findings in a clear and actionable way. Analytical thinking means looking at a problem from multiple angles, asking the right questions, and testing your ideas with data to see if your solution works. So once you've got these skills under your belt, you will be ready to take on more advanced topics and solve real-world problems using data. And don't worry, if it feels overwhelming at first, just take it step by step. Practice often, and soon enough, you will be a data science pro. Now it's time to talk about some advanced skills that will set you apart in 2026. The first one is machine learning with scikit-learn and TensorFlow. Let's start with machine learning. Now, this is a huge part of data science, and in 2026, it's going to be even more important. But what exactly is machine learning? Machine learning is the way for computers to learn from data and make predictions or decisions without being explicitly programmed. For example, imagine you want to build a recommendation system that suggests movies based on what people have watched before. Why scikit-learn and TensorFlow? Scikit-learn here is a Python library that's perfect for getting started with machine learning. It's like your beginner toolkit. It will help you build models quickly and easily. You can use it to classify images, predict stock prices, and even detect spam in emails. TensorFlow, on the other hand, is more advanced library which is used for building more complex models, especially in deep learning. Now, if you want to build systems that can recognize images, translate languages, or even drive a car, TensorFlow will help you do that. Now, both the libraries are powerful tools that data scientists use to make machines smarter. If you get comfortable with both, you will be able to tackle a wide range of data problems. The next one is deep learning, when and how to use it. If machine learning is the engine that powers a lot of data models, then deep learning is the high-performance engine for real complex tasks. So what exactly is deep learning? It's a type of machine learning, but it works differently. It uses neural networks, which are inspired by how our brain works. These networks are made up of layers that process data and learn from it. It's especially useful for things like image recognition, speech-to-text, or self-driving cars. Now, you might be asking, when do I use deep learning and when do I stick with regular machine learning? Now, deep learning is great for problems that are complex and involve large amounts of unstructured data, like images, videos, or sound. Now, if you're working with structured data like numbers or categories, regular machine learning using tools like scikit-learn might work better. For example, if you need to classify images of cats and dogs, deep learning is the way to go. And if you want to predict house prices based on location, square footage, and other factors, machine learning with scikit-learn would be a good fit. And in coming years, deep learning will be used more often to solve highly complex problems. And knowing when to use it and how to apply it will make you stand out as a data scientist. The third one is generative AI and prompt engineering basics. Let's talk about it. This is one of the coolest areas of AI right now, and it's definitely going to grow. Now, generative AI refers to AI that can create new data. For example, it can write text, generate images, or even make music. Now, instead of just analyzing data, Gen AI creates something new and useful from that data. Think about tools like ChatGPT, which can generate text based on prompt, or Nano Banana by Google Gemini, which can create stunning images from descriptions. So what is prompt engineering? Now, with prompt engineering, you can learn how to interact with generative AI tools in the most effective way. It's all about asking the right questions or giving the right instructions to get the most useful and accurate results. For example, if you want a Gen AI tool to write a blog post about data science, you would give it a clear prompt like write a 500-word blog post explaining the basics of data science with examples. The clearer your prompt is, the better would be the result. The next one is natural language processing for real-world applications. Natural language processing, NLP, is a fascinating part of data science that deals with understanding and analyzing human language. You can think about it how we interact with computers through voice assistants like Siri, Alexa. That's NLP in action. Now, what is NLP? NLP is a branch of AI that allows computers to understand, interpret, and generate human language. For example, when you type a question into a search engine, NLP will help the engine understand your query and return relevant results. Or when you use a chatbot on a website, NLP is used to understand your question and give you helpful answers. Let's talk about the applications of NLP. Now, NLP will be used in many industries to improve customer service, create chatbots, or even analyze customer feedback. For example, if you could build a tool that analyzes a product reviews or find out what people like or dislike about a product, NLP will help you turn all the messy text data into useful insights. Now, if you master NLP, you will be able to create systems that can understand and respond to human language in real, meaningful ways. The next one on our list is time series forecasting and anomaly detection. Finally, let's talk about time series forecasting and anomaly detection. Now, these two are essential techniques for analyzing data that changes over time, like sales, weather patterns, or stock prices. Time series forecasting is the process of using past data to predict future trends. For example, if you want to forecast next month's sales based on the past sales data, you can use time series forecasting techniques, and this is important for businesses that want to plan ahead. Now, talking about what is anomaly detection. Anomaly detection is the technique which is used to identify unusual or unexpected patterns in data. Imagine if you're tracking website traffic and suddenly there's a huge spike in visits. Here, anomaly detection will help you figure out this in a normal pattern, or if something unusual is going on, maybe even a security threat. In coming years, businesses will rely heavily on time series forecasting and anomaly detection to make data-driven decisions in areas like finance, retail, and healthcare. Now, if you're able to analyze trends over time and spot problems early, you will be a valuable asset to any team. And by mastering these advanced skills, you will be ready to tackle some of the toughest challenges in data science and make an impact in the world of data. Now it's time to discuss about some tools and platforms to master. Mastering these tools will make your work easier, faster, and more efficient. At first, we've got Jupyter Notebook. It's just like a digital notebook where you can run and write code and see results instantly, add explanations, and it's perfect for data science projects where you need to test, visualize, and explain your project. Next one is VS Code, a powerful code editor that will help you write, test, and debug code. Think of it as your digital workspace for coding. After that, we've got Git and GitHub. Now, these tools will help you track changes in your code and collaborate with others. They are a must for teamwork and managing large projects. We've also got cloud platforms like AWS, GCP, and Azure. These cloud platforms let you store, process, and analyze huge amounts of data without worrying about hardware. They are just like having a supercomputer in the sky for your data. You've also got big data tools like Spark, Databricks, Snowflake, a fast engine for processing large data sets. It's just like having a high-speed train for data. Databricks is built on Spark, and this tool will help you easily build and deploy machine learning models on big data. Snowflake is a cloud-based data platform that will store and analyze data from various sources all in one place. We've also got some visualization tools like Tableau, Power BI, and Plotly. Tableau and Power BI are the tools that will help you create interactive and easy to understand visualizations of your data like charts, graphs, and dashboards. Plotly, on the other hand, is a Python-based tool that will create interactive plots and graphs for deeper data insights. Now, by mastering these tools, you will be ready to tackle any data science challenge in coming years. Alright, so now that you have got the skills, let's talk about how you can showcase them and how you can build a job-winning portfolio. So let's talk about some project ideas aligned to 2026 industry demands. So when you're building a portfolio, it's very important to work on projects that will reflect what's in demand. You want to show that you're ready to take on the challenge businesses will face in 2026. So here are some of the cool project ideas to get you started. First one is generative AI for content creation. You could create a project where you can build a tool that generates blog posts or social media content based on trending topics. This is a great example of generative AI at work, and it's something businesses are increasingly interested in as they want fresh content without doing everything manually. Next, we've got real-time data analytics dashboard. you can build a dashboard that tracks something in real time, like weather data, stock prices, or even website traffic. Imagine you create a dashboard that updates every minute and shows live trends. This kind of real-time analysis is huge for businesses looking to make immediate data-driven decisions. Next is customer churn prediction model. You can create a model that predicts whether customers are likely to leave a service or a product. Use past customer data like purchase, behavior, or feedback to predict who might churn. It's a predictive modeling project that companies in any industry will find valuable. By working on projects that aligns with what's needed, you can show employers that you're not just practicing, you're solving real problems they face today. Now, let's talk about some open source contributions and Kaggle competitions. Now, if you really want to stand out, getting involved in open source contributions and Kaggle competitions is a fantastic way to open your skills. You can also jump into open source project on GitHub. These are real world projects where people need help solving problems. Contributing to these projects is a great way to practice your skills, and it shows employers that you can collaborate and work with teams. For instance, you could contribute to improving a machine learning algorithm, fixing bugs, or adding new features. It's all about getting hands-on experience and adding value to the community. Talking about Kaggle is a platform where you can compete against data scientists from around the world to solve real-world data problems. They also have challenges like predicting house prices, classifying images, or building recommendation systems. Next, it's important to create a personal blog or GitHub project directory. Let's talk about GitHub and personal blogs. Now, these aren't just places to store your code. They are ways to share your work with the world. GitHub project directory will make sure your projects are organized in a clean and easy to read manner. When employers visit your GitHub, they should be able to look at your code, understand what you did, and see the impact. This will help the recruiters and hiring managers quickly see what you're capable of. And personal blog, you can start with a blog where you can write about your data science journey, you can share tutorials, insights, or even project walkthroughs. It's a great way to improve your communication skill and show employers that you can explain complex concepts easily. Next is storytelling skills in portfolio work. Now here's the secret sauce. Storytelling. Your portfolio isn't just about showing what you've done. It's all about telling a story of how you solve problems with data. So here's how you can tell that story. Problem. You can start by explaining the challenge. For example, I was tasked with predicting customer churn for a subscription service. Then you can find the solution for it, like describe the approach you took. I cleaned the data, used feature engineering to select the most relevant data points, and trained a random forest model to make predictions. Then you've got results, where you can finally talk about the outcome. The model achieved 85% accuracy, and it helped the company retain 15% more customers over the next quarter. Showing your process from start to finish lets employers see how you think and how you approach solving problems. It's just like telling them, here's what I did, how I did, and the impact it had. Now, with a portfolio like this, you are definitely be ready to impress hiring managers and land that data science job. Now, let's talk about how you can choose your data science career path. You might be probably wondering, what specific role should I go for? There are different paths that you can take, and the best one for you depends on your skills, interest, and what excites you the most. The first one is data analyst. You can think of data analysts as the detectives of the data world. They look at data to find trends, make sense of numbers, and generate reports. Now, if you enjoy exploring data and visualizing insights, like creating charts or graphs, this might be the role for you. You'll use tools like Excel, SQL, Tableau to answer business questions like which product are selling best or how can we improve customer retention. The next one is data engineer. Now, data engineers are the builders. They focus on designing and building the systems that allow companies to store, process, and manage massive amounts of data. They work with tools like SQL, Hadoop, and Spark to set up data pipelines and databases. Now, if you enjoy working with technology, building infrastructure, and solving big technical problems, this could be your fit. Next one is data scientist. This is where things get a bit more complex. Data scientists take the data cleaned and organized by data engineers, and they use advanced methods like statistical analysis, machine learning, and predictive modeling to find patterns, build models, and make predictions. If you love solving complex problems and turning data into actionable insights, data science could be the role for you. Then we've got machine learning engineer. ML engineers specialize in taking the machine learning models created by data scientists and turning them into production system. They focus on the technical side, making sure that models run smoothly, efficiently, and at scale. Now, if you love programming, automation, and creating things that work in the real world, ML engineering could be the right path for you. We've also got some emerging hybrid roles like AI product manager and data ops engineer. Let's talk about AI product manager. This role is for people who are interested in both AI, ML, and business. Now, as an AI product manager, you will be working on developing AI-driven projects, collaborating with data scientists, engineers, and business teams. You will need to understand both the technical side of AI and the needs to business to build successful products. If you like leading teams and shaping the direction of AI products, this could be an exciting path for you. The next one is data ops engineer. Data ops is just like DevOps, but for data. Data ops engineers focus on automating and streamlining the process of managing and delivering data. They ensure that data is flowing smoothly and efficiently across the system and teams are in organization. Now, if you enjoy building pipelines, automating workflows, and improving team collaboration, a data ops role might be a good fit for you. Now, with all these options, how do you choose the right path for you? Here's a simple way to think about it. Now, if you enjoy analyzing data and turning it into insights, you might want to explore data analyst, data scientist role. If you love building things and working with technology, consider data engineer or ML engineer role. And if you're interested in both the business and technology, hybrid roles like AI product manager could be a great fit for you. And if you enjoy problem solving and automation, data ops might be the way to go. Now, let's dive into some resumes, interviews, salary expectation, and work models in data science. So first, we'll talk about resumes, do's and don'ts. So your resume is your first thing employers see. So it needs to make a great impression. Here's what you should do and avoid. First one, let's talk about the do's. You can highlight relevant skills, focus on technical skills like Python, SQL, machine learning, and data visualization. You can show what tools you've worked with, such as Pandas, TensorFlow, or Tableau. Then you can show your impact. Don't just list tasks, show what you have accomplished. Example, build a recommendation system that increased sales by 15%. Next is, keep it clean and simple. Use bullet points, be concise, and avoid further clutter. Recruiters spend seconds on each resume, so make sure yours is easy to read. Now let's discuss about the don'ts. First of all, do not overload it with jargons. Keep it very simple. Employers don't need to know every tech term. Focus on the most important ones. Next is using outdated skills. Now, if your resume lists Excel as your top skill, it may not cut it anymore. Focus on modern tools and techniques. Forget your personal project. Now, if you're a fresher, your personal project can make you stand out. Be sure to include any Kaggle competitions, GitHub projects, or open source contributions. Next, we'll talk about interview questions and how you can prepare for interviews. Interviews can be nerve-wracking, but with the right preparation, you can nail it. Here's how. You can prepare for common questions like, tell me about a project you've worked on, or how would you explain a complex algorithm to a non-technical person? How do you handle missing data? Give me an example of a problem you solve using data science. Let's talk about how can you prepare for these. First of all, know your projects. Be ready to walk the interviewer through your work. Explain your problem, solution, and results clearly. Brush up on technical concept. Be ready to discuss topics like machine learning models, statistical tests, or data wrangling. Don't just memorize fact. Focus on understanding the concept. Then ask questions. At the end of the interview, ask thoughtful questions about the company of the team. It will show you that you are genuinely interested. Talking about the salary expectations. In the US, you can expect around $70,000 to $130,000, whereas in India, the salary starts from 6 lakh and it goes to 15 lakh. And the salaries can go even more higher than this in top companies. Next, it's very important to continuously learn. Data science is rapidly evolving, so it's very important to stay up to date from the latest tools and technologies. You can focus on blogs, getting along with people on LinkedIn, and so many other platforms. Now, if you're looking to kickstart your career in data science, I highly recommend checking out Data Scientist Master Program by Simplilearn. This is in collaboration with Microsoft and Simplilearn. It's an 11-month live program, interactive session led by top industry experts, giving you hands-on experience with AI-powered tools like Python, SQL, machine learning. You will be working on real-world projects, including a capstone project and earning Microsoft certificate along with Simplilearn's data science certificate, and earning a Microsoft certificate along with Simplilearn Data Science certificate to showcase your skills. So whether you're just a beginner looking out to upgrade your skills, this course is perfect for AI enthusiasts, students, or recent graduates. And the best part is, you will get career support to help you land your dream job. So what are you waiting for? Hurry up and enroll, and you can find the course link below. Let's talk about one more important thing, which is remote job versus on-site job. Now, the world of work is changing and remote work is now becoming more common than ever. So, in remote work, there are some pros and some cons. The pros are flexibility, work-life balance, and access to job worldwide. You can collaborate with teams from anywhere. Cons are still there, like you might miss out on networking opportunities, and it can be harder to communicate complex ideas without face-to-face interaction. Next is on-site work. The pros are it's easier to collaborate, quicker feedback, and better networking opportunities. Some people prefer structure and social aspect of working in an office. There are also cons like less flexibility, long commutes, and less work-life balance. Which one is right for you depends on your work style. If you prefer flexibility and working at your own pace, remote might be ideal job for you. And if you enjoy team interaction and structured environment, on-site could be better. So starting your data science journey now gives you a huge edge. You're getting in at the perfect time with the latest tools, technologies, and demand for skilled professionals. By diving in, you will be ahead of the curve and ready to ride the wave of emerging trends like generative AI and real-time analytics. To stay ahead, make sure you're always learning and keeping up with industry trends and communities, places like Kaggle, GitHub, and LinkedIn.
The humble Microsoft Excel still stands as one of the most trusted and widely used tools for data analysis. Even in the age of artificial intelligence, automation, and advanced analytics platforms, Excel stands tall. Despite the rapid rise of technologies like Power BI, Tableau, Python, and machine learning, Excel continues to be the starting point and often the finishing line for millions of professionals analyzing data around the world. Whether you're a financial analyst building forecasts, or marketer tracking campaign performance, or a student learning statistics, chances are Excel is where your data journey begins. Now, let's start with the first module, which is about what is data analytics and its purpose. So let's start with a simple but important question. What exactly is analytics? At its core, data analytics is a process of collecting, transforming, and examining raw data to uncover meaningful insights, patterns, and trends that help support decision making. It's not about numbers, it's about turning data into stories that drive actions. For example, imagine you work for a retail company. Every day, your store generates sales data, customer feedback, and inventory records. Data analytics helps you interpret that information to identify which products sell best, when sales peak, and what marketing campaigns are most effective. In a sense, analytics transforms confusion into clarity. It helps decision makers understand what's exactly happening in their business rather than relying on the gut feeling. The purpose of data analytics goes far beyond just collecting and storing data. Anyone can have data, but not everyone can make sense of it. Analytics helps organizations to identify opportunities and risks early to improve operational efficiency, optimize marketing and sales strategies, enhance customer experience, and ultimately make data-driven decisions instead of assumptions. As the saying goes, without data, you're just another person with an opinion. That's why analytics has become such an essential skill in today's digital world. Now, let's go to the section 2, types of data analytics. Now, data analytics isn't one size fits all. It actually comes in 4 major types, each one answering a different question and serving a unique purpose in decision-making process. Let's go through one after the other. First one, descriptive analytics. What happened is the question here. So this is the foundation, the starting point of any analysis. Descriptive analytics looks at historical data to summarize and understand past performance. For example, you might generate a sales report for the last quarter, calculate average monthly revenue, or track website visits over time. The goal here isn't to explain why something happened, but simply to describe what happened. Tools like Excel are great at this, using formulas, pivot tables, and charts to make data easy to interpret. Now, the second type, diagnostic analytics. This answers why did it happen. Once we know what happened, the next logical step is to ask why. Diagnostic analytics digs deeper to uncover the causes behind the trends and anomalies. Maybe sales dropped in July. Was it due to seasonality, pricing issues, or reduced marketing efforts? Diagnostic analytics helps pinpoint the reasons using techniques like correlation analysis, variance analysis, and drill down reporting. In Excel, you can easily explore relationships between variables using charts, filters, and regression tools. Followed by that, we have predictive analytics. What might happen next is the main purpose of using predictive analytics. Predictive analytics uses statistical models, forecasting, and machine learning techniques to anticipate future trends. For example, an e-commerce company might forecast next month's revenue based on historical sales and market spends. In Excel, you can build predictive models using functions like forecast, trend, or even more advanced methods through Power Query or Excel's built-in AI tools. Predictive analytics transforms historical insights into forward-looking predictions. Now, the next one, which is prescriptive analytics. What can we do about it? Finally, prescriptive analytics takes things to one step further. It doesn't just predict outcomes, it suggests actions. It answers questions. Given what we know, what should we do next? For instance, if predictive analysis shows a potential drop in customer retention, prescriptive analytics might recommend increasing loyalty rewards or adjusting pricing, while Excel has limitations here compared to specialized AI tools. So, its what if analysis, goal seek, and solver add-ins allow users to test scenarios and determine optimal decisions, making it an accessible gateway to prescriptive modeling. So, these four types, descriptive, diagnostic, predictive, and prescriptive, form the foundation of modern analytics. Together, they help organizations move from simply knowing what happened to confidently deciding what to do next. Now we enter the module 3. Why Excel is still relevant for data analysis. Now you might be wondering, with so many modern tools like Power BI, Python, R, or Tableau, why does Excel still matter in today's world of advanced analytics? Well, the answer lies in its balance of simplicity, versatility, and power. Let's break down. First one, accessibility and ease of use. Excel is one of the most widely available tools on the planet. From students to CEOs, almost everyone has access to it, and that universal familiarity makes it incredibly powerful. You don't need to be a programmer or data scientist to start analyzing data. Excel provides a low barrier to entry with drag and drop features, pre-built templates, and intuitive functions that allow anyone to learn. It's often the first step in a person's analytics journey. Many professionals use Excel as learning environment before transitioning into tools like Power BI or Python, and because of its available on virtually every operating system, Excel remains a democratizing tool, bringing data analysis capabilities to anyone, anywhere. Now, powerful analytics capabilities is the second reason. Behind its familiar grid interface lies a surprisingly advanced analytical engine. Excel supports a vast range of functions, formulas, pivot tables, data visualization tools, and automation features. Here are a few examples. Pivot tables summarize and explore large datasets instantly. Conditional formatting highlights trends and anomalies. Power Query allows for efficient data cleaning and transformation. Power Pivot enables advanced modeling and relationship between tables. Charts and dashboards communicate insights visually with ease. And let's not forget Excel's AI-powered tools such as Analyze Data and Ideas, which automatically suggest insights, trends, or patterns. With these capabilities, Excel isn't just a spreadsheet, it's a comprehensive analytics environment in itself. Now, the third reason, integration, and compatibility. Another major strength of Excel is how seamlessly it integrates with other platforms. You can connect Excel to databases, APIs, Power BI, Google Sheets, SharePoint, or even cloud services like Azure and AWS. This flexibility makes it a perfect bridge between simple data analytics and more advanced analytics platforms. For example, a financial analyst might export or import real-time data from SQL database, clean it with the help of Excel, and then publish the results to a Power BI dashboard for interactive visualization. This smooth workflow keeps Excel at the heart of many enterprise analytics ecosystems. The fourth reason is real-world use cases. Across industries from finance and HR to marketing, logistics, and education, Excel continues to be an indispensable tool. A few examples: finance budgeting, forecasting, variance analysis and KPI tracking; marketing, campaign performance analysis, ROI calculation and customer segmentation; human resources, workforce analytics, attendance tracking and salary modeling; operations, inventory management, scheduling, and performance dashboards. Even in organizations that use sophisticated BI tools, Excel is still used for quick exploratory analysis, ad hoc reporting, and presentation-ready summaries. It's like a Swiss Army knife of all data analytics. Simple enough for beginners, yet powerful enough for professionals tackling complex business challenges. Now, with that, let's dive deeper into data analytics. Excel continues to be a cornerstone for analytics around the world. In the next module, we will dive into Excel's interface and explore the key functions that make it such a reliable tool for any data-driven professional. Some of these essential functions include the following: trim, to remove unwanted spaces and text; clean, to remove unprintable characters; text, to format dates, numbers, and values; average, median, standard deviation for statistical analysis; index match and lookup to perform advanced data searches and relationships. Mastering these functions will take your Excel skills and your analytical confidence to the next level. Now, let's dive into the demonstration of building dashboards with Excel. So now, let's get into data analytics. On my screen, we have a banking data set. So here we have the customer details: gender, marital status, age, education, occupation, contact numbers, the state, the PIN code, bank IFSC, region, account number. And apart from that, we also have bank related data where we have the same customer details, and I have added a few more columns here. So the reason is we will be attaching these entries to this particular sheet so that we have all the data segregated in one place. You'll learn that on the go. We'll be using some lookup functions for that. And now here you can see the bank details. So here we have a few more details based on the account type, the account balance, what are the type of transactions happening in their account, transaction type, is it check transfer, card transfer, net banking, phone related transactions like Google Pay or Phone Pay, and is it any other transaction like NEFT or RTGS, or is it about EMI options, and a lot more options here. So all these data sets that I'm using today are not real data sets. Those are created data sets. So you might find some names here which are not real names or doesn't belong to any of the real customers. Even the customer IDs and all the phone numbers, those are not real numbers. So you're just using this data set created by artificial intelligence for analytics purpose only. And all the names of the banks are also created names, not the real names. Let's take care of it. Now, so here we have the account balance and transaction type. Is it a wire transfer, check transfer? And we also have a payment network which we have considered. We are having Maestro, Visa, MasterCard, etc., RuPay, and also the card type. Is it contactless card, virtual card, or a student card, premium card? The card type as well. Is it a debit card, credit card? And then you also see here we have loan types, and not all customers have loans. A few of them have savings accounts or current accounts or business accounts, and a few of them have loans here. And also we have a wide variety of loan types available, which is term loan, education loan, business loan, etc. And here we have the principal amount, loan tenure in terms of months, and rate of interest, and the remaining balance they need to pay. And if any of the accounts have converted into NP or non-profiting or no, we have the details over here. So you can also have some blank cells, which means that these customers do not have any accounts or loan accounts related to this particular bank. Now that we have a brief understanding of what exactly are we dealing with, let's get started with data cleaning, data segregation, and then some data analytics. Now, if you see on the first row, we have customer details. So AI created customer details in this particular fashion, which has the customer ID along with the customer first name and the last name. But in real time, this might not be the good scenario to work with, right? So we will be cleaning this particular data set. So for that, let's insert a few more rows. So here I'm using maybe one or two different rows. And now the cleaning. Select the column that you want to be split or cleaned. Go to data, and here we have text to columns. Now what does a text to column operation do? So here if I click on or hover onto this particular option, it says split a single column into multiple columns. For example, you can separate a column full of names into separate first and last name columns. You can choose how to split it up, fixed, within, or split at each comma, period, or other character. So it is nothing but a delimiter. It can identify the delimiter, and then based on the delimiter, it will split a column into one or more different columns. So here we have a delimiter set as hyphen. Now there are multiple ways of cleaning this data. Let's go with the first option, which is text to columns. So I'll click this text to columns, and here I am selecting delimited with characters such as comma or tabs separate each field, right? So in our case, we have the hyphen, right? So we will go with delimited option and then go to next. Here we have preset delimiters like tab, semicolon, comma, space, and others. So we have a hyphen, so we'll go with the other option, and we'll mention the delimiter, which is hyphen. And you can already see the preview on the screen. So we have the customer details column, and then the first name column and the second name column. Once you're happy with the preview, you can just click on next, and then you will have this particular data format, general, text, etc. So you can always go with general, where Excel decides the data type based on the data present in the columns, or you can also choose the type of data item or data type which you want for your data set. So I want text here, so I'll go with text. So all the customer details, which is the customer ID, is a text format, and first name and last name is also a text format. So I'll go with text option, and then you can click on finish, and as soon as you do that, you will have the data already available. So replace it. So there you go. This is one way of doing it. Let me quickly undo it. And the next way is flash fill. Now that's one intelligent feature where you don't have to manually check for the option which is text to column and all those things. You can copy this particular first customer ID and paste it over here, and then select the first name and copy it over here, and then the last name, copy it and paste it over here. Now you have a template which Excel understands. If you double click, right, let me just quickly undo that. You can see an option, a small box, right? That is flash fill option. If you double click it, Excel has automatically understood a pattern. It means it now can segregate the first names and the last names along with the customer ID all by itself. Now let's quickly perform that flash fill option. Let me expand the data a little bit. I'm just double clicking on the square box like this. I think there has been a small mistake, but not a problem. It needs a little training. So what I'm doing is I'm trying to copy and paste the elements a little bit so that it understands what to do next. Yeah, that's the flash fill logo. There you go. I think there has been a small error, but that's resolvable. Basically, that's how the flash fill works. Now, let's go with the initial approach of text to columns. Not a big deal. So I'll go with delimited option, then comes next. And our delimiter would be hyphen. That's the preview. And go to next. and my data format would be text, and then finish it. The data already exists. Do you want to replace? Yes, I want to replace it. Now I'll rename the columns. So instead of customer details, I'll have it as customer ID, and then this will be customer first name, and this will be customer last name or second name. There you go. So far so good. Now here we have gender. I'll delete this column, we don't need this anymore. And we have gender, marriage status, age, education, occupation, phone number, and all those things. That's good. Now I see we have a lot of unique ages here. We have 30, 39, 24, 19, etc. But when we are dealing with creating visualizations for transaction based on age types, this might be a lot clumsier, right? You'll have a wide range of barriers. Now, what if I segregate them into age groups? Something like aged between 25 to 60 are middle-aged, and above 60 would be senior citizens, and below 25 would be like students or something like that. It makes a lot of sense, right? So let's try that. I'll insert a new column here, and I'll expand this a little more, and I'll name it as age groups. Now we have a wide range of opportunities to do this. We will go with if condition. So I have an if condition. If. So you have the syntax readily available from the Excel here. So you can see if function works with a logical test, and if the logical test passes, what should I value it as? Value if true, and if it doesn't pass, if it fails, should have a value for that as well. So value if false. This is the syntax for if condition. Now the logical test is we will have to provide the data for the logical test. I'll go with the column F2. If this particular value is greater than 25, then middle-aged, else I'll term them as students. So don't forget to add the double quotes because this particular data is text type data. So we should not forget the text representation, which is double quotes. And apart from that, we were also supposed to add the senior citizens. So I'll add another if condition, and the same value will be considered. The cell is greater than 60, okay, greater than or equal to 60, then senior citizen. So let me make a quick change here. So I think we had a small error with the formula. Let's quickly try that once again. So if condition, logical condition is the cell value should be less than 25. If this is true, then we will term them as students. This is my condition. If they are not, then we will have another if condition. So there is an age barrier where we will have students, and apart from the student's age, which is more than 25 to 60, we can call them as middle-aged. And for that, we'll write a new condition. So it will be encapsulated inside another if condition. So I'll open an if condition and we'll consider the same cell. And this should be less than or equal to age number 60. If it's true, then they are, okay, let's not take 60, let's go with 55. 55, then we can call them as middle-aged. Else, we can call them as senior citizens. Let's consider 55 for retiring age. Actually, it's 60. For the sake of data set, let's go with 55. And I'll call them as senior citizens. There you go. And you can go close the first if condition, then the second if condition. Once you're okay with the formula, enter. Now we have the first middle-aged entry. Now remember the flash fill that we were trying to separate the first name, second name, and the customer ID? We can also use this here. So you don't have to manually write the if condition to all these cells. So let me show you how many number of cells we have. So we have about 5,000 entries here. So we don't have time for writing 5,000 entries. So for the sake of saving time, we will use the flash fill. So here you have the small box. So just double click on it and automatically the formula will be applied to all the cells. Now you can quickly check that as well. So here we have a senior citizen, and followed by that we have all the middle-aged people and also a student entry. So all these are the ones. Now we have data segregation for customer first name, customer last name, age groups are also created. And now comes the bank IFSC. So if you check the dataset properly, we don't have bank names. Even in the banking details, we don't have the bank names. So here you have account numbers and account types, but no bank name. And also in the customer details. Now, how do you extract the bank name? That's the main question. That can be done, don't worry. So let's create a few more columns and let's make use of some basic functions like left and if conditions again. So here you can see we have SBIN, AXIS, ICIC, and PNB and a few more entries. So what we are going to do is we are going to extract the first 4 letters of this particular bank IFSC, and based on that we will deem or we will term that particular bank first name to be the complete name. Based on the first section of this IFSC code, we can name or term that particular bank's name. That's the idea. So basically, since I created this particular dataset, I have a clear idea that we have about 5 bank names here. So based on that, let's go ahead and name the banks. So I'll use the function left and text. So this is the text I want to go ahead with, which is in M2. And how many number of characters you want to extract? So SBIN. So we have about 3 to 4. So let's go with 4. I'll go with 4 and enter. We have the name here. And based on this name, we will consider the name to be given to this particular bank. So we will use the same if condition here as well. So equals to if, press tab to select the function. If this particular entry is equals to SBIN, then name it as State Bank of India. Or if this particular value is equals to AXIX, which is Axis, then name it as Axis Bank. Another if this value is equals to HDFC, then name it as HDFC Bank. Similarly, if this particular entry is PNB0, I think we missed the cell address, equals to PNB0, then name it as Punjab National Bank. And I think we have covered 1, 2, 3, 4, and one more is remaining, which is ICICI. If this particular value is equals to ICIC, then name it as ICICI Bank, and there you go. We can close the brackets. First bracket is done. First if condition is covered. Second if condition is also covered. Third if condition is covered. And fifth if condition. No, I think we have covered the fourth one. Last fifth, yeah, that's the one. There you go. Now enter. Now we have the first bank name, which is State Bank of India. Now we will quickly use flash fill to extract this left function to all the entries, and similarly another flash fill function for filling the bank names. So we can use the double click option. There you go. We have all the first 4 letters of the IFSC code, and similarly based on the IFSC code's first 4 characters, we'll also have the bank names. So we have bank name provided, and the first 4 IFSC. Let's name it as this. There you go. Now we have a better, cleared data. We have dedicated customer ID. We have dedicated first name, second name, or the last name, gender, marital status, age and age groups as well, and their education, occupation, phone numbers, state, regions, bank names, etc. Right? I think that's good enough. Now let's also check this. Do we have any other details to be added or not? That's okay. So we added bank name based on formula of if and left, right? Now there was another method, okay, this is just for learning purposes only. There's another method where we could have added these names manually to all the banks based on the IFSC code. Now, let me explain you how that can be done. Since we discussed that this dataset is created by me for learning purposes only, and we know there are 5 different banks. So let's add the names of 5 different banks here. ICICI Bank, HDFC Bank, State Bank of India, Axis Bank, and lastly, Punjab National Bank. There you go. And these will be my banks, right? Let me quickly arrange that in the form of a table. So here we are learning table formatting, right? So that's how you can color and you can create a table, add borders, etc. Now, let's say I have an option called bank name, select the bank name. So do I have a drop down option where you can manually select the bank name, and can we create it? Yes, we can create it. And that's called data validation, where you can validate the data, and based on the selection, you can have a drop down menu. So to do that, you need to first select the cell, go to data, and then here you have an option called data validation. So you can see it says pick from a list of rules to limit the type of data that can be entered to a cell. For example, you can provide a list of values like 1, 2, 3, or only allow numbers greater than 1000 as long as it's valid entries, right? So here we have that option. So you can click on data validation, and here you have the settings. So we have a wide variety of options to go ahead with. You can go with numerical values, add any value, or you can go with whole numbers or decimal numbers. You can also have a list of options like we have here. You can see we have ICICI, HDFC, and all the bank names that we're using in this particular data set. And you can use a list. And also you have an option to enter a calendar. You can provide a specific date and a calendar there, and you can select the date from the calendar. So there are a wide range of options in data validation. For learning more details on data validation, go through the tutorial on data validation from Simplilearn. So now we'll go with the list as we discussed. So here you can provide the source. You can manually type the source like ICICI like we typed here, or you can also provide the location where you have this particular source. So I have the location over here, so I'll select the location and then click on OK. So we have the location ready. Now, this is not just done yet. You can also make some modifications to it. So let me delete this particular validation. And here, let's not delete, you can also directly edit here. You can add an input message. So let me provide the title, select a bank, and we can also, okay, this can be the input message, and this can be banks list. Now you can also have an error alert as well, just in case if the user tries to enter any manual name apart from the provided list, then it should be an error, right? So I have an error message here. So I can use stop, warning or information. I'll go with stop, and the title should be saying wrong, or the you can say bank not found, and the message will be please select from the list provided only. There you go. So I'm done with my data validation and also the error messages. Click on OK, and there you go. You can see when you hover on this particular icon, you can see a message. This is a bank list, and you can select the bank name from this particular list. And let's say I select the list, and there you go. Using the same flash fill, I can extend this particular list of options. And now this particular cell has data validation. Now, apart from the available banks, let's go with some other bank name which is not provided in my list. Let's go with random bank. And if I press enter, I'll find an error. And the error says, please select from the provided list only, right? So this is the error. Now what this does is, this avoids any kind of misentries into your dataset. That's one good functionality of data validation. Now you can select the list entries only, and you can add the list, whatever you want. There you go. Now that's how you do data validation. Now the next job is to segregate all the data into one place. Then we can perform the filter operations. We can also eliminate the duplicates, right? We have about 5,000 different entries. So there might be a possibility or may not be a possibility. Both could be possible, right? You may have a duplicate entry or may not have a duplicate entry. But the best thing is, before you start with any data analytics on any platforms, whether it is Excel, Power BI, or Tableau, or any platform, the first step is data cleaning and segregation. So that's what we were doing so far. So we have segregated all the data that we needed. Now the remaining part is we need to collect all the data into one place. Since you're working on Excel, it's not so complicated. But if you're working on an analytics platform like Power BI or Tableau, that is called as data modeling, where you connect all the different data models in one place and they have a relationship established between them. Now, it's simple in Excel. All you need to do is just copy paste in the best way possible, or you can also build a data model in Excel. So both are possible. Let's go with the simpler version. Now, what we need to do is copy all the data and paste it in one single place. So, so far I'm comfortable with the data, whatever I have. So let me create a new sheet, and here I'll copy the bank details. So I have year here. I'll copy this and paste it here. Let's call this sheet as worksheet or workbook. And now go to the customer page. So we have selected all the data. So back to the workbook now. Before you paste the data, make sure you select this cell and then go to the paste options here and just click on the drop down, and here you have the option of paste values only. Why we are going for the paste values only? So you might be having a question. So if we go back to the data set, and here if you check the particular cell here, we have a formula, right? And apart from this, we have a formula for majorly all the cells over here. So when you're copying and pasting the cells with formula, then you will face the reference error in the worksheet. To avoid that reference error, we will use paste values only option, so that it gives you all the values without any kind of formulas in the cell and without any complications. So you have the customer's data and the first name, last name, and all the details that we had in the customer details. And now let's head back to the banking details, and we don't want these cells that I've inserted. So let me eliminate these cells, so you can just delete them, this one as well. Yeah. Now what remains is, we needed the account number, account type, and rest of all the data entries which are present here. And we'll copy these, and again the same approach. Go to paste special, and here values only. Now we have two entries of account number. We can delete one, not a big deal. So there you go. So again, before you perform any analytics, the first important major step is to clean and segregate your data. Now you can see the rows and columns are not properly aggregated, or not aggregation, basically organized. So you have a simple shortcut for that. All you need to do is select any one of the cells and click and Control A, which selects all the cells in one go. Then you have a shortcut key. Remember this. Press Alt and release once. Then alphabet H, press and release once. And then comes the alphabet O, press and release once. And lastly, alphabet I, press and release once. There you go. Now what this does is, it organizes the cells width and height. So this one was for width, and there's another one for height. which is for Alt HOA will be for height and Alt HOI will be for width. Now we have organized the cells in width. Now Shift, Control and arrow key selecting all the header cells. There you go. Now the header cells are also done. Now select all the cells and we have the borders. Now the data is correctly aggregated. And another important step is save the data after each and every iteration so that nothing is lost on the go. Now we have saved it. Now we also have some important statistical functions like sum, count, average, mean, median, mode. So let's also go through these ones. So the name itself speaks, not too much complicated. So we have, account balance. So let's freeze this particular column. You can freeze this by selecting the column and going to the view option. And here you have the freeze panes. Freeze the column. You can select the columns that you want to freeze. I'll freeze all these. Or you can simply shift this particular column so that you have a better readability. Press and hold. And there you go. You have moved it over here. Now you have a reference column with numbers to implement all these statistics functions, aggregate functions, which are sum, count, average, median, mode, minimum, range, standard deviation, variance, and quarter, percentile, etc. So let's go with this one after the other. Now let's go with sum. So sum function. So why are we doing this? So that we have a quick idea on sum, sumifs, and all those functions, right? So sum and select the range. It will give you the sum of all the entries. Give it a small error. Sum function. Enter. Okay, there is a data type error. Okay, let's consider a different column. I think it is due to the currency format, and here we are selecting the whole number format. Not to worry. We shall now explore with this particular function so that we can also have a filter. Go to data and here apply the filter to this particular column on and eliminate blanks. Let's paste it here. Now we'll have the filter, eliminate blanks. There you go. Now you can work on, there you go. It will give you the sum of overall numbers present here. And you also have the count function, which basically counts the total number of cells. We have about 2000 entries. So basically out of 3000 employees or 3000 account holders, more than 2000 account holders have gone with taking a loan with the bank. Now let's find the average tenure period provided to all the account holders. So you can do that by considering the average number, average function, and then providing the cell entries. And you can find the average amount of time given to clear the loan is about 96 months. And you can also convert that to years. And now here you have the median function, which is similar to average. So median of the cell entries, have the median here, so equals to mode and the numbers provided. We have the values. So now what do you mean by mean, median and mode? So let's have a definition for it. So mean is the sum of all values divided by the number of values, and it will give you, or it will represent the average value of the data set. And similarly for median, the median is the middle value when all observations are arranged in ascending or descending order. If there is an even number of values, the median is average of all the two sides of middle values. And lastly, the mode. The mode is the value of that occurs most frequently in the data set. So the data set will have no mode, one mode or unimodal or multiple modes. So basically, the maximum number of repetitions for a dedicated number is called the mode. So here you can see 120 is repeated most number of times apart from the other provided number of months per dedicated loans, right? So maybe it could be a home loan or a kind of a car loan or a bike loan. So most commonly taken loans are given the 120 10-year period. So that's the most repeated one. So in our terms, mode is 20, median is most widely considered as the average number, and mean is similar to average. So that's how it goes. Now we have the next two functions, which is minimum and maximum. So it is self-explanatory. So you can provide the function minimum min of all the provided numbers here, which gives you the minimum number of tenure, which is 12 months, and also the max number. So you can just type down max and press tab to select the function, give the range of tenure numbers, and you have the maximum as 240 months tenure period, so which is that one. And you also have a range function. So what is range? So range is a measure of how spread out or diverse or dispersed the data values are. It shows the difference between the highest and lowest values in a data set. So it's like a maximum value minus the minimum value. So you can perform it in two ways. You can select this cell, which is the maximum value, minus the minimum value, or you can simply use the range function from the available formulas, or you can just imply this particular one which we have gone with. And the next one is the standard deviation. So standard deviation measures how much the data values vary or spread out from the average. It tells you how consistent or scattered the number of your data sets are. So you can perform standard deviation using the formula STD-DAV. So you have two different types of standard deviation. So it is based on the entire population, and the other one is based on a sample. So you can just go with the standard formula, which is standard dev here, or the entire population one, or the one which you have over here, right? And you can provide the range of numbers of the entire population in your cell, and you have the standard deviation value here. Now next we have the variance. So variance measures how far each data point is from the mean on average. It represents the average of the square differences between each value and the mean. In short, it shows how spread out the data is, just like standard deviation, but without taking the square root. So you can also use the variance formula. So you have covariance and covariance P. We can go with this one. We use the covariance in a wrong way. So next we have percentile. And you can provide the percentile, and here is the percent you want. Let's say I want 25% of the range, and you can provide 25, enter, and you have that. So if I wanted 21% of the entire period provided for tenure, then I can provide the number as 0.21, which gives me 21% of the provided tenure. That's how you implement the percentile. And similarly, Q1 and Q4, this is also the percentile functions, where you can provide a quarterly basis function. If you want the first quarter, you can provide 0.25. Similar to this one, you can go with 0.50, 0.75, and 100% or 1.0. So that's how it works. So basically you provide 0.25 here, 0.5 for this one, 0.75 for this one, and 1.0 for this one. This is the quarter 1, quarter 1, quarter 4. That's how it works. And variance. Now let's go back to the, that was a quick scenario on the aggregate functions or the statistics functions in Excel. Now let's go back to the pre-worked workbook, and we are all good to go. Now let's also create a duplicate of this workbook, move or copy. So why am I creating a copy? Because I want, let's say I want to work on the loan section only, right? In that scenario, I don't want the other regular accounts. So for that, let me quickly apply a filter for this one. Go to the data section, select the filter, and a filter has been implemented. Now, what I'll do is I'll unselect all first. Now I'll select only the blank entries. Now, all these blank entries are about 3000 entries of all the customers, and I can quickly delete all these entries without affecting the master workbook sheet. Now, what will be remained in this particular sheet will be related to the data of only the customers who have taken a loan with the particular bank. That might take a while. We have about 3000 entries, right? There you go. All you have to do is just delete these entries. And now you can go to the column where we have applied filter, or just clear all the filters. And now you have all the data related to the customers who have taken a loan with any of the banks that we are dealing with, right? Now you can quickly rename this workbook as bank loan dataset, and you're good to go. Now it's your choice. You have completely finished workbooks for both the bank loan dataset and the overall customer dataset with 5,000 entries, where you have the data for both the customers who have taken a loan and who did not have taken a loan with any of the bank. I'll go with the bank loan dataset. So we have all the entries along with the loan details. So you can do some projections as well. Now, the best part is you also have a data analysis feature, which is an AI feature from Excel, which creates the datasets visualizations for you, right? You can just click on the dataset and then click on OK. You have two-factor replication, two-factor without replication. You have covariation. You have descriptive statistics as well, which you want to perform. You can also perform Fourier analysis and a lot of analysis that you can do with Excel. So I want to go with descriptive statistics and click on OK, and it will give you input range. You can provide the range. That's your range. Click OK. So I need to change the range. Okay, there has been a small error, but not to worry. Basically, I was trying to provide a forecast number, which can be done directly via the forecast sheet option right available here. So you can select the ranges, rate of interest, and remaining balance. Based on that, you can go with forecast sheet, and you need to also provide the years. So I'll take the years column and also the remaining balance, so that we can forecast what are the possibilities, right, for the remaining balance. So the thick line provides you the forecast for remaining balance. This is the duration on which, right, so many number of months they might take to repay the balance. This is the worst possible scenario, and this is the best possible scenario, and this is a predicted scenario. Based on this graph, they will repay the loans entire customers. So that's the forecast, and you can create this chart and use it, or you can just choose to cancel it and perform all the pivot table analysis all by yourself. So that's the next part, creating pivot tables and pivot charts and an entire dashboard which is completely interactive, and you'll also have slicers, filters, and everything included. Now that we have a readily available data, the next step is to go ahead with the pivot tables. And apart from that, let me quickly show you different ways to load the data onto workbook, right? So every Excel workbook is having a wide variety of options to import the data. So let's say if you wanted to import the data, you can get the data from a wide variety of sources. It can be an Excel workbook, it can be a CSV file, XML, JSON, PDF, folder, right? And you can also connect online data bases like SQL Server, Microsoft Access, Analysis Service, and a lot more. You can also connect data from cloud like Microsoft Azure Data Lake, and you can also have Power Platform and other sources like web, ODBC, JDBC, etc. And combine queries, you can merge different queries like different data sets as well, right? There are a lot of variety of options to load data onto the Excel worksheet. So this was supposed to be discussed before, but not to worry, we did not miss anything major. We already started off with a data set which was created for us. Now, the next part is about building pivot tables and pivot charts. So building pivot tables and pivot charts is not a big deal. You can just click any of the cell and then control auto select all the cells available on the data set. And then you can create a pivot table by entering into the insert option here and then selecting the pivot table. So here, easily arrange and summarize complex data in a pivot table. For your information, you can double click a value to see which detailed values make up the summarized total, right? So now we choose to select to create the pivot table in a new worksheet or the existing worksheet. So I'll go with the new worksheet, and we have provided the range of data that we are working with, and then click on OK. So here we have a fully functional pivot table or pivot page. So we will name this particular sheet as pivot 1. So why 1? We'll be creating a lot of pivot tables in this particular tutorial. Why a lot? Because we will be creating pivot charts. So here we have an option which says pivot analyzed, right? So we'll be creating a lot of pivot charts, and then so we'll be copying all those pivot charts into one single dashboard sheet, and then create interactivity between all those pivot charts, and then we'll have a fully functional dashboard. That's the overall agenda. Now let's get started. Now I want to know a few things. So I'll add age groups to the rows and account types to values. So now we have a detailed pivot table here. So middle-aged people have about 1046 accounts. Senior citizens maintain about 311 accounts, and students have about 359 accounts, right? So we have a pivot table for this. Now you can select this particular data and then go to pivot chart, and you can create a pivot chart for yourself. By default, we had a column chart, and then okay, based on age groups. So this is our first pivot table, and here we will insert another pivot table, and let's name it as pivot 2. Now I want to know the loan type. So I'll add loan type to rows, and then if I drag and drop the loan type once again to values, so I'll have the count of loan types as well. Now we will know you will have the count of loan types. You can select the entire data set and insert a pivot chart, and you can have a pie chart, and you can also choose which type of pie chart you want, and then press OK. Loan type. Now go back to loan dataset and insert. Now based on gender, you can do a gender analysis as well, gender distribution, and you can name this as pivot 3. You can also provide a dedicated name for your chart, but the time's sake I'm using pivot 1, pivot 2, pivot 3. You can also name them as loan types, and the first one would be account based on age groups, and pivot 3 would be gender distribution, right? Based on your requirement, you can feel free to use the names for your pivot charts. Now go to pivot table once again and create a new pivot table. So here we have year-wise data. You can add years to rows, and then you can see the number of loans provided in each year, right? So you can see the count of loans, if the loans are increasing or decreasing, right? And you need to work on if the loan numbers are decreasing, then you can market something so that you can see a potential growth in the number of loans distributed yearly. And since you're working with time period, you'll go with the line chart. So this is the one. You can name it as year on year growth. So I'll name it as Y on Y growth on loans. And then you can name it as pivot 4. Go to the bank data set again, and here you can insert a new pivot table again, and here we have age groups. We have done the age groups, and you can go ahead with education right now, education to the rows. So we have 3 different types of education: degree, diploma, and schooling. I've kept it minimal to avoid confusions. And you can also do region analysis, you can do state-wise analysis, and a lot of things that can be done. And here we have the loans. You can have a bar graph for this one. Let's quickly name it as pivot 5, and this one should be loans based on education or qualification. So you can already see, if you are from a schooling background, you can, I meant to say, if you have less qualification, if you have not done your degree or diploma, then the chances of getting a loan could be low. Again, getting a loan is just not based on qualification or your education. It can also be based on your credit score, or you can also call it a CIBIL score, right? So if your CIBIL score is good, and if you are having good amount of income, or if you have a good hierarchy of assets, then you can also get a loan. But for this particular data set, let's go with education. So we have not considered the CIBIL score in the data set. We have not considered the hierarchical assets you have. That's not included in the data set. So for the data set's sake, well, let's go with the education purpose. So if you don't have a good qualification, it automatically leads to lower chances of getting a loan in this particular aspect. Now, based on qualification is done, now let's go with the region-based analysis as well. You can go with the insert option here and insert. And then what I'll do is I'll go with the state and I'll drop it down to rows, and I'll have a loan type into the values. And based on states, we have so many loans. Now, state-wise loans pivot chart. We can go with a map chart. Build map is not available. For some reason, it is not recognizing. Can't create this chart with the data inside the pivot table. Okay. For some reason, it is not recognizing this as a geographical location, but not a problem. Let's go with the tree map. I think tree map should also help. There must be some problem unexplainable here. But yeah, you should have been identified this as a geographical location, and it should have given us a geographical location, but not a problem. Geo-wise, loan distribution. You can also have bank name level distribution. You can basically have this as KPI or KRA, right? I think it's called KPI. So based on KPI, you can have the numbers, which bank has provided how many number of loans, right? And so that could be a good KPI for you. And let's see if the card option is available here. It's not, but it's okay. Bank level and done. So most of the charts that we created are column charts and bar graphs and line graphs and pie charts. So not a problem. For some reason, the data in the pivot table is not recognized as geographical location. But to create a dashboard, we need pivot charts. So let's continue with what we have. Now that's one way of doing it. So now let's create a fresh sheet and call it as the dashboard. So there are a wide variety of chances of creating many more extractions or insights from this data set. You can also go ahead with occupation based chart, right? So let's do that as well. You can insert a pivot table, and here you can have occupation on the rows and loan type. And go with a donut graph for this. Now let's go to the dashboard, and here let's select these cells and combine them, and you can also color code them. Write it down as banking dashboard, and you can also choose to increase the copy and paste it to dashboard. So make sure that you're selecting a new cell when you're pasting the pivot chart. If you're not selecting a new cell, then the previous pivot chart will be replaced. So make sure you select a new cell on the dashboard when you're pasting. So this might take a little time, but we'll do it slowly. Now the gender distribution. So this will also be added to the dashboard. And to create interactivity, we'll also be adding slicers to this particular dashboard. That will be done on the go. So this was gender distribution and year-on-year growth as well. So since this is time-based analysis, we need to paste it in the form of line graph. Now, once you're done with this particular arrangement, you can also adjust the height. Slowly, we have a couple of more pivot charts. So here we have loan qualification. So here we will paste it in the new place. This is where I would like this to be present. And geolocation wise and bank level. So we have two more. go to the dashboard, select a new cell. I would like to expand this a little because it is geographical location, right? So we need to cover about all the states present in the country. And now let's make a little room for our slices as well. I think one more chart is left out, which is bank level. So I'll place this bank level in the last location, or you can also choose to expand this particular section. So I'll choose this location to be expanded. There you go. Now what remains is adding the slices and interactivity with the dashboard. We can minimize the size so that every aspect of the dashboard is clearly visible. There you go. So we need to go to the pivot chart, analyze, and click on the insert slicer option. So we have a wide variety of slicer options available in this particular window. So we'll go with the year, and we'll go with the gender. So basically what we did with the pivot charts, that's what we're going to do with the slices as well. So we will be going with the gender, we'll be going with the year, we'll also be going with geographical location wise, so state, and we'll also be going with bank name, and we'll also be going with the education, and we'll also be going with occupation. And once you are okay, I think we can also go with age groups as well. So once you're comfortable with the slicer options, then you can quickly choose OK, and you'll have all these slicers readily available at your disposal. Now the next job is to arrange all these slicers. So I'd like to select all the slicers once and select their height adjustments. Once I'm okay with the height adjustments, I can drag and drop them to the locations where I want them. Basically what I'm doing is adjusting the height, width, and length of each and every slicer so that it fits in the window of my dashboard. So it might take a little while. Not to worry, let's do it slowly. So far we have done with 1, 2, 3, 4 slices. So we have about 2 to 3 more slices. So let's do that accordingly. And I have the gender slicer here. So I'll send it to this particular location near to age groups, and I can also adjust the height of this particular slicer. And what is remaining is the last one, which is year based slicer, and which will be placed here. There you go. And now it's not done yet. Let's say if I select, right, let me adjust the gender slicer. Let's say if I select the data for Andhra Pradesh, there will be changes in only one particular, state, right? So it will not give me the entire changes in the overall dashboard level. Now, what do I do to get that interactivity? So for that, you need to right click and select an option here, which says report connections, right? Now, what this does is it helps you create connectivity between all the slicer options available on your dashboard. So far you have about 6 to 7 slices, right? So you need to create the same for all the slicers. So the first state level slicer is being connected with reports. So I need to do this to all the slicers. It might take a little while. Let's do it slowly. But doing this will help you maintain an interactive dashboard. That's the main agenda. So click OK. Similarly to this particular education slicer, let's undo that. I think I deleted it by mistake. So we need to do report instead of remove. So let's restore. There you go. Now similarly to the occupation one, right click, report connections. Select all the available pivot charts in your dashboard. There you go. And press OK. Now let's check this particular one if I had reported all the connections. Yes. And now we are done with I think almost 4 connections are reported. Now we have 3 more, just 3 more, and our dashboard will be completely interactive. So let us select 1, 2, 3, 4, 5, 6, and 7. Basically all the pivot tables and pivot charts that we have created in the dashboard. And similarly to gender, go to report connections, allow all the connections to be reported. So whenever you click on an option provided, you get complete interactivity on the dashboard. And the last one is year. And here, click on 1, 2, 3, 4, 5, 6, 7, and 8. There you go. Now, if you clear, you have a completely interactive dashboard. Now, this one also, let's clear this. Now, let us say I want to know the data for Goa region alone, with the candidates having a degree as education and business as occupation. And I want the data of only State Bank of India, and for male data, middle-aged person only, from the year 2022. Now I have the entire report, right? And similarly, if I wanted a few more entries for male and female as well, then you have the interactivity here, right? So if I clear all the filters, you'll have a fully functional dashboard back again. So this maintains an interactivity on your dashboard. Basically, you'll get all the details. Let's say I want to go ahead with another different state, let's say Maharashtra. Then I have the details of Maharashtra since past 5 years of data, and all the age categories and all the educational qualifications on the geo-wise distribution year on year growth. So you can see Maharashtra is developing. So you can see from 2021 to 2025, you can see a stable increase of growth of loans. So people are taking many loans and investing in better businesses and all those things, or home loans, right? So there's a business development in terms of this particular data set here. So that's how you create a fully functional and interactive dashboard in Excel.
Going to get started with this. Now, see, let's understand the journey to data science, right? So whenever you talk about any data science project, there is a crisp DM framework that we follow. We'll be studying that later, but you are doing a data science project. So like this. So whenever you talk about any data science project, so it will be always going through these all things. I'll just let you know in short what I mean by that. So whenever you have a project from the client, the first phase is where you understand. So let's say your client is Pfizer. So you understand what are they into, what is their domain, what is their problem statement, what are the challenges that they are facing. So a business analyst comes over here and understands all these things. Then he propagates the requirement to the technical team who will be getting the data, right? Who will be getting the data and starting to analyze the data, right? Because in a data set, let's say Pfizer, right? So there will be all pharma related terms. As a data scientist, you will have to understand each and every column and correlate it with the domain knowledge, because if you don't understand that, you will not be able to solve their real life challenges. So data understanding comes. Then after the data understanding comes the data preparation. So data preparation is the phase where the data in real life will never be as clean as expected. You expect the data to be awesome, but it's going to be worst. You really have to make your hands dirty for cleaning the data. So cleaning the data, doing some visualization on the data. So this is where your libraries like NumPy, Pandas, Matplotlib, and Seaborn comes into picture, right? So we are going to see this, right? So all of this comes into your picture. And then comes your modeling. This is where your machine learning comes into your picture. So the library that you learn is scikit-learn and some other libraries, but mainly scikit-learn. If you are doing deep learning, you learn TensorFlow, and then you get into evaluation of the model. So obviously, first you analyze, clean the data, then you create multiple machine learning models because one model may not be the best. So you try to create many, just like in a class as a teacher, I'm teaching to all of you, and then I am choosing the best student. Okay, so I have to send them to some Olympiad competitions. I will choose the best student, and that is what happens in the evaluation stage. So in evaluation stage, as I told you, you select the best model. And after that best model is selected, you get into the deployment stage. And deployment means obviously you have to share it with the model. So you productionize it. So today we are here in understanding these libraries. And once you understand these libraries, then you are good to get into this flow in the machine learning part, not now. But one thing I would like to definitely say that if a data science project, if you are talking about a data science project, and if a data science project, let's say it's taking a total of 100 days to complete successfully, then I want to say that 70 to 80 days go in phase 1, 2, and 3. Then I would say 10 to 15 days go in 4 and 5. And another 10 to 15 days go in 6. So although machine learning is so important, but for actually creating models, it does not take that much time. The highest amount of time taken is over here for getting these all things aligned, right? So this is something which is very important for anyone to realize. So data preparation stage is one of the most important thing. Okay. So that's how the overall data science pipeline is. And also, at times, if you are not able to create a good model, you can also see that you may have to go back. So let's say you do this thing in a little bit hurry and you try to create a model quickly. A model will be worse, something that, client will just not accept. So you may have to go back and do this. In fact, here also, if you do any misunderstanding, you may have to go back and understand the requirements. So it's not an easy job, friends. So that's something important to be understood by all of us. Okay. Now, we need not get into all of this. This was just to give you an idea. What is more important is getting started with the NumPy library. But, this helps you understand the overall flow. What are you learning and why are you learning? One of the model, which is productionized, looks something like this. So what are we essentially doing over here? I have hosted this model, which is productionized using the Streamlit app. So if you say this is a tick prediction app, we will be actually dealing with this data set when I explore for you the Seaborn and Matplotlib. So that data set we will be looking into at that point of time. Right now, it's not important, but this is that data set for a US restaurant where I am trying to predict what will be the tip that a customer is likely to give based on his or her total bill, how many people visited in all, the gender of the customer who paid the bill, whether he smokes or not, the day on which he visited the restaurant, and whether he visited for lunch or dinner. So you can actually play around with this. Let's say I go to the restaurant and my total bill is $15. It's a US data set, $15. And I went with my wife. So total two people. I was the one who paid the bill. I do not smoke. I went on Saturday and I went for dinner. So if these are the parameters, I'm likely to give a tip of $2.45. And in the same way, you can play around. Let's say Darshan went for a lunchtime, then $2.55. If Darshan smokes, or if the customer smokes rather than saying that, then this is the one. If I went ahead and let's say this is not me, this is some female, then the tip given is this. And if it is a male, then the tip given is this. So male gives relatively long, higher tip is what we understand. And smoker is giving 2.36, non-smoker gives relatively higher tip. So these are the things that we understand. You can also take a moment and try playing around with this because this is deployed on the cloud. So one can try that out. Now this deployment part, which I showed you, that comes at the end of machine learning or somewhere at the end of deep learning. Furthermore ahead, how does the data look like in this case? It's a CSV file. It looks something like this. This is how the data looks like, where this is the dependent variable which I'm trying to predict on the basis of other factors. Yes. So we'll be working on this data set as well later on. So now, let's get started with NumPy, right? So, getting started with NumPy. Um, oh, so what is exactly NumPy? Well, NumPy is the backbone of machine learning and data science in Python. It is one of the most important libraries in Python for numerical computing. See, you need to understand num in NumPy means numerical and pi means Python, right? And NumPy, why NumPy? I know lists. Why NumPy? I know the topic list, then why do I need a NumPy array? Because NumPy is super duper ultra fast. So NumPy is almost 10 to 15 times faster than list. That is what you need in data science, right? So NumPy supports large multidimensional arrays along with the collection of the mathematical functions. Next, it is very powerful for doing this. And it is super fast and efficient as it is implemented in C. Now, C, talking about Python, yes. So if just if I go back and if I say I want to write a function to check if not check, function to find factorial of a number. That's how you write it. And then while testing, you test it like this. Right? This is a recursive function to find factorial of a number. That's how you write it in this. So when you are giving a call to this factorial function, then control goes over here and some logic is applied to do the things. Okay. So the function, right? If you see over here, this function is in Python language. However, NumPy is implemented in C and Fortran. And that is why it is till today, one of the fastest language is C only. C, C++ are the fastest language. So whenever I am going to call some NumPy function, then the body of that function is written in C, mixed language programming. It is called as Python. I'll show you. Can you show the body of any NumPy function as it is written in C language? You can see over here. I think I did not give it properly. So, see, whenever you are giving a call, right? So, how does Python use and how is it implemented in the backend? Because whenever I'm saying sum, it will find out the sum of the array. So, in NumPy, finding the sum is this as simple as that. But in the backend, the code looks like this. And in return, when array sum is called, there is a Python code which is getting executed. Right? So that is I want to say, right? So that is what is called as Python code. Python and C together, you call it as Python, and it looks something like this. We are least bothered about it, but I am explaining you how they have created all of this. Huh? How they have created all of this. This is not important. This is not important, but internally, whenever I'm giving any call, this is how it is happening. Okay. So that is why I said NumPy is super fast. Do we say the operations of NumPy are vectorized in nature? Vectorized. Vectorized means the body is written in C and C++. Okay. Now, one last thing. Is that the only difference between a NumPy array and a list? No. Also, one more thing. NumPy creates arrays. And arrays are collection of items of the same type. Very, very important. List can have items of any data type, but array compulsorily of the same type. Now, how much is NumPy important? Well, too much important. Just to show you, I'm just randomly opening few of the deep learning case studies, right? I'm just randomly opening few of the deep learning case studies and one machine learning case study as well. So if you see over here in this deep learning case study of image classification, I'm importing the NumPy. And what all functions of NumPy have I considered using over here? You see np.newAccess, np.arange. Then I say np.where, np.random, right? So I may not be able to explain you what are we doing over here, but I just wanted to show you that it is getting used. NP is what I have imported NumPy as. Similarly, over here as well, you see np.expandims, np.arange, np.where, np.random. Similarly, np.round, right? Then flatten function, that's also of NumPy. np.mean. Okay. np.log. So this is just to make np.array. This is just to make you understand that, see, boss, this is required. This is just to make you understand that it is required. And you know what? See, when till 12th standard in the examinations, they never allowed us means we, the engineers, to use a calculator in the exam. But in the engineering, when we took admission, all of a sudden using calculators was allowed. So at that time, why didn't they expect me to do all the calculations by step? Why was a calculator allowed? Because calculator was mandatory at that time. When I was on 12th standard, I was in 12th standard, 10th standard, or anywhere below that, right? First, second standard, right up to 12th standard. Well, I was doing all the simple math. But now I am doing advanced math. So I am already assumed to be a pro over here. So when you are doing the advanced mathematics, if you need something, you use that, go up and continue coding the advanced level. So at that time, NumPy is like this, assume this entire thing to be like NumPy. The basics are over here. So whenever you do any machine learning stuff, you need not implement all these small things. For that, you can say, NumPy, could you please solve my issue? And it will do the needful for you. Right? As simple as that. So coming back, that was just to make you understand the practical significance of this topic. Okay. Okay, so now let us get into NumPy. Let us start with NumPy. So first thing is we will have to import the NumPy library. That's just import NumPy. So import NumPy as NP. Now, is it mandatory that you import it as NP? No, it is. It is a de facto standard to label it as NP, but it is not mandatory. So, but most of the people, or rather than saying most, almost everyone labels it as NP only. In fact, if you go to Google and look into any of the documentation as well, you will see that NumPy library only in picture. So import NumPy as NP. And then I would like to print the version of NumPy that comes as np dot double underscore version double underscore. Double underscore, sir. It's 2 times. And done. Now, if you go to Colab, maybe your version is different, but that does not matter, right? You just need not worry about it, whatever be the thing. Now, let us create a one-dimensional NumPy array. So first thing is syntax. np dot array, you have to give the data and the d type. You have to give the data and you have to give the d type, where data can be array-like object and d type will be this, and also d type is optional. If not provided, NumPy will infer it by itself. So if it is optional, I would like to first of all play around with it. So I say I want to create a NumPy array. So I'm using the array function np dot array, and you can pass in a list or a tuple or a set and it will create a NumPy array for you. But as I told you during the basics of Python, that whenever you do this, always 95% to 98% of the times you will be using list only. So I'll be using a list. So let's say if I say 1, 3, 5, 2, 8, these are the things, So I will print that array and also print the data type of that array. So print the data type of that array. Then after that, you see this. Now, how is a NumPy ideally array is created? So NumPy array, look at this figure. 1, 3, 5, 2, 8. 1, 3, 5, 2, and 8. This is exactly same like list. Yes. 0, 1, 2, 3, 4. In fact, -1, -2, -3, -4, and -5 as well. As you all can see, this is a 1D array consisting of total 5 items. Yes. So let's get into this. So here we have got this creation of an array and the data type is NumPy's ND array. Okay, n-dimensional array because it can be 2D, 3D, ND, etc. Now, after this creation of this, I want to show you how I can do indexing on this array because I see the indexes over here. So indexing, well, it is exactly same as list. So I don't want to invest a lot of time. ARR of 0 will be 1. ARR of 4 will be 8. -1 would be 8. -3 would be 5 and so on. So ARR of 0 would be 1. ARR of 1 would be 3. ARR of -1 would be 8 and -2 would be 2. And when I run it, you can actually see it. In the same way, slicing is also same as list. So if I say 0:2, then the starting index is equal to 0 and ending index is 3 - 1, which is considered as 2. So whatever you studied in list, everything is applicable over here. Okay. Then after this, I come to the creation part. Okay, so this is what we created. I also want to tell you that overall the D type is what I never gave, right? So this was the D type, but I didn't give it. That was the syntax. We'll take it over here so that the code becomes clean. So here I have 1, 3, 5, 2, 8, and I didn't supply the D type, but I can print the D type. So I can say print the name of the array is ARR. So I can say ARR dot D type. So what will it give? Int 64. If you are using a very old system, it might show int 32 as well. It shows 64 or 32. We are least bothered. It is integer. Rest all things we never require. It's just saying over here that whenever I say int 64, inside this 64 is nothing but the bit integer. If you understand this technical thing well and good, else it is just not important. If I supply over here one of the value as 2.5, then I said NumPy needs all the values of the same data type. However, here you can see it is a float. So it's a clear case of error. NumPy says what I'll do is convert everything to float, because float is a higher data type. Float is a higher data, so it converts everything to float. Okay. Then I can actually create a NumPy array with the same thing, and I can use the D type parameter. So D type, if I say float, then you can see it is of float type, right? And I can also say float 64, by the way, but not required, right? That's what I said, right? You write float or you don't mention it, it will automatically figure out. So you never mention it. That's always good. Better you don't mention it. Then if I say integer, obviously all the values are integer. So what is the point in mentioning? But imagine if there is a value like this. Now, if you say data is equal to integer, it will actually do typecasting on 5.22. So 5.22 became 5 because you forcefully asked it to get converted to this. Okay. That's one thing. Okay. So this was our 1D array. I want to say it was the 1D array. Now I am planning to create a 2D array. Something like this. 2 rows, 4 columns, having the values. It can be anything. This is the row 0, row 1, column 0, column 1, column 2, column 3. Let's call it as ARR only. You know, how do you define it? Every row is a list. And this entire thing, you have to put it in a bigger list. Every row is a list. And this entire thing, you have to put it into a bigger list. So here, I say, let us create a 2D array. So I will see over here how I create. For 1D array, I use one square bracket. For 2D array, there will be two square brackets. If you recall, this is how the figure was. Now there are two square brackets. That's my row 0. That's my row 1. Each has to be given in the form of a list. So it's built on the top of list only. So I can say Yara is equal to np.array square bracket close it. So outer list created, this outer bring bracket. Inside this, another list 10, 20, 30, 40, 50, 60, 70, 80. That's what we said. Now see how conveniently I have created it out. Figure and same, everything same. See 1D array, single square bracket, single square bracket. 2D arrays, two square bracket. It is not mandatory that you write it like this, one below other. You can also write everything on a single line, but this adds readability. So what I mean to say is, it is completely okay if I write it like this. It's just that it is not that readable while creation. So I don't prefer it. I prefer this. You don't end up doing mistakes while the array is getting created. 10, 20, 30, 40, 50, 60, 70, 80. It's a NumPy array. How do I know there are 2 rows and 4 columns? There is a shape attribute. So if you remember that I can print arr.dtype, and that gives me, it's in 64. And if I say arr.shape, that will tell me how many number of rows and columns are there. So I want to tell you that dtype and shape are attributes of the array, and they are not the methods. So the method that we have seen is the array, np.array. But dtype, do we have a round bracket after it, like np.array has a round bracket, or here shape? No, these are attributes. There are hardly 5 to 7 attributes. So there is nothing challenge as such in remembering them. Very, very few attributes are there. So right now, don't ask me what all are the other attributes. Anyways, we'll be studying them in detail. So right now, you just need not worry about it. I was saying, it showed me that there are 2 rows and 4 columns. But, can I write the same code here in the 1D array? It's also called as ARR. So it will once again declare ARR as 1D array. And if I give shape, then what happens? See here, when they created the function, the return type is a tuple. The return type is a tuple. So here also it will return a tuple only. 5 comma, indicating that there are 5 items in the array. There are 5 items in the array, or 5 values in the array. This is how you create a 2D array. And here, if I want to access number 20, it is at row 0, column 1. So indexing, print ARR, row 0, column 1, 20. I can also write the same thing as ARR of 0, 1. Both are same, both are same. You can see both of them are giving the same output. Whichever you find easy, you can write it down. Okay. Now, negative indexing is also there, but you need not do it, right? It's also there, but it's not required. How much ever is required, we can definitely look into it. So, in the same way, other things we'll do it later. Let's not get into the complicated part of slicing right now. I now want to do one thing, and that is I am planning to create one single array. Here. Let's assume this to be it can be any values. I'm just randomly assuming it. This was 1D array. This was 2D array. Now I aim to create a 3D array. Now the 3D array is not a true 3D array. So something like a three-dimensional object. No, nothing like that. It's called as a 3D array, but it's not three-dimensional. So you know how I say that this entire thing is one array, where this is the zeroth array and the lower is the first array. Inside the zeroth array, this is row 0, row 1, column 0, column 1, column 2. Inside the first array, this is row 0, row 1, column 0, column 1, and column 2. And the way I define it is something like this. First of all, every array is a list. So this is an array. I'll just mark it like this. So that's one, and you cover it by an outer one separated by comma. Done. That's one, and you cover it by an outer one separated by a comma. Done. And that's separated by a comma. That is how it becomes a 3D array. See, 1D array, 1 square bracket, 2D array, 2 square brackets, 3D array, 3 square brackets. Let's check it out whether that's really the case. So I say error is equal to okay, it actually heard me. You see over here. Now I can write everything on a single line as I told you, but I am not writing it. And let's check it out. First of all, the way I have declared it's exactly same like this string brackets. Print ARR has printed it exactly same like my figure. Inside this figure, when I say print array, entire thing came. Type of it is a NumPy ND array. Shape, you know, what is the shape trying to say? It says that we have two arrays, each of two rows and 3 columns. Perfect. That's perfect. It says I have two arrays, each of 2 cross 3. You can see that this is 2 cross 3, this is 2 cross 3. And when I want to access 60 is in the 0th array, row 1, column 2, 0, 1, 2. That gives me 60. Or I can write 0, 1, 2. 102 is it 90? 102. 1 is this, 0 is this, and 2 is this, 90. That's correct. So that is how you create a 3D array. Just pasting this as an image for your future reference. So that becomes little convenient for everyone to figure out. So that is how you create it. Now I want to say that I said when you look at 1D, now anything more about 3D, we'll check it out later, right? Right now it's not required. Right now this much is more than sufficient. This was the 1D array. I said that here by any chance, if I put a float value and I print it and I check the D type of it. I print the type and I also check the D type of it. Then it is everything converted to float. Because between integer and float, float seems to have been given a higher precedence. Therefore, everything became float. If I put a Boolean value like true and a false, they are not allowed because array has to be collection of the values of the same data type. But if I put it, then true gets converted to 1.0 and float to 0.0. No problem. You know what I am planning? I want to also show you some other functions, right? So I want to add over here some basic functions of NumPy, precisely the arithmetic operations, or not arithmetic operations, arithmetic functions. So I want to find the sum of these values. How do I find out? Well, print np dot sum of this. So sum of these values would be given over here. In fact, before I do this, let us do it on a basic array without a float. Without a float, let's keep it simple as well. I think that would be 1, or let's say 10, 20, 30, 40, 50, right? So let's see it. So 10, 20, 30, 40, 50 is the 1D array which is created. I just say I want to check the D type. Everything is int, so it is int, and the output is 150. That's good. Let us try other functions. So I have the minimum, I have the maximum, I have the average, which is mean, I have the median, I have the standard deviation, I have the variance. Many functions are there. So I can say np dot minimum of the array, which is 10, maximum, which is 150, 50, mean, which is the average, median, which is the center value after you take all of you are aware what is the median? After sorting the values, the one which comes at the center, right? Yes, after sorting the values, whatever comes at the center is nothing but the median. So, and then you have the standard deviation and variance. So we'll be learning this standard deviation and variance when we get into the statistics part, but in very simple words, standard deviation is how much you are deviating from the mean. For example, if I say for me to go from my home to office, it takes 1 hour because the distance is 25 kilometers. However, if there is no traffic, I'm lucky, I end up reaching in 45 minutes, 15 minutes earlier. And if there is heavy traffic, I end up reaching in 1 hour, 15 minutes. So the average time taken is 1 hour, average, which is the mean. And the standard deviation is 15 minutes. So I take mean plus or minus 1 standard deviation to reach my office. So it can be 1 hour minus 15 minutes, which is 45 minutes, to 1 hour plus 15 minutes, which is this. So that is the range which I take to reach my office. So this can help me to take a decision. If I have to go to my office and if I have a meeting, let's say with the manager, then I will end up considering this time. So if I have a meeting, I'll prefer to leave 1 hour 15 minutes early because I cannot be late. And if it's a regular day and I can take that risk, I can assume 1 hour or 45 minutes to reach the office. So accordingly, I can take that decision as well. Okay. So that is nothing but the standard deviation. So what am I doing over here is just take out this as well. And yeah, you have it over here. So standard deviation and variance. So standard deviation is nothing but the square root of variance. So 200 and square root of this is 14.14. Okay. You also have the product. What will the product do? 10 into 20 into 30 into 40 into 50. You also have the cumulative sum. What is cumulative sum doing? Well, cumulative sum is saying what is 10 plus 20? Here, yeah. So first it takes 10. 10 plus 20 is 30. Then this 30 plus 30 is 60. 60 plus 40 is 100. 100 plus 50 is 150. So this is happening with respect to the plus. If I use comprod, then it will be like, let's take this 10 down. What is 10 into 20? 200. What is 200 into 30? 6,000. What is 600 into 40? 24,000. 24,000 into 50. Yes, and so on. Okay. Difference. Now, what is this difference doing? So, as you can see, difference. It is finding the difference between consecutive values. 20 minus 10, 10. 30 minus 20, 10. And so on. NP dot non-zero. Now, I don't know actually what is this function. It's suggested, but it's never required in my career ever. NP dot non-zero. And what is it saying? So I don't know. It suggested me. So what will I do? No, let's say I don't know, but it is suggesting me something. So copy this. Go to Google. And first thing what I want to show you is the NumPy official documentation, which is available on numpy.org website. It says this version is released. I can click on that. Okay, this is what is the one. I can learn NumPy quick start tutorial and a lot of functions, lot of help available over here to learn shape, size, all these things. I'm gonna first of all come and just put in that documentation link here. Second thing, np.non-zero, I don't understand it. So I'll just search np.non-zero. And I'll also open up this Geek for Geek link and this link because you never know. Sometimes you don't understand from the documentation. Nowadays, I prefer using ChatGPT for getting these answers, but I'm showing you approaches. So this will return me the indices of the elements that are non-zero. Okay. So there is a example as well. So indices of the elements which are non-zero. 0, 1. Where is this? See, easy. 0, 1. This is row 0, row 1, row 2, column 0, column 1, column 2. So 0 and 1 is 8. 0 and 1. 1 and 0. 1 and 0 is 7. 2 and 0 minus 5. And 2 and 2 should be the last one. That is what it's the return. Simple. So in this way, if you get stuck up somewhere, there are a lot of resources available as help, nothing to worry about. Anyways, so I can just execute that, and none of the values are 0, so obviously it will not give me a 0 anyway. Okay. After that, sort. It's already sorted, so can't do anything. Arg sort. Now, what is this arg sort? Well, that's little difficult to say at the moment, but I'll explain it. See, right now, the minimum value in this array if you see, I'm talking about this argument. What is the minimum value? 10. What is the argument of that? 0. Argmax. What is the maximum value? 50. What is the argument of that? 4. Then arg sort is sorting as per the argument. So I'll do one thing. For this arg sort, I will say okay, it's not sorted now. I say entry dot argmin would be 20, sorry, minus 30, which is at index 2, argmax and arg sort. I'll just tell this now. Here. And here, this is the smallest value. It is at index 2. Argument. Highest value is 101, which is at index 1. Sorry, index 0. And if I have to sort it in the ascending order, the ascending order will be minus 30, 20, 40, 50, 101. Argument minus 30 is 2, 20 is 1, 40 is 3, then 4, and then 0. Same thing, no? That's arg sort. What will be the argument if the array is sorted? What will be the arguments which will be coming if the array is sorted? So I'll only take the common functions now. So we saw that these work. Okay, we saw that these work. Now here, when I am taking one item float, do this still work? They work. Okay, they work. The value which I changed is this became 2.2. That's fine. When I convert this, sorry, add a Boolean value. You see over here, Boolean values true and false become 1 and 0, and the D type is still float only. So float is having higher precedence as compared to integer. The Boolean, I'll do one thing. Now, let me add true and false. So So we know that nothing happens. It will be float only. But what if I add a string like darshan? Do you see what happened? So why is, okay, I wrote it in the same thing or what? Oh. Right, so we have this and I added darshan. So see, everything became string. Oh, that means float value did not convert everything to float. That also became string, which indicates that the highest precedence is string. String has the highest precedence. Okay, fine. That's understood. And if I uncomment this from cell number 10 onwards, you get this. It says that here only, right, on line number 10, it says I cannot find the total. Obviously, how do you find out the total of these string values? They are not integer. Everything is converted to string, and NumPy calls it as Unicode 32, and that is important. If you recollect, what did I say? NumPy is mainly used for, what is the full form of NumPy? What is the full form of num? So it is only used for numerical calculations. You cannot do string calculation. So it is very stupid if you try out any of the numerical computations, right? So over here, U stands for Unicode. Unicode is nothing but a string representation format. If you are not aware of that, Unicode number system, this is how it was U11. This is how it represents everything. So everything is represented by something, right, as per Unicode 11 format. So that's okay. That is done now. Then I say images. Abraham Lincoln. Whenever you represent images, images are represented something like this. Images are represented something like this. So as a human, this is how you see image, but a machine sees it like this. Combined, it looks like this. As per a machine, number 0 means black, number 255 is white. So you see over here, these are pure black and they are 0, 0. Or if you see over here, third last row, 255. Then what happens? Because all these values are between, all the values are between 0 to 255. What will happen if I perform the operation of dividing by 255? So what will happen when 0 is divided by 255? 0. What will happen when 255 is divided by 255? 1. Now answer one question. Do you all agree that any number between 0 to 255 when divided by 255 will compulsorily be in the range 0 to 1? Do you all agree that any number between 0 to 255 when divided by 255 will compulsorily be in the range 0 to 1? Yes. This is what is called as normalization. That will be helpful in machine learning and deep learning, but this is called as normalization. And why did I all of a sudden go out of the topic and started explaining this weird thing is because it has some significance now. So, like, because it has some significance, I thought of explaining this to you. The next function which I want to talk about is np.zeros. np.zeros. It says that if you give me 5, print it. I am going to create an array of 5 values, all zeros. If you give me 12, a NumPy array of 12 values, all 0. You can also have the D-type facility to be chosen. So if you say D-type integer, instead of all the float values like here, it will choose as integer. Okay. Now, it says that, Darshan, if you give me 3, 5, then I'll be creating a matrix of 3 rows and 5 columns, all zeros. And this 3, 5 can even be supplied as a tuple. It's not common, but you can supply it. So both of these are ultimately going to create a NumPy array only. If you want, I'll just print the type of array. It's a NumPy ND array. And here as well, it's a NumPy ND array. It's not that because a list is given or a tuple is given, something else is getting created. It's absolutely the same. Okay. So here as well, I have the facility to give D type. It will create a NumPy array of 3 rows and 5 columns. As you see over here, it will create a NumPy array of 3 rows and 5 columns. Okay. That is what we see. Well, what I wanted to say, yes. Just like this 0, you also have ones function, which will create an array of ones. And just like this ones, you also have twos functions, threes, fours, fives, by the way, which is wrong. I'm kidding. You don't have twos, threes, fours, fives. You only have zeros and ones. All the functions of NumPy are added for some purpose. They are not added for time pass. These functions are not added for time pass. They are added for some reason. As I showed you, whenever images which are usually in this range are normalized, they become in this range. And that's why only zeros and ones exist. Twos, threes, fours doesn't exist because sometimes in image processing, what happens is, let's say you are working on some, let's say Instagram, right? You upload some image to Instagram. This is, let's say, the image that you upload to Instagram, and you are trying to apply some filter on it. So Instagram will be creating a copy of this image. How is the copy created? The pixel values cannot be copied directly. First, you create a dummy matrix of all zeros, and then one by one, as and when you are applying, let's say, blur filter. So what will happen with that pixel? That operation will be replaced over here. So that 0 will be changed. What happens with this pixel? That new pixel value is saved over here. So by creating a copy, it can be a matrix of all zeros of the same dimension that you create, or could be one. And that is why these functions exist. As I told you, all of them exist for some reason, right? So these functions are mainly useful while the deep learning stuff. That was the zeros and the ones function. Now, can someone explain me in simple words what is an identity matrix? What are the properties of identity matrix? Okay, identity matrix is here, and in identity matrix as well, of course, you have that D type. D type is almost there everywhere. So you see over here, you have the D type. And there is a I function as well, which also creates an identity matrix. I can show you. NP dot I of 3. Now you will like, but how is this different? Because if I copy this and if I go over here, then it's absolutely same. Why? Then what is the difference between the identity and the I function? Well, here we have the K. Here we have the K. I'll do one thing. So I'll create a identity matrix of 5 cross 5. Okay. So this is how it looks like. So let us create it, and 5 cross 5. So oh, row 0, 1, 2, 3, 4. Column 0, 1, 2, 3, 4. By the way, that's K. K can take any of these values. How? Well, copying this, there is a parameter which is called as K. If I take K is equal to 0, if I take K is equal to 0, no change in the output because K is 0. Same like this figure. But when I say K as 1, now see what happens. The diagonal is here. Of course, it's not a perfect identity matrix, and I am not calling it as identity matrix either. Okay. When K is equal to 2, see it shifted here. So from here, 1, 1, 1, 1, 1 started. When K is equal to 3, it shifted here. And when K is equal to 4, it shifted here. And when K is equal to 5, all zeros. And when K is equal to 6, all zeros. But, we don't need it that often, but it just goes in complement with this. So see, all these functions exist for some reason, but this is very, very rarely required, the I function. It's not required only. I mean, it is applicable for positive values only. I don't know. I never tried it, to be very, very honest. And there is no need to try as well. But let's say if I say K is equal to -1, does it start from back or not? I don't know. But okay, it is -1 means it is taking the column wise, row wise. I never tried it. First time you asked me and I'm trying it out. Yes, I think. But not required, to be very honest. This is very, very rarely required, right? So don't worry about it. I just wanted to teach you identity function because I function goes complementary to that I showed you, but it's not required. Okay, so don't worry about it at all. But I'm sure Sanket and Sandeep, you got the answers to your question. Am I correct? Now, see, we have seen so many functions inside our NumPy. I don't even remember what all functions we studied. Let's say sum function, min function, sort function, argmin function. You studied the argmax, I, on and on, so many functions. And I say that we all studied this inside the module. In fact, there are some other functions as well, which I would like to talk about, like a rand function, rand int function, rand end function, all of this rand stands for random. And because these functions are more or less achieving generation of some random numbers, they are also dumped into a module which is called as random. And the best part is they are a sub-module inside NumPy. So if you have to call, let's say, the rand function, then you say np dot random dot rand. That is how you call this function. I just wanted to show you that, okay, this is how it is done. So I will just get these things for you. Now, we don't have to look into all of these functions, but you saw in the deep learning notebook that random module is little used, not too much, but little used. One of the perfect application of random module is it can be used for generating OTPs, right? Every time you're doing some transaction, some OTP has to be generated, which has to be purely random, not following any pattern, and that should go on to the user and then it must tally. So how do I use it? Well, np dot random dot rand of 5. So it will generate random numbers between 0 to 1. 5 random numbers. Every time I'm running, it is generating 5 random numbers between 0 to 1. Then you have rand n. It will generate the numbers between -1 to 1. See, every time I'm running, you have rand int. You specify the values and it will generate the numbers in between them, low and high. So between 1 and 10, generate 5 numbers. It will always be between 1 and 10. Look into the last line output. Between 1 and 10, 5 numbers will be generated. And many are there. So random model is responsible for generating any value between 0 and 1. Yes, very similar to the above one. I do agree. And so on. We need not look into all, but yes. So in deep learning as well, when you have a set of misclassifications, and if you want to randomly plot one of the misclassified image, that random module turns to be of very heavy help. Okay. Another thing, something very common in the machine learning, like I told you sometime back, code is not important right now. Right? In machine learning, let's say when you have a data set, you always have to separate what you have to predict from what are used to predict it. Like the pink values are used to predict the values in the yellow box. So you have to separate. So now what am I going to consider is a similar analogy where I have values 11, 22, 33, 44, 55, 66. So I want to tell you that usually, like here the tips column is the second column, but usually the column to be predicted is the last one, and the ones which are used for predicting it are here. So what I want to do is I want to separate it out, this blue part into X and this pink part into Y. And before that, I would like to write down some naming convention. This is row 0, 1, and 2. Column 0, column 1, column 2. I can also call it as -1th column, -2 column, and -3 column. Same row also can be called as -1, -2, -3. Let us create a data set. So I say np dot array. Perfect. This saves so much of my time. Now, how I do it is going to be very, very interesting. See, I say in my X array, which rows I want and which columns I want. So I say I want all the rows. That is from row 0 to row 2. So I want it from 0 to 2. So I will write 0 colon 3. And columns, I say I want all columns from C0 to C1, for which I will write 0 colon 2. Then only it will take column 0 and 1. Okay. I can also write this as just colon, because by default, if I don't give the starting and the ending index, then it takes everything. And I can also write this as I want it to start from 0 and go up to -1. So when I say colon -1, it's by default 0. And when you say -1, that means it will go from 0 to -1, -1, which is 0 to -2. Column 0 to column -2. That part. Hey. And as far as Y is concerned, I would say I want all the rows of column -1. So these are my rows. And this is my column, single column, which are single column. I didn't write colon -1. Colon means start from 0. I am directly saying -1. That means clearly I'm saying I want only -1th column. Let us check it out once. So X is equal to array you can see over here. Right? That's X and that's Y. Have a close look at it. It's not difficult, it's just different. I will also first of all like to add this image so that this doesn't go, and then you just quickly keep on observing this. I repeat, my X is all the rows. That means row 0 till this. So I can say 0 colon 3 because row 0 to row 3, which is going to take 0, 1, 2. And column is 0 to 1. So I cannot write 0 to 1. If I write 1, then it will go up to 0 only. So I will say 0 to 2. So it will go from 0 to column 1, column 0 to column 1. And this 0 to 3 can be conveniently just written as colon only, because 0 can be skipped and I can only write 3. 0 is optional because by default it is 0. And here also 0, that can be written as just colon 2. I can write it as colon 2, right? And 2 is nothing but minus 1. Na? 2 is nothing but minus 1. So I can also write it as minus 1. And that's what I wrote. Colon minus 1. And here, when I said colon, I mean to say I want 0 to 3, which is as good as saying everything. And here specifically, I can write I want column 2. Or I can just write 0 colon 3. And I want the minus 1 column. So ultimately, it's one and the same. So now that we are done with this, the next function, which is again very popularly used in machine learning, deep learning, and almost everywhere, that's going to be your arange function. So first of all, if you recall the range function, where I used to say for I in a range of 5, print I, that used to print 0, 1, 2, 3, 4. NumPy says I also have a same function called as arange. Absolutely same function called as arange. So arange will work same like range function, but the difference is arange would be storing these values into a NumPy array. So here I say np dot arange of 5. And if I, let's say, save it into a variable like arr, then you can see over here, it has this, and I can also print the type. You can see the 0, 1, 2, 3, 4. It's a NumPy array. This 0, 1, 2, 3, 4, it's a NumPy array. In fact, even if I say np dot arange of 12, 0 to 11, np dot arange of 1 to 12, it goes from 1 to 11. If I say 1 to 12 at a step size of 2, it goes like this, exactly same like arange. The difference is it will create a NumPy array. That is how this is going to be different. The most important thing over here is the output will always be a NumPy array. The next thing which I want to talk about is, if I say np dot arange of 12, there is one more function called as reshape. This reshape says I will reshape this array reshape says you have the values 0 to 11, right? Using np.arange. Further using reshape, I will reshape this into 3 rows, 4 columns. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Also, for this thing to work, 3 into 4 must be equal to 12. If and only if the multiplication of this turns out to be 12, this is possible, else it's an error. Let's try out the various scenarios. I can say 4, 3, and it works 4 rows, 3 columns. I can say 6, 2, 6 rows, 2 columns. I can say 2, 6 works. I can say 1 into 12 is also 12, right? So obviously now the thing is, what is the difference? Because np.arange and np.arange, and both of these are giving an output. That's the first output. That's the second output. Can you tell me what is the difference in the two, or they are the same? What do you think? Of course, they look the same. What do you say? Very nice. Very nice. Correct. This is one-dimensional array, single square bracket, and this is two-dimensional array. Super. Very good. Very good. 1D array and the 2D array. That is absolutely fine. Okay. Now this reshape. I said whatever you put over here the multiplication must be equal to 12. So 3 into 2 is 6, into 2 is 12. 3 into 2 into 2 is also 12. It does create a three-dimensional array. You can see it has created three arrays, each of size 2 cross 2. So if the multiplication is equal to this, it works. In the same way, if you want, you can create here 2, 2, 3, 3 to the 6, 6 to the 12. So see over here, two arrays of 2 rows, 3 columns. And now you see over here, this is 4-dimensional array. 4 brackets. You never require it. At least I never required it ever. But this is just for your conceptual understanding that, okay, a 4D array is also possible. Okay. So next thing after this is if you have a NumPy, this is I can call it as advanced slicing. Assume that I have a NumPy array and values are 0, 1, 2, 3, 4, 5, 6, 7, 8. Now in this NumPy array, if I say print ARR of control X, let's put it here only. Print ARR of this is giving the output as this. Okay. See, these are the rows and the column indexes which are selected. Row 0, column 1, 1. Row 1, column 0, 6, 3. Row 2, column 0, 6. Done. Now this is done. Now we will never use such kind of advanced indexing, but this is one way of doing the indexing. It is not mandatory that you have to use it. I never use it in real life, but if required, it can be used. As simple as that. Okay. The next is, I want to talk about the concept of broadcasting. This is again a very important concept, broadcasting. And broadcasting is a powerful mechanism that allows the NumPy to work with arrays of different shapes when performing the arithmetic operation. What I mean by that, we will understand it in the code, but this is required in machine learning and deep learning for handling matrix operations when the arrays are of different dimensions. You have a smaller array and you want to multiply it with a bigger array, or the vice versa. These operations can be done over here. So let's understand it with the help of a very basic example. If I say np dot a range of 15 and reshape it to 3 rows and 5 columns. If I say ARR plus 5, maths teacher is going to give a tight slap on my face, saying that Darshan, you don't know a single value cannot be added to an array. Two arrays can be added, but a single number cannot be added to an array. But NumPy says, don't worry, I can do that. It says, what do you want to add? I say, I want to add the number 5. The dimension of this is 3 cross 5. No worries, I will broadcast this 5. So this has become 3. Now it is 3 cross 2, 3 cross 3, 3 cross 4, 3 cross 5 done. Now I'll perform the addition. And there you see the result. So what has happened over here is exactly what we call as broadcasting. Just give me a moment. Now we say that's broadcasting. And in the same way, ARR minus 2 also works. ARR multiplied by 2 also works. So every value will be multiplied. You can just check out ARR and you can see every number is multiplied by 2. Now, if I have an array np.a range of 15 and reshaping it to 5 comma 3, and I have another array np.a range of 5 and reshaping it to 5 comma 1, and I say, now let's understand this. That's an important thing. So you are saying that array 1 and array 2 is to be added. This is array 1. This is of 5 cross 3. You want this to be added with this array 2, which is 5 cross 1, which is 0, 1, 2, 3, 4. Is that possible? No, because it needs 5 cross 3. It will broadcast this. Broadcasted one time. Broadcasted one more time. This also become 5 cross 3. Corresponding values will be added, like you can see. This 0 and this 0 are added. Answer is 0. Or let's say, for example, this 13 and this 4 are added. This 14 and this 4 are added. And you can verify few of the answers, and that's how you got it. So reshaping, that doesn't mean any reshape will happen. First you understand this, then I'll tell you the other part. See, anything cannot be reshaped. For example, this works. But if I have instead of 5, 1, 1, 5, then see it doesn't work. Because 1, 5 means you are saying that to this you want to add this. Even if you broadcast it, so this is 1, 5. Even if you broadcast it, let's say 1, 2, 3, 4, 5 times, it becomes 5, 5, right? So this is 5, 3. After broadcasting this 1, 5, it becomes 5, 5. Still the dimensions are not same. So will you extend the dimensions of this? No, it's not possible. So everything will not work. Only feasible operations will work, and they are useful in tensor multiplications in deep learning. So anything cannot be multiplied with anything. That's an important thing which I wanted you all to know. Okay. The next is, I want to go ahead with linear algebra. So linear algebra is the integral part of machine learning. And let me tell you that your NumPy was initially developed for linear algebra and matrix operations only. However, slowly and steadily, it translated to the machine learning part. So how do I get started with this? Well, let's do something which is called as matrix multiplication. So how do you consider multiplication of the two matrices? Let's say you have np dot array 1, 2, 3, 4, 5, 6. You have another array. This. First of all, what is the order for matrix multiplication? Well, a matrix A of order m cross p can get multiplied with p cross n to give the order m cross n, right? So the columns of first matrix and the rows of second matrix must match. And the way I can perform matrix multiplication is dot product printing C, or there is another way to perform matrix multiplication, and both of these are valid. And the third one also, you can see all of them are giving the same result. Either you use the dot function and supply the arrays, or you use at the rate in between the two, or you use the matmul. All of them are giving absolutely same output. You can check it out. Okay. Then, oh, remind me one thing. I have to show you the speed of the NumPy array that I forgot. Then after that, I say transpose. If you want to find the transpose of the array, let's say I have a NumPy array and I'm printing this. That's the quick way I can find out the transpose of the array, right? You can see what is transpose basically. 1, 2, 3, 1, 2, 3. Rows become columns, another row become another column. Same happens over here. So a dot t, that's a quick way. That's not a NumPy function. NumPy function is np dot. There is one more function which is a dot transpose. Again, this is not a NumPy function. Wherever you see np dot, only that is a NumPy function. So though these many are there, you can see the output of this, and this are the same. But of course, you need to understand this is the only NumPy function. NumPy offers function to do this. Then the next thing which I want to do is solve linear equation. So if I say, consider the following system of equations. I say 7x plus 5y minus 3z is equal to 16. Then I say 3x minus 5y plus 2z is equal to minus 8. And then I say 5x plus 3y minus 7z is equal to 0. Find the values of x, y, and z. We have done this thing in school days multiple times. So we have done this thing in school multiple times. So Control A, Control C, ChatGPT, and I go over here and I ask it to solve it. So 1, 3, 2. These are the outputs. Okay. How will NumPy solve it? NumPy says that what you can do is these all values. You save it into an array. Let's say A. And you know how will I save it? As a two-dimensional array. These all values. You save it into another array called as B. And then you just say not np.solve. And NumPy has a submodule, linear algebra, where you solve A and B, and it will give you the answer. So I say A is equal to this, B is equal to this, and I say np.solve. And you can see I'm getting the output over here as expected. So how are these values set up? Well, if you observe, 7, 5 minus 3, first list. 3 minus 5, 2, second list. 5, 3 minus 7, third list. They are stored as a 2D array. 16 minus 8, 0, 1D array. And then NumPy linear algebra solve and you get it. End of the story. Let's go ahead. Let us get into, do you remember something which is called as a determinant of a matrix you might have studied during the school days? Yes. If someone has forgotten the mathematics of how the determinant of a matrix is calculated, then I cannot teach you that right now, but I can give you the link to study it. So if I have to calculate the determinant of this matrix, it is always the 3 into 6 minus 8 into 4 minus 14. Talking about determinant of a matrix, and I say A is equal to np.array. And the way I find the determinant is simply NumPy's linear algebra modules DET function. Another way is determinant of A dot transpose, but I won't recommend that. I'm not even sharing that. That's the determinant. And then the next is inverse of a matrix. In the same way, you might have studied inverse of a matrix. If you do not recollect it, this is where you can study. It's very nicely explained. Just as an example, I can show you. So if you have this matrix, ABCD, and you want to find the inverse of it, then it is 1 upon AD minus BC, that is 1 upon the determinant of this matrix. And then this diagonal elements A and D are swapped, and the off diagonal elements are multiplied by -1. And that is the determinant. That's the inverse. So I say, so let's say you are having a NumPy array and you directly use the linear algebra's inverse function to do it straightforward. Do you know what is the trace of a matrix? Do you know what is the trace of the matrix? You're expecting, what is the trace of a matrix? Yes, very good. It's the sum of the diagonal elements. That's perfect. Trace of the matrix is nothing but sum of the diagonal elements. So I create an array and I say np.trace. So 1 plus 4 is 5. I have the trace ready. I have the trace ready. So that is nothing but the trace of a matrix. Then now the next one are the few important functions which I would like to say. So I say the next functions which are left out as per me. We're almost done. Just few functions which are left out. The first one is the line space function. Now, what is this line space function? So line space function will be generating all the values in uniformly. For example, if I say np.linespace, you know what will it do? Between 0 to 1, it will be generating 5 numbers, all equally spaced. See, 2.5 minus 0, 0.25 minus 0, 0.25. 0.5 minus 0.25, 0.25. This minus this, 0.25. This minus this, 0.25. If I say that generates 7 numbers, 0.16 minus 0, 0.16. 0.33 minus 0.16, 0.16. 1 minus 0.83, again 0.16 only. Okay, so that is what is the linspace function. The next function which is used is the empty function. So here so what does the empty function do? Very, very simple. If I am saying empty 2, 3, what is it doing? Well, it will be creating a NumPy array without initializing the entry. So array will be containing any arbitrary uninitialized values. Right? So that is the main idea behind it. Now you will be thinking, where is this even required? Well, see, empty function is required in high performance computing and the large scale machine learning pipeline. Because when empty will be useful when you will need to fill the array afterwards, avoiding redundant zeroing. So those all are the places where empty function is useful. In deep learning also, this is useful when you quickly you want to allocate the memory during the mini batch gradient descent technique. Difficult to say right now, but yeah, I mean, that's what I can say. The next thing is the flatten function. So what does the flatten function do? It will flatten the array. It is very popularly used in image processing. If you look, I say array is 1, 2, 3. For it's a 2D array, you know how it is visualized. You visualize it usually like this. But when I flatten it, see this is 2D, and after flattening, it looks 1D. That is the difference. Then second, you have np dot ravel. So ravel is also going to be flattening the 1D array whenever possible. That means it will always avoid copying the data unless necessary. So here, with respect to the Python example, you will see that this also does the same thing. You have the array and it is flattening it only. But the difference is, unlike flatten, it will always return a copy. So Ravel will return a view if possible, making it more memory efficient. Then very simple functions, but they are used in machine learning. The next is swap access. So what does swap access do? Let me show you. Have a look at this first. I have this array, one array of 2 rows and 2 columns. Original shape, one array of 2 rows and 2 columns. I am saying I want to swap the axis of this arrays and 0, 2. You can see I got 2 arrays, each of this comma this will do one thing. Let us print the swapped array as well. So you see it just changed the dimension, and I'll also print the original array. 1, 2, 3, 4 was printed as 1, 3, 2, 4. Now, is that really very helpful? Well, no, very, very rarely used. In fact, I don't remember me using it anytime in my work in last 6 years at least. So you can just consider it as an additional one. That's not really very, very important. The next one, which is important, is the horizontal stack and vertical stack. These are required. So let us start with the edge stack function. So what does this edge stack function do? I'll give you a very, very simple example. Let's say I have this array or let me say see, I have these 2 arrays, as you can see, and horizontal stack has taken 1, 2, and 3 for horizontally. And similarly, if I go ahead with V stack, it has taken 1, 2, 3, 4 vertically. See, it converted these two arrays into two-dimensional arrays. Each of this. No, there is a difference. No? Flatten and this, although working wise they are same, but horizontal stack can take up any number of values and stack it. Flatten takes a 2D and converts to 1D. But it can take this H stack can take any number of arrays and convert it into one flattened list. Flatten will only take one array and convert it into this. Right, yes. So horizontal stack and vertical stack. These are the ones. After that, I guess, I think we are done. One thing which I showed you in the deep learning that I didn't cover, rest all things are good. And the last function to be discussed is the where function. So what is this where function? It will be used in deep learning, as I told you. So what does it do? Well, look into this code. 10, 20, 30, 40, 50 is the array. I say np dot where the value is greater than 25. It tells the indexes. These are the indexes 2 and 3 where the number is greater than 25. Or if I create two arrays and I say condition x greater than 2. So here in this case, over here, in this case, condition x comma y. So you can see all the values in x greater. I'll show you what is condition, right? Let's print condition, then you will understand it. X greater than 2. So these are the values which are greater than 2, 3 and 4. It gave true and true. So 3 and 4, right? So index this. So now false, false, true, true. So in this, it will be mapping. 10 is false, 20 is false, 30 and 40 are true. Therefore, when I say np dot where condition x, right, which is this, and y, and I am looking for the results. I'm looking for the condition x is greater than this. So x greater than this has given me what? X greater than this has given me the 3 and 4. And that is what is here. And y has come as it is. But again, more than this, the first application is more helpful. This can actually little confuse you. This is more easy and more helpful. This completes the NumPy module. Now, out of these functions, which are the most common ones that we'll be using in, day out, there are too many for this. You are finding these functions too many. But according to me, these are the only functions that you'll be requiring it in a long run. And if you internally look into NumPy is a module which you can spend an entire month to read. Over here, you see over here, NumPy can be used for quantum computing. We did not cover this part, statistical computing. Neither we did cover this part. It is used for signal processing, image processing, and so many domains. Surprisingly, geoscience, geographic processing, and so on. So we don't need all of this. Bioinformatics, Bayesian theorem, etc., etc., etc. Right? So you don't need so much of these things is what you need to understand. Pandas. Right. So that is the agenda for our today's session. Let's get started. And we are getting started with the topic of pandas. So pandas is an important library for data manipulation. That means you can change the data, manipulate the data. We say data wrangling, which means cleaning the data, and analysis. It provides, or I can say, the functions of pandas are as intuitive and easy to use as the data structure it provides. Pandas is built on the top of NumPy, right? So it will work seamlessly. And one of the most widely used library anywhere in the data science field. Okay, it is used in each of these fields. That's okay. More importantly, it is helpful in machine learning and deep learning. Now I come on to the data structures of pandas. So pandas provides two main data structures. The first one is going to be a series. And what is series? Series is one-dimensional array. Yeah, we can say array. Very similar to an array only. Series is one-dimensional and there is also an access label. As you can see, it is very similar to a list or a dictionary. Okay, and how to do that, we will see it later. And data frame is a tabular one. So this is how it is. You can read about it later. But the most important thing is the data frame only. The most important thing is the data frame. Okay. Now, so many things, all of these operations can be done on data frame. Now, as and when we go ahead, we will be anyways implementing this operation. So let's not unnecessary invest a lot of time on it. Okay, but all of these operations which are suggested are perfect. Now, if I explain it to you right now, there will be a lot of questions because it recommended. I just took it. All the information was good, but let's do it in action only. So now series. And I like to look into the syntax for creating a series. pd.series index is equal to index. So data is the data that I want to save and index is the index. Now, if you not provide, it is integer by default and it returns a series. Now, obviously, it's better I explain. But before that, we have to import pandas. Do not focus a lot on the content which is generated and you try to read it. Whatever I explain, focus on that. So this will be printing the version of pandas after importing pandas. If you are having a different version, then also it's okay. Okay, so this is one. So this kind of recommendations that I'm getting over here, which can be helpful for you when you study. Let's get into the process of creating a series. So first and foremost, I'll keep it very simple. Let us say I am having a dictionary. So I have a population dictionary where I have California's population, population of Texas, randomly taking the values, Florida's population, New York's population, Pennsylvania population, Illinois population, and finish. I am printing it, and I am also printing the type. So it has to be a dictionary, right? In fact, I need not even write this. I will just keep it simple. I printed the dictionary and I printed the type of it. Simple, a very, very simple dictionary and the type of it. Now, if I say over here that population is equal to PD dot series, and here I am giving the population dictionary. So what am I doing? I am passing a dictionary to the series. We know dictionary is a key value pair, California population, Texas population. If I do this, let's see how it looks like. So this is how a series looks like. Later on, it will be required. So better make a note of it. So the keys of the dictionary are the keys in the series. And the values are the values in the series. At the bottom, you see it also prints the T type. Okay. Then so always a series will look like this, huh? Always a series will be looking like this. And the data type is pandas.core.series.series. As simple as that. Okay. Now let us get into the process of creating a very basic series. So I was talking about this as the syntax. Okay, I'll only take up this. Now, what I say, over here is S is equal to PD dot series, and let's say I give the numbers as 2, 6, 4, 8, 10. I did not give any index. And I say print the series and print the type of it. So you can see the default indexes are being given. You can see the default indexes are being given. Here, what do we understand is if you just provide a list, it creates a series. In the same way, you even provide a tuple, it will end up creating a series. But don't provide tuple, please. Don't provide it. You can even provide a set, but you will not provide it. That's number one. Okay, so here what do we see? Because index is not provided, default indexes are 0, 1, 2. In dictionary, when I supply dictionary, the keys became over here. Okay, that's the very first thing. Now here, you know how is this series saved? Exactly like list. Your indexing is also exactly like list, but I am not talking about indexing at all. So if I say S of 0, because it's a series, S of 0 should be 2. It is. So now we saw that how I can conveniently create a series. But in the series, I can even pass in the index. So if you see carefully in the series, I have passed in the index. And now comes a little bit confusion. That's why I didn't discuss. Now I should write S of A or S of 0. To solve that thing, I said we will be discussing this topic in detail. Right? Maybe S of A works, but there are some other caveats to it. We will discuss it later. Okay. You saw over here that I can do it. if I say S is equal to 2, just a single value, and printing S and printing the type of S. You can see over here, a single item is also assigned S. If I say S is equal to just a single number, I did not pass a list, just a single number, then also it converts it. If I say S is equal to single number, and then I pass an index, it works. That is also obvious. If I say S is equal to single number, but I am supplying A, B, C, D, E, that's a clear case of error. Am I correct or not? This is absolutely a clear case of error. Yes or no? What do you think? Quite obvious, right? Because one value and you are giving multiple things. But that does not happen. Let me just make you recollect. Do you remember yesterday in NumPy, we looked at the concept of broadcasting, with the help of which there was some NumPy array which was 2-dimensional, and I added number 5 to it, and the number 5 was added to each and every value of the matrix. Do you recollect? Yes. Because Pandas is built on the top of NumPy, here also, it doesn't let us down. It doesn't let us down. It broadcasts the value as many times as the number of indexes. Okay. So that's just, I wanted you all to know that 95% of the times you will use data frame only. Series will be only required this much. But whatever is required, at least we should know. So I'm covering all those things for you. Else series are very, 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 very less required. Okay. If I say I am creating a series by passing in a dictionary, maybe something like this. Two colon A. Then 1 colon B. And 3 colon C. Let's say that's it. So we know that, keys and values, whatever are being there, they will be coming down. How? What happened? Yeah, round brackets close. This is something which I'm not finding any interesting. But. In the same here, after this, if I'm giving the index, and if I specify the index as 1, 2, 3, because here while defining I gave 2, 1, 3, but if I specify the index as 1, 2, 3, does it work? Does it give an error? Well, it will work, and it will give more priority to the index order given, and therefore it becomes as 1, 2, 3. Important point to be highlighted. You can understand the difference between this and this. Okay. Does indexes needs to be specifically written? It depends. Depends on your application, Sandeep. You may need to write it, you may not need to write it. But ideally, in a real-time project, you will never create a series by yourself. Neither will you create a data frame by yourself. So practically the answer to your question is no. We never create a series only. Forget about indexes. We never create series. Also arranging the values along with the indexes. That's correct, Anivesh. Showing in the ascending order. No, not ascending order. Showing it in the order which I specify in the index. So what I mean over here, if instead of this, if I just say 2, 3, so it will only select 2 and 3. So it will select 2A and 3C. So it is selecting whatever I'm asking it, right? Yes. Whatever I ask, it will select in that order. There's no ascending or descending order to it. That's it. Now, let us take a step ahead. Now I go on to data frames. Series are all one-dimensional, data frames are two-dimensional. So, syntax is this. It's coming suggesting good. Okay. Now, I remember before that I having a population series created. Yeah, you remember this, right? So this was the series that we created. Now I want to tell you that a list is used for building a series. A series is used for building a data frame. List, series, data frame. So I am planning to take up this series of population and directly pass it over here. So I say Z is equal to PD dot data frame and I only pass the data. Only pass the data. And then I'll show you how this Z looks like. Yes. So it is converted to the data frame. In fact, just like yesterday, I can actually print the shape of the data frame by saying print Z dot shape. You see over here, it says that there are 6 rows and 1 column, which means it is two-dimensional in nature. Here, let's say here we had the series and I want to print the shape of the series. And if I say population dot shape, this is 6, 1, one-dimensional. One-dimensional. Observe over here, this is one-dimensional and this is two-dimensional. Now, we will be creating a data frame. Now, again, as I told sometime earlier, you will never be creating a data frame from the scratch. In real life, you will be reading the data given by the client. You will not be creating it. But in our session, we learn how to create it as well. Maybe for working with some toy data sets, you need it. So I say, let us create a student data frame and I'll copy the syntax. So I am in the process of creating a student data frame. So here we say now, first of all, you just have a look at the output, what we created. That will give you a perfect clarity on what we are trying to build. Okay. And how is it created? Let's focus on that. So you see, I have a simple dictionary. It's a simple dictionary, key value pair, key value pair. Keys are the names of the columns and the values are list. So whatever are the values, that are the contents of the columns. Now I want you to follow this. This dictionary, when passed into the data frame, it creates a data frame. I always advise people to print the data frame directly, as I showed in line number 11, as compared to what I showed over here in the print statement. See, the formatting is way more different and this looks much better. Now have a look at the code. It's really very simple. Perfect. It's better that you don't write print. It's always better. I mean, I always advise. Obviously, this looks good, right? It's better not to write it. And when it is, I'll show you. Now, that should not come up with any demands, but see here, it looks more better in the white mode, but it hurts the eyes. Right? So, yes. This is what we have. Right? So, without print only is always good. So that is how you can quickly create in a data frame. Okay, now that you understand how one can create in a data frame, I can also create it the raw way. So what will I do is, I'm going to import NumPy and I am creating a data frame, pd.dataframe. I need to give the following things: data, numpy.random.random. So it will be responsible for creating what? A 5-row, 3-column matrix. If you don't recollect it, let me show you separately. It will create a NumPy array of 5 rows, 3 columns, right? I'm running it again and again. You can see it's creating a NumPy array of 5 rows, 3 columns with the random values. Okay. Ran it so many times. From 25, I went till 69. So I ran it more than almost 35 times. So then the second parameter, if you recall the syntax, right? That was the syntax. So the next parameter is index. I can say index is equal to how many are there? Index. 1, 2, 3, 5 rows are there. So I can assign 5 numbers over here. And how many columns are there? 3 columns are there. So let me assign this. And I'll print the data frame. You can see over here. Every time you run it, it will be different values. Now, in this data frame, if I want to print the shape of the data frame, I will say print the shape of the data frame. And that says 5 rows and 3 columns. If I want to print all the column names, because here in this case, there are only 3 columns. In real life, you may have 1,000 columns, 20 columns, 100 columns, 200 columns. So when I want to print the columns of the data frame, just like dot shape, I use dot columns, and that will print all the column names. Now, some of you may be like, Darshan, what is this index of this? Why is it printing like this? Don't worry at all. It is Pandas style of printing. And for some reason, if you are not happy, though it's not recommended, better be happy. But if you are not happy for some reason, then what you can do is you can definitely typecast it to a list. But not required. This output is only what I strongly recommend. No one changes it. No one. If you want, you can change it, but no one changes it. So you are unnecessarily investing energy in the unnecessary steps. So you need not, as simple as that. But if required, it can be typecasted. Next. So this is for listing all the column names. If I want to print all the indexes, now in real life, you will never print the indexes because here there are only 5 indexes. In real life, there will be minimum 1000 rows, minimum 1000 rows. So what is the use of printing it? But if you want to do that, you have the index, which you see over here, how it comes. Right? You can see how it comes. Then, if you want to print all the values, see, these are the values, right? These all. If you want to print all the values, then you use the values. Now, let me tell you, this output that you get will be a NumPy array. When the contents of the data frame are printed, what you see is a NumPy array. I'll print that also for you. Print the type of df.values. So you can see it's a NumPy array, and this is how it gets printed. And there is no need to typecast it to a list, but I just typecasted it. It looks like this, but not required. I'll better remove this code. Right now, I want to talk over here that this shape or columns, index, and values, all of these are attributes of the data frame. They are not methods. See, what is a method? Did I write over here index open bracket, close bracket? No, that will not work. They are attributes. Did I write over here shape open bracket, close bracket? No. So these all are attributes of the data frame. These are all attributes of the data frame. And you might be curious on knowing how many attributes are there. I told you yesterday as well, very less, 7 to 8 attributes are there. Now it's like almost you studied most of them. Most of them are done. I think one more is required, which is D types that we'll study in some time, and that should be end of the story. Okay. Now, in real life, we will never be creating the data frames from the scratch. I was very, very clear on that. So how do we actually end up working on this? That is where we need to understand the things. So I want to show you the data set which I am downloading is available on my GitHub repository at this address. I am saving it first of all. So if you see, I saved this data set, I downloaded it, and this is the data set. Okay, I downloaded it. How did I download? When you click on that link, it will open this thing in the browser. Something like that will be open in the browser. You can check it out. Exactly like this, it will show in the browser. Right click on this and you have the option save as, and you save it as simple as that. Save as a CSV file, you are done. Okay. This is just to tell you that, hey, this is what I am doing now. I want to read this. This is a CSV file. Now, there are many types of files that which can be read. Right now, I'm focusing on CSV file. That's going to be the most common. So the link to download the data is this, right? This is the link to download the data. Now, how do I read the CSV file? Same, I say df is equal to Pandas has a function read. Now, if you see when I type REA, even in Google Colab, it will show you suggestions. So what all files can you read? You can read a CSV file. Excel file, feather file. Now, I have never used a feather file, FWF file, but if required, it's not a great thing to read it. You directly have the functions. You can read a JSON file, HTML file, Parquet file, pickle file, etc., 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 etc. So I say I'm gonna read a CSV file. If you write Excel over here and if you're reading a CSV file, obviously expect an error. So read the CSV file. And then what is the name? It is always advisable that this file, you save it in the same folder where your notebook is there. Else, you will have to write the complete path. Complete path in the sense, you will have to write C colon slash slash colon users colon slash 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 till student records dot CSV, right? So you'll have to copy that path here because you're putting it in the same folder. That's not a problem. And I'm done. Now I say, is the data frame red? It is red. It is red. Okay. So that's one thing. Have a close look at the code. Okay. After this, I'll just delete this. Then, if I copy this code and come down, right? If you are having an access to the internet, then you can directly give in the GitHub URL as well to read it, and it will read it seamlessly. You should have access to the internet. See, both of this code, here it's there reading from the local system, and here it is reading over here, right? So it can read it from the internet, as simple as that. But if you are reading it maybe on from some Google Drive or so, then the processes may be different. So ideally 99% of the time you will end up reading from the very popular sources and understand. Our session Pandas. What is Pandas for? Am I here to teach you how Pandas is used for reading each and every type of file? The answer is no. Our session is about understanding how to use Pandas. Reading is one-time affair. Reading is one-time affair. The code for reading a data can be found anywhere on the internet. If I say, let me go on to ChatGPT, and if I say that you are a Pandas expert, get me the syntax and the code to read the file from the most popular sources like, and more, whatever you think is relevant, right? So maybe I'll take one more SQL. I'll take, and there you go. Reading is just one-time affair. Reading is not going to make you an expert in Pandas. What is going to make you an expert is the later part of this. How do you do analysis, cleaning, etc., etc. We have a separate session on data cleaning. So today we are not getting into too much of that, but just remember. So df.read CSV, and you have that basic. CSV sometimes have delimiter other than comma. There are also files called as tab separated value, TSV. So over there, the delimiter is not comma, the delimiter is \t. So you can use this. Sometimes encoding issues come. So encoding is one of the common thing. Usually it's not required right now when you start with the EDA machine learning. At that time, sometimes this is required. Read Excel. Excel in CSV, there are no sheets, one single file, but in Excel, there can be multiple sheets. So you have to supply the sheet name. Then JSON, read JSON. So wherever is your JSON, you can just use this function and give that name of the file over here, right? So orient function is also there in JSON for the JSON in string format. Parquet file is mainly used in the data, what do you call it, in the distributed computing, because it is very fast and saved in purely columnar fashion. But anyways, it cannot be directly open to see the content, but it is saved in a compressed form. When you have huge data, CSVs are not preferred, Parquets are preferred. So that's how you read it, straightforward. For connecting to the SQL, you need to use extra module, import SQLite. And you have to connect to your database whenever you study that at that time. And then you use the standard command of SQL to get it connected. For connecting or reading a HTML page, you have the read HTML, right? I hope that gives you more clarity on that, right? So here, you can also read the clipboard data, whatever you have it on your clipboard. ORC file is again used in something like Parquet only. Feather file, I never used it. It's a fast binary format, but at least I never used it. Pickle file is the format in which machine learning models are saved. So that can be read like this. XML file. And reading from the zip file. This is usually required when you start with the, what do you call, deep learning, when the data sets are very big and you have lot of images to be read. So we usually compress it in the form of a zip file, right? And then after that, reading from S3, Azure or Blob, right? So this is all reading from the buckets. Just like supplying your GitHub URL, you are doing the same thing over here. Now, never ever in my life so far, I have ever read any data from the Google Drive. So in Google Drive, you have some data set. It's not that you click on share this data set and you get the public URL. It will not read it from there. So I have never tried it. And see, as I told you, right, if I have to ever read, no, in none of our consultancy use cases, you will ever read it from the Google Drive. No one puts it publicly on the drive. But if you want to read it, Google Colab is very nice for reading the data from Google Drive. I'll show you that also. But mainly, uh, we never have it, right? In practical life, you will never have it. So, but let's say, how can I read from my Google Drive to my local PS Code Jupyter notebook? Though it's not relevant, it's like not required, but since you are learning it for the first time, you may have all these type of concerns. What will happen here? What will happen there? Manually download. That's the easiest way. Second is there are some external packages like GDown or PyDrive, which can be done. So it's a third-party package. So if I am not there to help you, I think it's not a big thing, right? It says install this package, you install it, and then your link is there. Let's say this is the link. So you'll be giving the file ID which comes in the URL, the link over here, and it will download. And after downloading, it is again reading using the CSV file. So that is how it is. If it's one time or occasional, prefer the manual download option, as simple as that. Now, if you are having a GitHub URL, right, then there is absolutely no need to worry. If you are having a file on the GitHub, then you can directly read it on Google Colab. It's all set. Right? It's all set. Absolutely nothing to worry because it is reading from the internet, and anyways, Colab requires internet. So that is just out of question. This is sorted. Second, the second thing over here is if I have to read it from the file, not from GitHub, then you have the option over here, here, file section. I click on this. and you have the option over here to upload. You may end up asking this to me once again. So I'm telling it right now only so that I need not repeat it. You click on this. Then you click on this to upload. And now I am actually uploading the file. How? By getting into our regular folder. The student records.csv file is getting uploaded and it is temporary upload. You can see the message, warning message, read it. What am I trying to say from this is, if I go to the runtime, because if I close it, see, if I close this file directly, if I close this file, then this runtime which is there, it will be automatically disconnected after some time. And if I disconnect it right now, you see it says all the local variables and files will be lost. So if I disconnect it, it's all gone. So it's temporarily uploaded. Let me reconnect. Now after reconnecting, it doesn't come again. You have to upload it. Click on this and then you upload it. You should always wait for the upload to complete. Don't try to read before the uploading is done, specifically in case of bigger files. So that's one thing. Then how do you read it? Well, let me first copy this code. I come down. Entire code is same if you observe carefully. Entire code is same. I'll just click on this 3 dots and copy the path. I repeat, I click on this 3 dots and copy the path. Control V. And PD is not defined. Oh, I restarted the kernel, right? See, now it came. Right? It came. Achha, I want to tell you that even if you don't click on this 3 dots and copy the path, even if you don't do that. So let's say if I am taking the same code as I took, absolutely same code, you can see that absolutely same code. If I directly give the name of the file without giving that slash content, earlier I gave this complete path, but the default path is slash content only. So even if I do it like that, it works. That is the third thing. The default path is always slash content, so it need not be compulsorily given. Easy. And the last thing, let's say I go to see, there is one more. Let's say there is an superstore.csv file. I'm reading. You can directly read it the same way. But what will I do is I'll first download it. While you're downloading, please do not click on any text. It will select that text and ask you to copy. You don't want to do that, right? So click on this empty portion and you have the option save as. And I'm saving it. Okay. Now, what we do is I'm going to my folder. And then I'm uploading that superstore.csv file. In fact, I uploaded both the files. Now I want to, let's say, read this file. How can I read it? Well, there are some things that you have to understand over here. So where is this file? Well, it's in a lengthy path. I like to show you that. This file I have saved into the folder day2. which is ideally inside our this folder, which is ideally inside our this folder, which is ideally inside Simply Learn folder. So overall, friends, my drive path is very complicated. In my drive, I have created a temporary delete folder. Inside that, there is a Simply Learn folder. Inside that, there is a folder. Inside that, this is our folder. And inside that, this is our folder. And inside that, I have the file. Why am I telling you that is now I want to read that file. One way is, as I told you, I can directly read it. I can say ss is equal to pd.read csv, and you have the file read directly from GitHub, right? Directly from GitHub, you can see that. Okay. It is a big file, 10,000 rows and 31 columns. In fact, all the columns are not even displayed, neither are all the rows displayed. But I want to now read it. And let's say the size of the file is big. So you know what can I do? I have this option, mount the drive. So whenever your file is, let's say 800 MB, 900 MB, then uploading this file would be taking a lot of time. If you already have that file in one of the drive folder, if you already have that file, then it's better that you click on this. It is saying mount drive. When I click, some code will appear in the notebook. Connect to drive. I say yes. It says mounting the drive. No code has appeared. It used to appear earlier, but no code appeared. Earlier, a code used to appear and I had to run it. They automated it. That's good. And then I have my Google Drive mounted over here. I click on this drop down. I click on my drive. Then I look for temporary delete folder. Then I look for the Simply Learn folder. Alphabetically towards the end. Then I look at this IITK because I gave a very complicated path. Then if you give a simple path, then you may not have to do so many things. And inside that, I see these things. I want to read which data set. Superstore, click on this three dots and copy the path. That's it. So first you have to do the mounting. And after mounting, you go to that path and copy the path. Then after that, I can actually say ss1 is equal to pd.read csv, and this path, which it will be pasted by that path. Very lengthy path in my case, but in your case, it may not be such a lengthy path, and I read it. So every time you will have to mount your drive for reading the data. Every time you will have to mount your drive. And your path will be different than mine path. So these are the different ways you can think of reading the things in Colab. Right? So sometimes you will also see the files are zipped. Right? So files are zipped. So these are, another scenarios where you have to unzip the file and read it. But yeah, essentially, these are the ways you do it. Reading of the files and everything is done. And this is my data frame so far. So now we understand the various ways of reading the file and all these things are done. Now, if this is the data frame, I'll read one more data frame, which is the superstore. And let me get the superstore in the Excel file mode. So I'm downloading it so that I can show it to you here only. superstore.xls. ss is equal to pd.read excel. The name of the file is this. Excuse me. And I just say SS. And as expected, Pandas require 3.1 or newer version of PyXL to read this file sheet name. PyXL, I don't want to go open PyXL. It can be read using the Pandas as well. Maybe I have to upgrade my Pandas version. So I say pip install Pandas upgrade, printing the version. It's this one. So this is the latest one specifically. So, but it can be read in Excel as well. Maybe the version is older. That's the reason. But that's not a problem. So you all can see that this works. Maybe my version of Pandas is little old. Let me see what version it supports. Well, it's actually dancing up and down. I don't know why. I click here. 2.2.2. But anyways, it was giving some trouble, but you have it over here, right? So this is how you can read an Excel file. And there are many other third-party libraries. You can use OpenPyXL, and there are many, many more libraries other than OpenPyXL, which can be used for reading the Excel file. But we are here to only understand Pandas and runtime. Sorry, for saving it. Runtime, disconnect. So the code successfully works. That's completely fine today if it didn't work on my system, but I'm sure everyone followed how you can read a CSV file as well. I hope it's clear to everyone. Let's go ahead. And Pandas is like the heart, very, very important. So if you follow it, that's awesome. So now we have our data frame here. Now, what is this data frame? See, this data frame is about a student. There is a student called as Henry. His overall grade is A. He is obedient. He scored 90 marks in the research score subject, 85 marks in the project score subject. Based on that, will the university recommend him some kind of grant or maybe some admission fee discount, scholarship, etc.? Answer is yes. David, on the other hand, overall grade F, not obedient, bad marks, 10 out of 100, 17 out of 100. Recommendation, no. In this way, I have a toy data set. You know why am I considering this toy data set? The only reason is I also have the superstore data set, right? So I do have this superstore data set from where I can read this. The reason I have chosen going ahead with this toy data set is because it will help me understand. For example, if I ask you a question, can you tell me in this data set, which is having 9,994 rows, what all are the unique values in the category column? Can anyone tell me by looking at this, what all are the unique values? No, because you don't see all the 10,000 values. Right. On the other hand, I tell you that, can you tell me what all are the unique values in the recommend column? Can you say in this case, because this data set only consists of 8 rows? It only consists of 8 rows. Yes. So the only intention behind choosing a small data set while understanding the library is we are able to cross check our results. Whatever code I write, it will work on this data frame or it will work on a data frame of any number of rows. The reason for choosing a small data frame is understanding. Okay, don't forget that. The only reason for choosing a small data frame is understanding. Else, absolutely, there is no reason. So, here. So we have all of these things in place, and I was saying we have this data frame as well. Now, in this data frame, if I want to print the shape of the data frame, I will say df.shape. Done. 8 rows, 6 columns. In the same way, if I want to print all the columns of the data frame, I will say df.columns. That is what I will write. In the same way, as I told you, if I want to print the values of the data frame, I will say df.values, which is this NumPy array. If I say I want to print the index of the data frame, I will say df.index. We have already seen that, right? It goes from 0 to 8. This time it's not A, B, C, D, E. If you recall, it's going from 0 to 8. So it is saying that starting from 0, going to 8 minus 1 with a step size of 1. Okay. If they are A, B, C, D or anything else, then it will be displayed properly one by one. Okay. Now, the thing is, if I have to select one single column from the data frame, then I would like to propose you two ways. The first one is using the column name as an attribute, where the syntax is df.column name. Let's say I want to select the recommend column. I want to select the recommend column. So I will write df.recommend. I'll write df.recommend. And you see the recommend column is selected. Very, very easy. Selecting a column of the data frame, because to do some operation, you need to select that. So df.recommend is for selecting one column of the data frame. And overall, if I look into this, the type of df is a data frame. Okay. And data frame is two-dimensional in nature. You know what? What will be the type of this? It will be a series. Type of this will be a series. Listen to me very carefully. This entire thing is a data frame. Every column in the data frame is a series. So that's one series, second, third, fourth, fifth, sixth. So this data frame is a collection of 6 series. Data frame is a collection of 6 series. Okay. Now, this is the first way, and I would like to say that it is not recommended. Now you'll be like, it's so easy, why is it not recommended? No problem. I will like to go on to the second way. The second way is using the column name as the key. Now that may look a little bit complicated, but this is the best way. That's like this. df square bracket, and in double quotes, you write the column name. So you want to select the recommend column, you will write it like this and not like this. And this is what is recommended. Output will be same. You can see the output is the same. Even if I look into the type of this, it will be a series only. But why is this recommended? The reason this approach of selecting is recommended as compared to the other approaches is because, see here, in this data frame, if the name of the column to be selected is not recommend, but if it is research score, then df dot research score. I get this. But imagine the name of the research score column is not like this, but it is research space score. Then it will give an error. I can show you that. I know that df dot columns gives me all the column names. I say df dot columns is equal to paste it. And I say, please make this research score as research space score, overall grade like this for better column readability. And see, everything has changed. So this is kind of like changing the column names. And I was able to put in spaces. I can replace it by anything, but I just inserted spaces. Now, in this case, if I say df square bracket research score, because it is contained in the single quotes, it works, right? So it can be research score can be in double quotes or research score can be in single quotes. That's not a problem. But if I say df dot research score, it can fail. If I say df dot research score, it can fail. Maybe, I'll just comment it out. That's a clear case of syntax error. Therefore, I say it's not recommended. Maybe if you write something like this, it was expected to work, but that also doesn't work. That is the reason I said that the first way, which is square brackets, double quotes, is the ideal way to select. I use any one of these ways. I mean, I can use this one as well. I mean to say I can use this one as well, or I can use this one as well. I recommend you also, but just be aware that when there is a space, the first one doesn't work. Okay. So that is for selecting one single column from the data frame. Okay. What if I want to select more than one column from the data frame? So what all are the column names? Well, the names of the columns were obtained like this, right? So let's say I want to select the columns name, overall grade, and I want to select, let's say, recommend column. Okay, these are the three columns which I aim to select. So these are the names of the columns. So what will I do? I will select I'll create a list, columns to select. I have created a list, which is, these are the columns I wish to select. And then in the data frame, I will put the columns to select. And there you have it. In the data frame, I put columns to select, and there you have it. Look into this code. And because this columns to select is taken from here, then now I'm thinking that what if I actually cut this and just remove this? And here only, whatever I did cut, I paste it. Essentially, I did the same thing. These two are the same. I just replaced line number 2's content directly inside this, if you see. Directly, I replaced it inside this. So what do we understand? For selecting one column, you are going to use single square bracket. And for selecting anything more than one column, you will be using two square brackets. This is what we understand, right? One column or more than one column. And That is how you select it after this. Next we say over here. That's my data frame. Now, if the data frame is SS, it's consisting of these many rows and these many columns. Right. Now, here, obviously it's taking a lot of space on my screen. So what I want to say is, if I want to print the first 5 rows of the data frame, I use the head function of the data frame. So ss dot head, and you can see it only prints the first 5 rows. And inside this, if you supply a number like 2, it will read only the first 2 rows. Inside this, if you supply a number like 7, it will read the first 7 rows. Can you supply 8,000? Will it print all the 8,000 rows? No. Max to max number which I have tried from hit and trial is 60. But don't do that. So, see, this data frame is basically for understanding how the data looks like. It's like, how are you recognized at the airport? You show your passport size photo. This is me. That is the only purpose of this head function. It just shows how the data frame looks like. And if you have to look at the last 5 rows of the data frame, then it is the tail function. Last 5 rows. And in tail also, if you give a number like 3, it will show you the last 3 rows. Then this is what we understand. Now, with respect to the ss dot head only, if you see carefully, I'm not able to see all the columns of the data frame because there are total 31 columns. Now, this comes with a very simple code to be added. So, if you want to display all the columns of the data frame, then you will have to set the pandas display options. And I say over here, pd dot set option display dot max column comma none. None means maximum columns display. If you write over here 7, it will only display maximum 7 column, but you will always write none only. And now if I say ss dot head of 3, you see all the column names. You see a scroll bar as well. So category, city, country, customer ID, customer name, and so on and so forth. This is how the content of the data frame looks like. This is how the content of the data frame looks like. Okay. Now after this, getting back to my data frame df. Now, we understood how to select one column. If I want to look into the data types of all the columns, then I have the attribute called as d types. If I just say df.dtypes, every column's data type is printed. So research score and project score are integer. Depending on the data, it can be float also. If it is 90 point something, then all other columns are string, but Pandas calls string as either an object or category. So don't be worried about it. It is nothing but of the string data type or the categorical data type. Okay, so that's one thing which I wanted to show you over here. So this is all done. Then after that, if you want to print the information about the data frame, you have the info function. And this is interesting because if you look carefully, the output of D types is again printed here. So what all you see over here, it says that, hey, it is a Pandas core data frame. Second, it says there are 8 rows going from 0 to 7. Third, it says there are 6 columns. Next, it says these are the names of the columns, data types of the columns. In every column, how many non-null values are there? Like in name column, it says 8 non-null values are there. Because in our data frame DF, we know that there is nothing missing. Are there any non-null values? No. If there are any non-null values, they will be saved as NaN, not a number. But we can see the entire data frame. So you don't see any non-null values. It says that there are 2 columns of integer data type in this data frame and 4 of the object data type. The total memory usage is 516 bytes. And if I try the same thing with my superstore data frame, see, total 9994 are there. But in the order ID, it's clear that there are missing values. That's why it's saying 800, right? In the same way, going forward, you can look for other things as well. So we understand clearly the data types are there. The size obtained is 2.4 MB plus float data types 2 and this is what we understand from this. So this is over and then DF. Info, this. Yes. If I want to find out what all are the unique values in the recommend column, I can say I want to find all the unique values in the, let's say, recommend column. So I'll use the unique function and df dot recommend dot unique. That's it. So I know it's only yes and no. And it says that, and the output is a NumPy array, by the way. Oh, you don't be worried about it. And if I want to find the count of unique values in the recommend column, I use n unique function. So there are only 2 unique values, right? Yes and no. So the count is 2. Yes, no. Unique values. You get that. So in the Superstore data set, I remember there was a category column. What all were the unique categories over there? Office supplies, furniture, and technology. And if I use the n unique over there, because it was a big data set, there are 3 unique categories. And if I want to print the count of unique values in each column of the data frame, or let's say, I'll be very simple. Here, this recommend column is giving me, when I say df.recommend.unique, what is it giving me? It is telling me what all are the unique values, yes and no. Instead of this unique, if I say value counts, so value counts will be counting the unique values in the recommend column. Have a look at the output. And that's what will be returned. That's what will be returned. Whatever you said, it returned that. Perfect. 5 and 3. That's what it returned. And there is a parameter inside this recommend value counts, which is called as normalize. And the default value of normalize is false. I want to tell you that normalize equal to false is the default value. So if I run it, you don't see any change. You do not see any change with respect to these two codes. Phi 3 is the output here, and here also is phi 3. But if I write normalize as true, then it gives me the percentage. You know what is it giving? I'll tell you. How many times no is there? 5. 5 times no is there. Out of total 8 records, so 5 upon 8 is 62.5. Percentage wise, 62.5% of the times that column contains no, and 37.5% it contains yes. So this is what it is returning me. And if you want it truly in the percentage scale of 1 to 100, then you can definitely take the same code and multiply it by 100. So instead of 0.625, you get 62.5 and so on. Very easy and very convenient. Very easy and very convenient. Right. So this can be helpful in this category column as well. So in this category, if I apply the value counts, out of 9,994 records, I know that most of them are office supplies and the least are from the category technology. So it's very easy to identify at a scale, right? Now in this data frame, if I want to find the missing values, I have the function is null. So it will tell me where all missing values are there. Wherever you see a true, missing value is there. You see anywhere true? I don't see. I don't see. Even I don't see. But if I do the same thing on the superstore, I will go mad because there are 10,000 rows and 31 columns. I don't have time to keep on looking for true this way. I don't have that much time. So what will I do? I will apply the sum function ahead of this. So sum function will be telling how many times in this category column true is there, how many times in this category city column true is there, how many times in this region column true is there, every column total. That's nice. So order ID column has 9194 missing values. Returned also has this. Now it's very difficult for me to keep on searching. So what am I planning to do is this entire thing, can I sort it in the descending order? And I can do that using the function called as sort values, whose ascending is by default true. So I say descending. So what happens is it is going to sort this earlier printed value using the sort values function. Ascending is by default true. So I'm writing descending, which is nothing but ascending is equal to false. And now, because I know that I got the first zero over here, and because this entire thing is in the descending order, I need not even look below because everything is already in the descending order. And that is what is the idea over here. Hence the thing. See now over here, I want to say some important thing. Listen to this very carefully. Now, here in this case, see these are 0, 1, 2, 3, 4, and these are the ones. Internally, it also maintains numbers. And so these are the internally maintained numbers for every row and every column. If you want to refer to those, you have to refer to ilog. And if you have to refer to the external ones, which means the ones which are shown over here and here, you will have to go for log. What I mean by that is, let's keep our target very simple. So my target is to get everything from Henry to Marvin. So this is what is my target. How can I do it? I say df dot ILOC. df dot ILOC. I have to give the rows to be selected and the columns to be selected because I'm using the implicit location. Okay, ILOC means implicit location. So which rows I want to be selected? Well, the rows which I want to be selected are row number 0 to row number 4. I'm referring to the ones which are here. All right. I want row number 0 to 4, which means my starting index will be 0 and my ending index will be 5, which means it will go till 5 minus 1. And which are columns I want to select? I want to select 0, 1 and 2. So I want to select column 0 to 2, which means my starting index would be 0 and ending index would be 3. That is how 0 to 2 will be selected, and here 0 to 5 will be selected, which will take up to 4. Let me try it out. df dot ILOC, row number 0 to 5 minus 1, column number 0 to 3 minus 1. It should give me Henry till Marvin, Y till N. Does it? It does. Did you all follow the ILOC, which are nothing but the implicitly given numbers, which are in the yellow ink? Which are in the yellow ink. Yes. In this way, you can select anything. You can select anything. One operation is sufficient. You can select literally anything, but it has to be consecutive. You cannot say that, can I select one row and then third row and then fifth row? No, that all things are not. That is also possible, but right now we are not getting into it. Okay, this is clear. Now, I'll go ahead. Once again, print my data frame. I say df dot lock rows and columns. Which rows I want to select now? Refer the white one, 0 to 4. So rows I want to select 0 to 4. And the columns which I want to select are what? Right from name to obedient. So start would be name and end index would be obedient. Let me explain you. It has fetched the same thing first of all. Something interesting. The interesting part is in lock, for which I am actually using the pink ink. In lock, the start index had to be 0 and the end index had to be 4. And while giving that, I actually gave the same. I didn't give 5. Earlier, I gave 5. And here the start must be name and the end must be obedient. Exactly that is what I gave. I didn't give obedient plus 1 or something. That is the difference, right? The difference is in ILOC, the start index is start index, but end index is considered ideally as end index minus 1, whereas in lock, start index is start index and end index is also end index. Why? Obviously, you cannot say obedient plus 1 or research score minus 1. That all things, how can you do research score minus 1? That's not allowed. So in lock, start index is start index, end index is end index. This is one of the very important observation. This is one of the very, very, very important observation. Have a close understanding of this concept. What is start index and what is end index in each of these scenarios? So now I got this. I am going ahead. Now here in this data frame, not data frame, I'll go to the population. You remember population was a series that we created at the start. Here, this one, we created a dictionary, and from the dictionary, we created a series. I'm talking about this, right? This. Now, inside this population also, these are the indexes. So here I can say population dot ilog. So if I have to select California, California ideally is at index 0. You see, I'm getting the data for California, right? And if I got to do the same thing and I want to write over here California, then I will have to use log. Gets the same information, right? So this is internally 0, 1, 2, 3, 4, 5. This is what it is internally. Okay. In the same way, if I want to select the data from California to Florida, so California is at index 0, Texas is at index 1, Florida is at index 2. So that means I will have to write population dot ilog, and California is at index 0 and Florida is at index 2. So that will select the entire highlighted portion. So this if I want this as the output, then I will write population dot ilog. It has to be 3. Absolutely correct. Yes. And if this is the code for ilog to get me the following output. Log is about using the externally given indexes, which is California, Texas, and Florida. Now we get into some interesting operations. So what I say over here is, so we have a list of students. We have a list of students. Now, what am I planning is to create their report card. First thing, I am planning that I will like to find out the total of this and create a new column over here, which is called as total, in the sense 90 plus 85 should come here, 85 plus 51 should come here, 10 plus 17 should come here, 75 plus 17 should come here, 20 plus 30 should come here, so on and so forth. How do I do it? Very simple. Research score and project score has to be total. So I write research score like this. And I add it with the project score. Does that give the total? Yes. Did you notice over here, the beautiful part of Pandas is no for loop is required for doing the operations across every row. For loop nahi chahiye. It's not required. It can still manage it. There is a for loop which is running internally, because of which it is actually totaling. Are you all following it? Internally for loop. So it's all basic code is ready. You just have to do the addition and your job is done. Are you clear so far? How did this addition come without a for loop? Very, very important to know. Internally, there is a for loop. When I learned Pandas for the very first time, like an idiot, I used to actually write a for loop to find the total, because I was very much habituated to using C language, C++ language. It took me almost a month to understand that all of these are advanced level coding and I need not think of writing the things from the scratch. So I had a very bad experience when I learned Pandas for the very first time. It took me almost 3 months to be very comfortable with it. I mean, just playing around with everything. It took me 3 months. So, but one thing is remaining. This is okay. But I want this to be saved in a new column. So I say, what is the new column that I want to create? Total. So df of total is equal to this. I'm done. It will automatically create a new column. Best. That is the best part of it. You don't have to worry a lot about it. It will automatically create a new column. How convenient and easy it is. You need not even write a code to create a new column. If you say that I want to create a new column and insert it in between these two, then the things are different. There is a function which is called as insert for inserting it at a particular index. But by default, it is automatically inserted at the end. So let's say you want to create, I'm just doing a dummy column, dummy. Okay. So I want to insert a column. Let's say internally we know, right? This is 0, 1, 2, 3, 4, 5, 6. Let's say in between name and overall grade, I want to create a column called as dummy, which will just have one single value, 1, 1, 1, 1, 1, just like that, just to show you that I want to insert a column dummy in between this. And I don't know how to do it. Let's say I don't know how to do it. I am making you ready to solve any problem by yourself. If I am not there, how do you survive? Go to Google and search for insert pandas. Or let's say you don't know that also, right? So I say insert column in a data frame. Hi, you don't know what to Google, you don't know the name of the function, nothing. Insert column in a data frame. Pandas says I have a method. So this gives me some idea that, okay, I can do it this way. Geek for Geek is also giving me some help. I'm opening it. W3 School is also giving me some help. Let me look into the first help. Insert a column at a, okay, I got it. Insert a column at a specified location. And what it says, first you tell me at what index you want to insert. So that's one thing. Second, it says, tell me the name of the column that you want to insert. Third, tell me the value of the column that you want to insert. And do you want to allow the duplicates? You have over here true or false that can be given. Okay, I understood it. In fact, there is one example also given over here. Okay, that's one thing. Let's say I'm just putting this. Then this Geek for Geek is also there to help us out. So it says that if you have a data frame like this and you want to add a column with static value to the pandas data frame, what have they added? Let me see. What was there? Age, name, and address. Age, name, address. Okay, they added it at the end. Okay, that's okay. Then insert. See here. That's good. This is a good resource. W3 always is awesome. It says, they say you have a data frame. I tried it. This is a data frame, name, age, and qualified. And okay, name and age are only there. Qualified is not there. Let us print the data frame again. And let's run it. You can see name and qualified were there, and now it is name qualified age. It says you have a data frame like this. I say I want to insert at index location 1. The new column called as age. Okay, so this is 0th column. This is the first column. At first column, that means this column will be shifted. And the values will be 50, 40, 30. And that is how you insert, right? You can also insert it on the basis of some condition, but I think that we can take it later. And now that we have it, I don't wish to execute it because we already have it. So I will better comment out this code. You can run it at any point of time. The reason I'm commenting it out because the name of the data frame is df. If I execute this code, then my original data frame is also called as df. That would be lost. So I will have to change the variable name. But anyways, I did show you the output. So I don't think so I need to execute it. You should be able to automatically figure this out. Okay. So that's my data frame so far. Over here, I want to have one more column over here, which will be called as percentage. So how is the percentage computed for Henry? So on and so forth, computed for everyone. So the way I do it is df of percentage is equal to df of total divided by 200 into 100, exactly like this, because total value divided by 200 into 100, you need not write 175, 136, you just give the column name and it is good to do its job. You can see this. So what I want to do is I want to find the topper in the class. So I will consider sorting this data frame in the descending order of percentage, right? A very realistic operation to sort it in the descending order. So I say that I want to sort the data frame in the descending order of percentage column. So the function that I will be using will be the sort values, and you have to sort it by which column. It has a parameter by. So I will supply that I want to sort it by the percentage column, and ascending is equal to true is by default. If I say ascending is equal to false, it will be doing it in the descending order. So this is how I do it. Okay, now pay attention. The sorting happens but does not happen also. I'll tell you what I mean. df dot sort values by percentage column, ascending is equal to false. And you see that it's all in the ascending order, a descending order, all perfect. Let me print the data frame once again for you. Is it really sorted? Answer is no. It's sorted, but then when I printed it again, it is not sorted. Okay, so I was saying we actually sorted the things, and after sorting, we saw that the sorting result is not saved because when I printed it, I don't see this, right? And therefore, we see that the changes are not getting saved. So what will I do? Well, I'll tell you what went wrong. Here, when you said sort it, it actually sorts. It actually sorts in the descending order, but it is not saving it. So you will have to write df is equal to df dot sort. So what will happen is, after sorting, whatever is this result, it will be saving it into df. Okay, that's one way of doing. That is one way of doing. After sorting, you can save it. Data scientists use this second way, in place equal to true. Both of these ways are equally correct. It is not that one way is efficient over other. I'll tell you what is happening. In this case, You sort it on the left hand side, and whatever is the result of the sorting, you ask it to save it to the data frame. And in the second way, or both of them are same, equally efficient, you are sorting it, and I say that, hey, whatever sorting you are doing, do it in the same data frame. Do it in the same data frame. So this is a shortcut of writing. After writing this code, you need not come back and write df equal to. So this is what people prefer. But both of these ways are equally same. It's not that one is efficient over other. As simple as that. And therefore, now when I execute it, what happened? Df dot sort, additional space here. And now when I print it, I use the second syntax with in place equal to true. In place means sorted in the same data frame, and you can see over here, results are here. It is just a way of quickly sorting and ensuring that the changes are saved in the data frame. You can use any one of these two approaches. Both of them are same. Both of them are same. Right? Yes, both of them are same. I would recommend you to use the approach on line number 4, but both of them are equally efficient because they are doing essentially the same thing. All right? Yes. Perfect. Now, how do I know there is an in-place parameter? Well, you can Google about it. Here, sort values. You see over here, there are so many parameters. In place equal to false by default. And what does that mean? If true, it will perform the operation in place. Okay. Then, one interesting thing, the index numbers have changed. Earlier, it was going from 0, 1, 2, 3, but now they have changed. And that's absolutely phenomenal observation. So that's absolutely correct. So what I want to do is, I don't like this. So I will like to reset the indexes. So how do I reset the indexes? I say df is equal to, okay, first let's do it shortcut, df dot reset index. That's it. Let's see whether it resets the index. Data frame dot reset index. It does. See the indexes which were this. So this is a perfect function, right? This column which was here actually got inserted as a new column here. There should be the complaint. Yes, one extra column came. Yes, that's a good observation. Okay, but before I do that, first of all, I will have to save the operation. So I will say df is equal to df dot reset index or df dot reset index, and I say in place equal to true. Any one of this approach. This time I'm using the above one. And then I say, show me the df. Okay. Now there is one problem that we have one additional column inserted. Now I want to talk about dropping a column. So for dropping a column, which will be very useful while you are doing data cleaning, where let's say there are many columns and you don't need some of the column, or you want to drop the less important columns. I want to drop the column. So how do I drop a particular column? So the way one can drop this column is use the drop function. So drop function is used to drop the column. So it is used to drop either a row or a column. Now, how can the same function be used to drop a row or drop a column? Well, because it has an access parameter. So it has an access parameter where if you are supplying access is equal to 1, then it is rows, and if it is 0, it is equal to columns. We don't need all of these parameters, so I don't want to confuse you right now. Okay. Okay. So whichever columns I want to drop, access. Now here in this, labels is which row or column you want to drop. Access is this. Let us talk about it. Let us assume, I'm not actually finalizing this operation, but let's assume that I want to drop row 0 and row 5. Why? Just to show you. I'm not permanently say doing this operation, but I want to drop this too. So what will I do? df dot drop. And which all rows to be dropped? Row number 0 and row number 5. Row number 0 and row number 5. Because I have to drop the rows, I will write axis is equal to 0. And I will not write in place equal to true, else the operation will get saved. I just want to show you. So rows 0 and 5, are they getting dropped? This 0 and 5. Don't refer the index column, the original indexes now. You can see that 0 and 5 are no more there. So in this way, you can drop in the rows. Okay. In the same way, operation is not saved. We all know that. It's just a temporary operation. I want to drop a column. So I say df dot drop. And what I want to drop, you write down the name of the column. The name of the column to be dropped is index. So I'll write index. Axis equal to 1, in place equal to true. See now, if you want to drop more than one column, no problem. This is a list, right? Keep on supplying as many name of columns you want to drop, but that column should be there. If I say over here that could you drop for me the column index 1, there is no index 1 column. It will give an error, key error. That key doesn't exist. But index column is there. It stopped. Okay. Let's say I'm adding a dummy column, df of dummy column, which is just some constant value 100, just a constant value 100. You see a dummy column is added. I want to drop that. Now you know what is the code to drop it, but I want to show you a different way. df dot drop. And the column to be dropped is dummy. So if you see over here, I do have a columns parameter also. If I don't want to go ahead with this style, with the access, you can just say columns is equal to this. And now what will happen is it will still work without access because you clearly said no, that I want to drop the columns by this name. So when you say you want to drop the column, there is no question of access. So access becomes optional in this case. So we saw two things, how conveniently a dummy column can be added and how it can be dropped. So I understand Henry is the student who has got the highest percentage. Okay. That is something which is very clear from this. Let's take it ahead. How to drop the row in the second method. You have rows equal to also as one of the parameter. Rows equal to. So let us consider doing that. So let's say I want to drop the row 3. John's row has to be dropped. So drop row number 3. So you can put it this way. I'm not saving it, sorry. I don't want to save it. I just am trying to show you. That's how you can do it. So John is out. We have this. And percentage column is there. Now percentage is also sorted in the descending order. Now what I want to do is I want to round off the percentage column. So for rounding of the percentage column, I have two ways. So the first is I can say, when I say round off it will round off to 2 decimal places. This will round off to 3 decimal places. And if I don't give any number, it will round off to 0 decimal places. There. I will say, I can also use the round function of NumPy, where I say print. Now you can see round and np.round, both are doing the same thing. Which one will you use in a long run? Which one will you use? The round or np.round? And why? Why? Performance faster. That's correct. So we will use the NumPy. Now in this data frame, it does not matter because we have only 8 records, but in a long run, you will use NumPy, right? Now you understand the true idea behind NumPy. That's good. So friends, I have my data frame over here and I want to round off the percentage. Now, why do I want to round up? Because I want to show you that operation. Else, ideally, one never rounds off the percentage. That's quite logical. But let's say I want to show you that operation because I am trying to give you maximum exposure to pandas. So I say df, or I will say round the percentage column to 0 decimals. So df of percentage is equal to np dot round df of percentage. You need not even write this 0. That is still okay. And it is done. I'm only working on the percentage column, rounding it off, and it is done. After rounding it off, I want to check the data type of every column, or specifically the percentage column. I want to check the data type of that column. What should I do? So yes, there are two ways. D type, D types are not D type, D types. In NumPy, it is D type. Here it is D types. So I can say df dot D types. That's one way, and that's perfect over here, I would say. And it says percentage is of the float. Or I can also say df dot info, which will give this. Okay. So, but the question is, when you look at the data frame, is the percentage column now even expected to be in float? Do you think we should keep it float? Because anyways, there is nothing after dot, right? Yes. So I want to, or I wish to now convert the percentage column to integer. And for that, you have the as type function. df of percentage dot as type to integer. You can also write in double quotes integer. You can also write in double quotes in 64. But why are you complicating the code? This works. And percentage is converted to integer. Now what I want to do is I want to add a column which is called as pass or fail. I want to add a column pass or fail. So I am creating a user defined function called as calculate result, which will be taking in the percentage column. And if the percentage is greater than equal to 40, it will return pass, else it will return fail. Very basic user defined function, which is going to be helpful for adding a new column called as pass or fail. And I want to apply this function, and that is how I do it. I say on the percentage column, I want to apply the calculate result function. So see what happens, let me explain you what happens. First, the number 88, right? df of percentage dot apply calculate result. So number 88 is being passed here. it checks, is 88 greater than equal to 40? Yes, it returns pass, and that pass is saved into new column called as result. Then it sends 86, that will again evaluate and return pass. So on and so forth. It happens till 14. When 14 is sent, 14 greater than 40, no, return fail, and that is saved here. That is how this column is populated. And if you note over here, while giving a call to calculate result, I did not call a function like this. Usually you call a function this way, right? This is how you call it. But you if you give that, that's going to be an error. This is the right way you can call it. Apply is a advanced level function. It says you need not give round brackets. In fact, if you give it, I will give you an error. If you give it, I will give you an error. So you should not give that. And this is the reason we studied the lambda functions. This is the reason we studied the lambda functions. Where, see, if you remember, lambda function, what was the lambda function syntax? We had lambda, arguments and expression. So I can achieve the same task using the lambda function. I am saying df of result underscore lambda because that is already computed. See, lambda percentage, that's the argument. If the percentage is greater than equal to 40, return pass, else fail. So instead of writing a different function, lambda function can be integrated because this is one-time use logic. I'm not going to require again and again, and this is the ideal place where a lambda function is helpful. And then I want to drop this column, which is quite obvious that I need not talk about. So I have the result of the student populated so far. Let's go through what all have we done in the previous class and have a very quick glimpse of it. Pandas consist of two data structures. One is the series and another is a data frame. That's one thing that we understood. And then this is how a series was there. A data frame consists of series. That was another thing that we saw. Then this is the syntax for creating a series. pd.series, you given the data and you given the index. So that's what we have in over here. We also saw how do we do slicing and indexing in series, exactly same like list. In series, we can give indexes of our choice. That's another thing that we have seen and that successfully works. Right, that's how it comes. Then series also supports broadcasting. So if you have one number and multiple things, number is broadcasted. Then we understood a data frame, right? The syntax for creating a data frame, you give data, index, and columns. This population series that we had. See, always remember a series will be represented like this. It will always be like this because going forward down the line, you may experience it. So whenever at the, sorry, not even this, I would say, whenever at the bottom you see D type written with the values above it, always assume this to be a series. And the data frame looks like this. Then after that, when you have a data frame like this, as you can see, these are the rows and these are the columns. Then you can give the index and the columns as well while creating a data frame. Then I can read a data frame from the GitHub directly by pasting the link as it is over here, or you got to supply the complete path. We saw, right? You can read a CSV file, Excel file, all this was ChatGPT generated content. I quickly pasted over here for your reference. JSON file, Parquet file. Parquet is used in mainly the Apache formats. Apache formats in the sense when you are working on a distributed system, Parquet file save the same CSV file in a compressed form. So that is the biggest advantage of the Parquet files. And then SQL databases, you have to import a module and get it done. You can read an HTML file. Then clipboard data, if any table data is copied. ORC, again, it is used in the sense of compressed format only. Feather data set, mainly useful for the pipeline stages. Pickle file for machine learning. XML, we know. Google Sheets also can be read by giving this, this format equal to CSV. These things are important. Zip file can also be read using the read CSV zip, and then you have to unzip it. Then Amazon S3, right? And better option for Google Drive is to download and consume it, right? That's one thing I told you. Or GDown is the package which can be helpful. After reading this data frame, we also read a superstore data frame. We may end up using them little today as well because we are left out with little bit of pandas. So that will take another 1 hour, I guess, 1 hour, 1 hour, 15 minutes for completing pandas. And then we get started with the Matplotlib. Shape will tell me rows and columns. Columns will only print the names of the columns. Now values, the moment I say df dot values, the output that you see over here is a NumPy array. Always remember the output that you see is a NumPy array. To select a single column, you can use dot or you can use square bracket double quotes, of which the recommended syntax is this, because if there are any spaces, then this syntax is better. Then you have to change the names of the columns. You can write df dot column, but you can also change the name of the columns using the rename function. Right? You have a rename function which can be used for renaming the names of the columns. So here, rename pandas data frame column. You see over here, rename function. It needs a mapper. Have they given any example? Yes. So if you see over here, this data frame is being created. So column A, column B. Right? I hope you recollect. This is column A having, sorry. So this is column A having the values 1, 2, 3, column B having 4, 5, 6. So I say rename. Columns is equal to A will be renamed as small a and B will be renamed as small c. So that's how it comes. Initially, the column names are capital A and capital B, like this. But I renamed it to small a and small c. For selecting multiple columns, I said it's always good to use 2 square brackets instead of 1. Everyone knows that very well. Then if you want to see the top 5 rows, use the head function. Bottom 5 rows, use the tail function. And head can also be supplied with a number that will display only that many number of rows. The maximum number that we can give over here is what? What is the biggest value that I can give in the head? Head can display top 5, top 6, top 7. What is the biggest number that one can give in the head? And don't trust me, try it once. You never know, in the updated version of Pandas, this has changed. But I think they won't change it. Usually they don't change all these small things, but you can try it once. On the Superstore data frame, you can definitely try it. Set option. Set option is for displaying all the columns, because earlier you see dot in between the column names. So set option display dot max column will display all the column because the second parameter is none. If I supply 100 over here, it will only display the 100 columns out of, let's say, 500 columns, let's say. So you can choose that number over here. D types, we know all the data types are listed. Info is the information of the data frame. These all are very common functions. You need to use it every time in any project. Then you have to find out the unique values in the recommend column. So that's done using unique function. If you want to find out how many students were recommended and how many are not, that is how many yes and how many no, like here we can clearly see 1, 2, 3, 3 yes and 5 no's. If you want to have that and that too in the descending order, then value counts is the function. Whereas unique only prints the unique values. After that, the value counts can also be given normalized, which is by default false. If I keep it as true, it gives the things in the form of percentage. Multiply by 100 will get it on a scale of 100. So 0.625 becomes 62.5. N unique function, see these all functions, you may be like, these all are so stupid, silly functions. Why do we even need it? Imagine a data set which has 50,000 rows or 5 lakh rows. How will you know how many unique values are there? Because going forward, you'll be looking at a technique like get dummies. I'll tell you what it is. Machine says, Darshan, we do not understand English. Machine says, Darshan, we do not understand English. We only understand numbers. We only understand numbers. So what they do is, if you give it any kind of column which has categorical variables, like for example, this. Or I'll take one more simple example, this. Now, if I ask you, how many unique values are there in the sex column? What will you answer? How many unique values are there in the sex column? 2. Very good. If this data set had 5 lakh rows, would you have been sure about this number 2? If this data set had 5 lakh rows, would you have been sure that there is only male and female? No. Right? This is still okay. This is still okay. But you know what happens when you start with machine learning? Machines say that, Darshan, I do not understand English. So please convert it to equivalent numbers. What I mean by that, let me explain you. So what the get dummies function of Pandas does, we don't have to study it today. It will come in the machine learning part. But what does the get dummies function of the Pandas does over here is it will find out the unique values in this. So the unique values are found out to be male and female, right? So it will create 2 columns, sex underscore male, sex underscore female. And then it looks into the first one is male. So in place of male, it writes 1, female 0. Second is female. So in place of female, it writes 1, that's 0. Third is female. In place of female, it writes 1, that's 0. Fourth is male, it writes 1 over here and 0. Now, this means that one column is converted into 2 columns. If there are 5 unique values, then one column will be converted into how many columns? 5 columns. Now, you will be like, okay, fine, 5 values are still good. I can go ahead with it. If in a column, let's say instead of sex, the column is the products, and that company manufactures 50 different products. So this products column has 5 lakh values and there are 50 unique values. Now, in that case, your data set has one column called as product and there are another 50 such columns which are different, not products, could be sales, etc., etc. But before machine learning, one column would be converted into total 50 different columns. One column would be converted into 50 different columns. And that is not a good idea. That is not a good idea. over there, these functions in machine learning are very, very helpful because you can use the n unique function to find out how many unique values are there in one column. And then if the number of unique values are way more higher, that means if you transform it using the get dummies and it is going to become one column becomes 50 columns, then it's not a good idea. In that case, what is recommended is instead of dummification, you go for label encoding. So what does label encoding do? Label encoding is going to see that, okay, what all are the unique colors? Red, green, blue, red. Red, green, blue are the unique colors. It assigns one number for each. Red is 0, green is 1, blue is 2. Whatever in the order it receives, it assigns that number. And then entire column is replaced with the mapping as red as 0, green as 1, blue as 2, red as 0. So wherever red comes in this column, that will be converted as 0. Wherever green comes, 1. Blue comes 2. So one column is still one column. Now, in which case to use which technique, that's a different story. But I'm just trying to make you understand the significance of n unique. So n unique is number of unique values. You can understand the practical significance of it. That's the only idea behind it. Okay. We will be coming back to this technique later on when we start into the feature engineering session. Right now, it was just to make you understand that all of these functions exist for some reason. Then unique will print out the unique values. N unique will print 1, 2, 3. There are 3 unique values. Obviously, we are looking in recommend. So there are yes and no 2 unique values. In N unique of the category, 1, 2, 3, 3 unique values. Then isnl.sum is for finding out the missing value, the count of the missing values or the sum of the missing values in every column. It's always good to have this in sorted order. So we understood the sort values functions, which will be sorting it to the descending order. Then this iloc and loc were very helpful. Iloc is implicit indexing. Loc is explicit indexing. So iloc is used for implicit indexing. So it will be accessing implicit index 0 and 5. That is rows from 0 to 4. Columns from 0 to 2. And log will be actually going from row 0 to row 4 only and column name to obedient. We had seen that, so let me not get into the teaching part of it once again. We are just getting into the quick revision. Then we understood that we quickly totaled up these two columns and created this column like this. Then coming over here, total upon 200 into 100 gave us this new column called as percentage. Then we sorted the percentage column using the sort values function in the descending order, but this does not get saved. So you need to write preserve the changes. This is also one of the way, but I would recommend this. That's why I kept it uncommented. Because when you're typing the code, you type it left to right, 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 and then you realize, oh, I have to save the change. So you again go over here. That time should not be wasted. Start typing, continuing the typing. Then reset index for resetting the index, but that creates a new column. And for that, we understood that I can either drop a column or I can drop a row. If I want to drop a column, axis is 1. And if I want to drop a row, the axis is going to be 0 in that case. After this, I can also drop without using the axis. So in that scenario, as I told you earlier, what will you do if you want to drop without using the axis? Columns parameters can be used. Similarly, if you want to drop rows without using the axis, rows parameter needs to be used. That's obvious and straightforward. Then round and NumPy round, we rounded off. So I told you NumPy round will be faster. And then the percentage column is converted to any data type, whatever you want, using the as type. And this was an important master stroke over here, that we calculated the result. And see here, the logic is simple. So we can definitely do it using the lambda. So I say that percentage column, I want to apply the lambda function. So every value of percentage column one by one goes into the variable per. And then it checks, is per greater than equal to 40? Yes, return pass, else return fail. That's how it is computed. And the same thing can be done with the help of user-defined function. So the name of the function is calculate result. You can give a call like this. But in such cases, lambda functions are advisable. After that was the end of the session. Okay, now what am I doing? Closing this. And I'm kind of just for the reference, renaming this as old pandas. Okay, so right now I'm naming it as pandas continued and old pandas. Both of them are available. I'll import the pandas library. And we will read this data. We will read this data. Rest of the things, I guess, we don't need it, but both these data sets are being read successfully using this. Now, the thing is, I am planning to look into this. I say info. Now, if you look into this, there must be ideally 9,994 rows everywhere. Then there are no missing values. That's a problem. That's a problem. And rest all things are good. Fine. Chalo, missing values are there. I'm not filling the missing values, but what I want to know is, if you look into the code, what do we see? Okay, I'll just say now here. So now, what I want to see is, what is this data about? Number one, this data set is about categories. Categories like office supplies, technology, furniture. Three categories are there. I know that. All of these are US cities, countries only US throughout. Every customer who ordered a product, it's like an Amazon data, right? Every customer who ordered the data product has a customer ID, and then customer name, date on which he ordered, ordered ID. We don't need all columns. I'm not explaining. Postal code of the customer, product ID, whatever he ordered, product name, quantity ordered. The customer belongs to which region? US has 4 regions: Central, East, South, and West. East, West, Central, and South. There is no North in US. Central. Then, after that, we can see There are three segments in here: consumer, home, office, and office supplies. Then shipping date, shipping mode. There are 4 types of shipping mode. State to which the customer belongs. There are around 17 subcategories. 3 categories were there. There are around 17 subcategories. Discount offered, profit, quantity ordered, sales, return on sales. We don't need all the columns, so neither am I getting into discussion of this. Okay, so this is what we have. Now, what I want to do, what I want to do is I want to find out, there are 17 subcategories. So let's say paper is one of the category. You have binders as one of the category, and so on and so forth. You have 1, 2, up to 17 subcategories. And what I want over here is the average sales of. So I want to find out what is the average sales of paper, what is the average sales of binder, so on and so forth. What is the average sale of this category? Do you understand how you have to approach this problem? Not in code, but do you understand how should you approach this problem? If you have to solve this problem, let's say in Microsoft Excel, do you understand how will you have to do it? Or at least the logic part, you will have to first of all filter the data for paper and find out the average sales. Then you remove the filter. Then you have to filter the data for binder. You find out the average sales, remove the filter, and keep on doing this till the last category and find that. Or another awesome suggestion is the pivot table. And third one is the group by. The third one is the group by. Let's understand. So now that you understand the concept, I am going to make you understand how does the group by works. Then we will get into the pivot table. This is the best example to understand group by, according to me. Maybe according to you it is not, but trust me, it is easy. So just like I said, you assume this column to be subcategory. Assume this column to be subcategory. So what will you do is, there are 3 subcategories: X, Y, Z, X, Y, Z. So uniquely you have X, Y, and Z. You separate out all the X records. Separate out all the Y records. Separate out all the Z records. Then that is what is called a splitting is done. Till this point of time, splitting is done. Then you need to ask which function to be applied. If the user says apply the sum function, then 10 plus 40, 50. 20 plus 50, 70. 30 plus 60, 90. And then you combine this x50 here, y70 here, z90 here. In our case, we asked the function to be applied was not sum, but average. So 10 plus 40 upon 2, 10 plus 40 is 50, 50 upon 2 should be 25. 20 plus 50 is 70, 70 upon 2 should be 35. 30 plus 60, 90, 90 upon 2 would be 45. So here 25, 35, 45. If someone would have said, no, you got to use the minimum function, then minimum of 10 and 40 would have been 10. Minimum of 20, 50 would have been 20. Minimum of 30, 60 would have been 30. So this should have been 10, 20, and 30 respectively. And in this way, it could have been applied to any scenario. Am I correct? Right? This is called as the group by. This is called as the group by. Yes. So now that you say you understand it, I am going to copy the link of this and I go to the next one, group by. And this is the link for it for your reference. Now, let us keep the problem initially simple. In this data frame, what I want to do is, I want to find the average marks of the students who are recommended yes and recommended no. I want to find the average marks. So on what column will I group by? On which column will I group by? I want to find the average marks of student as per recommend. So before that, I would like to show you the syntax. One is this, but df dot group by columns dot. So I will have to specify whichever columns I want, followed by the function name and the columns. I'll explain you what it is. So I say, I want to find out the average marks as per the recommend column. So I say df dot group by recommend, df dot group by recommend. And after that, what do you want? You want the average marks, right? So you use the mean function. And what do you want to see? Marks? No, no, no. Marks is nowhere there. Research score marks. So you got to write that. Do you get that? No. In fact, what does it say? It says that aggregate function failed. And if I cut it and put it here, you get this. So this is one way of doing it. I'll talk about it, don't worry. Or I say df dot group by recommend and aggregate average of this. Okay, you see the same output. Now pay attention what I exactly did. So I'm saying this is something which I usually use. I like to use this, but this is also one way of doing it. It's your choice. Number one, I say group by recommend. Okay, so we are grouping by the recommend. Here also the same. After that, I say I want to see the research scores average. So average marks of the students who passed is this in the research score subject and failed is this. And here I say dot AGG. AGG stands for aggregate. So which aggregate function you want to use? So I say I want to find out the research scores average. So that is what you see over here. Now, whichever you want to use, you can go ahead. The first one, according to me, is more common. However, I want you to look into the format of the output. The format of this output and this output. So this output one is in which format? Or what is the data type of the output? And coming on to the format two, what is the data type of this output? If you want the data type of this output as well as a data frame, then this research score can be just put in double columns. And you'll see the same output. Now you can compare all the three. So this is the one which I usually like. This is the one which I usually like. So always have a habit of putting double square bracket. Okay, now if I copy this, if I copy this, come down and average marks of the students per recommend. Now research score also, and I also want project score. Is that allowed? Yes. So this is the average mark scored by the students in project score subject for not recommend and recommend. And this is for Research score, not recommend and recommend. Those of you recommended pivot table to me, we will come to that as well. Don't worry. Pivot table as well, we'll be looking into right now. I'm not looking into it, but we'll be looking into the pivot table as well. Right, so that's one very important thing. After that, now that we understand this, you can actually change the function. You can go for some function, you get the total marks. You can go for min function. You can go for max function. In fact, you know what? You can also directly type over here describe. So you all know that when I say df dot describe, this is what all you get. This is what all you get when I say df dot describe, which is nothing but count, mean, standard deviation, and all the quantiles from 0 percentile to 100 percentile. So for research score, if you see, I am getting count, mean, standard deviation, and all the percentiles still here. And similarly for the project score also, we are getting the same thing. That's one of the good things. So you can do that conveniently over here. Okay. So that's one thing that you can think of doing. Then the next thing is coming to our superstore data set. That's a problem because over here, what do we want to find out is what I want to find out, I want to find the average sales by each subcategory. So subcategory is correct. Yes, sub hyphen category and sales is sales, S capital. Let's run it then. What is it saying? Aggregate function failed. How is equal to mean? D type is equal to object. These things can happen. Check the D type. I am finding out the average of sales. So whenever you want to find the average, the sales column must be either integer or float. Whenever you want to find out average, it must be either integer or float, any one of it, right? Please look into this. What is the data type of the sales column? Object, right? So I will, this is where your role comes, right? SS of sub category is equal to SS dot subcategory and as type 2. What should I make it? Looking at this value, we can make it as float, right? Yeah, it's a point value is there. So I will make it as float. So I say float. You need not write float 64, only float is also fine. And then I'm looking into the D types. So it says value error. This line only gave an error. Now this code is fine. It says that could not convert string to float. Why? Oh yeah, not subcategory, na sales. 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 And then save it into sales only. Okay, now it should run. 1, 2, 3 run. Oops, again not running. It says could not convert string to float. What could be the issue? It is a clear example of float. Yes, that comma has made it go into coma. Because of that comma, that entire number is not recognized as a float, it is recognized as a string. Rectify this. So we understood what is the issue. In fact, if I say SS of sales and I just look at a sample of 10 values, looks everything good. Another sample, good, good. Here is where we see the issue, right? The sample is randomly picking any 10 values and this comma, right? So what I want to do, I want to get rid of this comma. Okay. So how to remove the comma? All right. Let us say, let us approach this problem as if we are completely new to Pandas and there is no one to help us. So what will you do? You will go to Google first and you will say remove comma from a number in a data frame. Remove comma from number in a data frame. And see, there is a Stack Overflow thing which is helping us out. So this also suggests me, but I'll go to Stack Overflow. And it says, use the replace function. Okay, I like it. I was anyways aware of it, but I'm trying to show you how do you use it. So it says that you use a replace function and this was the code for it. So in our case, this is sales. This is sales. So sales is data frame, not data frame, SS. So in this sales column, first of all, .str will make it a string from object and all the string functions will be available. See, I'll show you that. When I say str and I say dot, see all the string functions are available. You can see over here, all string functions are available, right? Whichever we have studied in the string chapter. And this is where I say, let me replace commas by nothing, commas by nothing. And now I say SS. No, that's done, right? Done. And then now I'm looking at samples once again, just to be double sure. Let a 4-digit number come. I don't see a comma. Everything looks good. Because everything looks good, the data type is still object. But now I think, let me try out the code to convert it to float. This works. Now the sales data type is float, and because it is float, now I can find out this. Does that work? Yes. So we had a glimpse of data cleaning as well. We had a glimpse of data cleaning as well, just because of this problem. And these all things are very, very important. In the same way, now I can find out the average sales per category also. I told you there are 3 categories. That's what I get. Now, if I want this average sales per category in the descending order, then I will apply the sort values function after this. So what will I do is this entire thing I'm going to put in a bracket and then I say sort values and sorting the values by the sales column. Ascending is equal to false. You see the difference? Sort the values by sales column, ascending is equal to false. So it came in the descending order. What if, if I say, do you understand this question? Highlighted one. I want to find out the sales by each category, subcategory. समझ रहे हैं इसका मतलब? right? For example, if most of them didn't understand, consider where we have students from first standard, second standard, right up to 10th standard, right? And in each standard, there are 4 groups. The red group, green group, blue, and the yellow. Here also the same 4 are there. You have that houses, na? Red house, green house, blue house, and yellow house. I hope you all are aware of all these things in the school. Pata hai na? You have the houses. Now, what I want to do is I want to know what is the average marks secured per standard per group. So what is the average marks of the red group in first standard? Average marks of the green house in first standard? Average marks of the students in the blue house of first standard? Average marks of the students in the yellow house of first standard? Average marks of the students in the red house of second standard? So on and so forth till the average marks of students in the yellow house of 10th standard. Now, did you all understand the question? What am I expecting over here? Now, imagine this to be your category. You have 3 categories, right? You assume this to be category and assume this to be subcategory. So, I want to know category, subcategory by sales. So, I will just put category and subcategory. And you get this thing. So, this makes it more clear that, okay, inside the category furniture, these are the subcategories and these are the average sales of that. Inside the category office supplies, these are the subcategories and this is the average of that. Inside the category technology, these are the subcategories and this is the average of that, right? Did you all understand how easy it was to do? I just increase one column. So you can do further more group by if you have further subcategories inside this also. Samajh gaye? Are you all clear with this? Right. Is this exactly what is called as a pivot table? According to me, it's no. This is not truly a pivot table. I don't deny to you. If you recall, in pivot table, you have some rows, you have some columns, and there you fill in the values, right? So based on something over here, you fill up these values. But here you have all of these things over here and the values are here. So I can, now look at this. I'll tell you, I'm copying the same code, pasting it down, and then I am applying the unstack. Now, do you think it's a pivot table? Yes, this is a pivot table. This is a pivot table. Pivot table will always have one column on the rows. It will always have another column on the columns, and the values will be dumped inside it. That's how we understand a pivot table looks like. Some of you may say that we see some odd things like NaN and NaN. See, if the category technology has a subcategory accessories and that is the sales of that. Obviously, if the category is technology, how can the category, if accessories is going under technology, how can accessories go under furniture and office supplies? It cannot. So it's saying not a number, not a number. That means missing values. That means missing values. If there was a value, it will come. If there was no value, it will not come. Like for example, if you see in over here, if bookcases is in furniture, Bookcases cannot be anywhere in the office supplies. If machines are in technology, machines cannot be anywhere in office supplies or furniture. Therefore, for machines in office supplies, machines in furniture, it should be NaN. Let's check it out. You see? But for technology, it's there because machines were in technology. Do you understand why this is getting printed this way? So we did that using this an unstack function. Remember this unstack. Now, if you think that Darshan sir, this code was too complicated, do we have a direct thing to do this? Yes, I can achieve the same thing, and that can be done using a pivot table function. Something like this. Now pay attention. I'll show you. Output is same. Point number one, output is same. How is the code different? Please understand very carefully. What did I say? The index must be category. So that's the index. Obviously, it's a data frame. Then this is the index. That's category. Then it says the columns must be subcategory. So obviously, these are the columns, and that is subcategory. And the third thing which it says, the values must be sales. Which one? Average of sales. The values must be average of sales. So all of these are average of sales. See, whichever you find it easy, you go ahead. I usually find the group by easy, so I prefer that. But if you find the lower one of pivot table easy, you can use that. You know, in this case, according to me, the best way to represent this is this one. Not even the unstacked one, not even the pivot table. This is the best because you don't get confused, because here there are a lot of NaNs as well, right? So in such scenarios, it's not advisable to go for unstack or pivot. This is the best. Now, if I want to find the names of the students, who secured more than 60 marks in the research core subject. So obviously, I will have to select the research core subject. And in the research core subject, that's going to select that entire column of the research core subject. And what I want to know, I want to know the students who got more than 60 marks. So if I do that, you know, if this is greater than 60, it will give true. Greater than 60, true. Greater than 60, false. True. False. True. False. True. You can just have a look at it. When I do that, this is what you get. But you know what? I'm not interested in that. I am interested in finding out where all this condition is giving true. So in the data frame, look for this condition. In the data frame, you look for this condition. So I'll copy this, comment out this. In the data frame, you look for this condition, and I get this. But what are we interested in? I clearly said what I want. I want the names. I want the names of the students. I want only the names. So this is giving a data frame. So from this data frame, I want to select the name column. So for selecting any column, I said that you write in square bracket this. So I can write it ahead of this only. I can write it ahead of this only. And This is what we get. And what is the data type right now? NumPy, DataFrame, series, Pandas, series, right? Yes. From this series, do you all agree that these are the indexes of the series and this pink box is the values of the series? Index values. We have studied all of this, huh? Yes. I am interested in the values. I am interested in the values. So I will further say dot value. See, I'm showing you all step by step. I'll further say dot values. Now, what is the data type of the output? Could you tell me? It's a list, NumPy array, series. It is a NumPy array. It is a NumPy array. Always remember, whenever you see array written in a pandas type of work, it will be a NumPy array. That's why I proved it, right? It's a NumPy array. Okay, chalo. You understand that it will be a NumPy array. So from the NumPy array, I have to convert it to the list form. How can I convert a NumPy array to list? Using the function toList. See, NumPy array is converted to list using the function toList. Or you can also use to_list. It doesn't work. But it works in some cases. It will work in Google Collaboratory. So I'll not do that. In Google Colab, it works. Both the versions of it work. So you can do it this way. That's one way. Or you can say so see, this is also fine. You can typecast it to a list or take this entire thing and use the toList function to do it over here. Okay, so we understand this. And now let's say I want to find out the students who secured more than 60 in the research course subject where this, right? These were the students who got more than 60 in the research course subject and more than 70 marks in the project score subject. So this is what I want. So this was the code for finding out the students who got more than 60 in the research score subject. And for the project score, I will replace it like this. And that was for more than 70. Yeah, these are the students who got more than 70 in the project score subject. But I want to look for both. I say in my data frame, I want to look for condition number 1 and condition number 2. I want to look for both. That's my first condition. That gives me true or false. That will be pasted here. That's my second condition, which gives true or false. That will be pasted here. And now you get the combined output. Then, if I want to find the names of all the students whose name starts with alphabet H, then I'm going to write a code like this. DF, that's the condition, and then DF of name, which will select the name column. .str will convert this object to string for timing so that all the string functions available. One of the string function is starts with. I say starts with H. These are the true things. Look for that Boolean condition inside the data frame, and that will give it this. And then further, if you only want to find out the names, you can write square bracket name dot values dot to list. That's okay. Now let's get started with that. We are now getting into the last part of Pandas, which is concatenating two data frames. Have a look at this. I have created a data frame one. How to create, I am not going to talk about. We know that. We created a data frame one. We created a data frame two. I say concat the data frame one and data frame two. So how is it concatenated? A, B, and C, D. So if you see, this is my, let me use conventions. So I say, this is the data frame one, and this is the data frame two. So how did it actually happen is data frame one and two, when you say concatenate, they are getting concatenated side by side. Okay, this is what we see as the default behavior. And as you can see, A and B, these all things came, and inside the C and D, these all will come. But obviously, because for A and B, you don't have the corresponding values of C and D, they are not a number, and same goes over here. Now, obviously, this is not an ideal case of concatenating, but I just wanted to show you how the concat function works. Okay. Now, one should never use concat without the access. One should never use concat without the access, and the default over here is access equal to 0. So if I actually do that, you see the same thing because the default is access equal to 0. So I can say it's the OR. Okay. And if I say access equal to 1, now you see something meaningful. What has happened is data frame 1, data frame 2. Now you can see this is your data frame 1, and exactly to the side of it is your data frame 2. And this is what access equal to 1 does, right? Truly side by side concatenation and not row wise. So depending on the use case, you can think of concatenating it. Now you'll be like, but where do we actually need concatenation? So let's consider you are Adani Electricity. So today you have a customer base of 50,000 customers in a particular location, right? So many people are using your electricity connection. This is the status as of April 2025. In May, new buildings were built up and they actually started, and another 100 customers, or let's say another 1,000 customers have started consuming that. So Adani might be already having its customer database of these 50,000 customers, customer 1 to up to 50,000. So that could be considering the customer name, customer CA number, customer PIN code, customer units that are consumed, etc., etc., etc. Now, another 1,000 people have purchased that connection, so that 1,000 will be appended below. What are we doing? Isn't that concatenation? Yes. So these all are the practical places where concatenation is usually helpful. As simple as that. I'm talking about the merge function. PD dot merge function implements a number of types of joins. One-to-one join, many-to-one join, many-to-many join. All three types of joins are assessed via an identical call to the ed.merge interface. The type of join performed depends on the form of input data. So I'll explain you everything. Right now, let's get started with one-to-one join. I say they are similar to column-wise concatenation. So I'll explain you with the help of a simple example. It's very, very helpful because in real life, you will never have your entire data into one table. For example, consider Amazon. How it might be storing its data, customer data in one table, all the orders given by customer data in another table. These are linked. Then its employee data in another table. Then its products data in another table. And its transit data in another table, and all of these are linked together. So tomorrow, if you want to figure out which customer has given which order, you may have to refer only two tables, or you may have to refer three tables at once and get from this your result. So you got to create a join of this, and that's exactly where we need this. So I am going to create a data frame, pd.data frame, and let me create a data frame of employee over here, where I say we have employee, and let's say the employees are Bob. Then another employee, let's say Jake, Lisa, and Sue. Okay, that's done. And then after that, let's say the group to which they belong, accounting, engineering, HR. Yeah, that looks good. And yeah, that looks good. In the same way, we have another data frame, which is pd.data frame. And inside that, let's say I have employee, which is Lisa, Bob, Jake, and Sue. And let's say the higher dates are 2004, 8, 12, and 14. Let me print data frame 1 and data frame 2. Right? Now, I say df3 is equal to pd.merge, and I'm showing you df3. Now let's understand this code, right? So these two data frames are created. As far as the code creation is concerned, I'm least bothered. You know how to create a data frame. I'm just not interested in explaining you this, but I'm interested in explaining you this. Whenever you are trying to merge, whenever you try to merge, always remember that merging is possible if and only if there is at least a single column in the data frame which is common. Can you tell me between the yellow and the pink data frame, is there a common column? Is there a common column? Yes. And I'm sure you are talking about employee. Okay, great. Now see how it happens. Bob belongs to accounting group and Bob is hired in 2008. Bob accounting 2008. Jake belongs to engineering group. Jake is hired in 2012. Jake engineering 2012. Lisa engineering. Lisa 2004. Lisa engineering 2004. Sue belongs to HR and Sue is hired in 2014. So Sue HR 2014. So by default, it considered the common column and did the merging. There are many other use cases of it. Okay, that's easy. Then I get into the next one, which is many to one join. So I say many to one joins are the joins in which one of the two key columns contain duplicate entries. For many one the many one yes for the many to one case, the resulting data frame will preserve those duplicate entries as appropriate. Let's see that. How does that happen? I am creating a data frame 4 and this is going to be consisting of group. And let's say group, I'm saying accounting, engineering, HR and supervisor, let's say Carly, Guido, Stu. Okay. And I'm just printing data frame 3. Data frame 4. And merging this. Let's understand what have we done. First of all, you can see I have a data frame employee. I have a data frame over here about the group of the employees. Do I see a common column? Employee group, hire date, group supervisor. Yes. Group is a common column. Then I say Bob belongs to accounting group hired in 2008 and for accounting his supervisor will be Carly. Okay, so that's one-to-one mapping. Jake belongs to engineering group hired in 2012 and for engineering the supervisor is Guido. Jake engineering Guido. Again one-to-one. Lisa belongs to engineering hired in 2004. So for her also the supervisor will be Guido. Yes. Many people are mapped to one supervisor and hence it is called as a many to one join. Next thing you can verify by that. I'm done. Many to one comes to an end. Right? I'm sure everyone understood it. Please acknowledge. Perfect. Thank you, my 57% of the audience. Okay. So now, the next one is many-to-many join. Many-to-many joins are a bit confusing conceptually, but are nevertheless well defined. If the key column in both the left and the right array contains duplicates, then the result is a many-to-many merge. Then I'm saying data frame 5 is equal to, I'll say I'm gonna create a data frame, and inside that group is accounting, let's say, and once again, let's say accounting, engineering, and then I'm planning to go for HR and HR. And then I say skills, let's say math, spreadsheet, coding, Linux, spreadsheets, organization. Okay. Printing the data frame 1, data frame 5, and 3 and 5 merged. Let's understand this. So you can see employee data frame. You can see groups department, the common employee group skills. So common column is group. Now, how is it many to many? Let's see it out. Bob belongs to accounting group, and for accounting group, one needs to have the skill of math and spreadsheet. So one too many has already happened over here. Bob accounting 2008 math, Bob accounting 2008 spreadsheet. Jake belongs to engineering group, and for engineering, you need the coding skills and the Linux one too many. Jake engineering 2012 coding and Jake engineering 2012 Linux. Lisa also belongs to engineering, and for engineering, again, the same skills are required. So now you see many to many as well, right? Because many people like, see, Lisa and Jake, both are belonging to group engineering. And for engineering, you have requirement of two skills, many to many. End of the story. Now let us talk about the confusion that one can have at times. Here we see that group and group are common. Imagine there was one more column called as the employee. So now the problem is this employee and employee would also be common, and this group and group also be common. So when you say pd.merge data frame 3 and 5, it will be grouping on what? It will group on this, or it will group on this. Confusion. So to solve such scenarios, they say that if this is the kind of thing, then in such scenarios, what you can do is you can think of using our parameter on. So I say on is equal to whichever column you want to group. So let's say if I'm saying df1, let me come in here. Let me first check it. Let's say data frame 1 and data frame 2, right? So here when I say pd.merge data frame 1 and data frame 2, you see this. But if I want to specify the common column is employee, now assuming that there is one more column, so I can always say that on is equal to employee, right? So that on parameter specify the column on which to join. Simple. Okay, now I'm creating one more data frame. I call it as data frame 3, and that is equal to pd dot data frame name Bob, Jake, Lisa, Sue, salary 70, 80, 120, 90. Now, you know what is the problem? Tell me a common column in this scenario. Which is the common column in this scenario? So you people were able to figure it out because you are humans, correct? How will the machine figure it out? How will the machine figure it out that this employee and this name are the same? As per a machine, it's a confusion. So you have to tell the machine, because if I directly come over here and I say pd dot merge data frame 1 with data frame 3, it gave an error. So, now understand the way I see about this. See, listen to me. That's my code, right? Give me a moment. So now, saying that, you know what? Now, just like I am looking at you, let's say this is you. You are looking towards the screen. You are looking towards the screen. So we all know that this is your left hand and this is your right hand. So to the left hand, you have data frame 3. To the right hand, you have data frame. Sorry, left hand, you have data frame 1. Right hand, you have this. So what did you all just say? That here in this, you consider employee and here you consider name, right? So you got to specify it that way. So I have that parameter. Left on is employee, right on is name. And see, now it works. To the left side, df1, which is employee. To the right side in df3, consider name and then do the job. Yes, you do see one problem over here, that employee column and name column 2 times have come. But that's okay. I think that's not at all a big thing, because if they are coming for 2 times, you can always say that I want to drop the name column and you only have the column of interest. Name column, it's a column, right? For dropping a column, you need the axis parameter and it is done. Left on and the right on. Remember this parameters. Okay. Understood? Acknowledge quickly. Now we are almost at the end, and then I will keep the scope open for questions on pandas. So I say, I am creating a data frame 6 as pd.dataframe, and that's going to be name as Peter, Paul, and Mary. And I'm considering food as fish, beans, bread. Name as Mary Joseph, and drink as right. So we have these two data frames created. I just want to talk about the merge function. Have a look at this. The common column is name. We know that. I didn't do anything. Peter eats fish, but because no Peter is available here, no record keep. Paul eats bin, but because no Paul is available here, no record came. Mary eats bread, Mary drinks wine. So Mary, bread, wine came. Joseph drinks beer, but no Joseph here. So no record comes. This earlier we never used to see this, that okay, there is only one common record and only that comes, because I had taken the records of the data frame in that way, so that you are focusing on that concept. But now I want to tell you that if it is not available, it does not come if you are doing an inner join. In fact, I can do the same thing, and here you have the parameter how is equal to inner. Same record and same output. So that how parameter can help us out. And you can create any other join like left join, right join, outer join, and the inner join. So I'll copy these things, df6 and 7. So common column is name. Peter eats fish, but no Peter available. So Peter fish, not a number. Paul drinks bean, but no Paul available. Paul builds lot a number. Mary bread, Mary wine, Mary bread, wine. Joseph beer, but Joseph not available. Joseph beer, food not available. Outer join, it will take all the records. So depending on the use case, you can take any one of the joins. I'm sure you have already studied joins at some point of time. So this is what I wanted to say over here. Now, welcome to the world of data visualization. We are going to start the very first visualization. Now, ideally, when it comes to data visualization, it will make more sense when we visualize the data for a data frame. But the basics needs to be understood in a simple way. That is what we are intending to get started right now. So, just to give a heads up, I would like to now get started with visualization with Matplotlib. So Matplotlib is a multi-platform data visualization library built on the top of NumPy arrays. That Matplotlib is a multi-platform library built on the top of NumPy arrays. That's the very first important thing. So over NumPy, Matplotlib is there. One of the most important features of the Matplotlib is its ability to play well with many operating systems and graphical backends. And this cross-platform everything to everyone approach has been one of the greatest strength of Matplotlib. Okay, now this visualization library was built as an alternative for the MATLAB users. So there was earlier a software which is called as MATLAB. Right? This is how it used to look like. And it's a paid software. For your kind information, it's a paid software. It can be used for all of this. And today also it's available, but it is paid. That's the logo for it. And it was very popularly used for data visualization. And this is how the software used to look like. Matplotlib was originally designed or it was written as a Python alternative to the MATLAB's plotting capabilities. And you will see much of its syntax and functionality is similar to this. However, I would say in the recent years, Matplotlib has begun to show its age. You have newer tools like Plotly, ggplot, and Seaborn have emerged that offer modern capabilities. However, or I would say, making Matplotlib feel clunky and old-fashioned. Still, I am of the opinion that Matplotlib, opinion that we cannot ignore Matplotlib's strength as a well-tested cross-platform graphics engine. Okay, let's go ahead. So now let us get started with the library. Now, first and foremost thing, let's import the libraries we need. So import Matplotlib, right? So PyPlot. PyPlot is the library for creating static, animated, and the interactive visualization in Matplotlib, and you will need only that. I mean, since last 15 years, I have been consistently working on this PyPlot only. So that should be more than sufficient. Now, the next is plt.style.use, and you can use any style. So what all styles are available? Well, if you want to actually find out, I want to print all the available styles, then you have plt.style.available. So these all are the styles which are available. So styles are nothing but the themes, right? So any visual can be plot. I'll show you. So this set of visuals, if you use the style instead of BMHS classic, will look like this. In dark background will look like this, and so on and so forth. Similarly, this will look like this, like this. So these all are the available styles. But you can see how each of these visuals are looking like. Now, which one can I use? Well, let me use this time. Seaborn, colorblind. You can choose any one of it. It's your choice. Right? You can use any one of the style. It is your choice. By default, it is classic. So I was saying by default, it is classic, and there we go ahead. So now I set the style as this. And now I will kind of recall NumPy. So there is a function of NumPy which is called as linspace. So if I say 0, 1, 5. So what it does is it returns 5 uniformly spaced numbers in the range 0 to 1. So if you now try to find out 0.25 minus 0, 0.25, 0.5 minus 0.25, 0.25, this minus this 0.25, 1 minus 0.75, 0.25. Everywhere it is 0.25 only. If I say 0, 1 into 10 equal parts, you can find out the difference, right? This minus this 0.111. This minus this is also 0.111. Same thing. Or if I say 0 to 7 in 10 equal parts. See, this minus this is 0.77. This minus this is 0.77. This minus this is also 0.77. So what am I doing is I am saying 0 to 10 into 100 equal parts. 0 to 10 into 100 equal parts. So I have 100 values. I'm sure all of you understood this. 0 to 10 divided into 100 equal parts. I don't want to print it. This is just for your reference. And the y will be the sign of each of these values. Sign. So what is sign of 0? That would be y. sine of this, and so on and so forth. So these are the sign of the 100 values. I'm going to comment on this also, but you understood what is X and Y. Can I assume that all of you have understood what is X and Y? Yes. Now I say, let's get to the plotting. So I am talking about the plot function. So plot function says I need plt.plot X value, Y value, color, marker, line style, label. So X value, Y value, color of the line, example can be given like this. Marker of the line style of the line, label of the line. Let us check it out. I say plt.plot X and Y. So I'm saying that X consists of the 100 values, Y consists of the sign of those 100 values. So it's very simple. We have to plot these. I got this. You see over here, I got this. I just gave these two parameters. And one can understand this really well. Then after that, I don't like this. You know, what is this? This is basically saying that this figure is saved at this address. I don't want it. So I prefer to put a semicolon. Semicolon will suppress that. See, that has not come. But if I don't put semicolon, it comes. You see, this comes. And here it doesn't come. Another way is you can avoid that semicolon is by saying plt.show function, which is mainly used to display the plot. Plt.show is used to display the plot. See, that also hides it. So plt.show is a very common way of going ahead whenever you have to display the visuals. Okay. Now the size of the figure is very big. So I say this has a function which is called as a figure function, which has a parameter which is called as a fixed size. If you make it 1, 1, that means it will keep the size of the figure as 1, 1. Becomes 1 inch cross 1 inch. Can I make it 3, 1? You can. Can I make it 1, 3? You can. Can I make it 3, 3? We can. And I think 3, 3. Okay. Can I make it 4, 3? We can. I think 4, 3 is looking good. Or maybe if I say 4, 2. Yeah, 3, 2 is looking good. I think I need not, in my notebook, 3, 2 looks like a good size. So I'll stick to this. You can play around with these numbers. I'll get in your correct values also. Okay. Now, plt.figure. By default, it gave the blue color. By default, it gave the blue color. You can also set in the color over here. So I set color as red. And red color. So color which I can give is red, green, blue, black, white, or I can also give color in short forms. anything is possible. So this is red. If I give the color in short form, K is black, W is white, R green, blue, black, white. There are many colors available. Okay. Then you have the line style. So line style can be dash. So I'll tell you what all are this. Dash means a solid line. Dash dash means a dashed line. This means a dotted line, and this means a dash dot line. You see, it has become a dashed line. If I say colon, it becomes a dotted line. Okay, so that becomes the thing. Label will use it later. We'll use marker in this case. Well, marker will also be interesting. Marker. Marker is equal to O. That means dots. Marker size is 5. Marker size is 2. 0.5. 0.05. So let's remove the line style. And now you see the marker style over here. Right? So marker size, if I keep it as 0.5, you see the dots over here. If I keep it as 4.5, you can see the dots over here. If I make it 2.5, you can see the dots over here. And if I set the marker as D, that would be diamond. Observe carefully, there is a diamond. And this can be easily understood when you plot a scatter plot. See this. When I go for plt.scatter, same code, size of the marker, if I keep it as, you can see this. If I'm keeping the marker as D, that's a diamond. If I keep the marker as plus, it would be plus everywhere. So what all markers can you put? So these all are the various types of markers. Or you can also refer this. Or we can also refer there was one very good image. I was just looking for that. Yeah, this can also be considered. You can use the marker style of your choice. That's upon you. So you can plot it. You know, I'm not talking about scatter plot and all. We'll be looking into all of these things later on, but this is what we see. Now let us say, I simply say plt.plot x comma y, and then I say plt.show. Correct. Now, Here in this case, just like x and y, I can always say x versus NumPy dot cos of x. So sine and cos both. So when sine and cos both are getting plotted, you see these colors are automatically being chosen, but I'm not able to understand which is sine, which is cos. So what I can do is I can put in over here the line style as this. And here I can put the line style as this. So I know that a solid line is a sine wave and a dashed line is a cos wave. Or I can also think of using the label parameter that this will be labeled as a sin x and this will be labeled as a cos x. Does it come? No. If you have to display it, you'll have to use the legend function. You have to display it, then you will have to use the legend function to display the legend. Legend function is used to display the legend. Okay. Now, if I use the same code and inside this legend, you also have the parameter location of the legend, which I can set it as any one of this. So if I say location has to be upper right, it will get shifted to the upper right and you can give any one of these values. I would recommend you to always put the location value as best. It will automatically choose whatever is the best place for itself. Automatically choose the best place. So it will not be overwritten anywhere. Now, what am I doing is, see here at the top, I'm going to save it as Darshan. So Darshan is equal to plt.figure. So this figure, which you see right now on the screen, is saved or not saved, is saved into the object called as Darshan. See, I printed Darshan. You see that. Now, if I want to save the figure, then I have to say darshan.png and you can just give in these parameters or you can skip it as well. So let's say you can directly say print figure saved as darshan.png. Is it saved? I can check it in my local environment, darshan.png. Yes. And if you want to save it as a particular DPI value or something, this is Darshan one, DPI 300. This is the regular one. This is the one. This is what all you have. Now, what all formats in which you can save it, right? So that can be looked into Darshan dot canvas dot get supported file types. So you can save your figure in any one of this format. I did choose the PNG, which is most popular. Don't ask me about all of the others. I don't use anything other than PNG, but EPS, these all things are understood. This is also understood. RAW is okay. SVG is okay. TIFF and WP. Rest all of the formats, even I don't know. And I don't need it as well. Okay. Now, the next thing that we are looking into is when I say, listen to this, sir. This is important. This is let's say this is your figure. you want to divide it into two parts, two equal parts. Then I can say this is two rows and one columns, inside which I call this as panel 1 and this as panel 2. So this is the first one where I want a sine wave to be plotted. This is the second one where I want a cos wave to be plotted. That's my panel 1. That's my panel 2. How do I do it? It's very simple. You have to use the subplot function. So plt.figure, creating a new figure. plt dot subplot two rows, one column, and currently I'm talking about panel 1. I want to plot x and y. Similarly, I say plt.subplot two rows, one column, panel 2. Have a look at it. Two row, one column, panel 1, panel 2. Or when you have two rows, two columns, this is panel 1, panel 2, panel 3, and panel 4. Left to right, top to bottom. So I say plt dot figure plt dot subplot two comma 2 comma 1 in this first panel x and y. In the 2 comma 2 comma panel 2 cos of x. In 2 comma 2 comma panel 3, I am saying tan of x. And I forgot about panel 4. I didn't write anything about this. It will be empty. Or if I forgot about panel 3, this will be empty. Have a look at the code. And then we have this Control S. Now this is Matplotlib style of doing it. You can also say over here that, let's say, I can also think of it. Listen to this very carefully. I can also think of this, that this entire thing is my figure and I am having access. I am having access. This is row 0, row 1, column 0, column 1. So this is 0 comma 0, this is 0 comma 1, this is 1 comma 0, this is 1 comma 1. So say, how do you do it? This is a different style of doing it. The function which we used over here is subplot. I am doing the same thing, but different. So what am I doing is figure comma axis is equal to plt dot subplots. Is there a difference in the function earlier and now? Do you see a difference in the function? What is the difference is there? What is the difference? Same, na? There is no difference. Difference is there or not there? In the earlier function and new function. The earlier function is there in the chat box. And the new function is there here on the screen. Yes. Extra S subplots. That's correct. So this is subplots. Don't forget that this is the subplots. Figure is the name of the figure, and this pink, all things which are written is those things. So I say over here, figure is the object, AX is the axis of the object, AX 0, 0, 0, 1, 1, 0, 1, 1 are this. Now I say over here, AX 0, 0 will be sine, 0, 1 would be cos, 1, 0 would be tan, and 1, 1 is tan hyperbolic, and you plot it. This is another style of doing it. Whichever is convenient to you, you can use it. This is the object-oriented style. That was the Matlab style. Whichever is convenient to you, you can use it. Now, I think anything else other than this, yes, I want to also talk about few last simple things which are left out. If I say plt.plot x and y, right, and right in this, there is no label on the x-axis, no label on the y-axis. I can say plt.title sine wave, plt.x label x-axis, not x-axis, I would say x only, and plt.y label sine of x. So you see, I have a title x and y, and I can also say over here font size is 20 to make it more bigger, and that is what you have in over here. Perfect. So x label, y label also done. Then after that, we are good to get started with the, I think this is done. Yeah, then we are good to get started with the data set on which you can do all of these functions. Yes. Now we get into the actual use of the charts. Which chart to use when? So I was saying which chart to use in which scenario. This is what we are going to look into right now. So we say histogram. What is a histogram? Histogram is nothing but a frequency chart. So if you look into this, where is my histogram? Yeah, here. Now, what do you understand when you look at this histogram, right? Why do I call it as a frequency plot? Is because we see that this is the tallest. What do we understand? If you look into this number, which is the height of trees, so we understand there are 50 or I can say most of the trees in the data set are in the height range 250 to 300. So that is one of the insight that we understand. Most of the trees will be like this, right? So that's a histogram. Now, if you look into this, the next one is the pie chart. We all know that pie chart is mainly used when there are categories, but I would say as far as pie chart is concerned, one should always avoid it. We are going to plot all. But you know, the problem with pie chart is if I ask you, this is big or this is big, tell me. It is so similar, it's very difficult. Some of you may say they are equal. Some of you may say that this is little bigger than this, but we don't exactly are sure about it. And that is the problem with the pie chart. I call pie charts as evil, because you cannot really use it nicely for prediction. On the other hand, if it was a bar chart, then even if they are very, very similar, one would have been here and one would have been here. You would have clearly said, you only tell me with respect to this and this, which is taller. Tell me which is taller, one is taller or two is taller, right? But this pie chart will confuse you, correct? Because human eyes are not good at ascribing angles. So pie chart would confuse you. Agreed? Whereas bar charts would never. Am I correct? Yes, pie charts will always confuse you. And also, when you have too many categories, avoid going for a pie chart. Or you have to label it like this is the 6 and 7%, very close. If these labels are not there, you are gone. And when there are too many categories, it is always advisable not to go for a chart like this. That's utter stupidity. One should go always for a bar chart. Never a confusion to compare these two. Okay. So when to use it, when not to use it, it's all written. Donut chart. It's nothing but alternative to the pie chart. Box plot. Box plot is mainly used for understanding this. So you know what is it there in the box plot? This is the 25 percentile, this is the median, 50 percentile, this is the 75 percentile, this is the 100 percentile, this is the 0 percentile. So the 5-point summary is there in the box plot. So it is mainly used in identifying outlier, anything which is going below the actual, right? So when you have small data sets, don't use it. When you have complex comparisons, don't use it. Word cloud. What is a word cloud? Well, if I take you to this restaurant and this is the menu card of the restaurant, what would you order? If I take you to the restaurant and this is the menu card of the restaurant, which is the item you are most likely to order when you get a menu card like this? What is the restaurant owner trying to say? Yes, he is trying to say that bigger the text, more popular is the item in my restaurant. So in my restaurant, coffee is popular, romantic dinner is popular, drink is popular. Whereas what is not popular is luxury. What is not popular is grinder. So this is what we understand, right? So this is the word cloud. Whenever you have text data, word cloud is helpful. Now, I didn't get a very good image, but you understand what I mean by this. Like here, right? You clearly understand the most famous item over here in this restaurant or hotel or shop is which one? Chocolate. Yes, chocolate. Chocolate. And if I ask you which is the least popular, which is the least popular? Rice. Yeah, rice is least popular, very small. So that's a word cloud. So use it when you're emphasizing the word frequency and the prominence in the text data. And don't use it when you have complex data analysis or precise comparisons. Bar chart, we already discussed. When you have too many categories, avoid using it. Column charts are nothing but bar charts only, similar. But for longer category labels, they are good, like this longer label. If there are many categories or complex comparisons, don't use it. Example also I have given customer satisfaction by department. Line chart. When will you use a line chart? You will always use a line chart when on the x-axis you have either time or date, like how time-wise the temperature has changed, or how per date the stock market is going up and down. These all are the cases where you will end up using a line chart. Temperature changes, website traffic, etc. Scatter plot is the case where, let's say, on the x-axis you have temperature and y-axis you have the sales of ice cream. So we see that as the temperature increases, the sales of ice cream increases. So in such scenarios, you are advisable to go for a scatter plot. When you have a continuous variable plotted against another continuous variable, it's a line chart. Don't use it when you want to show the trends over the time. Here, line chart will be used, not a scatter plot. So in this case, you'll use a scatter plot, and here, not continuous versus continuous will be a scatter plot, not a line chart. Sorry, scatter plot. Stacked column chart, when the column chart has to be further broken down into subcategories, you go for stacked column chart. When to use it, when not to use it, you got to study it. Area chart, we won't be using it. That's for Tableau and Power BI as well. Bubble chart, we won't be studying it. Heat map. Heat map is used for showing the correlation. For example, if you look into this, as you can see, I have temperature versus sales of the ice cream. And when plotted, we clearly see there happens to be a good amount of correlation, because we see as the temperature is increasing, the sales of the ice cream is also increasing. They say the correlation is found out to be this. But what are the values of correlation? Well, the values of the correlation can be something like this. If you see a line like this, straight line passing all 1. Straight line but moving downwards, -1. Straight line but not covering all but others are very close, high positive correlation, something like 0.9. This is the case of high negative, -0.9. There can be 0.95, 96, 97 also. These are intermediate examples. Low negative correlation, low positive correlation, and as good as no correlation is 0. So when this correlation is plotted, you get a heat map in return. Right. So that is useful for representing data as a color intensity in a grid. So when you have too many categories, looking at each and every correlation value, this can be 0.1, this can be 0.9, this can be 0.3. Looking at so many numbers is going to be difficult. So you look at it in the form of a color. So here, if you look into this, see, when you have so many values, let's say in a heat map, where all will you look? You'll go crazy, you'll go mad. But it's very easy for me to identify that these all things are the same because they are of a lighter color, or these all things are of the same because they are of the darker color. So if I'm interested in finding out the high correlation or low correlation, this color can help us to find out rather than looking into so many numbers. That is where a heat map helps. So you cannot look into a map like this, right? There are too many values and that's too much of confusion. Or look at this. So colors help us to understand that, okay, these two are similar. Tree map, we will never be plotting in our coding. In Tableau Power BI, we may need it, but not here. Then dual axis chart, we will not be plotting in Tableau Power BI. It is helpful. You have something on x-axis, something on y-axis, and something one more on y-axis. So this is the primary y-axis. This is the secondary y-axis. X versus y is the graph. X versus y dash is the line. But you don't need it. It can be done conveniently in Tableau and all. Here it's not required. 3D charts, I would say always avoid 3D charts. There is, in data storytelling, we clearly understand, but you should always avoid 3D charts. I'm asking you, whose supplier share is big? A, B, C, or D? Whose share is the largest? Whose share is the largest? This pie chart is 3D, na? A or B? It's A. And you know why it is? Because the way this pie chart is tilted, it appears that this one is bigger and that one is smaller. And hence you should avoid 3D charts. See, now over here, January is bigger or February is bigger, or both are same. First of all, do you notice over here, this chart is a 2D chart. Forcefully, we have given the third dimension. Iski zarurat hi nahi thi, it was not required. And therefore, I always say, never use 3-dimensional. See, if it is really not required, don't use it. As simple as that. So, in worst cases, if you think that can be helpful, you use it, else you don't use it. This is where your dual axis charts can be helpful. Let's say you are having a subcategory, and subcategory wise, if I'm looking for sales, and let's say I'm also looking at profit. So you can clearly see it has two different charts. Subcategory wise sales is here, subcategory wise profit is here. You can convert it to a dual axis chart. Now, obviously this one is for the profit. So I'll take into the sales and get it converted to a bar chart. And the profit, I'll get it converted to a line chart. And this is what you see. This is called as a dual axis chart. Now, I don't like dual axis chart because you are comparing wrong thing with the wrong thing. You know why? See, this is 0 to 50,000 now. And this is 0 to 50,000. You are just comparing wrong things, right? The margins are not synchronized. And when you synchronize it, now you get the true picture. See, this is 0 to 50. This is 0 to 50. So you have to use it wisely. That's what I wanted to make you understand. So today we are going to do the data visualization using the Matplotlib and Seaborn library. So first and foremost thing, we'll be importing NumPy, Pandas, Matplotlib, Seaborn. Now, let me print all the available data sets in the Seaborn. All the available data sets in the Seaborn. So this Seaborn library is preloaded with these all data sets. And that is done using the get dataset function, right? So SNS dot get dataset names. get datasets name. And these all are the datasets which are already available inside the Seaborn library, free, already available. And one of the dataset which we are going to use is the tips dataset. We'll be using the tips dataset. So now, do you need a pd.read CSV for reading this data? No. pd.dataframe for reading this data? No. You have a very standard function for reading this data. So we'll be using that particular thing. So I'm going to call this data set as tips, and it is loaded like this, right? So I say there is a very standard data set called as and the process of loading the dataset is very simple. SNS.load dataset, and I'm saving it as tips, and let me print the first 5 rows of the dataset by saying tips.head. Now, what is this dataset mainly about? So if you look in carefully, this is the dataset about a restaurant. So if you look in carefully, in this restaurant, the customer who came, right, his total bill was around $16.99. The tip which he gave was $1. She was a female, non-smoker, visiting on Sunday, dinner time, and the size is 2. And the size is 2. Then, second customer, male, Sunday, dinner time, and etc. Then, let me print the number of rows and columns in the dataset, which is the shape. So I say print the shape. So we understand there are 244 rows and 7 columns, right? So this is what we understand. Now, let's further understand this dataset. So if I say I want to print the summary of all the numeric columns in the dataset, I will say tips.describe. So I understand the average total bill in this restaurant is $19 and the median is $15, $17. Little skewness. Average tip is $2.99 and the median is 2.9. Most of the passenger when come to the restaurant usually come in the size 2 to 3 because you see 2.5. Minimum is 1, maximum is 6, median is 2. Then I print the summary of all the categorical columns in the data set. So I say df.describe or tips.describe include is equal to object, and it does not work. So what you can do over here is include is equal to, let's write all. So everything will come. Now, if you look in over here, we understand there are 2 unique values in the male, mostly sex, mostly male, female. Smoker has also 2 unique values, maybe yes and no. The day has only 4 unique values. So the restaurant seems to be open on only 4 days. Time has 2 unique values. One is dinner. I think next should be lunch. Okay. Now let's understand it. So I'll take all the categorical columns. And yeah, this is what I have. For column and categorical columns, I have the unique values in each and every column quickly printed. That's what I see. Okay. Then now you can see what all are the unique values. As discussed, the restaurant, right? The restaurant seems to be open only on Thursday, Friday, Saturday, Sunday, right? So that's what we see. Then I want to print tips of column dot value counts. And normalize into 100. So we understand majority of the customers coming to this restaurant are male as compared to female, 64%. Smoker wise, most of them are non-smokers. This is what we see. Then 61% are non-smokers. Majority of the customers come on Saturday, followed by Sunday, followed by Thursday, and Friday is the least. Quite surprising. And we don't have the data, or the restaurant is not open on Monday, Tuesday, Wednesday. This is another thing that we understand. Percentage wise also, you see almost 70% of them come on weekends. The restaurant, majority of them come for dinner, 70%. Most of them come in a group of 2 couples, or maybe friends. And very few come in group of 1 or 6. Okay. So we get an idea about our data set. So we get an idea about our data set. So let's get started. With data visualization using Matplotlib. So the first one is bar plot. And I will start with the use case of a bar plot. Bar plots are ideal for comparing quantities across categories, and they are very common in exploratory data analysis. They are very common in exploratory data analysis. Okay. Let's look at the syntax. Now, there are many common parameters over here than what I am discussing, but we will keep our focus to the important ones. You have height, width, you have the color parameter. Okay. So now, what am I doing is, first and foremost thing, I want to find the total bill total bill sum by day. So I say bill by day is equal to, I'll be grouping by day and finding out the total bill. And let me print the bill by day. Now, never coming. Let me stop this. The default of observation equal to false is deprecated and will be changed to true in the future. Observe equal to false to retain the current behavior. Third equal to true. Ah. Anyways, we can do one thing. I can suppress that warning. And the way I can suppress this warning is import warnings, warnings dot filter warnings, ignore. So this is to ignore the warnings which are generated by the code. Let me run all. And you can see no warnings are there. Okay, fine. So here I'm printing this. Now, see in this bill, if you see, okay, no, not. If I say dot index, it should give me Thursday, Friday, Saturday, Sunday. And if I say dot values, it should give me these values. So if I say dot index, it should return me this. And if I say by values, it should return me this one. And so on, right? And yes, you can see it is being written. Now I am actually commenting out these 3 lines because I don't need it. I'm getting into my bar plot. So how do I create a bar plot? I say plt dot figure. Let's say fixed size. I'm setting it as 6,4. plt dot bar, the index versus the values. And I just say plt dot title, total bill, plt dot x label is the day of the week, plt dot y is the total bill amount, and plt dot show. Right. So this is what essentially is the main code. Bar plot of this versus this. And you get a nice thing over here. You can see you're getting a nice visual over here. And that's how you are getting a bar plot. And the code is very, very simple. Let us copy this once again. And I am setting color is equal to orange and width is equal to 0.5. So you can see the width of the bar is adjusted. You can play around with this value that I leave to you, but that's completely up to you. What is the insight? Most of the total bills are on Saturday and Sunday. That's an insight. Now we have this. Right. Now, another thing which I want to show you is print bill by day. Right. So that's the index and that's the values, right? So what I want to do, if you want to add the grid lines, you can just say plt.grid. Grid lines will come. And if I say axis is equal to y, then it will only come on the horizontal y-axis. If I say line style is equal to dashed, you will see dash, 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 dash. And obviously they are actually looking like intersecting the plot. So I will make those lines lighter. And for that you have the alpha parameter. So if I give alpha as 1, it's dark. If I give alpha as 0.5, it's light. If I give alpha as 0.3, it's further light. So you can play around these values. Now, I also want to add data labels. So you see, I have added that. And all of them are perfect. See now, listen to this. What has happened? You know, I am saying for I comma v in bill dot values. Let us first try to understand this. Have a look at this. For I comma v in enumerate of bill by values, right? So basically we are iterating through this. It will be considering this at index 1, this as index 2, and so on, right? Because bill by values is going to give you only the values. If you want, I can show you. Right? It is like a NumPy array. So this is at index 0, this is at 1, this is at 2, this is at 3. So I say for I comma v in enumerate. So enumerate means I will be 0, value would be this. I will be 1, value would be this. I will be 2, value would be this. I would be 3, value would be this. So I am having all the values of I and I am having all the values of v. You see this. So what I want to do, see when I'm looking, I is going to go from 0, 1, 2, 3, and V's are going to go from 1096 to 1627. So I say for I comma V in this plt dot text at I comma V. I is over here and value is at 1096 on the y-axis. Exactly here where my pointer is with the horizontal alignment as center. If I don't write that, you see it's getting plotted from here. So obviously from here, it starts printing this value, whatever is the value over here. So over here, plt dot text syntax is like this. So obviously you have horizontal alignment as well, right? So I comma v are this I and v where it is. And from here I start writing. And then of course I'll be also having vertical alignment is this. And okay, some more suggested. So we can actually look into this. Font size and all, we can play around with this. Horizontal alignment, font size, color. And alpha also we can set in, but okay, let's not there. So I'm not doing it. So see over here, you can plot it, but you know, I don't like plotting the text and all that. It's just a waste of time. See, I don't know how much of you will, how many of you will agree completely with me, but in my opinion, you know, as a data scientist, when I do my projects, I don't believe in plotting these visuals unless and until I feel there is a hardcore need. Because according to me, looking at this also, I understand everything. I don't think there is a need for plotting a visual. Don't you think so? It's waste of time to plot the visual. Only this much is more than sufficient to understand. Right? It's a very important thing that you should note. Right? Yes. So we visualize for whom then? See, this is another important thing that everyone must make a note of it. When you are using a software like Tableau for data visualization. So yes, when a software like Tableau is being used for data visualization, where you are actually connecting to some data set, and then you come over here and let's say you are looking at the category wise sales or category subcategory wise sales. Now, in this case, or let's say if you're looking at just subcategory wise sales, or you're changing it to a pie chart or a horizontal bar chart or a tree map, right? Or even you change it to a bubble chart. So when you are doing all of this in Tableau, you are creating this visuals for whom? You are creating it for the management and the stakeholders so that they understand the insights from the data. But when you are doing the same thing in the Jupyter notebook, this is not for sending or sharing with the managers. This is only for you. This is only for you. Max to max, let's say your manager says that, okay, fine, you can show me the insights in your notebook, then you can create it. So usually what happens in data science, you remember I explained you the CRISP DM pipeline, cross industry standard for data mining. See, this is a very simple and important observation for all of you. So whenever you look at a data, not data analysis, the machine learning project or a deep learning project, it has to go through the following stages, starting from business understanding, understanding of the data, looking over here, what is the data about? Are there any cleaning necessary? So that exploratory data analysis, visualization, all come over here. But why are we doing all of these things? So that we can create machine learning models. After that, we can evaluate which machine learning model is good, and then we can productionize it. For that, we are doing it. There are no other reasons for us in doing it. So the same thing applies over here. If no one is going to look at the charts that you have created, and your end goal is to create a model, and if you are comfortable to go ahead without doing data visualization, for some visuals, maybe visualization is helpful. So understand over here, this visualization is not something where you have to be really awesome about. In real time, it is important, but you need to understand in which situation will you create it and in which situation you can conveniently ignore it. So based on your use case, you take a decision. Like for such things, it does not make sense even 1% to plot the visualization. And after that, taking more efforts in plotting the text on it is even high level of stupidity. I'm being very practical over here. Plotting makes it look good and all, but you're wasting your time. You're wasting your precious time. That's what one thing I want to tell you. So that's one thing that we understand. And the next visual that we get into is a histogram. So the use case of histogram is histograms are used to visualize the distribution of a single numerical variable, and it is essential for understanding the frequency distribution of the data, the skewness of the data, or the modality of the data. So let me look into the common syntax. plt.hist bins, which is by default 10. So I'm just writing Color can be whatever color name you want to give. Alpha, you can give that, you can give the edge color as well, right? So how do you create it? So histogram, it's a univariate plot. It's not a bivariate plot. It's a univariate plot. Univariate means it can be plotted using only one variable. Just like here, you need something on the X and something on the Y. So I call this as a bivariate plot. Bivariate means you need two things. X and Y, X-axis and Y-axis, bivariate, bivariables, two variables. And histogram is univariate. So let us quickly go ahead and plot a histogram. So I'm planning to go for this. So plt.figure 6 comma this, and we'll be seeing tips of total bill and bins 20, color orange, alpha is the transparency, edge color I am setting as black, title will be distribution of the total bill, X label, Y label, grid, you know that, and this. So maybe alpha, I'll keep it as 0.9. Have a look at the code and the output. If I know, if I do not give the bins, by default, Matplotlib will have 10 bins. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now looking at this, do you realize, I mean, the tallest one is this, second tallest one is this. To understand the distribution better, I increase the number of bins. You have to play around with it. And do you realize now most of the customers who visit this restaurant are having their total bill between $10 to $20? Convinced? Most of them are having their total bill in between $10 to $20. Sahi hai ki nahi? Right? Yes. And very few customers have their total bill in the range. What? 0 to $5 and $40 to $50. Yes. More significantly here, $40 to $50. So insight is the distribution is right skewed. Right skewed means the tail is longer on the right side, and most of the total bills are between 10 to $20, and very few are between $40 to $50. So do you think this information that most of the total bill is between $10 to $20 useful for anyone? Is it useful for the restaurant owner to know that most of the customers visiting his restaurant are having this total bill? Yes, for the management. Yes, right? So they can think of increasing this average total bill amount down the line if they wish to. If they wish to, they can certainly work around it. Okay. So we understand the most common spending behavior of the customer. The next thing which I want to go for is, yes, combos and discounts. Yes, that's also a good one. Scatter plot. Scatter plot is mainly used for having two continuous variables plotted. For example, the percentage that a particular student has scored versus the number of tears falling from his or her eyes. So obviously, the greater the percentage he or she scores, the lesser are the tears coming from the eyes. And the lesser the percentage he or she scores, the more are the number of tears coming from the eyes. So you will have both the things to be numeric. You will have both the things to be numeric or continuous. One example could be temperature versus the sales of ice cream. So as the temperature increases, sales of the ice cream also increases. So I say scatter plots are used to visualize the relationship between the two variables, and they are useful for the correlation and trends and regression analysis. How? Let's look into the common syntax. plt.scatter, color name. So you can give the color name of your choice. So let's say you are giving the color as purple. You give the alpha. Size. Marker. Now, S is the size of the marker. Marker means a scatter plot which you want to plot dot, 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 right? So size of the marker, shape of the marker, transparency of the marker. And let's go ahead to look at the relationship between total bill versus tip. Do you think as the total bill increases, the tip given by the customer increases? I'm not talking about you personally, but in most of the case scenarios, do you agree that as the total bill increases, the tip given by the customer increases? So if I eat for 500 rupees, I'm giving a tip of 10. If I'm eating for 20,000 rupees, I give a tip of 100. Something like that. Does it happen in most of the scenarios? So total bill versus this. plt.figure is this. Then I say total bill versus the tip. Color, I am keeping it as orange. Transparency, I will keep it as 0.8. Then I keep the size, I'm not playing, nothing I'm playing right now. And title, X label, Y label. Grid I like to show. Not required actually, grid I can say and show. So you see over here, we can see that. So you can see as the total bill amount increases, the tip given by the customer increases. Now, see, you cannot understand this relationship without plotting. In this case, plots are important. Can we identify this or can we assume this? No. In such case, plotting is important. But in that bar plot wala scenario, plotting was not important. Understand this scenario as well, right? Where you do, where you do not do it. Okay. This is what we understand now. Inside. As the total bill increases, tip given also increases. This indicates a positive correlation between total bill and the tip amount. Here as well, you have the size and the marker option. Size is 100. Size is 200. Maybe size is 30 is good. Marker is O. I'm giving marker as X. Oh, that's good. Marker as D. D means diamond. Marker as plus. Okay. Marker as F. Error. So you cannot give anything. So what all can you actually give in? I give marker as small o. Capital O doesn't work. And these are all the marker values that you can give. If you want, you can visit this. This is where these all things are available. None for nothing. Capital P for plus. Capital H for hexagon 2. You can see hexagon. I don't know where it came, but it is there on the documentation. And small h for hexagon. So it's so small that it's not seen, but if you look carefully, it's a hexagon. Dekh lo acche se, it's a hexagon. So you can play around with it. The most common is O only. So yes, this is what we understand, and this also helps us understand good amount of things. The next is we go for a pie chart. Pie chart is again univariate because you don't need anything. So pie charts, they represent parts of a whole. They are used for category, proportion, visualizations. Let me tell you, they are less used in data science due to the limitations in accurately representing the data. What? Really? Why? What is the problem? Well, I'll show you what is the problem. Tell me, looking at this visual, Canada versus other versus Australia, which is the second smallest? Ah, but there can be confusion, right? There can be confusion because, as we know, human eyes are bad at what? What did I say? Human eyes are bad at technically. Yes. Ascribing angles. Correct. Human eyes are bad at ascribing angles. So they are less used. But let's look into the syntax. plt.py and then values, labels, colors, auto PCD, start angle, and explode. Explode. What is going to explode? I'll show you. So that becomes really very, very interesting for anyone. So the first thing that I'm interested in calculating the percentage of smokers and non-smokers. So I say smoker count is equal to tips of smoker dot value counts, and I'm going to print it. Okay. Now, you know what I want? I want this to be plotted on a scatter plot. I want this to be plotted on the scatter plot. Now, scatter plot will be automatically converting this to percentage. In the sense, if I print this, scatter plot will be automatically converting it into 61 and 38 automatically. So I am not going to use this. I am not going to use this. I'll be using this only, which is this. I'll be using this only, and it will automatically convert it into 61% and 31%. How? Let's try to understand. So I say plt.figure. Then I say plt.py, and I'm just passing the smoker counts, which is this, smoker counts, and labels. Let's say I'm not giving anything, and I just say plt.title and show. You can see over here, it has automatically converted. What were the values? The values were 151 and 93. Percentages also we know. Now let's make it a little better. So I say smoker counts, and I'll also put labels is equal to smoker count dot index. So you see no and yes are also being added. Just give me a second. So we got no and yes. If you want to plot some values on it, first of all, it's not recommended, but let's say if you also wish to plot some values, then you have color is equal to, because there are two colors, I can supply two colors. And you can see I supplied orange and blue. So it will automatically, to whom it will give orange and to whom it will give blue. Well, how it is found in the smoker counts in the same order. Smoker count is about no and yes. So no will be orange and yes will be blue. So always remember that it will follow the same style. Then auto PCT. What is this auto PCT? Well, let's give auto PCT as 1.4F. So in this auto PCT, nothing will change except this 4. The value after this dot, only that will change. So because I said 4, there are 4 digits after dot, which is not looking good ideally, but I just wanted to show you. If I said 2, there are 2 digits after the dot. If I say 1, there will be 1 digit after the dot. Right? So that's your auto PCT. Start angle. Start angle 0, right? So this is 0 degree. Am I correct? So from here, that no is plotted. From here, the no is plotted. And then remaining thing is for yes. If I say start angle must be 90 degree, it started from here. From here, the no is plotted and then it plotted yes. If I say start angle is equal to 45 degree, it starts from here. You can play around with this inside, right? Most of the customers are non-smoker who visit this restaurant. It is spelling error. Okay. Then, only over here I am going slowly. When I start with Seaborn, I will increase my speed because the code is more or less going to remain the same. And you also understand the visuals, right? So at that time, I'm not going to go slowly over it. Going ahead. Now the next one. Horizontal bar plot. So horizontal bar plot are used when the category names are long or when you want to emphasize relative lengths horizontally. So the function is bar h. That's it. The function is bar h. Because it is suggesting, I'm quickly taking it. Why to lose it? So I am finding out the average tip by day. So I am finding out the average tip by day. So average tip by day is grouping by this. All good. Okay. Now you know what is in dot index and what is dot values. Am I correct? I need not explain you by printing again, right? Yes. Good. So because you know that, I will get into the figure and I'll directly look into this. Let's say I am not explaining you anything. Can I still assume you understand this visual if I don't explain you anything? The insight is same, right? What we got for the vertical bar plot, but horizontal bar plots are useful when these names are really very, very long. So let's say the name of the variable is total sales of the week, average sales of the week, mean sales of the week. So such long names are there. In such cases, horizontal bar plot is recommended. Else you can go ahead with the vertical as well. So yes, I think that's good. Insight. The average tip is highest on Sunday and lowest on Thursday. Cool. Then the next plot after that is a line plot. Line plot is helpful to plot what kind of information I explained you yesterday. Line plot is helpful when you have what on the x-axis, what time, and anything other than that, date. Yes. Now, if we look into our data set, do we have the time or date? No. So we have to do jugaad. We have to do some jugaad and get it possible. Right? So what am I doing? These line plots are used to visualize trends or changes over a continuous variable, typically time or index. They are often used for tracking model training, metrics, or time series data. Let's look into the syntax. plt.plot x, y, color, line style, line width, line marker, and what about the label part? Important thing only is not there. Label all of these are very much self-explanatory from the name itself. So that kind of eases my job. But I don't have any time-related information, right? That's a problem. So what I want to do is I want to find the average tip amount, not by day, but I would say over the table size. The average tips by size is grouping by size and finding out the average tip. So we understand the average tip given by the group of 4 people is when a customer comes in a group of 4, what is the average tip given? Ah, yes, that's correct. And what is the average tip given when a customer comes as a couple? As a couple? Ah, perfect. Yes, it's 2.5. Perfect. So I'm gonna try to plot that only. So we know that this is the index and these are the values. I'm just trying to do jugaad, right? So first you have a look at this. Table size 1, 2, 3, 4, 5, 6. Average tip given and each and everything is plotted. I could have gone for a scatter plot as well, but I went for a line plot. As you can see, this dots are there. Then dot index versus dot values. We know that very well. Color is orange. Label is average tip. Because of that, this legend appeared, right? Label is given, then legend function should come. Else that label will not be there. So this is to add legend to the plot. Then line style is dash. So dash means solid, solid. Dash is there, then it is dashed line. Line width is 2 and marker is 0. So line width is the thickness of the line. If I make line width as 6, see, doesn't make sense, right? So you can play around with that. Have a look at the code. Then inside, the average tip amount increases with the table size. Yes, except for over here, right? Average tip amount is highest for table size 6 and lowest for table size 1. I had shown you a box plot. Yesterday also I shared a sheet where which chart to use in which situation that I had already showed you. So that should not be a problem. I go ahead with a box plot. Box plot can be univariate or bivariate. Right now I'm talking about univariate. So they are used to visualize the distribution of numeric variable and identify the outliers. They are useful for comparing distribution across the categories. Okay. And one more, they are frequently used feature analysis for machine learning. So, syntax. plt.box plot. X-axis is X column, Y-axis is Y column. Data is, oh no, that was I thinking, why is it showing so odd? plt.box plot, only data. And some other parameters are there. They are not very common. It is suggesting, but even I'm not aware of patch artist. I used it around 5 years back. I had seen that, but I don't remember what it is. Notch also had used it long time back, but today honestly speaking, I don't remember. I was planning to go ahead with only one parameter, but let me take some risk. You never know. I once again recall the things. Okay. So it says over here, the data we know is the data to be plotted. So I'm mostly going to plot the tip column. Vertical or the horizontal alignment. So box plot should be like this or like this. Patch artist, that is fill the box with what color, okay? So example can be patch artist equal to true. Acha, that's it. Notch is whether to show a notch in the box plot. Example, notch equal to 2, and width will be the width given. Okay. So I'm planning to look at the tip amount box plot. plt.figure, plt.box plot. First of all, I'm getting rid of all of this, plotting it. What happened? This is the box plot, where you see this is the minimum value 0 percentile, this is the 100 percentile, 25 percentile, 50 percentile, which is the median, 75 percentile. And these are the outliers. So some of them, have given much more than $6, which is way higher than the average. And we are quantifying it as outlier. Outlier can also be on the lower side. This is what we see. And how to handle the outlier, we'll see it in due course of time. And here, if I say vertical is equal to true, it is like this. So if I say vertical is equal to false, so that's how you see that. And if I say patch artist, so it will be filling that. Okay. Do I have the option color as well? No. Then, okay, what color can we fill it by? We don't know. No problem. Notch is equal to false. And let's try notch as true. So this is a notch. Yes. Where the median is there, it will give a khachal thing, right? Just a slot, notch. And width is equal to 0.5. So you can see the width has increased as compared to this. Okay, that's what we understand from the box plot. Now, the last thing over here is getting into the subplots. We had already studied subplots earlier as well. Do you recollect subplot topic in the previous session? We had already studied, right? So what is subplots mainly used for? Having more than one plots plotted together, right? So I can say it is for multiple plots in a single figure. Use case used to create multiple charts in a single figure. And these are useful for side-by-side comparison or grid layouts. Syntax, figure comma axis, and rows and columns and figure size. Okay, that can be good. Then the next is we come out to this. Now, figure comma axis, I am creating a figure, let's say of 12 rows, 12 comma 4, that is the thing. Now I say figure and axis, and I say 12 cross 4, and this is 2 cross 2. No, I'm planning just to go for 1 cross 2. So 1 row and 2 columns. So 0 and 1. So axis is 0 comma 1. I am planning to go for a histogram of this, and alpha is this, edge color is black, and the bins I'm planning to go is, let's say, 50. In the same way, I'll be setting the title and X label for it, Y label for it. Grid line, okay, let's set that. And then this is 0, 1. 0th row and first, no, I should be 0, 0, right? I should have gone with 0, 0. Better it goes first, right? And then in the 0, 1, I want to go for a scatter plot. So I say scatter this. Okay, that's good. Oops. 2 were given. What did I say? 1 row and 2 column. That was correct, no? So this has to be 0, 0, 0, 1. Yeah. What is the thing? 1, 2. Right? With 1, 2, it doesn't work. These two are empty. Okay. It I can make it work. I'm just thinking why it is not working. Okay, let me just plot it over here. So if I say I want 1, 2, then let me just keep 0 over here. That will work. But this also should have worked. And this will be just 1. Now it will work. See, this is the 0th plot. This is the first plot. If you want to create 1, 2, right? Just have a look at this. Yeah, you see the complete code and the plot now. Like, yes. So you can see this is working, everyone. I'm sure you got this. And here, let's say, no, before this, I'm creating a box plot. And a pie chart. Yeah, that's looking good. Oh, it has to be made bigger. Yeah, much better. Better I show it separately here. Yeah, that is how it is. See over here. Let me increase the speed. So the ball is falling in whichever bucket that is increasing. Okay, so whichever bucket it is falling, we are increasing that. And what you see right now, which is getting plotted, is a histogram. Now, so what does histogram mainly look for, right? So histogram will be looking for, not a good one, not a good one. Now, see over here. So histogram will be looking over here. How many records are having the value 12? So there are 6 workers having the value 12. 8 workers having the value 17, and so on. So these heights are being plotted. The frequency plot or the count is being plotted over here anyways. In the same way, so there are only 5 ends. That means that between 0 to around 12, there are 60 values in the total bill. So there are around 50 customers whose total bill is between $0 to $12. Between 12 to 22, there are 120 customers. Between 22 to 32, there are again around 50 customers. Between 32 to 42, there are around 20 or 19 customers, and between 40 to 50, we have hardly 5 or 10 customers. This is what is the histogram saying. So it is counting how many people are falling into which bin, depending on the number of bins that we create, and it will automatically divide the data as per the bin. So as per 5 bins, you can see it goes from 0 to this. So it has to divide the minimum to maximum into 5 equal bins. If I say make it into 6 bins, it's like this. If I say make it into 7 bins, so you can see when you make it into 7 bins, 0 to 10, around 18 people are there. 10 to 15, not 15, 10 to 15, we have around 90 people, and so on. That's how you understand it, Anivesh. How count, right? It is nothing but the count that we see. Yes, right. So that was how the histogram is plotted. Getting into the Seaborn library. The Seaborn library. Seaborn is a powerful visualization library built on the top of Matplotlib. Yes. So you'll see a high level interface to do that. And Seaborn coding is more easy than Matplotlib. Yes, more easy than Matplotlib. Let us get started with the very first one, which is a histogram. Now, use case and all, we know it. I will go ahead with the syntax. SNS dot histplot. Data is the data frame. Bins is whatever bins you want to set it. KDE is the kernel density estimator. Color is the color. So we are looking for the histogram of the total bill. Now, data is equal to tips, and X is going to be this. Now, see, this is very simple. Now, if you look, why I say it's powerful. Number one, I said I want to create a histogram, and for that the function is histplot. Okay. Then I said the name of the data set is tips. Okay. The column which I want to plot is the total bill. Okay. Number of bins, let's say not give it, so it will automatically decide what is the best. Okay. KDE is this line around it, kernel density estimator, which I have kept it as true. Color, I have kept it as orange, and transparency, I kept it like this. Now, see if you look in over here, did I give the X label? No. Did I give the Y label? No. Seaborn automatically gives that. Seaborn automatically gives that. That's the power of the Seaborn library. And if you want to give it, you can use the code to get it like this. So you can definitely write down the code, and you see Matplotlib code comfortably working inside Seaborn. And why is that working? The only reason is because Seaborn is built on the top of Matplotlib. That's the only reason for this code working. Again, if you see insight-wise, this looks like a more clear plot as compared to the earlier one, is what you can see. And rest of the things, you have it over here. So every plot of Seaborn will have this format. What format am I talking about? The data parameter, where you have to supply the name of the data set and the X equal to and the Y equal to parameter, which says what do you want on the X axis, what do you want on the Y axis. Finish. Always. In Matplotlib, you remember you used to write instead of this tips, square bracket, double quotes, and the name of the column. Here it is like this. Very simple for anyone to understand. Then The next one is the box plot. Syntax is sns.boxplot. As you can see, data x, y, u, and palette. So we will be understanding it as and when we use it. So I say, let's look at day-wise total bill. Right? So data is tips. The name of the column to be plotted is day versus the total bill. And then I will say title, X label, Y label, grid, and show. You see over here. Look at the visual, right? So the syntax is very simple, and I have plotted it as a bivariate. X-axis is the day of the week, Y-axis is the total bill amount, and you see the histogram plotted. Okay. If I do the same thing, and I use the parameter like palette. You know, palette is what? Palette is nothing but the style. I'll show you. Theme, palette is the theme. So if you palette, Seaborn. So you can feel free to give any palette. You know, if you're giving a palette as tab 10, these 10 colors would be chosen. Based on how much more saturation and luminance you want, you can select the colors. If you give it as bright, these colors would be chosen. If you give it a pastel, low saturation, high luminance. If you look into high saturation by giving dark and less luminance, this is how it will be. This is HLS. This is HUSN. And if you see, this is gradient color, right? Dark to light, rocket. This is Mako. Many are there. That screenshot over here. So palette I have given set to. So you can see the earlier color and new color. Okay. Width, if I'm giving 0.5. So you can play around with the width of it. Right? This is the width. You adjusted the width. You can see the earlier width and the later width. Then here. The next parameter is notch. So notch is just going to put a khacha-like thing here, right? That's it. Wherever the median is there, it will be having that V insertion in between. That's the only difference. Just to clearly identify the median, notch is going to put that. It's optional, but it's easy to identify. That's the reason people use it. Now coming on to the factor like U. So U is what I am planning to give as sex. See over here I did not give you same code. Thursday, Friday, Saturday, Sunday, total bill box plot. Here I added you. Thursday, Friday, Saturday, Sunday, total bill box plot, but bifurcated as per the U. So U is going to divide the X wala value based on sex, because U is very common parameter in Seaborn in many plots. You'll see this parameter in many plots. So whenever I say U, it will just divide it on the basis of that. And U will always be a categorical variable. U cannot be a continuous one. I cannot put U as tips. That will not work. I'll show you. U, if I'm putting as tip. See, every tip is given a different. This is the legend only. And then the box plot. Sense in even the useless. Purely useless. So see, you might have seen that the typical thing is it is not PLT dot. First change. Second, it is like giving the data and what you want on the x-axis and y-axis. Rest all of the things are more or less same. Yes or no? Right? These are the two changes. Instead of PLD dot, it is SNS dot. And data is the name of the data set and what you want on X and Y, right? My suggestion to all of you is by default go for Seaborn only. Seaborn is better than Matplotlib. So I would say as much as possible, avoid Matplotlib and use Seaborn. Also, if you here look in over here very carefully, in Matplotlib, you remember you had to earlier do the value counts, then value counts ka result ka index versus the values. You don't have to do all those things in Seaborn. That is another big advantage. You don't have to first find out value counts, then index plotted and value plotted, and then you give that. Seaborn is taking care of all these things automatically. That's why by default, this should be your choice. Seaborn is built on the top of Matplotlib, and hence both of them are good friends. The next is scatter plot. SNS dot scatter plot, and you have data X, Y, U, style, size, palette, alpha. Style is the categorical variable to change the marker style. Right? In Seaborn, it was marker, and here it is style. That's okay, na? So let's look at total bill versus tips. Data, total bill versus tips. And then that's good. You can see over here, you have it. Here only. If I give the U as the day, so if you remember, let me give U as the sex first. So male, female was divided. Do you understand this scatter plot? Earlier it was like this, and now it is divided as per male and female. Difficult to interpret, but mota we understand that the total bill and the tip given by males is the highest. Of course, here there is a mix, but see, females give very less tip also. That's not the case with males. However, the largest bill is observed when the bill payer was male. Okay. And if I do it by day, I think that won't make sense because 4 colors inside this is crazy. Let me actually do it by smoker. Smoker yes versus smoker no. Can this scatter plot convey that usually non-smokers give more tip or smokers give more tip? Do you get any significant insight like this from the scatter plot? Smokers are giving larger tip or non-smokers are giving larger tip. Something like that. Do you think it is clearly visible from the plot? No, na? It's kind of mixed. It's kind of mixed. Even I agree. It's kind of mixed. And here, if I'm giving the style, let's say as time, what will happen? Smoker, non-smoker ka division as per time. That goes little complicated, but as you can see, smoker, non-smoker ka division as per time. So obviously a blue dot in a blue color in circle will be lunch. A blue color in cross would be dinner. So this is dinner and this is lunch. A orange color in circle would be lunch. Orange color in cross would be dinner. So this is dinner and this is lunch. Do you understand this? Is that clear? What is the style parameter doing? and this is the style as sex. This is the style as sex. Rest all of the parameters are Lallu Panju. Size as per size. Size is one of the column which is about the people are visiting in how many groups, single or as couple or in a group of 3 or 4 or 5 or 6. Most of the people in this data set are visiting in what group size? If you recollect, tell me. Most of the people in this data set are visiting in, very good, very good. So you know what is this parameter size going to do? Size parameter is given a size. So you have these dots, right? You have these dots and crosses. If this particular customer who came, this is a male smoker. This is a male smoker. So that will be bigger in size if the group is bigger. So you see over here. Now I need to adjust the figure size. Right? So bigger the size of the circle, higher is the one. So I'll do one thing. Let me remove the style over here so that I can focus on one parameter only. And you see the style, U as the smoker. If I remove the U also, just to be very clear. Right? So see, smaller dot size is 1. This is size 6. So this is like size style 6, less, and etc. So I was saying that you see the style parameter, right? So bigger the size of the circle, that will be quantified by the size, right? That is one thing that you see in over here. And then anything important, sizes 20 to 200. So I can play around with the size, minimum size 20, maximum size 200. If I make it instead of 200, let's say 500. So sizes, I'm playing around with the sizes. You can play around with that. Then alpha, we know that. That's my alpha value. I kept it at 0.8. And we are done. Now, I'll come back to the smaller version of the plot. And I'll remove the things as well. Right? Now I get into joint plot. Now look at this joint plot. Joint plot is nothing but a scatter plot, but you can create many more things other than a scatter plot also. Have a look at this. Now, everyone, if you see, joint plot by default creates a scatter plot only. I'll copy this. Let's see if I'm not giving the kind as scatter. By default, it's a scatter plot. But, hey, what is happening? Why is the joint plot of this? Why is it? Maybe the size is small. Tight layout. See what happened because of tight layout. This one, which was just skipping out, if I comment it out, it was going in. Tight layout compresses it. Okay. Now, if you see in carefully, the code is joint plot, x-axis this, y-axis this, color orange, alpha this. So you see a scatter plot only once again. But do you see the powerful nature of the joint plot? A histogram of the total bill is here. You remember 10 to 20 is the tallest, and the histogram of tip is here. So most of the people give the tip in between $2 to $3.5, 2 to 3.5. So that is how good it is. Here, if I say, right, this is what we heard. Here, in this plot, which gave the score, instead of kind, if I say REG, so REG basically stands for a regression. Okay, regression says alpha should not be there. So I'll get rid of it. You see this. I just change the parameter kind is equal to scatter to kind is equal to REG. You get a kernel density estimator around this. And this line which says that as the total will amount increases, the tip given also increases. And the gray area around the line is the error in the line, which you can ignore right now. In machine learning, that can be helpful. For now, you can ignore. So this is far more powerful than a scatter plot. Okay. Acha, do you see carefully? Let me know if you observed it, that there are very less values over here, and this is very thickly populated over here. Did you all see? It's thickly populated over here, and it is thinly populated over here. Why am I talking about it? Is now I'm going to replace this by hex. See, thickly populated, and the color is thinly populated. That is what HEX parameter will help us. HEX. Some parameter, na? Recede was only there. I don't know where it went. Oh. Recede. That is also not there. Even I was thinking why it recommended these two. I forcefully asked it. I can use KDE. Hist also I doubt. Hist also I doubt. Let me try it out. Okay, hist. Darker the color, denser the population. So hist and hex are the same. Darker color, lighter color. It's the same. And then KDE is lot for us. You know what it says? The data is dense here and not dense here. Basically, what it is, this is basically a way of measuring the depth of the ocean. Ships use this to measure the depth of the ocean. Thinner the concentric circles, more deeper it is. And the wider the diameter, the more shallow it is. So obviously we will never require it, but just remember KDE as this helps us to plot this. Okay. So all of this, all of this with respect to Seaborn or with respect to Matplotlib, you'll find it all in the documentation. So Seaborn has a very nice documentation. Seaborn.pydata.org. Here, if you get into the gallery, any visual you want to learn, you can learn it from here. Let's say you are interested in learning about scatter plot. Join grid, no, not join grid. Let's look into what we learned. What we have learned so far. Box plot, LM plot, scatter plot. I'll click on this. See over here. They have used the diamonds data set of Seaborn and subplotting as well. But the most important is the scatter plot. What on X, what on Y, what on U. This is still the tutorial, right? If you are stuck up with the code. if you actually get into the Seaborn, and if you are looking into a scatter plot, just Google for scatter plot Seaborn, you will be landing into the official page, and you find all the parameters of it. And what all values, everything can take, you will find everything mentioned below, right? Legend can take these all values. So this is the best way. And the same goes for Matplotlib. So let's say if you want to look into the scatter function of Matplotlib, this is what you have in the next one. The next one is a bar plot. So bar plot, SNS.bar plot, what you want on x-axis, y-axis, hue, palette, confidence interval, estimator. The default estimator is mean only. So I'll tell you what are we looking for. PLT.figure. And I'm saying I want to look at the day-wise tip. So dataset is tips. And day-wise, I said I want to look at the tip. So day-wise tip. And palette, let's say I'm giving as muted. I know the palette, so I'm just giving them title, X label, Y label, grid, and show. But you can see it's nothing but a bar plot where we see that the average tip given is the highest on Sunday and least on Friday. This data, if you plot it with the help of a pie chart, it won't be making a lot of sense because this Thursday and Friday are very near to each other. Confidence interval is SD, means standard deviation. So this lines are for confidence interval, and you see they have become more lengthier. Right now you don't need it, so and go ahead. Cap size is equal to 0.1. So you can see this is just marking it. Again, you don't need it. And then estimator, if I'm looking at the median of the, okay, let's say I just want to get rid of it. So I can say that I don't want all these things. Huh? So none. So I don't get that confidence interval lines because I really don't want it. Estimator is median. So by default, it is mean, as I told you. So what is it? It is the day-wise average tip given. Day-wise average tip given. Right? And here, right? These are the values which I wrote. We are not interested in that, but I just wrote it. This is the day-wise average tip given. Okay. If I want to print the day-wise medium tip given, median, day-wise median tip given. So same code, I just wrote estimator as median. Rest everything is same. You can see this. Right? Rest everything is same. Have a look at the code. Day-wise median tip given. So the median values are written. Earlier average were written. You can change around that estimator. Okay. Now inside wise we already know. Bar plot is a bivariate plot. You have something on the x-axis and something on the y-axis. But now I am going for count plot. Count plot is bar plot only. Count plot is bar plot only. But in bar plot, as I told you, you have something on x and something on y. And that y can be the mean. The y can be the median. It can be the standard deviation. But in bar plot, sorry, not in bar plot, in count plot, the y will be always count. It will be always count. So you don't need to give y. You see, I only gave x. Yeah, the y-axis is always count. Day is this, x is this. Rest all things are straightforward. Y is always count. So that is a count plot where we understand that all Saturday maximum customers come. Then I go to box plot. Here you have gaps in between the bars. There you don't have any gaps in between the bars. The next is a violin plot. Okay, before violin plot, let me show you box plot. Box plot is same only. Same like that. You don't have anything new in the code. Day-wise tip, you have the box plot. Have a look at the code. It's self-understandable. Day-wise tip, you have the box plot. And if I copy the same code, and if I put over here U as smoker. So that is bifurcated like this, right? U as smoker. So each day is bifurcated. What do you understand, right? If in box plots, it's always good to compare the median. Do you see the average tip? The average tip given on Thursday by smokers is more than non-smokers. On Friday, non-smokers give more tip. Saturday also non-smokers give more tip. And on Sunday, smokers give more. If I look at total bill, total bill by smokers is more on Thursday as compared to non-smokers. So Saturday as well, Sunday as well, but only on Friday. The total bill by non-smokers is more than smokers. That means as a restaurant owner, I will focus more on the non-smokers on Friday. And on the other day, I will focus more on the smokers. Are you all getting this insight? This is just a small insight that we received from this. Okay. And I'll just do this. And now I am going to go for a violin plot. Violin plot and box plot are the same. How can they be same? Because they are actually the same. Box plot gives us this. I just go and say violin. So in box plot, how much wide it is or how many values are there in between this are not known. But violin, it is box only. But how much data is stored, the wide width of this helps us understand. This is like a histogram plotted on left side and the same histogram on the right hand side. So you actually understand that, okay, the data is thick here, here it's thin, and here it is more thin. So there are less and less number of people. As the total output increases, which was not observed in box plot, because box plot will simply plot a line. How many points are there? Here you understand. This is like the tail of a lizard. This is the tail of a big lizard. This is the tail of a crocodile, even more thicker, right? So you understand where more data is there, where is less data in the tails. So they are little bit more good as compared to the box plot. And here, if I give you, then it becomes a little bad. right? Because it looks like too many things are being put up inside this. Too many things are being put up. So what we do is there is a parameter called as dodge. Uh-oh. Split. Okay, split huge. Uh, so there is a parameter called as split. What did it do? Have a look at it. Compare both. Here, two are plotted, two different. Here, we know that whatever is on the left hand side, same is on the right hand side. Same goes here. Left hand side and right hand side are the same. It says here, let me only plot the left hand side, and here I will plot the right hand side. That's exactly what my split equal to true is doing. Now there are so many parameters. You might be like, oh my God, we have to remember so many things. I'm confused. I don't know what all parameters are there. He has taught us some of the parameters. There may be so many other parameters I may have to remember. Then let me tell that to you confidently that you will not need anything more than this. That much I can assure you for sure, because I am covering each and everything, whatever is required. Worst case, you have to learn one or two things. I think you should be prepared for it. You can't really say that, okay, this is the end of my knowledge absorbing stage. So don't get confused. Only these parameters and whatever I'm teaching, I can assure you is sufficient. Looking into this, do you all agree as the temperature increases, the sales of ice cream increases based on the scatter plot? Right? Yes. Which means that there is a high correlation between the temperature versus sales of ice cream. And they say the correlation is this. So, any correlation value, if all the dots are on a straight line, it's +1. If it's going up, if it's coming down, it's -1. This is 0.9. This is -0.9. This is 0.5. This is -0.5. This is as good as no correlation. There is a formula to calculate it. Here, right now, this is not important. Don't worry about it, but that's how they got the value as this. So, I was talking about heat map, SMS.heatmap data, annotation, and so many parameters. Look at this. So core function, right? Core function is responsible for calculating the correlation between the numeric columns of the data set, only the numeric columns. So it says total bill when plotted against total bill, the correlation is 1. Tip versus total bill, there is a high correlation, 0.67. Size versus total bill also 0.59. No negative correlations found, right? So, but the correlation value will always be between -1 to +1. So here I'm saying that plot a heat map of this. Have a look at this. You see this? Lighter the color, closer it's to 1. Darker the color, closer it's to 0.5. There is no value below 0.5. Therefore, it didn't show that in the color bar. Now let us try to understand it. First of all, you have the parameter annotation equal to true, which will plot in the values. Annotation equal to true. You understand it? For your kind information, this is not available in Matplotlib. This is not available in Matplotlib, although you can create it, but there's a complicated process to do it. Even I have forgotten. but you can do it. We will do it. I'll show you why it is complicated, but first, let's complete this. CMAP is equal to cool warm. That is nothing but the theme. Yeah, you can see cool and warm. Good. Then line width is equal to 0.5. Line color is black. See this line width and line color. So line width, if I make it as 3.5 thick, of course, that doesn't look good. 0.5. Line color white. And color bar equal to true. Yeah, this also looks good. Color bar equal to true. This is what you see in over here. Then after this, you can clear a line plot. And the syntax is this. Obviously, total bill versus tip does not make sense, but I'm forcefully creating it. Forcefully, you need to give a proper column. But I think you understand it very well, right? I'm forcefully trying to create it, but you have to give a proper column. Okay. V size versus tip could be good. Okay. The next is LM plot. LM plot basically stands for a regression line plot. Straightforward only, nothing great. I'll show you the plot, then it will become more clear. So I'm going total bill versus tip. You see, it's scatter plot only. It's scatter plot only. And here as well, if I'm putting you as smoker, you get 2 lines. Have a look at the code. And then pilot as set 4, not there. Set 2 is here. Markers and confidence interval equal to none. So you have the markers here and confidence interval equal to none. So you don't see that gray portion around the line. Right? Scatter KWS is the size. If you see this, instead of 50, I'm making it as 20. You see, they have become small. Scatter keywords. S is 20. That's a little different way of writing it, but yeah, that's how you have to write it. You can also give alpha inside this, so it will adjust the transparency as well. Smokers give higher tip above a certain bill. Wow, that's very nice, Shiva. That's very nice. Good. And then this is the plot. The last one, which I want to show you, is a pair plot. Now, pair plot plots every numerical column versus every other numerical column, and it is not recommended. I will tell you why. See, I'm not giving anything to the pair plot except the name of the data set. I'm not giving anything to the pair plot except the name of the data set. Data is equal to tips. What it does is it takes all the numerical columns and plots them. All numerical columns are plotted. First, if you see, it is plotting total bill versus total bill ka histogram. We know that $10 to $20 most of the customers are there. This is tip ka histogram. Most of the tip given is between $2 to $3.5. Most of the key people come in size of 2. Here, if you have the total bill versus tip scatter plot, total bill versus size, as the total bill increases, the size increases. Tip versus size. These plots, these three, 1, 2, 3, and these three are the same, right? That's an important thing. If I come down and I put U is equal to smoker, so you see, everything is bifurcated as per the smoker. Everything is bifurcated as per the smoker. And if I say kind is equal to KDE, then here there is no more an histogram, but here you have kernel density estimators. And that's it. That's it. This is how it is. This is exactly how it is. Now, let me quickly look into our day one. We don't have the library called as Plotly as far as I understand. Do we have it? No. When I shared with you the curriculum, this was how it is. So we completed so far, and the next part is the mathematics and statistics. But, are you interested in looking at one more awesome library in 10 minutes of time? I'm not recommending it, but it's good. Yes? Okay. You all will not ask me lot of questions related to it. That's a sincere request. Else we will end up investing huge amount of time. Second thing I can assure you is it's easy. It's easy. That is what I can assure you for sure. So I will continue in the same way. And this time I'm going with the Plotly library. The advantage of Plotly is the visuals are interactive. When you hover, you can see the values. No need to use the plt.text function. So first, let me get into histogram. So I already have the data set. I have to import the library. That I'm doing it quickly. Import plotly.express as px. px.histogram instead of SNS. Data is tips. Total will. Number of bins, not bins, n bins. Color is as per sex, and you have this. Now you'll be like, Darshan, what is great? Well, let's remove the color first of all. Okay. So this is the total bill histogram. You'll be like, it looks the same. Yes, but now see how many are there in this bin? All of these. It's awesome. Plus you have some other features like zoom, pan, etc., etc., etc. And if I use over here, color is equal to sex. So you have the same thing distributed as per male and female. Isn't that cool? Right? Nice, na? I told you, right? It's good. It's awesome. Yes. This is also something which is very popular in the industry. The next one is a box plot. I'm not doing anything great. px.box, name of the data set, x and y. Color is the U parameter. I hope you understand now here. Color is like the U in the Seaborn. Whoa, wow. मजा आ गया. आया कि नहीं मजा? Awesome, right? That is the USP of Plotly. You hover and you see it. This is much, much better. The next is the scatter plot. Total will versus tips ka scatter plot. Let's not color it by sex first. Let's not do it by this. Right? Wow. 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 And when I hover the data, it should show me day also. So therefore, it's showing day also, Saturday. So on Saturday, the total bill by this customer was $28 and the tip was $6.5. Here also you get it. And here, color it by sex and size as time. Size as size. So coloring by sex and size as time. You get a lot of insights. It's interactive. That's the best part of it. Bar plot. See this. I'm looking at the average tip given per day. Look into the code. I'm pretty sure you will understand. I computed it by doing the group by. Then I'm doing it. Violin plot. Wow, that's good. px.violin, data, x and y. Color it as per sex. Because I said box equal to true, inside this you see a box. Points equal to all. Therefore, you see this scatter plot as well. And rest all things are understood. You got to go for a pie chart. So you hover and you see the results. So first, value counts, smoker given, smoker counts, name as smoker. Therefore, you see smoker equal to yes, name, value as count. Therefore, you see count is equal to this. Then I'll get into a line plot. You see over here. It's same X versus Y. You just need to give a time related column here. I had to forcefully give something. And I was also, I also promised you that I'll show you how to create a heat map using the Matplotlib. That's not good enough. See, heat map created. But in Seaborn, it was so simple, sns.heatmap. Now here you look into the code. After loading the data, you are computing it. Then I'm creating IMShow to show the correlation metrics, CMAP and interpolation. Then X ticks and Y ticks for having in Seaborn, it was just annotation equal to true. And then here I had to plot all of these things. Then color bar. कुछ नहीं करना पड़ता Seaborn के अंदर. It's far much easy. It's far much easy. That's one of the strong reasons why one should not use this. But yes, Matplotlib not for heat map. Use Seaborn. Let me now ask you, we looked at so many Plotly codes. I just want to get a confirmation. Did you all understand all the codes which I just showed you? Not only the visual, the code also in the Plotly. Did you all understand it? Easy, right? Yes. Plotly is far more complicated as well. But we are not getting into that. I just gave you a quick introduction. You can visit the Plotly website, Basics of Statistics. Now we all know that mathematics is a big part of our lives, especially stats. And what is statistics? Statistics is nothing but a branch of maths. Statistics, in simple words, is a branch of math and which focuses mainly on analyzing what is happening in the world around us. So it's basically nothing but a collection of data and its representation. So statistics compare the data through mean, median, mode, etc. So we all have heard that we live today in something which is called as the information age, where we deal about the world around us, and most of the information is mathematically determined using statistics. How? Well, let's understand why and how is this important. As I told you, statistics, they are nothing but set of mathematical equations that are used to analyze what is happening in the world around us. So much of the information is determined mathematically using statistics. What is happening in the world around us? And when you use it correctly, statistics can tell us the trends in what is happening in the past, which can be helpful for predicting what will happen in the future. How? Well, machine learning has the backbone as statistics only. So how? How can statistics be helpful? Let's consider an example. Some of the examples of how statistics shapes your life when you don't even know it. Example. Consider weather forecast. Do you ever watch weather forecast sometime during the day? What is the weather today? Right? But the question is, then, how do we use that information? How do we use that information? Have you ever heard a forecaster talking about weather models? So these computer models are built using statistics that compare the prior weather conditions with the current weather conditions to predict the future weather conditions. So statistics comes in picture over there. Or The second one, emergency preparedness. So what will happen if the forecast predicts that there is going to be a hurricane, or maybe there are going to be tornadoes which are likely to occur? This is something which happens in US very commonly. So emergency management agencies move into the high gear to be ready to rescue the people. So these emergency teams also rely on statistics to tell them when the danger may occur. Or consider predicting the diseases. So a lot of times on the news reports as well, statistics about a disease are reported. So the reporter simply reports the number of people who either have the disease or who have died from it. So, let's say Corona is going on. So every day they are reporting how many people have Corona, how many people died from it. So you'll be like, wow, that's an interesting fact for me. But it may not mean a lot to you unless and until anyone from your home gets admitted. So I want to say that when statistics becomes involved, you have a better idea of how that disease may affect you. How? Well, studies say that 85 to 95% of the lung cancers are mainly smoking related. Now the statistics is kind of telling you that 85 to 95%. So it's like telling you that almost all the lung cancers are related to smoking. And if you want to have a good chance of avoiding lung cancer, you should not smoke. That is how statistics comes into picture. Or to talk about medical studies. So scientists, while preparing vaccines, right, they must show a statistically valid rate of effectiveness of any vaccine or any drug that can be prescribed. So statistics is behind every medical study that you hear about. Consider genetics. See so many places where it is used. Many people we know are afflicted by disease which are coming from their genetic makeup, and these diseases can be passed on to their children, which is one such disease which comes from the genetics. One of the very common disease which we get from the genetics. If your father or mother has it, you are likely to get it. Exactly. Diabetes, sickle cells. Okay, that is also something I never heard about it. But yes, diabetes is very, very common. Right. So statistics are critical in determining the chances of a new baby being affected by that disease. Or consider political campaigns. Whenever there is an election, the news organization is going to consult their models when they are trying to predict who the winner is. So candidates consult the voter polls to determine where and how they campaign. And statistics play a part in who your elected government official will be. I have four more examples. Insurance, and all of these apply to ML. So see, by law, if you are going to drive a car, then you need to have car insurance. If you have if you have a house, right? If you mortgage your house, then you insure it as well. So the rate at which the insurance companies are charging you. So let's say your car premium comes out to be 20,000 rupees per year. as an insurance cost. Now, how are they calculating that cost? That cost is based on the statistics of all the drivers in your area. So let's say overall, we realize that you stay in some area X. The number of people which stay over there are 30 lakhs. And there is some area Y which is equally big, but the number of people which are staying over there is just 3 lakh. Now tell me, in X and Y, if you are in which area, if you are staying, the chances of your car getting brushed up by other car is higher in X or Y? X, right? Yes. So you consider this to be like Mumbai and consider this to be, let's say, like Jammu. This is thickly populated, this is thinly populated. So the rate at which the insurance company is going to charge you, the insurance premium depends on the overall number of cars, overall number of accidents, overall number of claims, and many other factors. And obviously here it is likely to be higher. Similarly, if you are buying a property or leasing a property, here it will be higher and here it would be lower. Then coming on to the next one is consumer goods. And when it comes to consumer goods, the best example which comes to my mind is Walmart, which is a worldwide retailer which keeps the track of everything they sell, and they use statistics to calculate what to ship to which store and when. So they have so many food chains, so many food chains. Which store will be short of what at what point of time and when to ship it? It will do that. So from analyzing their past vast store of information, Walmart decided, long time back that people buy strawberry tarts. What are strawberry tarts? Strawberry Pop Tarts. Have you ever had this strawberry Pop Tarts? No. Seriously, no. Even I never had it because it is available popularly in USA, not in India. So coming back to what I was saying, right? It's not available in India. I don't know. I mean, nowadays everything is available. We should be getting it. Maybe on, if I go on to Amazon that in, do we get that today? Everything is available. See here, order it and have it. Everything is available. In fact, nowadays, when I travel to any of the foreign countries, I do not get anything from there. There was a time when the things over there were special, but now you get everything available everywhere. When I went to the US also, I literally didn't even buy a single t-shirt over there. All those t-shirts were made in China. So paying over there 800 rupees for a t-shirt and buying the same quality t-shirt over here at 250 rupees. Useless. But coming to the point. So Walmart, right? I was talking about it. So Walmart decided to buy. So Walmart found out that people buy strawberry Pop Tarts when a hurricane is predicted by the weather department in Florida. That is a real-time case study. So Walmart found out that people buy strawberry Pop Tarts when a hurricane is predicted in Florida, and therefore they ensure that they are shipping this product to the Florida stores based on the weather forecast. Well, my question to you is why are people buying strawberry Pop Tarts due to hurricane? Any reason behind it? Why people are buying it? Can be kept longer. You remember during the Corona time also when they were like anytime lockdown can occur. So people used to dump their food with so many items. Same funda. Right. So whenever these kind of warnings come, people are not going to move out of their houses. So they should have something to eat. And strawberry Pop Tarts are tasty and they have a longer shelf life. And therefore, people might be using that. Okay. So that was the example of consumer goods. Last two examples. How statistics can shape your life when you even don't know it. Quality test. Companies, we all know, they make thousands of products every day, and each company must make sure that a good quality item is sold. But a company can't test each and every item that they ship to you. They can't test each and every item that they are shipping to you. That is the consumer. So what does the company do? The company uses statistics to test just a few called as a sample of what they make. And let's say they are making total 1 lakh products a particular day. They will take a 10% sample and they will perform all the tests on it. And if all the tests are passing on that sample, the product is approved. And if all the tests are not passing on that sample, then this entire 1 lakh products are not approved or disapproved. And one last, stock market. Another topic that you might have heard a lot in the news. So stock analyst uses the statistical computer models to forecast what is happening in the economy around us. Therefore, I say statistics is shaping our lives without even us knowing it. And today it has been taken over by machine learning. So machine learning is using this in the backend. So now finally we say, what is statistics? It is the science of how data is collected, analyzed, implemented. Collected, analyzed, implemented. That is statistics. Always remember these three words: collection, analysis, and interpretation. But there is a difference between what is data and what is information. How many of you are aware that data and information are different things? People use it interchangeably, but they are different things. How many of you are aware that they are different? Information is the process data, right, which can affect us. Yes. So if I give you the data set of, let's say, Superstore, which we saw, right? So in the Superstore data set, you have 9,994 records. That's what we saw during Pandas. But when I apply the unique function on the category column, how many unique categories were we able to find? In that Superstore data set, how many unique categories were we able to find? No, not 60. Technology, furniture, and one more was there. Three. Three. Acha, if you recall the student data frame that we were working, in the recommend column, how many unique values were we able to find? In the student data frame that we were, two. Yes and no. And out of that, 5 were no and 3 were yes. So, yes, that was the information. And the data set is nothing but the data. So typically the data takes the form of observed measurement like height, temperature, etc., or descriptions like dog, cat, blue, female, etc. So, thus we say statistics as a discipline concerns how we use the data to say the things about the real world. And we want to turn this raw information into what we call as useful knowledge. So, we might want to summarize the data, and this can be done visually by looking at maybe a graph of the last week temperature, or we can look with numbers, like we can look at what was the average temperature last week, etc. Just read it. Wise Words by Karl Popper. Now, one very, very important thing which I want to conclude before I move ahead, because now I have to get into some of the basic terminologies of statistics. But before that, there is one most important thing which I want to tell you. Uncertainty is rampant. That means statistics means uncertainty. Statistics means uncertainty. So, we use statistics to answer questions about the things that are unknown. So, if I ask you, can you tell me the total number of trees in the Jim Corbett National Park? If I say that, can you count, given a task, can you count the total number of trees in the Jim Corbett National Park? Possible or not? But I say no. Okay, let me ask you one more similar problem. If I say, can you tell me what is the average weight of an adult male in India? So we have a population of around 143 crores. And let's say I'm assuming that there are 50 crores male. And if I want to find out the average, so let's say government created a nice system. We have created a nice Android and an iOS application where every person has to measure his or her weight at his home and upload his weight on the app. Very much streamlined. Now, do you think we will always be right, or we can go wrong? And if we can go wrong, what do you think? Why? Why can we go wrong? App is created, everything is perfect. What can be the reason? Death. Okay, yeah, that's a valid point. Yes. People might give wrong information. Yes, that is also very much fine. Many people might not have mobile. Okay, that is also perfect. So, if you look at weighing scale, over here, have you seen weighing machines which are not showing zero by default at times? Right? Yes. Or consider this. This is a very typical example, right? In analog machines. So what if someone used this kind of machine, and you can see it's not exactly aligned with zero. Again, there is an issue. Let us say all these things are also sorted. Let us say all these things are also sorted. You know, my weight today is 100. Sometimes I see my weight as 101, and sometimes I see it as 99.5. Weight also keeps on changing. Let's say I had a very heavy lunch, it increases. Or let us assume I had 1 glass of water. My weight changes. Or someone went to the washroom, doing potty and all. So again, his weight changes. So at what point of time are you measuring the weight? That's also a problem. Moral of the story, what I want to conclude with these examples is there is no way you can do this correctly. Similarly, over here. So I don't say that we will be grossly wrong, but there will be a small scope of error, and hence I was saying uncertainty is rampant. Uncertainty will be the theme of our class. We can't know for sure will be the answer given by me to a lot of questions, and statistical tools are useful for making the most out of this limited information. Let us look at some of the statistical statements. I say I sleep 7 hours per night on an average. So does that mean that right from the day I have born, my average sleep is always 7 hours? It is never 7.1 hours, or it is never 6.5, or it is never 6.95, etc. No. So statistical uncertainty. Students who attend the class regularly tend to get higher grades than those who don't. Well, not necessarily, right? There are some students who don't attend the class, but still do well in the exam. Okay, now let us get started with the thing. So now what we just understood is whatever is the thing that we are calculating. Let's say if we have collected the data of height of adult females living in US, so that becomes our variable. Height is our variable. So height of female 1, female 2, so on and so forth. Now, coming on to what you guys were saying. Considering the problem of finding out the average weight of an Indian adult, which is practically not possible because the weight is changing. So what they say is if the things are practically not possible, you have a population of, let's say, 70 crores and you cannot find out the average weight. Then what do? We say, let us take out a sample. Sample is usually 10% of the population, not necessarily, but usually. So 7 crore. And then we find out the average. Let's say on this, we found out the average weight of the sample came out to 70 kg. So here we infer that the average weight is 70 kg. Now, what are the chances of us being wrong? Of course, they are there, but we will be very close to what is correct. But when you will be very close to what you are, what is correct, when your sample is good. For example, if you look into, I have to choose, let's say, population of 7 crores. And this entire population, if I am choosing from Maharashtra, and I found out that the average weight is 70 kg, and therefore I say that all of India's average adult weight is 70 kg. Do you think I made a good decision by taking everything from Maharashtra as a sample? No. What do you suggest me in that case? What should I ideally have taken? How should I taken 7 crore people? Yes, by distributing that proportionately, by taking it. And that is where, very nice. I'm happy to hear that. This is exactly where what comes into picture are the sampling techniques. We'll be learning about them as well later on, but right now I just wanted to highlight this. So essentially, population is the entire overall group we are interested in. And therefore, I say, if you're trying to get an idea of the average height of US adult females, then the population of interest will be all the US adult females. That's called as a target population, and they can be large or small, but usually they are large only. And sample is nothing but a subset of the data, usually 10%. So the variable of interest is measured on each member of the sample. And a single member is called as an observation. And thereafter we take the sample because the entire population of interest is not available to us. Like for example, if we are studying the height of the US adult females, we will collect the height of or the height data from that sample. We are not going to measure the height of every woman in the United States. So that's how we say that this is the population, this is the sample, and based on the sample, whatever readings you get, you will likely infer on this. Okay. Next. Now coming on to types of statistics. Broadly, we are going to study two types of statistics. The first one is called as descriptive and the second one is called as inferential. Inferential is exactly what we studied or understood on the earlier slide where you yourself suggested that you should have taken samples from each state, right? So from the population, where you take a sample, you do the calculations on this and then you infer on this. That is what is called as inferential. And descriptive is the one where you look into formulas like finding out the sum, min, max, median, mean, mode, standard deviation, variance, skewness, kurtosis, etc. As and when we require, we will be looking into this. So, see, we don't know all of this, but at least we know most of it, sum, mean, median, etc., etc. Same applies over here. So that's what I said. Descriptive statistics will involve describing a data. We can make a graph of it or find out the average or find out how spread it is using the variance. So we can tell any interesting features about it. And inferential, as I told you, it's all about inferring. Now, after this, the next thing which I want to talk about is directly the types of variables. So what is a variable? Variable is any characteristic, number, or quantity that can be measured or counted. Anything that can be measured or counted is a variable. So let us get started with the discrete variable. What is discrete variable? Well, discrete variable is also called as a categorical variable. Like I say that my gender, right? So gender consists of only limited values, male and female. It becomes discrete. Your qualification can be undergraduate, graduate, or postgraduate. That becomes discrete. So can you say that you are undergrad and a half? So always, whenever you talk about discrete, they are distinct and countable in nature. So now the next is continuous variable. Continuous variable is what? A continuous variable is the one that can have infinite number of values. Like, what is your height? So someone will say my height is 165.2 centimeter. Someone may say it is 190.63 centimeter. Someone may say it is 180.1, etc. So any value can be taken. So whenever you see floating numbers, it is continuous. And whenever you see countable values, it is discrete. For example, if I talk about temperature, so 29.3 degrees Celsius, 34.29 degrees Celsius, etc. All of these are continuous in nature. Then coming on to qualitative variables. Then I'll go to independent and dependent. Qualitative variables are the ones which are based on qualities or categories. Basically, you cannot do any arithmetic operations on them. Basically, you cannot do any arithmetic operations on it. And I can give you an example. Hair color. Hair color can be white, black, gray. You cannot do any arithmetic operation. Or if I say city name, Mumbai, Delhi, Chennai, you cannot add, subtract, do all these things. Whereas quantitative variables, you can add it or you can subtract it. So you consider age. Someone's age is 22, someone's age is 24, someone's age is 30. You can do that. And salary. Salary is again a quantitative in nature. I will quickly get into the figure of this. This is what best explains it. So let me explain each of this with an example so that it makes more sense to you. Variables are first of all divided into two types: numeric variable and categorical variable. So numeric variables, they are always and always the measurable quantities. What I say? They are measurable quantities. The count of cars that one has, the count of children that one has. and continuous, as we can understand. So continuous is all about having the values can be decimals or fractions in a range. So example can be height, example can be weight, it can be temperature, it can be time taken to cover a distance. Are you all clear with the left hand side of the plot, numeric, and how is it bifurcated into continuous and discrete, right? Next, we get into categorical. So over here, you will always have categories or group. Okay. Tell me over here that what all are the various gender which are available. The various gender which are available are male, female, transgender. Anything other than that I'm missing? Did I cover everything? Let me talk about what are the various religions available. First, I can say Hindu. Next, I can say Muslim. Next, I can say Sikh. And next, Christian. Next, Buddhism. Okay. Jain, Jews, Parsi, Shanto. Okay, I don't know that. Maybe available. Okay. I am talking about the another example. I don't have space, so I'm writing here education level. So education level can be undergraduate or graduate or postgraduate. Or I am talking about size of shirt. It can be small or medium or large. If you see carefully on this side, do you see over here and do you agree that undergraduate qualification is less than graduate is less than postgraduate and same is over here, small less than medium, right? So can I say that we do see some order over here? Therefore, we call it as ordinal over here. And in nominal, there is no order. So is it like female is greater than male is greater than transgender, or male is greater than female is greater than transgender, or Hindu is greater than Muslim and Muslim is less than Sikh? No, that is what is nominal. That is what is nominal. Now we get into the topic of finding the central value. Now, when I say central value, I'm actually getting into the descriptive statistics where we will be looking at mean, median, mode. So now I'm going to teach you something which is very easy. So I'm going to go fast. When you have two or more numbers, it is always good to find out the center of it. Like if we have just two numbers, 3 and 7, then what we do? We say, how do you find out the central value? 3, 4, 5, 3, 7, 4, 6. Central value is 5. Or you can also do And that's exactly the central value in this case is what is called as mean. And if you have more than two numbers, then the idea is adding and then dividing. So if you have something like this, then 3 plus 7 plus 8 upon 3, which is 6. That's what we do. So we are calling this thing as the mean, which is essentially adding up the numbers and dividing by how many numbers. But sometimes mean can let you down. Example, let's say I want to organize a birthday party for my kid, and I need to know what is the average age of the kids which are going to come at the party. That's important. I want to find out what is the average age of the kids which are going to come for the party. So I am having the following things. There are 6 kids which are aged 13. And there are 5 babies which are aged 1. What is the average of this? 7.54 something. That's correct. Yes. So because the average age of the kids coming to my kid's birthday party is 7.5, I decide to get what is called as a jumping castle. And this turned out to be a very bad idea. 13-year-old kids will feel very embarrassed to jump in this. They are too big for playing this. And 1-year-old babies, they can't jump. So mean let me down. So I say over here that mean was no doubt accurate, but was not useful. Mean was accurate, but it was not useful in this scenario. That's just an example to show you some drawbacks. Then, therefore, I introduce median. What does the median say? Simply list all the numbers in the order, precisely ascending order, and choose the middle one. So if you consider birthday activities, I'll do one thing. I'll list all the ages in order. 1, 1, 1, 1, 1. 5 babies were there. 13, 13, 13, 13, 13, 13. How to find the middle one? This, 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 this. 13. Yes. Okay. So that is middle one. And therefore, I say, let's have a disco. So what will happen? 13 years kid will enjoy dancing, and 1-year babies will enjoy the music. And that's how we see median is helpful. Sometimes you have two middle numbers. In such cases, you have to find out the average of the two. Like if I ask, what is the median of this? First of all, the numbers 12, 12, 2, 2, 3, 3, because two values are there at the center. Done. Therefore, I say median is 8. Okay. Next. These are something which we have studied in the school. So I am going little fast over. but it is there as a topic in descriptive statistics, so I don't want to skip it. That's the reason, right? Yes. Mode. The mode is the value that occurs most often. Example. But the example continue. The first thing is we group the numbers, so we can count them. So we have 1, 1, 1, 1, 1, 13, 13, 13, 13, 13, 13. 1 came 5 times, 13 came 6 times. So I understand that mode will be 13 because that came out repeated many times. Therefore, I say mode is most. Mode is most. Also, one important thing about the mode, sometimes it can be tricky because there can be cases where you have more than one mode. How? What is the mode of this number? So if you see over here, in this scenario, 3 came 1 time, 4 came 2 times, 5 came 1 time, 6 came 2 times, 7, 10, 1 time. So the highest value is this and this. And because there are 2 modes, you call it as bimodal. And if there are anywhere more than 2 modes, you call it as 3 or multimodal outliers. What do you understand by looking at this image of outliers? What is an outlier? Recall your box plot. What is an outlier? See, always we can say that outlier is outside the group. For example, consider the salary of Mukesh Ambani at Reliance as compared to the salary of most of the people. Obviously, Mukesh Ambani might be taking the highest salary because it is his own company. Yes, that's what I wanted to tell you. That always something which is very, very away is not necessarily something that we remove. It could be a part also. We need to introspect. Here we say outliers are the values that lie outside the other values and they can change the mean a lot. So we cannot use them. Like for example, what is the mean of this? The mean is 24. So we clearly understand that the mean in case hour is 24. But one thing is for sure that the number 24 certainly does not represent the above numbers well at all. The number 24 does not represent the above numbers well at all. And if I say, let's try to do that without this. So if I have values 3, 4, 4, 5, and you also had 104. Let's not consider this. Now you tell me what is the mean. So if you are going to exclude that outlier, please tell the people that you are actually excluding it. Median. What is the median of this value? 4, right. So median is also good in this scenario. Whenever there are outliers, one should go for median. So I say, go for median when outliers are present. And what is the mode over here? The mode is yes, 4. That's absolutely correct. Now there is something out of the syllabus which I'm going to teach, but I think that is good and important for everyone. Only one topic, only one topic. There are two topics which I have to teach. One topic you already know, and one topic is a new one, but you will understand why am I teaching you this, and it's important. So now, just keep your calculators ready. I want to talk a little bit more about the means. So the mean that we have been looking so far is arithmetic mean, which we covered. But there are two other types of means. The first one is the geometric mean. The geometric mean basically multiplies the numbers together, then does the square root or cube root depending on how many numbers are there. What? I'm not understanding. Idea is very simple. If you have, let's say, if I ask, calculate the geometric mean of the numbers 2 and 18, what will you do? Because there are two numbers. Because there are two numbers, you take the square root. If there were three numbers, you would have taken the cube root. Of what? Of the multiplication of these numbers. Something like this. Okay, just understand the mathematics. Just understand the mathematics. I'll take one more example. I have the numbers 10, 51.2, and 8. So, because there are three numbers that will go inside cube root, 10, 51.2 into 8. What does the final answer come out to be? 16. So in this case, we understand that the geometric mean is 16. Something like this. So this is the general formula for calculating the geometric mean. Now the $1,000,000 question. I taught you this concept, but is there really any use of it? Because we understand now there are two types of means. One is the algebraic, next is the geometric. The question is which one to use in which scenario and how can it be helpful? Let's look into this. When do we use geometric mean? Geometric mean is useful when we want to compare the things with different properties. I'll take an example. Let's say you want to buy a camera. So you have first camera, and this camera has a zoom of 200. Number of reviews by customers is 8. He has second camera and it has a zoom lens of 250 and the number of reviews are 6. The question is, which one will you buy? Difficult to figure out because you cannot use the arithmetic mean over here. Okay, camera 1. You cannot use the arithmetic mean over here. You know how we solve this? If I solve it using the arithmetic mean, if I solve it using arithmetic mean, then that is 200 plus 8 upon 2, 104, and this is 250 plus 6. This is what we see. So, why has this happened? See, zoom. The zoom is such a big number that this number of reviews that is almost getting lost. And therefore, we look at the geometric mean now. Geometric mean is we have 208 and 250 and 640. Yes, okay, that's correct. So now this is what is perfect. So I will say I will buy camera one. So what do we observe? We observe that even though the zoom of second camera is 50 bigger, the lower rating of 6 is still important. That is what is called as the geometric mean. The last type of mean after geometric mean, I told you there are two types of mean after that. Harmonic mean. Harmonic mean is going to add up 1 divided by the number. Difficult to say. See, 2, 4, 5, and 100. Number 2, I'll take it as 1 by 2. Number 4, I'll take it as 1 by 4. Number 5, I take it as 1 by 5. Number 100, I take it as 1 upon 100. And because there are how many numbers? 1, 2, 3, 4, 4 numbers. 4 upon this. That is what gives the harmonic mean, which in this case is, I think, 4.17. So essentially, we understand this is the formula. 1 upon 1, 1 upon 2, 1 upon 4. Perfect. Why harmonic mean? Well, harmonic mean, friends, is useful in some rate type questions. Example, go back to the CET exam type questions. We travel 10 kilometers at a speed of 60. At the speed of 60 kilometers per hour, you are driving a distance of 10 kilometers. And another at 20 kilometers per hour, then what is the average speed? I did a mistake. What is the mistake? You have blindly calculated, looking at my ink, 1 by 60. And this should be 1 by 20. Huh? So yes, the correct answer is 30 kilometer per hour. Now, after this, next comes the standard deviation and the variance topic. But before that, there is one more topic which is called as the mean deviation. Let us understand this is very, very simple. More than formula, what is important is we need to understand what is the significance of it. Right? Formula is easy. Formula is easy. I can explain that to you in a second. Let's get started. So here I say, conclusion so far, mean, median, mode are the most common ways of measuring the central values. Use the one that suits your data, or better still, use all of the three. Now we are going to talk about the mean from the frequency table. And that's very, very easy to calculate. They say you add up all the numbers and divide by how many numbers are there. Sometimes you don't have list of numbers, but what they provide you is a frequency table, which looks something like this, saying that number 1 came 2 times, 2 came 5 times, 3 came 4 times, 4 came 2 times, 5 came 1 time. How will you calculate the mean over here? The mean over here can be calculated like this. 1 came 2 times, 2 came 5 times, 2, 2, 2, 2, 2. 3 came 4 times, 3, 3, 3, 3. 4 came 2 times, 4, 4. 5 came 1 time, divided by how many numbers. That's exactly what is the mean, but that looks like a lengthy approach. So if you have that frequency table, a more better approach to calculate the mean would be 2 times number 1 came plus 5 times number 2 came divided by total. I think somewhere around 2.6 as per me. Just check it out. Okay, so that's the mean. So essentially, we understand that this is the formula, summation of frequency into that number upon the summation of the frequency. Now, after that, weighted mean, I'm gonna skip. That's not there in your outline. And I get started with the range thing now. Not that weighted mean is not helpful, but it's not there in your outline. So maybe at the end, if I have some time, I'll take on covering it. I don't want to cover the topics which are mentioned in a hurry at the last because I covered something additional before. Now we are getting started with the measure of the spread. Now, what do you exactly mean by the measure of the spread? Let us say it takes me 1 hour on an average to go from my office to home, or let's say I'll take the other way around. Let's say it takes 1 hour for me to go from my home to office on an average. The average time taken by me to go from home to office is 1 hour. But if there is traffic, I take 1 hour 15 minutes. And if there is no traffic, I take 45 minutes, 1 hour minus 15 minutes. This thing is what is called as the standard deviation. And standard deviation is nothing but the spread of the data. So standard deviation is one of the ways of measuring the spread of the data. Standard deviation is one of the way of measuring the spread of the data. How much is the data populated around the average? How much is the data populated around the average is nothing but called as the spread of the data. Understood to everyone? This is a very high level definition, but it's very convenient for anyone to put it into its head. Is standard deviation the only thing over here? No. I just explained you. Let's start with the very first one. Range. The range is the difference between the lowest and the highest value. Like for example, if I say I have a set of values 4, 6, 9, 3, 7. The lowest value is 3. The highest value is 9. Therefore, range is 9 minus 3 is equal to 6. Range is a way of measuring the spread of the data. Range is a way of measuring the spread of the data. So I'm clearly saying that we don't need standard deviation. Standard deviation formula is very complicated. So never use standard deviation, go for range. Because you can quickly identify how much spread of the data is. Range is the one which you'll always use, no standard deviation. So let's look at this now. My slide is contradicting me. The range can sometimes be misleading when there are extremely high or extremely low values. Like, can someone please quickly tell me what is the range over here? Now, because of this culprit, which is an outlier, you see the single value in this range is large, but most of the values are around the number 10, right? So we realize this as a problem, and hence we go for interquartile range or standard deviation. So I take back my words now. I would say opposite. Never use range. Either go for IQR or go for standard deviation. Yes, always remember. Range never kabhi jana hi nahi hai. Never go to that direction of range. Always go for IQR or standard deviation. When there are outliers in the data, how to handle it? So, when there are outliers in the data, how to do that? Quartiles. Now, you remember a box plot, you'll see everything here only, that's not a problem. So quartiles are the values that divide a list of number into quarter. And the way you obtain that is you put all of them in the order and cut it into 4 equal parts, and the quartiles will exist at the cuts. How? Something like this. Let's have a look at it. If I said these are the things, first all of these are sorted in order, and then this number 2 is at Q0, this is at Q4, Q1, Q2, Q3, and Q2 is also called as the median. In box plot, you remember we had studied these all things. In fact, in pandas as well, when we did df.describe, we did get the minimum value, we did get the maximum value, we did get the 25 percentile, we get the 50 percentile, we get the 75 percentile. So statistics, all the things which are already learned by statistics, our Python developers have converted to Python representation. That's it. I am telling you, you are not learning anything ideally. All these things are already implemented by you. Rather, we are doing reverse engineering now. Whatever we studied, how are they related to mathematics is what we are studying. And without this also, without a knowledge of this also, how are this calculated and all, we are hardly getting affected. Because even if someone says, I don't know how are the quartiles calculated, the question is practically, do we ever have to calculate the quartiles by ourselves? We just say df.describe, it's done. Never ever in life you will be ideally doing the calculations. I am showing you, but I'm just trying to tell you that we don't need it. We don't need it. That's very important. Things are so nicely automated in Python that your life has become super awesome. Okay. So in this case, these are the quartiles. How are they calculated? I'm showing you. Don't worry about that. They also say that sometimes the cut comes in between two numbers. So obviously in this case, this is Q0. Q4, and this will be Q2. So as you can see, these are the values. So now I say, how are the values actually computed? Let us look into that example. So I am assuming that I want to calculate, or let's say I have even set of numbers. Let's say 5, 7, 8, 12, 13. Keep your calculators open. I need your help. Keep your calculators open. I need your help. 14, 18, 21. Is the data sorted? Yes, of course. I think it's already sorted. So that problem is gone. Now the thing is, how are we actually computing the things? The idea is very simple. Q0 is the minimum value, that is done. Then Q4 is nothing but the maximum value, that is done. Q2, which is median. How is it calculated? So Q2 will be the average of this value. So Q2 is basically average of this value. So I can say n by 2. Yes. So Q2 is ideally calculated as n by 2. So in case if our n is even, right? So we are looking into this example. So Q2 is going to be no. I mean, wait. That's okay, but see, answer is not important. Wait. Answer is not important. Imagine instead of just 6 numbers, 8 numbers, you had 50,000 values. Then your calculator will not help you, right? So I want to show you the formula for calculating it. Getting it? I want to show you the formula. Here, even I can calculate it that way. Right. So yes, that's what I'm telling you. So here in case of this, Q2 is calculated if my n is even, it's calculated by n by 2. So I say how many values are there? The value of n over here is 1, 2, 3, 4, 5, 6, 7, 8. 8 values are there. So if I have to calculate my Q2 is given by, not this actually formula, just a moment. I will list down the formula that would be even more better so that all of us are aligned. So my Q2 is 12.5 only, but it is computed like this. N in this case is equal to 8. So Q2 will be computed as n upon 2 plus n upon 2 plus 1. Yes. X of n upon 2 plus x of n upon 2 plus 1 divided by 2. Now, n is 8. N is 8. What is the number? X means what is the number at n by 2th position? 8 upon 2? 4. 1, 2, 3, 4, 12. What is the number at n by 2 plus 1 position? N by 2 is 4 plus 1 is 5. 1, 2, 3, 4, 5, 13. So now that becomes universal. Now that becomes very much universal. And we also have to compute Q3 and we also have to compute Q1. So in this case, the Q1 value is computed if my n is even by using the median of first n by 2 values, right? So Q1 is nothing but the median of first n by 2 values. So what are the first n by 2 values between Q0 and Q2? What is the median of this? So that will be the centermost number over here. Q1 is median of first n by 2 values. Q1 is ideally the median of first n by 2 values. And in that scenario, it is going to be, what are the first n by 2 values? So I'll also write it. The first n by 2 values are 5, 7, 8, and 12. So this will be the second value plus the third value divided by 2, 7.5. And in the same way, your formula for calculating Q3 in this scenario, when the value of n is even, will be the same like before. So you want to calculate Q3. So Q3 is going to be, you need to use the last n by 2 values. That is the median of last n by 2 values. So 13, 14, 18, and 21. So this is going to be, Q4 will be 14 plus 18 upon 2, which is 16. Not Q4, Q3. This is how it is going to be. And in the same way, you calculate it for your odd number as well. So for odd number also, you will have to use the formula. So let's say, if you have odd number of values, in that case, your Q0 is nothing but the first item. Your Q4 is nothing but the last item. Your Q2 is going to be nothing but the item at n plus 1 upon 2th position. Q1 is going to be the median of first n minus 1 upon 2 values, and Q3 will be median of last n minus 1 upon 2 values, and it's done. So I think when you have the numbers, substitution part can be taken care of by you. Yes or no? All right, I need not do that. Come on, let's not do that. And we never need it also. That also I told you, you never need to do this calculation all by self. So that's not a problem ever. Okay. Now, okay, chalo, let's go ahead. This example, then what is going to be the interquartile range? 7 minus 4, right? Yes. Which is 3. So what do we understand? See, what I understand by this is if you see a box plot which we plotted during the Seaborn, because now you clearly know that when a box plot comes, what is Q0, what is Q1, Q2, Q3, and this part is what is called as interquartile region. Let us consider a box and a whisker plot. So see, this is the box, and this what you see around this, they are called as whiskers. Okay, so these are the values. First thing is we'll have to put them in the ascending order, and then we find out the quartiles. And once we have the quartiles, I get Q1, Q2, Q3, Q4, which is computed over here. Lowest and the highest values are also computed over here. Then Q3 minus Q1 is going to give the IQR. So which I plotted, it gets plotted like this. And this is what we understand. Okay. So they say whenever you have outliers in the data, don't consider this, only consider the data in the IQR region. This is wrong. I mean, I won't say 100% wrong, but you can definitely say 50% wrong. What I mean by that is you don't have it in your curriculum, but there is a technique which is called as Winsorization, or it is also called as soft capping for outliers. That comes in machine learning. Let's look into this. We don't understand the code, neither am I interested, but I want to show you some important things. Let me see if there is something here. So, see, in this data, the author of the notebook says there are outliers. You can see over here, there are outliers. Outliers are there on the higher side, not on the lower side, because this is about the income. Okay, fine. Now, we say that this method should not be preferred over the z-score when the particular column is not normally distributed because it is having values here. Now we say how we do. So listen to this. What does data scientists say? That you know what? Your IQR is this much, no? So you go 1.5 into IQR. So if your IQR value comes out to, let's say 100, then you do 1.5 into 100. That comes out to 150, right? So they say that from here, you go 1.5 times of IQR. You can see this line over here, right? They say that from here, you only go 1.5 times of IQR. So Q3 plus 1.5 IQR, which is this 150 in our case, is this. And on the lower side, you go lower side 150. So here you went plus 150. Here you go minus 150. Q1 minus 1.5 IQR. So essentially they are saying that whenever you have outliers in the data, you only consider the data here and here. This data, remove it. And if anything over here is remove it. That can be the first option. Remove the outliers. Anything which is going outside 1.5. Now, how 1.5? They came up to this conclusion after some research. That we need not get into that. I'm just explaining you one of the technique. Anything which is going ahead of minus ahead of 1.5 IQR and below minus 1.5 IQR, you're gonna remove it. I was talking about another technique, Winsorization. What does Winsorization says? It says the same thing. You calculate plus 1.5 IQR, calculate minus 1.5 IQR, and anything which is going out of this, or let's say there are some outliers here, anything which is going out of this, all of these value, let's say if this value, this value has to be 100. Let's say this line is at 100 and this line, let's say, is at 150. This is at 140 and so on. They say that all of these values, you get it at 100. Every value you get it at 100, and here also you get it at this. So basically what are you doing? Anything which is going out, you are squashing it in the range plus minus 1.5 IQR. Are you understanding it diagrammatically what I said? If yes, then I'll show you how we do it in code. Diagrammatically clear, all these values, bring it, compress it. So values will change, but outliers are there, right? So that's how we handle it. Consider a data set which has outliers. Ensure that the sample data set has at least 50 records. Plot the box plot for it. Print the code for. And now what am I doing? We have our day 5 ready, right? So I am going to create a Google Colab notebook over here only so that it remains very handy for us. The reason I'm doing it quickly is because I don't have this topic in the syllabus. So we are using ChatGPT to quickly get it so that we are not spending a lot of time on it. And according to me, it is important. So I call this as outlier capping. Now, let's see what data has it generated. Okay. Bf.head. By that time, I'll get the box plot code of it. Okay, so this is what is the data generated. How many rows are there? 50. Let me plot the box plot. tlt.boxplot. Do you see outliers? Well, let me say, I want you to modify the code such that the outliers are there on the upper side and the lower side as well. Get me the new code printed. Let it be there on both the sides. What are the values at Q3 plus 1.5 IQR? Yes, 4060. Yes, perfect. What is the value over here? What is the value over here? 40 and 60. Okay. What we want is these all values will come to 40. These all values will come to 60. And so this will be empty and this will be empty. Let's see that. Explain Winsorization for soft capping outliers. So as you can see, it's a technique used to limit the extreme values by replacing them specifically by this. Or let me say, I'll go for IQR capping first. Okay, Q1 minus 1.5 IQR, Q3 plus 1.5 IQR. Okay, I generated code again. No, I need not do that. So what are they saying? See, have a look. Now they say, let us calculate this. We have a box plot. 40 and 60, we know it. I'm doing it manually. Q1 is of this original column. Is that column called original? I don't know. Value column. We'll have to modify it. $44, $52, 8.59. Exact values. Okay. This is what we understand. 25% 75% calculated. Then I'm calculating this. So Q1 and Q3 are here. This is Q1, this is Q3, and I calculated IQR. Then I'm also calculating the lower bound and upper bound, which is 40 and 60 respectively. So I would say see 31 and 65. Q1 minus 1.5 per Q3 plus 1.5 here. Q1 minus 1.5 here, Q3 plus 1.5 here. How come 31? God knows. Is the data changed or something? Runtime run all. 31 and 65. Okay. And then when you have this, then I'm doing this. DF of original, which is our column, apply lambda function. If anything is less than lower bound, make it at lower bound. And if anything is greater than upper bound, make it at upper bound. So I'm going to do that. It's just that the name of the column is not original. Name of the column is value. You see over here, things are capped. Original versus the IQR data. So now that we are clear, the next topic is the mean deviation. Mean deviation. Read through this. I'm sure you will not understand. It's very, very easy, but when you read through this, you will not understand. First point, everyone might have understood. You compute the mean. Second point, you said distance of each value from the mean and then mean of those distances. Once you see the example, you will quickly understand. Let us take an example. Keep your calculators ready. 1, 2, 3, boom. Can you quickly tell me what is the mean of these values? The answer should be 9. The second step, if you go back, the second step is I need to find out the distance of each value from that mean. Means the first thing that I will find out is what is 9 minus 3? 6. Yes. What is 9 minus 6? 3. This is also 3. This is going to be 2. This is going to be 2. Then this is going to be what? After that, what's the next value? 1. After that, next value? After that, next value? After that, next value? Minus 6. And after that, last value? Last value? Yes, minus 7. Now, if I say that when I travel from office to home, let's say this is a 3-kilometer distance. Does that mean that when you travel from home to office, the distance becomes minus 3 kilometer? No, right? And that's exactly what you all did. I circled out these values. That's because that only. Did I ever say that you subtract? No. Distance, distance. So positive or negative, we will write it as positive only. So this is exactly what I mean. So the distance from 9, so obviously 9 minus 3, 6. Similarly, this. So here also it's going to be like this. Whatever I wrote, maybe I may went wrong while writing, but yes, this is the final answer. And one of the very important ways you can do that is, we know that the mean is 9. In this way, I have plotted this and this, right? So number 9 and 3, 9, 3 unit, 9, 3 units. This is 7, 16. So 9 plus 7, 16. What is the total of the values on the left hand side? Sum of this 15. Sum of these, if these two numbers are not same, LHS and RHS, then wrong. If these two numbers are not same, then you are somewhere wrong in doing the computations of this table. This is the way to quickly cross check your answer. We have the mean deviation, which is the mean of those distances. Mean of those distances means we got this. Find out the mean of this. Tell me what is the mean of these values? What is the mean of this? 3.75. Yes. So we get that means our mean is 9. Mean deviation is 3.75. So what is exactly mean deviation telling us? Mean deviation tells us how far on an average all values are away from the middle. How far on an average all the values are away from the middle. So I can also say that deviation is as good as distance. So the formula which was recommended by you and applied by you right now is that only. Initially you calculated mean, then every value you subtracted from the mean and took the absolute, and then the total of that divided by n, that is the average. And that's what we did. Read everything. Read everything which is there on this slide. This is not standard deviation. Let's take this example little ahead now. I'm taking this example little more ahead, where I say, you and your dogs, use your calculator 1 second. You and your dogs have measured the heights of the dogs in millimeters. You and your friends have measured the height of the dog in millimeter, and following are the heights. Neck level, shoulder level. So this dog is 600 millimeter. This is 470 millimeter. This is 170, 430. I want to calculate the mean deviation. You have these values, and we know that the formula is something like this, right? So let me not disturb you, and can you tell me what is the final answer? First of all, you calculated the mean, and the mean came out to be 394, right? So then you find out the absolute deviations, and the total of that is 636. So the final answer will be 636 upon 5, which came out to 127.2. Am I correct? That's how you got it, right? 127.2. Yes. Perfect. Now we say that means therefore on an average, the docks heights are 127.2 millimeter from mean. But this is mean deviation. We are interested in standard deviation. So standard deviation is how much data is spread around the mean. So now this is what we already did, LHS and RHS. I need not explain that. Just few things. LHS, RHS 318, 318. If they are not equal, then you have made a mistake. Now let's get to the next topic, standard deviation. So what is standard deviation? Standard deviation is the measure of how spread out the numbers are. Exactly, if you remember, mu plus or minus standard deviation, the topic which I covered before the range function, I'm talking about that only. I'm talking about that only. And then after that, it is denoted by the symbol sigma, the Greek letter, and the formula for calculation of standard deviation is square root of variance. So standard deviation is square root of variance. So now the question is, what is variance? If standard deviation is square root of variance, then obviously, what is variance? So read it and see if you understand. Again, like the mean deviation, this is very, very similar to mean deviation, very similar. One difference, only one difference, formula is same. Yes, square. Earlier, x minus mu absolute was taken, but now we are taking the square, and that is nothing but your variance. Let me not invest a lot of time and take a step ahead. So I'm going back with the dog example. What was the mean value? 394. Now what do we have to calculate? The distance in between the mean and every dog. Right, so we have to calculate this distance, we have to calculate this distance, so on and so forth, which came out to be like this. I just masked the dogs over here, and these are the distances which we have. Then you will find out the square of each. So variance is this. And what is standard deviation then? What is standard deviation? Square root of 21704. So we understand this. That means it is 394 plus or minus 147. That is mean plus or minus standard deviation. That's what we see over here. And then this is what we understand. So what is the use of doing it? What is the use of doing it? Well, Now I understand all the values which are going outside of the range of one standard deviation up and down. So this is mu plus 1 sigma. This is mu minus 1 sigma. And so now I say, because of standard deviation, I have a standard way of knowing what's normal, which is in this range, what is extra large and what is extra small. So if you see this guy, this dog is extra large, and you look at this extra small, that's what standard deviation has helped me to find out. Rottweilers, they are tall dogs, and Dachshunds, they are a bit short, right? Yes. So standard deviations helps us to find out that. And the formula for standard deviation, as we just understood, is every value minus the mean square summation upon n, and that is going to be standard deviation of population. If you want to find out standard deviation of a sample upon n minus 1, that is what researchers say. It's there here. For sample, you won't take n, but you will be taking division by n minus 1. So in our case, I assume that the 5 dogs were the dogs in the entire population. So we divided by n. But if I say that, hey, there were 500 dogs, out of which I took this 5, then it becomes a sample. And then the formula will be like, instead of dividing by 4, you will divide by 5 minus 1. Instead of dividing by 5, you will divide by 5 minus 1. That becomes the variance. And this becomes the standard deviation. So the formula looks like this. So okay, this one also, this divide by n minus 1, you can consider it as a correction in your formula. So these are the formulas. This is divided by n for population, and for sample, divided by n minus 1. Now, we saw that in standard deviation, every time we were squaring, and that came as a doubt to my mind, because see, we have clearly seen that mean deviation was also giving us some answer. Then why are we going for standard deviation? That came to my mind, that if mean absolute deviation can do it, then standard deviation is required. Why? I mean, mean absolute deviation was saying that you take the absolute. That was also working good. Then why standard deviation? And that is exactly where I got the answer. If I consider these values, let's say, if I consider a line, and these are the points. This distance is plus 4. Let's say this is also plus 4. What is the mean of it? Do you think that the mean of this data can be 0? Calculation wise, I see that it is 0. It's not that I am disagreeing. Calculation wise, I see that it is 0, but can the average of non-zero values ever come 0? No. What is happening? What is the problem? The problem or the issue over here is the positives and the negatives are canceling each other. So they said that, hey, you don't go for mean, you go for absolute mean. That's exactly what happened in mean deviation. Mean deviation makes more sense. It actually captures that there was an error of 4. Are you all getting it? What advantage mean deviation gave and why we did drop off mean and we went for the mean deviation initially? Are you all okay? Understood this? Now, if mean deviation is taking care of this scenario, then why did we go for standard deviation where we squared it? I mean, that formula was also okay. Well, that answer lies here. Why are we taking the square? Well, consider one more example. Let's say this distance is +7. This distance is +1. This is -6. This is -2. Can you calculate the absolute mean for this? Can you calculate the absolute mean for this? Bolo, bolo, quickly. This is where I have the problem. Now you'll be like, what is the problem? There is a problem. See, if you look over here in this example, you can clearly see that the smallest value is -4. Let me write it. The smallest value is -4 and the biggest value is +4. So let's say here somewhere is 0. In this example, the smallest value is -6. The smallest value is -6 and the biggest value is +7. So come on, it's quite obvious that this is a bigger range as compared to this. So obviously the error over here also must be high and the error over here must be low. But mean absolute deviation is like, Darshan, the error over here is 4 and the error in this line is also 4. That's exactly what it is saying, and that is where it is going wrong. The error on the first line is more than the second line. Anyone can see it from the eyes also. Right? You can, even if you observe this, see this is spread out only in this range and this is spread out in this range. See, the width of the box is higher as compared to this. So obviously the error also must be higher over here. This definitely has to be more than 4. It cannot be same. That is the problem. That is the problem. Wait a minute. If that is the problem, then do you mean to say that the squaring of the mean has solved this issue? Yes, I actually mean to say that. If I find, use your calculators. Squaring of the mean. 4 square, sorry, 7 square, 1 square, -6 square, -2 square upon 4. What is the answer? 16. Oh, you see, 16 is smaller than this. 16 is smaller than this, and this is awesome. This is awesome. This is perfect. That's exactly what I wanted, and this is getting quantified here. That's good. Now, one problem is all the values are in the range -6 to +7, here -4 to +4, but the errors 16 and 22 look very big. So you calculate the square root of this, which comes out to 4.74. Yes, thank you. And here the square root comes out to 4. Yes. Now, see, just like these were 4 and 4, in the way this is 4.74 and 4, and we see that the square root means or seems to be square, and then finding out square root seems to be a much better metric. And thus I say standard deviation is bigger when the differences are more spread out, just like what we want, and hence we don't use mean absolute deviation, but we use standard deviation. So you statistically also understand why researchers initially invented mean. Then they found out how mean can let them down. Then they went for mean deviation. Then they found out scenarios where mean deviation is also letting them down. And then they came up with the mean squared, which is the standard deviation. And it works fine till today. These all things happened across several years. It didn't happen in a single stroke. Someone invented, someone found out the drawback. When someone invented, someone found out the drawback, and so on and so forth. These metrics are being invented. Now, we understand why are we squaring it. Last one thing over here is we just understood in the example of dog, mean plus or minus one standard deviation, which was 394 plus or minus 147. Am I correct with the values? 394 plus minus 147. Is that correct? The dog example for standard deviation? Yes, no? Yes. Now, the last and the important thing, you cannot sustain without knowing standard deviation, variance, and the next topic, which is a small topic, which I'm going to talk right now. In machine learning, you cannot sustain without that. Till earlier, I mean, whatever I was doing, it is you just cannot sustain without knowing what is a continuous variable, what is a discrete variable, what is a categorical, nominal, ordinal. If you don't know that, machine learning is not for you. Telling it right now. Most important thing that we learned today. Next, you need to understand IQR. Without that, machine learning is not for you. You need to understand the soft capping. Without that, machine learning is not for you. You need to understand the standard deviation and variance. Without that, machine learning is not for you. And the fifth one is the empirical rule of standard deviation. Without that as well, machine learning is not for you. So these all things are important. Maybe harmonic mean, geometric mean can be still kept optional, but without these all topics, you cannot understand anything in the machine learning code, at least the interpretation part. This is called as the standard deviation empirical rule. So this has come out of the minds of the researchers. You know what does researchers say? That Darshan, you calculated that 394 plus or minus 147. Researchers say that after our lot of efforts, we have come to a conclusion that the data, 68% of the data will lie always between mean plus or minus one standard deviation, 68%. Then they said 95% of the data will lie between mean plus or minus two standard deviation, and 99.7% of the data will lie between mean plus or minus three standard deviation. If anything goes still out of that, then that is also one more way of identifying outliers in machine learning. This is also one more way of identifying outliers. So I was saying standard deviation, and the question is, we know that when I talk about the standard deviation of population, it is denoted by what? If you recall, by what do we denote the standard deviation of the population?
Here's what I found.
My Siri started talking. Okay. How do you denote standard deviation of the sigma? Mu was the mean of the population. Mu was the mean of the population. Standard deviation of the population, which is denoted by sigma, and it was every value minus the mean whole square, summation of that divided by n, and the whole in root. In the same way, standard deviation of sample, which is denoted by what? Yes. You need all of this in hypothesis testing. I mean, in real life also, while coding also, you need this convention. That's why I'm insisting on it. In coding also, you need to use this convention, and these conventions are very standardly used everywhere. Everywhere. Everyone on planet Earth uses these conventions. So better you also use it. So that's going to be summation every value minus the mean square upon n minus 1 in the root. Now, coming on to our say. So the question is, why do we divide by n minus 1 for sample, but by n for population? See, ideally, it is completely okay if you don't know this. But if someone is asking you in the interview, then at that time you cannot say no, that okay, Darshan sir showed that it's completely okay. Why are you asking? He also knows that it is not required. But he will test your knowledge on how technically sound you are. So at that time, it's good to know why to let down. So I am saying the solution. So it's all about accuracy and fairness. You can start by saying that it's all about accuracy and fairness. We all know when I talk about a population, you have the data from every member of the group, right? And when you talk about a sample, you have the data from the part of a group, and you are trying to estimate from the for the entire population. So populations, small group is a sample, and based on this calculation, what are you going to do? You are trying to infer or estimate for the whole population. So let us say, as an example, we have total 4 students, and their test scores. Okay, and this entire thing I am assuming to be the population, not a sample. So let's say their scores are 70, 80, 90, 100. So how do you calculate the mean? The mean is 70 plus 80 plus 90 plus 100 upon 4, which will be 85. Okay. Now, in order to calculate the population standard deviation, which is nothing but sigma, you in this case, the first thing that you do is you calculate the distance between mean and each score. That's one thing which I taught you. Then after that, you square these distances. Then after that, you add them up. And then after that, you divide by 4. Why 4? Because it is the whole population. And then after that, you take the square root. And this is completely fine because you are not missing any data. Then from here, you get here. So I start writing from here. But what if you only have a sample? So let's say, for example, you randomly pick 2 of the 4 students, assuming that these are the 2 that you picked up, 70 and 80. So your mean of the sample, which is denoted by x bar, that's going to be 70 plus 80 upon 2, which is going to be 75. But I would say now the key idea is 75 is not the true average of the whole group, but it is only your best guess based on the limited data. So here I say, now if you do absolutely same steps just like you did here before, but you are dividing by 2, which is the number of scores, then you tend to underestimate the true spread, which is your standard deviation of whole group. And therefore, I say that in order to fix that, you divide by n minus 1, which in this case here is 2 minus 1, which is equal to 1. which makes the result a bit bigger. And therefore, I say you tend to, or I say, because it makes the result a bit bigger and more fair for estimating the true variability in the whole population. So I can say in a very simple way, I can say that imagine if you are trying to guess how tall everyone is in a particular class. So you only measure 3 people. So you shouldn't assume those 3 perfectly represent the whole class. And to make your estimate more accurate, you inflate your result a little bit, and that is why you are dividing the thing by n-1, right? So that is one important thing that we do that. So these are the reasons why we do it over here. In fact, here I would like to add on one more thing over here. That's not the only reason behind it. So I would like to add on one more slide. And come over here. Now let's get into little bit technical part of it, right? So there is a concept which is called as degrees of freedom. There is a concept which is called as degrees of freedom. Again, that's something which is very, very important in statistics, right? Are you aware of it, Naresh? Would you like to tell us what it is? We'll be happy if you can just tell in simple words, what is degrees of freedom? And if you know it, not mandatory. Okay, no problem, no problem. That's fine. So, yes. So I was saying degrees of freedom. So, in fact, this is the real reason. It is central to why we are dividing by n-1 in sample standard deviation. So let's first understand what is degree of freedom. Going forward, we'll be calling it as DOF. Now, DOF mainly refers to the number of independent values that can vary in a calculation without violating any constraints. The number of independent values that can vary in the calculation without violating any constraints. The number of independent values that can vary in a calculation without violating any constraints. So whenever I am calculating the sample variance or standard deviation, there is one key constraint. The sample mean is already fixed by your sample values. What is the constraint? The sample mean is already fixed by your sample values. So when you calculate how much each data point is deviating from the mean, only n minus 1 of those standard deviations are free to vary. And the last one is automatically determined to make the total match of the sample. I say over here, therefore, when you'll understand this. I'm going to take an example to make it clear. Don't worry about it. Therefore, when you calculate how much of each data point deviates from the mean, only n minus 1 of those deviations are free to vary. Only n minus 1 of those deviations are free to vary. And the last one is automatically determined by, or I would say determined to make the total match the sample mean. Let's understand by taking an example so it becomes more clear. So let's consider I am having a sample of 3 numbers. And the sample mean, which is known to me, that is 10. So I am saying, let's call the 3 numbers as x1, x2, and x3. Therefore, we know that x1 plus x2 plus x3 upon 3 is equal to 10. Therefore, x1 plus x2 plus x3 is equal to 30. Now, let's say if we understand this, that's coming to the point. If we listen to this very carefully, that's where I'm actually nailing it down, and this is what he expects. So I say, if we pick any of the two values, because you have x1, x2, x3. So let's say we are picking any of the two values. Degree of freedom says n minus 1, right? So 3 are there. N minus 1 is 2. Therefore, I say if you are picking any of the two values, let's say that x1, which is 8, and let's say x2, which is 11. then my x3 is 30 minus x1 plus h2, which is 30 minus 19, 11 plus 8, which is 11. So I understand that once you choose to, the third is locked in. And this is because you had 2 degrees of freedom. That is n minus 1. That is n minus 1. And coming on to the last one, why does this matter for standard deviation? Well, so the answer is very simple. If you look into the formula for variance, right? And also standard deviation, we know that it involves summation of square differences, and therefore in this case, if we use sample mean, and which we know that sample mean, which is itself purely based on the data, then in that case, we have used up one piece of information. What do I mean by that? One piece of information is 1 degree of freedom. So they say that in order to make an unbiased estimate of the population variance, we divide by n minus 1 and not n. So the advantage over here is this corrects for the fact that we are using the sample mean as an estimate of the true mean, which introduces a small bias. So the idea is, we understand degree of freedom is nothing but the number of values in your data that can vary independently. And in the sample variance, one value is constrained by the sample mean, which is n-1 degrees of freedom. And when you divide by n-1, it adjusts for this, giving an unbiased estimate of the population variance. That is how we think of answering this. What do you do? Start reading from here. Let's go ahead. Can I assume these things are clear? Enough for explaining anyone at the interview. So kind of, even if you know this much, it is more than sufficient. Continuing with the standard deviation part, we have an example which kind of says right now that 95% of the students at the school are between 1.1 millimeter and 1.7 millimeter tall. 95%. 95% is how many standard deviations? 2 standard deviations. Yes, that's very important thing. So they are saying that mu plus or minus 2 standard deviation is this. So mean minus 1 standard deviation, minus 2 standard deviation is this. Mean plus 2 standard deviations is this. Okay. So assuming that our data is normally distributed, can you calculate the mean and the standard deviation? Mean is very simple. This is the lowest value. This is the highest value. Mean will be at the center. So mean is halfway. This plus this upon 2, 1.4, we get it. And then they said 95%, which is 2 standard deviations on other side. So I say 95% is 2 standard deviations on either side of the mean, which means 2 on that side, 2 on this side. So total is 4 standard deviations. Therefore, I say 1 standard deviation is equal to highest minus lowest divided by 4, and that is the value of 1 standard deviation. So precisely the mean is 1.4. The mean is 1.4 plus or minus 1 into 0.15. 1 standard deviation, this and that side. Or 1.4 plus or minus 2 into standard deviation. That's the value of standard deviation. 1.4 plus or minus 3 into 0.15. Something like this, 1.4 plus 1 standard deviation, 1.4 plus 2 standard deviation minus this. This is what we understand over here. So we get the mean and standard deviation calculated as asked in the question. So I say, it is good to know the standard deviation, because with the help of that, I can understand that 68% of data is likely to be between 1 standard deviation. 95% of the data between 2, and 99.7% of the data between the 3 standard deviations. So if I continue with my example, where the number of standard deviations from the mean, also called as the standard score or sigma or the Z score. So the question is, in the same school, one of your friend is 1.85 meter tall. So how does that get quantified? Like this, 1.85. So 40 plus 15, 55. 55 plus 15, 70. 70 plus 15, 85. So this is where your friend is. So in the same school, one of your friend is 1.85 meters tall. So you can see that on this bell curve that this 1.85 is mean plus 3 standard deviation. So we say that your friend has a Z score of 3. Your friend has a Z score of 3. So I say it is also possible to calculate how many standard deviations is 1.85 from the mean. So how far is 1.85 from the mean? This minus this, which is equal to 0.45. And because it is 3 standard deviation, one standard deviation being this, so 0.45 upon this gets me this answer. Although it was already clear from the figure, but I talked about it. Now, if you see this, that's good. Now everything is available and aligned. Now, we are talking not about standard deviation now, but I am talking about a new topic, standard scores. So if you remember the example of the dog, when I was saying mean plus or minus 1 standard deviation, so mean was 394 and this was 147. That's exactly what we understood yesterday, right? The dog's height. Am I correct? 394 plus or minus 147. That's exactly what we found out. Now, machines say that, Darshan, these all are too big values. I will not be able to understand that. Machine learning models also say that. Machine says that, hey, Darshan, can you bring down this mean to 0 and the values in such a way that the values are plus or minus around the 0? So is there a way you can make this 0 and rest all things proportionately aligned? Proportionately, I'm not saying that keep it as it is. You have to proportionately align. So basically converting that into a representation which is centered around 0. You can do that. And that is exactly where the Z score or the standard score comes into picture. That's the formula. Find the mean of the data and then divide by standard deviation. Find the mean of the data and then divide by standard deviation. Basically, the Z score is every value minus mean upon sigma. Every value minus mean upon sigma. And that is what is called as standardizing or also Z score. All are the same. So this happens something like this. You see the mean over here, 1010. You can see minus 1 plus 1 standard deviation, so on and so forth, minus 3 and plus 3. Now the mean has become 0 and all the values will be between minus 3 to plus 3. If anything still goes outside, you call it as outliers. That is how it goes. So how to convert that? That's very simple. Consider these are the values. First thing is you will have to calculate mean and standard deviation of it. If these are the set of values, I am not going to tell you how do you calculate the mean and the standard deviation of this population. You know that very well. Okay. Now what will we have to do? We have to apply the formula every value minus mean upon sigma. Like for example, if I have to talk with respect to the very first value, what will 26 become? So 26 will become 26 minus 38.8 divided by 11.4. And this divided by this becomes this. So that became minus 1.12. So 26 is minus 1.12 standard deviations from the mean. As you can see it here. In the same way you do it for all. 33 minus this divided by this. Right up to 34 minus 38.8 divided by 11.4. And these are few of the values as you see. And when you actually do it for all, this is what you get. Now, the mean 38.8, which was there, obviously becomes 0. Right? So this is 0. You don't believe me? Well, try to find out the total of all of this. It will be 0 only. I mean, the total of all of the average of all of this, not total, the average. The average would be 0. That's why these values are like that. And I can prove it to you. I can prove it to you. So let's say so I'm taking some values from our Superstore data set, which we have already some exposure of. Let's say I'm randomly taking these values. These are the values which I am taking. And I want it to be converted to the standard score. So that's a formula. Okay. So this is one of the scaling technique which is used in machine learning. The first thing is, sorry, you will have to calculate the mean and you'll have to calculate the standard deviation. So that's going to be average of A2 to A22. Yeah, that's correct. And I'm going to take standard deviation of the entire population, this formula, and A2 to A22. Correct. Now here, the value will be this value, which is X minus mean upon standard deviation. So I will say in bracket X, sorry, in bracket X minus this bracket close divided by standard deviation. And I get this value. So this is minus 0.3 units from the mean. And let's do one thing. What I wanted to do, yes. See, when I drag it down, it will let us down. And why is this happening? This is happening for the very obvious reason that right now it is A2. When I drag it down, this becomes A3. Then it becomes A4. So these all values are there. But as and when you take it more down, it becomes a problem. Also, if you see, in this case, divide by A23. This is divide by A23. So when I'm dragging it down, it will divide by A24, which is wrong formula. Then it will divide by A25, A26. We don't want that. So Excel says you need to lock the cell, and that happens with the help of dollar. I am sure you have an idea about relative referencing and absolute referencing. I don't want to lock these values, but these two values I definitely want to lock. Right? Yes. F4, yes. In Mac, it doesn't happen with F4, but anyways, it's done. Now, if you see all the values are in the range -3 to +3 and we will also try to compute, the mean and standard deviation of this. So the average of this should be 0, right? Yes, it is. And the standard deviation of the population is 1. So that means none of the values are going below +1 and -1. The maximum allowed values are -3 and +3. If it goes ahead of that, it's an issue. But yes, this is one of the technique over here which we see it. It's F and F4 in Mac. Okay. Oh, it doesn't work in my case for F and F4 also. I'll tell you why. Let me try it. So it is like that. And then I say, in my case, what is when I used to press Fn, I have a shortcut enabled over there, because of which my emoji box opens like this. So this is to open FN key. But yes, it's working. Thank you. This was a great achievement after a long time. So I was saying this is standard scaling. In the same way, there is one more thing that you will end up studying in min-max in machine learning. At that time, I'm not going to explain you again. I'll say that, remember, we studied that. So min-max scaling does apply this formula. So what is the min-max scaling saying? Min-max scaling says every value minus minimum of that value divided by maximum into minimum. So let me find out the minimum and maximum. Minimum of A2 to A22 is this. Maximum is this. So I say is equal to every value minus minimum divided by maximum minus minimum. And I need to lock this cell. I need to lock this cell. And I need to lock this cell. Now, the USP of the min-max scaling is it does not have the mean as 0, but the lowest value in the original column will be scaled to 0 and the highest value will be scaled to 1. Find out the lowest value in this column. It should be this, that has become 0. Highest value should be this, that has become 1. And all those values are proportionately squashed in the range 0 to 1. So if I this is minus 64, right? If I make this as minus 100, you will see this becomes 0 and all other values adjusted. See, this is 1. If I'm making it as 1000, this becomes 1. So the formula internally does this thing. And that is what is called as scaling. Right, so that we understand what is happening over here. And these are very, very important for machine learning. Right now, we just understood standard scaling. Yes, what is the purpose of this calculation? This is for the easiness. Like, let's look into this. That's the formula that we just understood. And this was quite obvious also. But why do we standardize? Well, the advantage, these are the exact two questions were asked by two of you. It can help us make decisions about the data. Example, Professor Wilson is marking a test, and these are the results that students have got, or the marks that they have got out of 60. Now, out of 60, how many do you think are passed? Out of 60, how many are passed according to you? Very high, medium, or very less have passed? What do you think? Out of 60, how many have passed? Many have passed, less have passed, or medium have passed? Less. less. Out of 60, very less have passed. So that means if these results are put up on the notice board, then it is going to look like the test was having very, very bad, the paper was very bad. If you remember in CAT examination, the same thing happens. You don't have the percentage system. What you instead have is a percentile system. So let's say out of the paper of 250 marks, the highest marks was 99. Then we say that this student has got 100 percentile and all others are scored as per that. So standardization helps us with these all things. So when you have like this, we see most of the students didn't even get 30 out of 60. So most will fail. That means that the test must have been really hard. So the professor decides to standardize all the scores and only fail the people which have one standard deviation below the mean, one standard deviation, which is 68%. 68% of them will pass. Anyone which falls outside the range of this 68% fail. Given this data, I don't think so finding out the mean and standard deviation is a challenge for anyone. So I directly conclude mean is 23, standard deviation is this. And then we all have applied the formula for scaling, standard scaling. So these all values are scaled. Now, mean plus or minus one standard deviation, right? So that means any value which goes above or below -1 is failed. So you see, this is below this is below this, right? So obviously we are going for standardization. So we'll be looking at all the values who have scored below. So these are the only two scores which have gone below -1. So I say that only two students will fail now. The ones which are lower than -1 standard deviation. And now this is much fairer. That can be one practical use case of doing standardization. It is very helpful in machine learning. You will be using it almost in every algorithm. So fortunately, I had this example, but every time it's not there. You know, some of the things are best understood when you actually get started with ML. But that's okay. Let's take it ahead. Histogram, if I remember Matplotlib and Seaborn, at that time I had discussed about it, so I can go a little faster. It is a graphical display of the data using the bars of different heights, similar to bar chart. But here you have the data into ranges. The height of each bar shows how many fall into each range. And then you decide what ranges to use. Like this is how an histogram looks like. And from this histogram only, we understood how to identify the skewness. So let's consider I have a orange tree farm and I want to make sense of all the data. So I plan to measure the height of each and every orange tree and I divide it into groups. How many trees are between this height range? So minimum and maximum is this. So my groups are something like this. How many are between 100 to below 150? How many from 150 to 200? And so on. And I can get a tree. And then maybe I can discover some insights from it, just like you have seen in the histogram. Like for example, in this, I discover over here that most of the trees in my farm are in the height range 250 to 300. So I get an idea about the overall statistics of the farm. That's an histogram. However, Histograms, as I said, they are a great way to look at continuous data, be it weight, height, age, time, salary, etc. But don't get confused between a histogram and a bar chart. They are different. So histograms have no gaps. And here you have numbers. Here in bar chart, there are gaps and you have discrete values, categories. This is the major difference. Major difference. And the y-axis on histogram is by default the count. Whereas over here, it can be any continuous value. But here it is always count. These are the three major differences in between the two. And that is what we understand in this. The most repeating frequency in this case is what? What is the most repeating frequency in this case? Correct. It is 2. The most repeating frequency in this case is 2. Then normal distribution. Now that's again an important thing because most of the machine learning algorithm expect the data to be normally distributed. And what is a normal distribution? A distribution which looks bell-shaped. Therefore, this normal distribution is also called as Gaussian distribution. It is also called as bell-shaped distribution. And yes, this is how the shape it will take. It will have exact 50-50% data on the left and right of the mean. As we all know that this goes up to 3 standard deviations on this side and 3 standard deviations on this side. So when you plot a histogram, your data can be distributed in different ways. It can be spread more on the left-hand side. It can be spread more on the right-hand side, or there can be no shape at all. Let's understand example. If I'm taking the scenario where I am considering the speed of car on express highway. Can you tell me what is the usual speed of your car? The average speed, the most of the cars are driven on the expressway in the speed range of 100 to 120. Then there are very few drivers who drive around 125, 150, 160, even 140, but they are very less. Also, there are relatively less people who drive in the range 80 to 100 and furthermore who drive in between 60 to 80. But most of them are in the range 100 to 120. And that is what we say when we plot the distribution of the speed of so many people. You will see this distribution is technically left skewed. Or we also say that the data is negatively skewed. The data is left skewed or right skewed. And this is a scenario where the data is right skewed or positively skewed. Here, also let's say I can consider the speed of the car in the city conditions. So we all know that because there are always traffic jams, most of the cars are in the speed range of 50 to around 25. If the traffic jams are really bad, the average speed can be even 10. And let's say if you're driving at a odd time of the day, maybe late night or somewhere in the afternoon, you may get an average speed little higher. And late night you can get an average speed which is little more higher. But most of the times, if I talk about the city, it will be this. So this is what you see as a right skew distribution. In fact, let me ask you, if you look into the salaries which people get, tell me whether it will be normally distributed, left skewed or right skewed. Salary of the people in an organization. Salaries of the people in the organization. Okay, I see your responses. So those of you who are saying left skewed, let us initially talk about them. So you mean to say most of the people in the organization have the salary on a higher side. So let's assume that most of the people are having a salary between 1 lakh to 3 lakh. Very less people are having salary between 60,000 to 80,000 and very less people are having between 40 to 60. This is what you mean to say. Is that really the scenario? If that would have been the case, then there would have been no poverty. I wish even I had a salary of 5 lakh rupees per month, 10 lakh rupees per month, 20 lakh rupees per month. But that's not the case. Most of the people have lesser salary. And very few people, maybe managers have little more salary. The directors have even more salary. The managing directors have further more salary, CFOs, CXOs, owners, but they are less. Most of them works on a lower salary. So it is right skewed. It is right skewed. Is that clear to all the people who said left skewed? Why it is right skewed? Yes. So just to quickly finish off this topic, machine learning algorithms don't like skewed data. They prefer normally distributed data, which looks something like this. Right? So it is bell curve. No left, no right. So the bell curve is nothing but a normal distribution. And most of the things in real life will be normally distributed. For example, in your office, if you measure the height of the people, most of them will have height between 5 feet 3 inch to 5 feet 6 inch. Most of them. Very few people will be shorter than this. Very few people will be taller than this. Like I am 6 feet 4 inches tall. But how many of them are there so tall? Very few. Or even if you consider size of the things produced by the machine, errors in the measurement, or in your society, if you go and measure the blood pressure of each and every person, most of them will have normal blood pressure. Very few have high BP, very few have low BP, but most of them have normal BP. Similarly, marks on a test. It is normally distributed. And what is normally distributed? When it is normally distributed, we say that your mean, median, mode are same. Fifth, symmetry about the center, as you see here, and 50% data less than mean and 50% data greater than mean. That can be seen very conveniently in this quincunx. Have a look at this. That's called as a Pascal triangle. I'm just trying to put in the value, then it is going into the right bin wherever the ball falls. increasing the speed. So that's a histogram. And this comes because it is using the Pascal triangle distribution. The data will always come out to be normally distributed. That's not a luck. That's how it falls. Every time you run it, you'll see the same thing. You also try it out, you'll see the same thing. It will be normally distributed only. Or if I look into this YouTube.
So you just mentioned that you want to learn Python. So do not learn Python in manual way in 2025 because learning Python in manual way will.
I'm considering over here large balls. Let's see what kind of histogram do we get. Forward it. See, it's normally distributed. You can see that. These are with the, now the next one is with the medium balls. See, it's again normally distributed. With the small size balls, it may not follow that, small balls, because the holes are big. Holes are big, right? Distribution. And see, this is also running the same way. Or even if you look into this. If I play this. Fall multiple balls. And this is the average of this triangle. You can see the mean and the standard deviation. Now we get into the topic of correlation. So what is exactly correlation? Well, the images over here will quickly help you understand what exactly correlation is. Well, do you all agree that as the temperature increases, the sales of ice creams as well increase? Do you all agree to the fact that the percentage that you scored, as the percentage that you scored increases, the sadness decreases? The more percentage you score, the less sad you are. Correct? Yes. Do you also agree that the number of cigarettes that you smoke, the greater the number of cigarettes that you smoke, the lesser are the number of years left in your life in most of the cases? Now, don't give me any odd examples, right? The more the number of cigarettes you smoke, the lesser are the number of years left in your life. And what have you understood from this example says there is some kind of correlation in between all of these things. That's exactly what our topic is. That's exactly what our topic is. So if you look into this, that's an example of a perfect positive correlation. This is an example of a perfect positive correlation. And This is an example of a high positive correlation. So this is 1, highest value, 0.9, little lower than that. This is 0.5 because little lesser than that, as you can see. And then this is as good as no correlation, 0. And this is low negative correlation, minus 0.5. Of course, there can be values in between this also. It can be 0.91, 92, 93, anything. This is minus 0.9. And this is perfect negative, which is minus 1. So as we understand correlation, co means together, and relation is relation. So when two sets of the data are strongly linked together, we say that we have a high correlation. And the correlation is assumed to be linear, following a line. Usually, as per machine learning, we expect the correlation to be between minus 0.7 to plus 0.7. If anything goes above 0.7, that's a alarm. If anything goes below minus 0.7, that is also alarm, because machine learning models don't like it. Anything not in this range is hated by machine learning algorithms. Why? You will understand when you start with the very first algorithm. Right now, let's not get into this. But remember, I'll be asking you this question. Machine learning algorithms expect the correlation between minus 0.7 to plus 0.7. Okay. Then correlation is not good at curves. So, for example, if you say that I have a scatter plot, something like this, can you find out the correlation over here? No, don't do that. So in such cases, don't go for correlation. If and only if there is a linear relationship, straight, either up or down or straight, then only correlation. For curved, no correlation. The correlation only works properly for straight line relationships. So let's consider an example. There has been a heat wave in the temperature, right? Ice cream versus temperature versus sales of ice cream. So if there is a heat wave, it becomes so hot that people don't even go out of their home. So the sales starts to drop. So ideally, I said as the temperature increases, the ice cream sales also increase. But after a certain temperature, it becomes so hot that people don't start going out of the house. So the sales of the ice cream starts to decrease. If something like this is the data, then you cannot use correlation because you see curve over here. The next thing, this is again something very important, not in your curriculum, but correlation is not causation. That means just because two things are correlated doesn't mean that one thing caused the other. Like a common saying is correlation is not causation, and what it really means is that correlation does not prove one thing causes the other. So the thing is, one thing might cause the other, or the other might cause the first to happen. They may be linked by a different thing, or it could be just a random chance. There may be many reasons that the data has good correlation. I'll give you an example. Remember one thing, correlation is not causation. So the first example, sunglasses versus ice cream. So, where I stay, right? I stay at New Bombay. So, our ice cream shop owner finds that how many sunglasses were sold in the in-orbit mall each day, and he compares them to the sales of his ice cream. So he is like, if there are 20 sunglasses sold in my ice cream shop, 20 ice creams are sold. If that sunglasses shop sells 120, then I also sell 120. If that sunglasses shop sells 130, then I also sell around 130. If the sunglasses shop sells 30, then I also sell the ice cream around 30. So he says that, hey, you know what? That there is a correlation between sunglasses versus ice cream. But does it mean, answer me this, does it mean that it is the sunglasses which is making the people want ice cream? No, right? Correlation is not causation. Obviously not, right? Or poor suburbs are more likely to have high pollution. So obviously, if you try to introspect that, poor suburbs. So let's say, for example, I don't know, let's say, I don't know, I have no idea about it, but let me compare Mumbai, Bangalore, Hyderabad with poor suburbs, let's say relatively poor. I don't know how much poor, so don't take the example literally. Let's say, let's compare it with a state like Bhopal or Sikkim, or if you consider Kolkata, or let's say Bangladesh, right? Relatively weaker economy. So poor suburbs are more likely to have pollution. So why? So does this mean that the poor people are making pollution? Do you mean to say by this line that poor people are making pollution? No. Or does it mean that are the polluted suburbs the only place poor people can afford? No. Is there a common link such as factories with low paying jobs and lots of pollution? Probably yes. Right? So correlation is not causation. That's what I wanted to tell you over here. I'll give you one more example. A few years ago, a survey of employees found there is a strong positive correlation between studying an external course, just like you are right now studying an external course at Simplilearn, and the sick days that you're taking at office. So do you mean to say that studying is making you sick? Will your office conclude that studying is making you sick? No. Or do we conclude that sick people study a lot? जो बीमार होते हैं वो ज्यादा पढ़ते हैं? No. Or did the people like you lie about being sick so that they can study more? Maybe. So without further research, we can't be sure why. And hence I say correlation is not causation. This is again something very popularly asked in the interviews. You should know this thing very well. And these examples will end that question here only. The interviewer will not ask any other question once you give him such solid examples. Okay. Then now we get into the very first type of correlation calculation, which is called as the Pearson correlation coefficient. The first one, ice cream sales. So, same example. The local ice cream shop keeps a track of how much ice cream they sell versus the temperature on that day. Something like this. So can I consider plotting the temperature on the x-axis and the sales of ice cream on the y-axis to actually see how the relation looks like? Should I do that? Do you think that will be helpful for us in finding the correlation? Yes? Okay. Let me do that then. Now tell me, what is the value of correlation as per you? Temperature versus sales of ice cream? Oh, it's 0.9, 0.85. Highly positive, yes. So we can easily see that warmer weather and higher sales go together. The relationship is good, but not perfect. In fact, it is this value. But you might have a question that how are you getting this value, Darshan? How is the value like this? That's where the mathematics comes into picture. We know these things. The way you calculate Pearson correlation is by using this formula. This formula looks really very, very dangerous. Don't you think so? It looks very difficult, at least in the first impression. I think it looks like something very heavy calculation, right? Yes. By the way, it is very easy. And I'm going to make it very simple. I would say let's ignore what is shown over here, and then we'll come back to this page. So to start with, it's super simple. Ignore everything. Done. If you understand this table, you understand that formula. If you understand this table, you understand that formula. Number one, this is the temperature. This is the sales. First of all, I found out the mean of the temperature, average of these values, 18.7. Then I found out mean of sales. These are the values. Now then I said 14.2 minus 18.7 minus 4.5. 16.4 minus 18.7 minus 2.3. So on. So every value minus the mean. So 215 minus 402 minus 187. So on and so forth. So A and B are computed. Then I am doing A into B. A into B. Minus 4.5 into minus 187, 842. So on, you get all of this. A's square minus 4.5 square is 20.3. Minus 2.3 square is 5.3. So on. B square minus 187 square is this. Minus 77 square is this. So on and so forth you get for all. Then this total is this. The total of this is this. The total of this is this. And then I get three values. 5,000, 177, 1,70,000. 5,000 divided by in root 177 into 1,70,000 gives me this number. Now, that is how easy it is to find out. And now if you look into the formula, we did the same thing. We found out the average of every value, then every value minus average. And that total is multiplied A into B. Then every value minus average ka square total. And similarly for Y's difference total. Whole inside root. And I think now the formula is clear to you thanks to this figure. Right. It's a very intuitive way. And again, in real life, you will never, ever have to calculate it by yourself. How do you get the correlation? Let us say you have a data frame, and when I'm doing df.head, you are able to see a data frame where you have name, age, and salary. That's a data frame. Now, obviously, you cannot find out the correlation between name and age because name will be object and age will be integer or float, and salary will be float or integer. So you have to do df.core, and earlier that was the only function, but today it has become mandatory for you to use the parameter numeric underscore only is equal to true, because by default it is false. So in the data frame, by only considering the numeric columns, which is age and salary, get me the correlation. So it will give a result something like this: age, salary, age, salary. That's how the result will come. And if you remember, I have already shown you these results when I was teaching Pandas. So today we just understood what is happening in the calculation. Correct. So what will be the value here? Age versus age will be 1. Salary versus salary would be 1. And these things, we need the values for it. So maybe age versus salary is 0.95. So this will also be 0.95. And that's how the results come. That is nothing but the calculation of the correlation. Now, after this, the next thing that we need to understand after correlation is skewness, the degree of distortion from symmetrical bell curve or normal distribution. It measures the lack of symmetry in the data distribution. It differentiates extreme values in one versus the other. Symmetrical distribution will have skewness 0. We have covered this. Now, how do you identify? See, in the symmetrical distribution, or you call this as a normal distribution, or you also call this as a Gaussian distribution. We know that 50% of the data is to the left and 50% of the data is to the right. Right? So, when you have a scenario which is called as, what kind of skewness is this? Positive is written. What is the next name for it? Right. Yes. Wherever the tail is longer, that. Okay. Don't forget the name. Wherever the tail is longer. Right. Here the tail is longer on the left side. Left skew. So I was saying over here, always do one thing to quickly figure out whether the skewness is left or right skewed. Mean minus median. See, if you look in over here, I don't know what is the value of mean, but if I assume this to be 70, then this value is certainly lesser than that. Let's say 65. Let's say 70 minus 65 is positive. So we say it is positively skewed. Similarly here, if I'm assuming this to be 65, then this will be higher than that, whatever be the value, but higher. So mean minus median, always give more respect to the mean. 65 minus 70, that's going to be negative. It's negatively skewed or left skewed. That's how you can identify this. This is the ideal formula for calculating skewness as a standard deviation. When is skewness too much? Well, these are the rules of thumb. We will be using it in our EDA session. If and only if the value is between minus 0.5 to plus 0.5, we say it is fairly symmetrical. If it is between minus 0.5 to minus 1, because the value will not go below minus 1, we know that. Or if it is between 0.5 to 1, we say it is moderately skewed. And if and only if it is less than minus 1 or greater than plus 1, highly skewed. So that's the reason to worry. About two scenarios are okay. So anytime the value goes below minus 1 or above plus 1, then only there is a reason to worry, else you need not. Kurtosis, this is done, right? So kurtosis. Kurtosis is all about looking at the tails of the distribution. We are not looking at the peakedness. Like in skewness, we are looking at the peak. Here, we are looking at the tail of the distribution. So it is mainly used to describe the extreme values in one versus others. So therefore, we say it is the measure of outliers present in the distribution. And kurtosis is of three types. This is what is called as normal distribution and desirable, mesokurtic. But this is called as platykurtic, where the data is more or less flat. And this is leptokurtic, which is a reason to worry because over here also we say the data is having thick tails. So how much of data is available in the tail? So look in below this curve, how much of data is available. This is what is ideal. So I say a mesokurtic distribution has a kurtosis similar to the normal distribution. It means extreme values of distribution are similar to normal distribution, and this definition is used so that the standard normal distribution has a kurtosis of 3, right? So 3 is what is expected. If it is greater than 3, then it is called as leptokurtic. Like this, leptokurtic, where the tails are fatter. Which means the data are heavy tail or profusion of the outliers. And here you'll see the outliers stretching across the horizontal axis of the histogram bar, which makes the bulk of the data appears in narrow vertical range. And platykurtic is where it's less than 3. So it is having a lower peak and it is broader than mesokurtic. And the reason for this is extreme values are less than the normal distribution. Extreme values are less than the normal distribution. So in simple words, I can say that kurtosis is a in simple words, we can say kurtosis is nothing but a statistical measure that describes the tailedness or peakedness of the distribution, which is how much of data lies in the tail and how sharp the peak is. I said how much of data lies in the tails and how sharp the peak is. And here also you have a formula. So kurtosis is having a formula where we say this is equal to 1 upon n into summation of all the values from I is equal to 1 to n, where I have every value minus the mean upon sigma whole raised to 4. So that sigma part is included here, where obviously xi is nothing but every data point, right? Xi is every data point which is being used over here. So we expect the kurtosis value to be equal to 0. Mesokurtic is nothing but we say bell-shaped. When it is leptokurtic, which is a tall thing, and thick tails like dinosaur, heavy tails, sharp beak, more outliers are there. And if you have platykurtic where kurtosis is less than 0, it has light tails, it is flatter, so it is broad and flat. So essentially, what I want to tell you with respect to the practical aspect of this is, where is kurtosis helpful? It is helpful in outlier detection. So if you see the kurtosis is high, then means we have extreme values. And this is useful in fraud detection or anomaly detection. Second, risk analysis. So in finance, if you see leptokurtic data in finance, if you see the leptokurtic data, then we understand that there is high risk, and high risk because of outliers like stock market crashes, etc. So that is where kurtosis is very, very helpful. Getting started. What is probability? How likely something is to happen? Many events cannot be predicted with total certainty. And the best we can find out that is how likely they are to happen. And that is the idea of probability. So there are a lot of images over here. Consider I am tossing a coin. Then what are the two possible outcomes which I can get whenever a coin is tossed? Correct. Head or a tail. What is the probability of me getting a head? 50%. Correct. And the probability of me getting a tail is also 50% or 1 by 2. That's absolutely correct.
Companies around the world are generating vast volumes of data every hour. This data could be in the form of log files, web server and transactional data, as well as various customer-related data. Also, data is being generated at a rapid rate from social media websites and applications such as Facebook, Instagram, Twitter, and WhatsApp. Companies want to use this data to derive value out of it and make business decisions. That's where data analytics comes into use. Data analytics is the process of exploring and analyzing large data sets to find hidden patterns, unseen trends, discover correlations, and valuable insights to make business predictions. Data analytics improves the speed and efficiency of your business. A few years ago, a business would have gathered information manually, performed statistical and complex analytics, and unearthed information that could be used for future decisions. But today, that business can identify insights on the fly for immediate decisions. Most organizations have big data, and many understand the need to harness that data and extract value out of it. So, they use a lot of modern tools and technologies to perform data analytics. Some of the tools I will discuss in detail later in this tutorial. Now that we have looked at what data analytics really is, let us understand the ways in which you can use data analytics.
What's in it for you? Now we're going to go over what is NumPy, installing and importing NumPy, NumPy array versus Python list, basics of NumPy, finding size and shape of any array, range and arange functions, NumPy string functions. And then in part 2, I'll move on to cover axes, array manipulation, and much more. So let's start with what is NumPy. NumPy is the core library for scientific and numerical computing in Python. It provides high-performance, multi-dimensional array object and tools for working with arrays. And I'll go a step further and say there are so many other modules in Python built on NumPy. So the fundamentals of NumPy are so important to latch onto for the Python, so that you can understand the other modules and what they're doing. NumPy's main object is a multi-dimensional array. It is a table of elements, usually numbers, all of the same type, indexed by a tuple of position integers. In NumPy, dimensions are called axes. Take a one-dimensional array, or we have, and remember dimensions are also called axes, you can say this is the first axis, 0, 1, 2, 3, 4, 5. And you can see down here it has a shape of 6. Why? Because there's 6 different elements in it in the one-dimension array. And they usually denote that as 6 comma with an empty node on there. And then we have a two-dimensional array where you can see 0, 1, 2, 3, 4, 5, 6, 7. And in here we have 2 axes or 2 dimensions, and the shape is 2, 4. So if you were looking at this as a matrix or in other mathematical functions, you can see there's all kinds of importance on shape. We're not going to cover shape today, but we will cover that in part 2. Did you know that NumPy's array class is called NDArray for NumPy Data Array? Now we're going to take a detour here because we're working in Python, and 2 of my favorite tools in Python is the Jupyter Notebook, and then I like to use that sitting on top of Anaconda. And if you flip over to jupyter.org, that's jupyter.org, you can go in here. You can install it off of here if you don't want to use the Anaconda notebook, but this is the Jupyter setup, the documentation on the Jupyter. Jupyter opens up in your web browser. That's what makes it so nice, is it's portable. The files are saved on your computer. They do run in IPython or IronPython, and you can create all kinds of different environments in there, which I'll show you in just a minute. I myself like to use Anaconda. That's www.anaconda.com. If you install Anaconda, it will install the Jupyter Notebook with the Anaconda separate. And you can install Jupyter Notebook and it'll run completely separate from Anaconda's Jupyter Notebook. And you can see here I've now opened up my Anaconda Navigator. What I like about the Navigator, and this is a fresh install on a new computer, which is always nice. I can launch my Jupyter Notebook from in here. I can bring other tools, so the Anaconda does a lot more. And under environments, I only have the one environment, and I can open up the terminal specific to this environment. This one happens to have Python 3.7 in it, the most current version as of this tutorial. And then you open a terminal if you're going to do your pip installs and stuff like that for different modules. You can also create different environments in here. So maybe you need a Python 3.6, Python 3.5. You can see we're having a nice framework like Anaconda really helps. So you don't have to track that on your own in the Jupyter Notebook and your different Jupyter Notebook setups. We'll go ahead and launch this Jupyter Notebook. And then I've set my browser window for a default of Chrome. So it's going to open up in Chrome. And you can see here, this opens up a folder on my computer. We have a couple different options on here. Remember, I set the environment up as Python 3.7. You would install any additional modules that aren't already installed in your Python on this. And it keeps them separate. So you do have to, for each environment, install the separate modules so they match the environment on there. And in here we have a couple things where you can look up what's running. You have your different clusters. Again, I just installed this on a new machine, so I just have a couple things in here that were run on here recently. And where we go on here is we then have on the upper right, New, and from the pull down menu you'll see Python 3, and this will open up a new window. And now we're in Jupyter Python, so this is a Python window, and we'll just do a print. And this, of course, is, let's go hello world. And we'll run that, and it prints out hello world in the command line. There's a couple special things you have to know what we're not going to do today, which is on graphics. If you've never seen this, one of the things you can do is you can also do A equals hello world. And if you just put the A in there, now if you do a bunch of these where you have A equals hello world, B equals goodbye world, and you put A, B, A, then return B, it'll only run the last one. But you can see here, if you put the variable down here, it will show you what's in that variable. And that has to do with the Jupyter Notebook inline coding. So that's not basic Python, that's just Jupyter Notebook shorthand, which you'll see in a little bit. So back to our NumPy array versus Python list. Python list being the basic list in your Python. Why should we use NumPy array when we have Python list? Well, first, it's fast. The NumPy array has been optimized over years and years by multiple programmers, and it's usually very quick compared to the basic Python list setup. It's convenient, so it has a lot of functionality in there that's not in the basic Python list. And it also uses less memory, so it's optimized both for speed and memory use. And let's go ahead and jump into our Jupyter Notebook. Since we're coding, best way to learn coding is to code. Just like the best way to learn how to write is write, and the best way to learn how to cook is cook. So let's do some coding here today.
But before we move on, let's understand first what is Jupyter Notebook. So guys, as you can see all over here, that Jupyter Notebook is a popular open source tool that basically allows you to create and share documents which contains codes, equations, you can have visualizations also. Basically, it is used for data analysis, machine learning, and scientific research, which makes it a very essential tool for developers like data scientists and researchers alike. Now, before installing Jupyter Notebook, I request you that you have Python installed in your system. So the requirement should be Python 3.6 or greater. So now let us officially navigate to the Python's website. So guys, as you can see all over here, so on python.org, if I click on download Python, so we're going to see that all over here, download Python 3.125. So as I already told you that the requirement of Python should be greater than 3.6. So just you can click all over here and you can see the download had started. So guys, as you can see all over here that we have installed the Python. Now let us open the file. So you can see the given software is going to install on this directory. Okay, so just click all over here. So guys, as you can see all over here, the Python installation of 3.125 is in progress. Let's wait for some time till it gets installed. So as you can see guys all over here that we have successfully installed our Python. Now let us open our terminal and let us check whether Python is correctly installed. So we are going to type python/version. So as you can see all over here, we have successfully installed our Python. So guys, that was our prerequisite. Now, there are two ways to install Jupyter Notebook. The first one can be pip. Okay, pip is a package manager, or using Anaconda distribution. So let us see with pip first. So guys, pip is a package manager which is used to install and manage software packages, libraries written in Python. So you can see all over here that the Python with version greater than 3.6 have default pip installed in them. Okay, so we can use pip command to install our Jupyter Notebook. So guys, as you can see all over here, we have come to the official documentation of Jupyter.org, and it is saying that installing Jupyter Lab with pip command. So what you can do guys, you can just copy all over here. You can go right all over here and click on this. Now, as you can see all over here,
it has started downloading the Jupyter Lab. So guys, we are going to install our Jupyter Lab with the pip command. So this is the official documentation of Jupyter Notebook. Okay, and just all you have to do is copy this and type on your terminal. So as you can see all over here, it has started downloading the packages which is required to download the Jupyter Notebook. Let us wait for some time. Okay guys, so we have successfully completed this step. Now let us move on to our next step. So as you can see all over here, so we have installed, okay, then what we have to do, then you can type this, you can launch the Jupyter Lab with this command on the terminal. Now let us wait. So as you can see all over here guys, we have successfully installed our Jupyter Notebook. So you can go all over here and just create a new notebook, and you can also choose your kernel and you can start working on your Jupyter Notebook. Suppose I'll show you one snippet. So 3 plus 5, let us try to run this notebook. So as you can see, it is giving us the 8 as answer. So it is following the Python syntax, and in this way we have successfully installed our Jupyter Notebook using the pip command. So now, as you can also see all over here, you can also install Jupyter Notebook with this command, pip install notebook, and then you can just open it. This is also another alternative. Similarly, you can install with Voila also. Same command and just open the Voila. Now, if you are using any other operating system like macOS or Linux, then you can install by brew install Jupyter Lab. So Homebrew will be the package manager for macOS and Linux. So I hope so you are pretty clear with how to install Jupyter Notebook with the pip command. Now, I have downloaded Anacondas from this official website. So as you can see all over here, this is the official website of Anaconda. Okay. Now just type your email and you can just download it. So similarly, as you can see, after installing, I'm going to launch my installer and let us click next. Okay. Let us click agree. Okay. And let us install this on the given directory. Let us wait for some time till the installation gets complete. So guys, as you can see all over here, we have completed our installation of Anaconda. So just click on finish and you can say we have successfully installed our Anaconda. Now let us open our Anaconda navigator. So just click on So as you can see all over here, just right click on this and our Anaconda navigator will be opened. So as you can see all over here, this is our Anaconda navigator and it is loading the packages. And for us to install the Jupyter Notebook, so as you can see all over here, just click on launch. So guys, if you click on launch, it is going to open our Jupyter Notebook. So as you can see all over here, it is saying launching the Jupyter Notebook and it is hosted on localhost 8889. So this is our hosted Jupyter Notebook. And similarly, you can create a new notebook all over here. And in this way, you can start working.
And just like any modules, we have to import NumPy. We almost always import it as NP. That is such a standard. So you'll see that very commonly. We can just run that. And now we have access to our NumPy module inside our Python. And then the most common thing, of course, is to go ahead and create a NumPy array. And in here, we can send it a regular list. And so we'll go ahead and send this a regular array. Let's go 1, 2, 3 to make it simple. And then I'm just going to type in A, and we'll run this. And so you can see down here, the output is an array of 1, 2, 3. And we could also do print, just a reminder that this is an inline command, so that wouldn't work if you're using a different editor. You can see that it's an array 1, 2, 3. But we'll go ahead and leave it as A. Kind of a nice feature so you can see what you're doing really quick in the Jupyter Notebook. And just like all your other standard arrays, I can go A of 0, which is going to be a value of 1. Of course, we do A of 1. You go all the way through this. A of 1 has a value of 2 in it. So whether you're using the NumPy array or the basic Python list, that's going to be the same. That should all look pretty familiar and be pretty straightforward. Remember, the first value is always 0 and when we set on there. So let's take a look why we're using NumPy, because we went over the slide a little bit, but let's just take a look and see what that actually looks like. And what we want to look at is the fact that it's fast, convenient, and uses less memory. So let's take a glance at that in code and see what that actually looks like when we're writing it in Python and what the differences are. And to do this, I'm going to go ahead and import a couple other modules. We're going to import the time module so we can time it. And we're going to import the system module so that we can take a look at how much memory it uses. And we'll go ahead and just run those so those are imported. And so we'll do b equals range of 1. Yeah, 1,000 is fine. And so that's going to create a list of 1,000, 0 to 999. Remember, it starts at 0 and it stops right at the 1,000 without actually going to the 1,000. And let's go ahead and print. And we want system.getSize of. And we'll pick any integer because we have, 0 to 1,000. We'll just throw one in there, 5. It doesn't matter because it's going to whatever integer we put in there is going to generate the same value because we're looking at the size of how much memory it stores an integer in. And then we want to have the length of the b. That's how many integers are in there. And if we go ahead and execute this and run this at a line, we'll see, oops, I did that wrong, comma. If we multiply them together, we'll see it generates 28,000. So that's the size we're looking at is 28,000. I believe that's bytes. That sounds about right. So let's go ahead and create this in NumPy, and we'll go c equals np, and this is arange. So that's the NumPy command to do the same thing that we were just doing in a list. And we'll also use the same value on there, the 1,000. And then once we've created the value of c for np.arange, let's go ahead and print. And we can do that by doing c.size times c.item size. And that's very similar to what we did before. We did get the size of, so the c size is the size of the array, and each item size, just reversed. So it's the size of an integer 5, item size is going to be the integers, and c size. And let's just take a look and see what that generates. And wow, okay, we got 4,000 versus 28,000. That's a significant difference in memory, how much memory we're using with the array. And then let's go ahead and take a look at speed. Let's do size. We tried this with lower values, and it would happen so fast that the NP array kept coming up with 0 because it just rounded it off. So size, and let's create an L1 equals range of size, and we'll do an L2. I'll just set up to the same thing. It's also range of size on there. There we go. And then we can do on A1 equals np dot arange size. And then let's do on A2 equals np dot arange. We'll keep it the same size. And what we're going to do is we're going to take these two different arrays and we're going to perform some basic functions on them. But let's go ahead, actually let's just load these up now. We'll go ahead and run this so those are all set in memory. Except for the typo here. Quickly fix that. There we go. So these are now all loaded in here. And let's do a start equals time.time. So it's just going to look at my clock time and see what time it is. And then we'll do result equals, and let's do, let's say we got an array, and we're going to say, let's do some addition here. X plus Y for X comma Y. And we'll zip it up here. Two different arrays. So here's our two different arrays. We're going to multiply each of the individual things on here. L1, L2. There we go. So that should add up each value. So L1 plus L2, each value in each array. And then we want to go ahead and print. And let's say Python list took. And then we'll do time dot time. We'll just subtract the start out of there. So time, whoops, I messed up on some of the quotation marks on there. Okay, there we go. Time minus the start. And we'll convert that to seconds. So we'll go, because that's in milliseconds, so times 1000. And let's hit the run on there. And this is kind of fun because you also get a view while we're doing this of some ways to manipulate the script. And as you can see also my bad typing. There we go. Okay, so we'll go ahead and run this. And we can see here that the Python list took 34. Actually, I have to go back and look at the conversion on there. But you can see it takes roughly 0.34 of a second. And we can go ahead and print the result in here too. Let's do that. We'll run that just so you can see what kind of data we're looking at. And we have the 02468, so it's just adding them together. It looks pretty straightforward on there. And if we scroll down to the bottom of the answer, again we see Python list took 46. A little different time on there depending on what core, because this is on an 8-core computer, so it just depends on what core it's running on, what else is pulling on the computer at the time. And let's go back up here and do our start time. Paste that into here. And this time we're going to do a result equals, and this is really cool. Notice how elegant this is. It's so straightforward. This is a lot of reason people started using NumPy is because I can add the two arrays together by simply going A1 plus A2. It makes a lot of sense both looking at it and it's just very convenient. Remember that slide we're looking at? Fast, convenient, and less memory. So look how convenient that is. Real easy to read, real easy to see. And I don't know if we don't need to print the result again, so let's just go ahead and print the time on here. And we'll borrow this from the top part because I really am a lazy typer. And this isn't the Python list, this is the NumPy list, or NumPy array. And let's go ahead and see how that comes out. And we get 2.99. So let's take a look at these two numbers, 46 versus 2.99. So we'll just round this up to 3. That's a huge difference. That's like more than 10 times faster. That's like 15 times roughly at a quick glance. I'd have to go do the math to look at it. And it's going to vary a little bit depending on what's running in the background on the computer, obviously. So we've looked at this, and if we go back here, we found out it's much faster. Yes, there's going to be different speeds depending on what you're doing with the array. Very convenient, easy to read, and it uses less memory. So that's the core of the NumPy. That's why a lot of people base so many other modules on NumPy and why it's so widely used. So we did glance at a couple operations while we were looking at speed and size. Let's dive into a little bit more into the basic operations. And these are always nice to see. I mean, certainly you want to go get a cheat sheet if you're using it for the first time. Look things up. Google is your friend. We did this for the most basic NumPy.array or np.array. And we'll go ahead and create an array. Let's do pairs, 1, 2. And then let's do 3, 4. And if we're going to do that, let's do 5, 6. There we go. And if we go ahead and take this and run this, I can go ahead and do our A down here so it's in line and it'll print that out. You can see it makes a nice array for us. So we have A, and if you look at that, we have 3 different objects, each with 2 values in them. And hopefully you're starting to think, well, how many dimensions or indexes is that? And you'll see 3 by 2. So let's go ahead and take a look, and let's go, how about A.nDimensions? Speaking of which, we'll run that, and we have 2 dimensions for each object. And then we can do the item size, so A dot. We saw this earlier, where we looked up how many items. It was up here, where we wanted to multiply item size times the actual size of the object. So the memory is being used versus the item size. And we should see 4 there. Memory is compressed down. That's always a good thing. And then the shape. The shape is so important when you're working with data science and you're moving it from one format to another. So we have our shape. We just talked about that. We have 3 by 2. 3 rows by 2 objects in each one. Generally, I don't look too much at the size, but the dimensions I'm always looking up. And this is nice, you can automate it. So you might be converting something, you might need to know how many dimensions are going into the next machine learning package so that you can automatically just have it send that information over. So we looked at A shape. Let's go ahead and create a slightly different array, np.array. Let's go ahead and just do as our original. setup here. And one of the features we can do, which is really important, is we can do dtype equals, in this case, let's do np float 64. And so what we've done is we're converting all of these into a float, and we type in A. And now instead of having 1, 2, 3, 4, 5, 6, you see they're all float values. 1.0, there's no actual 0 in there, just there's a 1 dot, or the 1 period, 2, 3 period, 4 period, 5 period, 6 period. And this, again, data science, I don't know how many times I've had to convert something from an integer to a float so that's going to work correctly in the model I'm using. So very common features to be aware of and to be able to get around and use. And we'll also do, let's just curiosity, item size. We'll go ahead and run that. And we see that it doubled in size. So it's not a huge increase. Well, doubling is always a big increase in computers. But it's not a huge increase compared to what it would be if you're running this in the Python list format. And then we did the shape earlier without having it set to the float 64. Let's go ahead and do a shape with it set to 64. And it should be the same 3, 2. So it all matches. So we've gone through, and remember, if this is all brand new to you, according to the Cambridge study at the Cambridge University, if you're learning a brand new word in a foreign language, the average person has to repeat it 163 times before it's memorized. So a lot of this, you build off of it, so hopefully you don't have to repeat it 163 times. But we did manage to repeat it at least twice here, if not a little bit more. And let's go ahead and take this. We're going to go look at one more setup on here. And let me just take this last statement here on the converting our properties of our data. And instead of float 64, let's do complex. Let's just see what that looks like. And let's go ahead and print that out and run it. And so we now have a complex data set up, and you'll see it's denoted by the 1 dot plus 0 dot j. And if we flip over here and do a basic search for NumPy data types, better to go to the original web page, but pull up a bunch of these. You can see there's a whole list of different NumPy data types. Shorthand, complex, we have complex 64, complex 128, complex number represented by two 64-bit floats, real and imaginary components. One option on there, float 16, float 32, float, shorthand for float 64, most commonly used, and of course all the different ones that you can possibly put into your NumPy array. So we covered a basic addition up there when we were comparing how fast it runs. But some very basic components, how to set up a NumPy array, how many dimensions it has, item size, data type, again we went to item size, and there's also the shape. Probably one of the more used. I use a shape all the time, very commonly used. And then down here you can see where we actually created a NumPy complex data type. So let's look at some other features in NumPy. One of them is you could do NumPy dot zeros, and we're going to do 3, 4. There we go. And we'll go ahead and run this, and you can see if I do np.zeros, I create a NumPy array of zeros. This is really important. I was building my own neural network, and I needed to create an array where I initialized the weights, and I wanted them all to be the same weight. In this case, I wanted them to start off as 0 for the particular project I was working on. And there's other options, like you can do NumPy1s, and we'll do the same thing, 3, 4, we'll run that. And you can see I've created an array of NumPy1s. In this case, it comes out as a float array. And then this is an interesting to note, because we have, let's go back to our Python and do lrange 5, and we'll print the L, so that's our list. And if I run that, it doesn't create the range until after the fact, until you actually execute it. That's an upgrade in Python. Python 2.7 actually created the array, 0, 1, 2, 3, 4. This one actually creates the script, and then once it's used, it then actually generates the array. And if we do that in NumPy arange, remember that from before, and if we do NumPy arange 5, and let's do L equals, or we can just leave it as NumPy, that's fine. There we go, just run that. You can see there we actually get an array, 0, 1, 2, 3, 4 for the value of the NumPy range 5. It generates the actual array. And for part 1, we're going to do just one more section on basic setup. And we're going to concatenation, do a concatenation example. There we go. We're going to do strings. Let's take a look at strings and what's going on with there. And let's do, print. Let's do an NP character, something new here. And we're going to add, and then here's our brackets for what we're going to add. And let's say, let's do hello, comma, hi. And in the brackets on there, let's create another one. And this one's going to be ABC, and we'll do XYZ. So we're just creating some, randomly making some up on here. And then we'll go ahead and just print this. If we run that, you can come down here, and of course make sure all your brackets are open and closed correctly. And then you can see in here, when we concatenate the example in NumPy, it takes the two different arrays that we set up in there, and it combines the hello with the ABC and the hi with XYZ. And if we can also do something like print, let's do np character dot multiply. So there's a lot of different functions in here. Again, you can look these up. It's probably good to look them all up and see what they are, but it's good to also just see them in action. And let's do hello space, comma, 3. And we'll run this one and run that without the error. And you'll see it does hello, hello, hello. So we multiplied it by 3. And we can also, and let's just take this whole thing here instead of retyping it. And we can do character center. So instead of multiply, let's do center. And over here, keep our hello going. Take the space out of there. And let's do center at 20. And fill character equals, we'll fill it with dashes. So if we run this, you can see it prints out the hello with dashes on each side. And we keep going with that. We can also, in addition to doing the fill function, we can play with capitalize, we can title, we can do lowercase, we can do uppercase, we can split, split line, strip, join. These are all the most common ones. And let's go ahead and just look at those and see what those look like, each one of them. Here we're going to do the hello world, all-time favorite of mine. I always like to say hello universe. And you can see here we did a capital H with the world, but so we want to capitalize. So capitalize is the first one in the array. So we get hello world on there. And we can also take this, and instead of capitalizing, another feature in here is title. And let's just change this to how are we doing? How are you doing? Instead of we, we'll do you. And let's run that. And you can see here, because we created it as a title, it capitalizes the first letter in each word. And in this one, we're going to do character lower. Two different examples here. We have an array. We have hello world all capitalized, and we have just hello. And you can see that one is an array and one is just a string. If we run that, you get an array with hello world lowercase and hello lowercase. And if we're going to do it that way, we can also do it the opposite way. There's also upper. And let's paste those in there. And you can see here we have character.upper, opposite there, python.data, and we'll do Python is easy. Hopefully you're starting to get the picture that most of the Python and the scripting is very simple. It's when you put the bigger picture together and starts building these puzzles, and somebody asks you, hey, I need the first letter capitalized, unless it's the title, and then you start realizing that this can get really complicated. So NumPy just makes it simple, and we like that. And so in this case, we did Python data. It's all uppercase. Python is easy, like shouting in your messenger. Python is easy. And then if you're ever processing text and tokenizing it, a lot of times the first thing you do is we just split the text, and we're just going to run this np.character.split. Are you coming to the party? If we do that, it returns an array of each of the individual words. Are you coming to the party, splitting it by the spaces? And then if you're going to split it by spaces, we also need to know how to split it by lines. And just like we have the basic split command, we also have split lines. hello, and you'll see here the scoop in for our new line. And when we run that, if you're following the split part with the words, you should see hello, how are you doing? The two different lines are now split apart. And let's just review 3 more before we wrap this up. Commonly used string variable manipulations. We have strip, and in this case we have Nina, admin, Anita, and we're going to strip A off of there. And let's see what that looks like. And then you end up with nin, demin, nate. It basically takes up all leading and trailing letters. In this case we're looking for A. More common would be a space in there, but it might also be punctuation or anything like that that you need to remove from your letters and words. And if we're going to strip and clean data, we also need to be able to reformat it or join it together. So you see here we have a character join. We'll go ahead and run this. And it has on the first one, it splits each of the letters up by the colon and the second one by the dash. And you can see how this is really useful if you're processing, in this case, a date. We have day, month, year, year, month, date. Very common things to have to always switch around and manipulate depending on what they're going into and what you're working with. And finally, let's look at one last character string. We're going to do replace. If you're doing misinformation, this is good, pulling news articles and replacing is and what. In this case, we're just doing he is a good dancer. We're going to replace is with was. And you can see here, he was a good dancer. Hopefully that's not because he had a bad fall. He just was from the 1920s and has gotten old. So there we go. We've covered a lot of the basics in NumPy as far as creating an array. Very important stuff here when you're feeding it in. How do we know the shape of it, the size of it? What happens when we convert it from a regular integer into a float value as far as how much space it takes? We saw that doubled it. Item size, you have your in dimensions, and probably the most used is shape. And we'll cover more on shape in part 2. So make sure you join us on part 2 because there's a lot of important things on shape in there and setting them up. We also saw that you can create a zeros-based array. You can create one with ones. If we do a range, you can see how it is a lot easier to use to create its own range, or a range as it is in NumPy. And you saw how easy it was to add 2 arrays. We saw that earlier, just plus sign. Then we got into doing strings and working with strings and how to concatenate. So if you have 2 different arrays of strings, you can bring them together. We also saw how you can fill, so you can add a nice headline, dash, dash, dash. We saw about capitalize the first letter. We saw about turning it into a title, so all the first letters are capitalized. Doing lowercase on all the letters, upper for all the letters, just lower and upper, nice abbreviation. We also covered how to split the character set, how to strip it. So if you want to strip all the A's out from leading A's and ending A's or spaces, you can do that very easily. Also how to join the data sets. So here's a character join option for your strings. And finally we did the character replace. Now let's go ahead and dive in there since we're going right into part 2, which is getting some coding going under our belt. And here in our Jupyter notebook, we can go under new and create a new folder, Python 3. I think I forgot to do this last time, but we could just do the Control++, which in any browser enlarges a page, makes it a lot easier to see. Always a nice feature. Another beautiful benefit of using Jupyter Notebook. And let me go ahead and show you a neat thing we can do in Jupyter. This is nice if you're working with people and you're doing this as a demo on a large screen. I'm going to do the hashtag or pound symbol array manipulation, kind of a title of what we're working on. And then I'm going to call this cell type markdown as opposed to code. And you'll see it highlights it here, and then if I run it, it just turns it into array manipulation. And then we're specifically going to be working on array manipulation, changing shape to start with. And we'll go ahead and mark this cell also a markdown, so it has a nice little look there. And then it comes up, and you can see it, just like I said, it just highlights it and makes it in bold print, just making it easier to read. Not a Python thing, but a Jupyter thing that's good to know about, especially if you're working with the shareholders, since they're investing money in you. Of course, the first thing we want to do is import. We're going to import NumPy as in P, and that should be standard by now. By now, you start a Python program, you're doing some data science. NumPy is just something you bring in there. And let's go ahead and create our array, and we're going to do that as the np.arange. Remember, that's 0, well, we're going to do 0 to 9, and then we'll go print, put a little title on the original array. We'll just print that array A. Remember from the first lesson, so we have our array which is 0, 1, 2, 3, 4, 5, 6, 7, 8. And let's add a print space in between. Let's create a second array, B, but we want this to reshape array A. And what does that mean? And the command is simply reshape, and then we have 9 items in here, and this is so important right now. So be very aware, if I did some weird numbers in here, it's not going to work. And we want multiples of 9. We know that 3 times 3 is 9. So we're going to reshape our A array by 3 by 3. And then we're going to print, well, let's give it a title. Oops, I had too many brackets in there. Modified array, and then let's go ahead and print our B. And let's see what that looks like. And as we come down here, you can see we've taken this and it's gone from 0, 1, 2, 3, 4, 5, 6, 7, 8 to an array of arrays. And we have 0, 1, 2, 3, 4, 5, 6, 7, 8. And so we split this into 3 by 3. And you can guess that if I tried to reshape this, let's just do a 5 by 3, which is 15, that's going to give me an error. So it's not going to work. You're not going to be able to reshape something unless the shape, all the data in there matches correctly. So we can take this flat 9, and they call it a flat because it's just a single array. And we can reshape it into a 3 by 3 array. And first you might think matrices, which this is used for that, definitely. I use it a lot in graphing because they'll come in that I have an array that's xy, comma xy1, y1, comma x2, y2. And so the shape of it might be 2 by the length of the number of points. And I need to separate that into x flat array and a y flat array. And you can see this can be very easy to reshape the array doing that. And we can of course go back. We can do b, do a print, and we'll do b dot flatten. Remember I said it's called a flatten array? And if we run that, you'll see it just goes back to the original one. It takes this 0, 1, 2, 3, 4, 5, 6, 7, 8 and flattens it back to a single array. And then one other feature to be aware of is if we flatten it, one of the commands we can put in there is order. Let me just go ahead and do that. Order equals F. Strangely enough, F stands for Fortran. The whole Fortran days. I remember actually studying Fortran programming language. In this case, you'll see that it uses the first, like 036 is the order. So instead of flattening it like we had before, 0, 1, 2, 3, 4, 5, 6, 7, 8, it now does 0, 3, 6, 1, 4, 7, 2, 5, 8. And if you go to the NumPy array page, you can see here that they have the flatten. I just open up the NumPy ND array flatten setup to look it up. And they have 3 different options. They have C, F, and A. And it's whether to flatten in C, which was based on how the C code works for flattening, or originally worked, which is row major. Fortran, which is column major, or preserve the column Fortran ordering from A. So whatever it was in, the default is the C version. So the default that you saw, you could put order equals C and it'd have the same effect as we saw there before. You could even do order equals A. That would also have the same effect because that's the default. So really the only other thing you really should change on here is to change it to C if you need it. And you can see right here, or F, I mean not C. The only thing you really want to change it to is to your F for the Fortran order, which then does it by column versus by row. And let's look at, here we go, reshape. So let's create a range of 12, and let's reshape it. And we'll do 4, 3 for this one. And remember this is NumPy. I forgot the NP there. np.arange. And we can type in just A for print, or you can do full print A. And of course in Jupyter Notebook you even have a little extra print at the beginning. If we run this, we'll see we create a nice array of 0, 1, 2. It's reshaped it. So we have 4 rows and 3 columns, or you could call that 3 columns and 4 rows. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this one is so important. We'll do NP transpose A. Let's go ahead and run that. And it helps if I get all the S's in there and don't leave an S out. And you'll see here we've taken our array. If you remember correctly, we had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we've swapped it. So we've gone from a 3 by 4 or a 4 by 3 to a 3 by 4. And this really helps if you're looking at like a huge number of rows and the data all comes in. Like let's say this is your features in row 1, your features in row 2, and this is X, Y, Z. Well, when you go to plot it, you send it all of X in one array, all of Y in one array, and all of Z in another array. And so it's really important that we can transpose this rather quickly. This is kind of a fun thing. I can highlight it and do brackets around it, and if you remember correctly, because we're in Jupyter, it doesn't matter where we do the print or not. It'll automatically print it for us. And you see if I hit the run button, it comes up with the same exact thing. And let's play with the reshape, and you know what, let's zoom this up a little bit here. Make that even bigger so you can really see what's going on. And let's play with the reshape just a little bit more. We'll do b equals np.arange. Let's do 8. And reshape, we'll do 2, 4. Let's go ahead and print b, and then run that. And you'll see we have now the 2 rows. This is a bit more like, so we have 4, maybe 2 rows of 4 things. So this might be all of our x components and our y components. So we can switch it back and forth real easy. Important to note here, whether we do 2, 4, or in the case of 4, 3, this has 12 elements. And so however you split it up, it's got to equal 12. So 4 times 3 equals 12. That's pretty straightforward. Same thing down here. 2 times 4 equals 8. If I change this, and let's say I do 2, 3, let's just run that in, and you'll find we get an error because you can't split 8 up into 2 rows by 3. You have to pick something that it can split up and arrange it in. So let's go ahead and run that. And just for fun, let's go reshape our B again, if I can type. Reshape our B again. And what else goes into 8? Well, we could do 2 by 2 by 2. So we can take this out to 3 different dimensions. And then if we, because this is going to come out as a variable, we can just go ahead and run it. And it'll print it. We could also do a print statement on there, just like we did before. And you'll see we have 2 different groups of 2 variables of 2 different dimensions. So 2 by 2 by 2. And let's go ahead and assign this to a variable. C equals B reshape. And let's do something a little different. Let's roll the axes. Roll axes. And we'll take our C and do 2, 1. And if we go ahead and run this, it's going to print that out. Whoops. Hit a wrong button there. Let's do that one again. And you roll the axis, and you can see that we now have, instead of 0, 1, 2, 3, 4, 5, 6, 7, we now have the 0, 2, 1, 3, 4, 6, 5, 7. So what's going on here? We're taking and we're rolling the numbers around, and let's just simplify this. We'll just do it with C, 1 and run that. And so if we roll a single axis, you got 0, 1, and then it rolled the 4, 5 up, and then we have 2, 3, 6, 7. And if we do 2, let me see what happens there. And this is one of those things you really have to play with and start feeling what it's doing. We've now taken 0, 2, 4, 6, 1, 3, 5, 7. So you can see we've now rolled by 2 digits instead of rolling the 1 setup. We now rolled 2 digits up there. And so if we go back and we do the 1, so we've rolled it up, 0, 1, 4, 5. And then we're going to take the 2 in there. And we've rolled the 0, 1, 2, 3, 4, 5, and 6, 7. So we start rolling these things around on here. There's a lot of different things you can do on this. But it's another way to manipulate the numbers on your NumPy. And finally, let's go ahead and swap axes. We'll do C. And let's just go ahead and run that. It's going to give me an error on there. That's because it requires multiple arguments. Left out the arguments. So now we can swap them. We get the 0, 2, 1, 3, 4, 6, 5, 7. So you can see everything's been swapped around. So next thing we want to go over is we want to go over NumPy arithmetic operations. How can we take these and use these? Let me just go ahead and put this cell as a markdown. There we go. We'll run that so it has a nice thing. All right, nice title on there. That's always helpful. And let's start by creating 2 arrays. We'll do A is an NP range, A range 9. And let's reshape this 3 by 3. So by now you should be seeing this reshape stuff, and this should all look pretty familiar. We have our 0, 1, 2, 3, 4, 5, 6, 7, 8 on there. And let's create a second one, B. And this time, instead of doing A range, let's do NP array. We'll just create a straight up array. And we'll do an array of 3 objects. So it's going to be 3 by 1. And if we go ahead and print B out, we run that. This is actually pretty common to have something like this, where you have a 3 by whatever it is and a 3 by 3 array. When you're doing your math, you kind of have that kind of setup on there. And what we can do is we can go np.add AB. Don't forget, we can always put a print statement on there. So if we add it, you'll see that it just comes in there and it goes, okay, we're adding 10 to everything. And we could actually do something more, make it more interesting. 11, 10, 11, 12. So let's change B's now, 10, 11, 12, and let's run that. And you can see that we have 10, and then you had 1 plus 11 is 12, 2 plus 12 is 14, 13, so 10 plus 3 is 13, 11 plus 4 is 15, and 12 plus 5 is 17, and so on. We'll put this back, since that's how the original setup was. Let's do 10 by 10 by 10, and run that, and get the original answer. And if you're going to add them together, we need to go ahead and subtract AB, and we run that. We get minus 10, minus 9, minus 8, just like you would expect. So we have our subtraction. 0 minus 10 is minus 10, and so on. And if you're going to add and subtract, you can guess what the next one is. We're going to multiply. And we'll multiply AB. And this should be pretty straightforward. You should expect this. If we multiply 10 times 0, we got 0. 10 times 10 is 10, and so on. And finally, if you're going to multiply, what's the last one we got is divide. What happens when we do divide A by B? And we run this, and we're going to get 0. And this is 0 divided by 10 is 0, 1 divided by 10 is 0.1, 2 divided by 10 is 0.2, and so on and so on. So the math is pretty straightforward. It just makes it very easy to do the whole setup. And again, if we went this, and let's say, let's change this up here. Instead of 10, we do 100. And make this 1,000. There we go. And if we run that, and then we do the add, you can see we got 10 plus 100 plus 1,000. Same thing with the subtract. Same thing with the multiply. And then you can also see the same thing here with the divide. So a lot of control there with your array and your math. Again, let's set this back to 10. Oops, it's right up here, wrong section. There we go, 10. And we'll just go ahead and run these and get back to where we were. And this brings us to our next section, which is slicing. And let's put in our, we'll just make this a cell type markdown. And then we run that. Of course, it gives us a nice looking slicing there. And slicing means we're just going to take sections of the array. So let's create an array np arange. Let's just do 20. And if you remember, if we do A, we have a 0 to 19. And then we can do A, and remember that we can always print these. This can always be put in a print, but because I'm in Jupyter, if you're doing a demo in Jupyter, it's just so great that you have all these controls on here. So we can slice 4 on, and this should look familiar because this is the same as a Python and a lot of other different scripting languages. If we do 4, it goes 0, 1, 2, 3, it's the first 4 in the thing, and it skips some and starts with this one. The first 4 are skipped, and then from there on. You can also do the opposite and go till the 4th one. If we run that, we get 0, 1, 2, 3. Quite the opposite on there. We can do a single item, so we can pick object number 5 on the list, run that, and 5 happens to be 5 because that's the order they're in. And then this one's interesting because I can do s equals slice, and let's create a slice here, and let's do 2, 9, let's leave a 2 on there. So we'll create an s slice on here. And then if we take our array and we do array of s, we're taking our slice in there, and let's go ahead and run that. And let's take a look and see what it generated here. First off, we started with 2, so we have 2 at the beginning. We're going to end at 9, which happens to be 8, so it stops before the 9. Remember when we're doing arrays in Python. And then we step 2, so 2, 4, 6, 8. We could do this as 3. Let me run that, and you can see how that changes, 2, 5, 8. And we could do this as, let's leave this at 3, and if we change this to 10, oops, let's make it 12, there we go. And we run that, we have 2, 5, 8, 11. So that's pretty straightforward. It's a very nice feature to have on here where you can slice it and take different parts of the series right out of the middle. So now that we've accessed the different pieces of our array, let's get into iteration. And this is interesting because my sister, who runs a college data science division, the first question she asks is, how do you go through data? And she's asking, do you know how to iterate through data? Do you know how to do a basic for loop? Do you know how to go through each piece of the data? And in NumPy, they have some cool controls for that. So put this in as a markdown. There we go, and run it. And it's called the ND iter. I'm not sure what the ND stands for, but ND iter for iterator. So before we do that, though, let's create an array or something we can actually iterate through. We'll call it A equals NP arange. Let's do something a little funny here, or funky. And we'll do 0, 45, 5. I'm not sure why the guys in the back picked this particular one, but it's kind of a fun one. And if I run that, we do this, you can see we get 0, 5, 10, 15, 20, 25, 30, 35, 40. That's what this array looks like. And that's just from our slice. This is just a slice. That's all that is we created a slice of 0 to 45, step 5. And so we can do with this, we can also do A equals reshape. Let's go ahead and take and reshape this. And since there's 9 variables in there, we'll do a reshape at 3 by 3. So if we run that, whoops, missed something there. That is the A. That really helps. So if we do the A reshape, and we'll go ahead and print that out, we get 0, 5, 10, 15, 20, 25, 30, 35, 40. And then we simply do 4xn, our NumPy ND iter of A, colon, and we'll just go ahead and print x. And let's see what happens here when we run through this and we print each one of those. It goes all the way through the whole array, so it's the same thing we just saw before. We got 0, 5, 10, 15, 20, 25, 30, 35, 40. So it prints out each object in the array, so you can go through and view each one of these. And certainly, if you remember, you could also flatten the array and just do for A and that also and get the same result. There's a lot of ways to do this, but this is the proper way with the ND iterator because it'll minimize the amount of resources needed to go through each of the different objects in the NumPy array. And hopefully you asked this question when I just did that. And the question is, how can I change this instead of doing each object? So first of all, let's go ahead and take my cell type, and we're going to mark that down and run it. And so we're going to work on iteration order C style and F style. Remember C because it came from the C programming, and F because it came from the old Fortran programming. So let's give us a reminder. We'll do a print A, and we'll do 4xn np iterate A. But we also want to do this in a specific order. And you know what? I'm a really lazy typer, so let's go back up here. This is the ND iterator. I knew I was missing the ND part of A. And let's do order equals C. We'll print X on there. And let's do that again. And this time order equals F. There we go. Order equals F. And let's go ahead and run this and see what happens here. And the first thing you're going to notice, our original array, 0, 5, 10, 15, 20, 25, 30, 35, 40. When we do order C, that's the default, 0, 5, 10, 15, 20, and so on. And then when you come down here, you'll see F, order F, is 0, 15, 30. So it takes the first digit of each of the subarrays, or the second dimension, and then it goes into the second one, 5, 20, 35, 10, 25, 40. So slightly different order for iterating through it if you need to do that. So we've covered reshaping, we've covered math, we've covered iteration, we've covered a number of things. The next section we want to go ahead and go over is going to be joining arrays. So we need to bring them together. Let me go ahead and take the cell and make it a markdown. Cell type markdown. There we go. And run that. So let's work on joining arrays so we can bring them together and with different options we have. And let's do, we'll do an NP array 1, 2, 3, 4. We'll go ahead and print. Let's do, oops, first. These arrays aren't that big, so let's just go ahead and keep it all on one line, A. So if we run this, first array 1, 2, 3, 4. Whoops, I forgot that it automatically wraps it when you do it this way. So we'll go ahead and keep it separate and print A. There we go. And let's go ahead and do a B. And we'll do 5, 6, 7, 8. And notice I'm keeping the same shape on these two arrays. Depending on what you're doing, those shapes have to match. And let's go ahead and print second array. Do a print B. We'll go ahead and run that. Oops. Messed something up there. Let me fix that real quick. When I was reformatting it to go on separate lines, I messed that up. There we go, run. All right, so we have first array 1, 2, 3, 4, second array 5, 6, 7, 8. And we'll put a carried return on there. And the key word we use is concatenate. And if you're familiar with Linux, it usually means you're adding it to the end on there. And we're going to do what they call along axis 0. So we have concatenate AB along axis 0. Let's go ahead and run that and see what that looks like. And so we have 1, 2, 3, 4, 5, 6, 7, 8. So now we have an array that is 4 by 2. Has a nice shape of 4 by 2 on here. And if we're going to do it along the axis 0, you should guess what the next one is. We're going to do it along the 1 axis. And let's see how those differ from each other. Let's just go ahead and run that. And again, all we're doing is adding in the axis equals 1. So we have our concatenate, we have AB, and then axis 1. Remember a couple things. One, these are the same shape. So we have a 2 by 2, same dimensions going in there. You're going to get an error if you're concatenating and they're not. If you have something that instead of 1, 2 is 1, 2, 3, 4, 5, 6 with a 5, 6, 7, 8. They'll give you an error on there. In fact, let's take a look and see what happens when we do that. Let me just take this. 1, 2, 3, 3, 4, 5. And let's run that. And if we come down here, oh, we got there. It says all the input array dimensions except for the concatenation axes M must match exactly. So it'll let you know if you mess up. That's always a good thing. Let's go ahead and take this back here, and let's go ahead and run that. And so we have our 0 axes, which is 1, 2, 3, 4, 5, 6, 7, 8. And we bring them together. And you'll see a very different setup here when we do it along the axis 1. We end up with, instead of 4 by 2, we end up with a 2 by 4. 1, 2, 5, 6, 3, 4, 7, 8. And that's just changing which axes we're going to go ahead and concatenate on. What I find is when you're talking about the concatenate or the joining arrays, you really got to play with these for a while to make sure you understand what you mean by the axes. It looks very intuitive when you're looking at it. Axis 0, 1, 2, 3, 4, 5, 6, 7, 8. Axis 1 is then splitting it a different way, 1, 2, 5, 6, 3, 4, 7, 8. When you're actually using real data, you start to really get a feel for what this means and what this does. So if we're going to do that, let's go ahead and look at splitting the array. And do that under Markdown and run it. There we go. So you have a nice little title there. And we'll go ahead and create an array of 9. Let's do NP split. We'll do A, and we're going to split it by 3. Let's just see what that looks like. So if we split it, we get an array 0, 1, 2, 3, 4, 5. We get 3 separate arrays on here. Now remember, we're looking at, let me just print A up here. So we're looking at 0, 1, 2, 3, 4, 5, 6, 7, 8, and then we can split it into 3 separate arrays. And let's take this, we're going to do this right down here. I'm just going to move the A split down here. Instead of the 3, let's do 4, 5. Put that in brackets. And so when we do it this way, we have 0, 1, 2, 3, 4, 5, 6, 7, 8. And that's kind of interesting. I wasn't sure what to expect on that, but we get, when you split an A by 4, 5, you get a totally different setup on here as far as the way it split the array. And to understand how this works, I'm going to change the 5 to a 7. And this will visually make this a little bit more clear. So we had 4 and 5, it went 0, 1, 2, 3, 4, 5, 6, 7, 8. And you see the markers 4 and 5. When we do 4 and 7, I get 0, 1, 2, 3, 4, 5, 6, 7, 8. And so what you're looking at here is the first markers, this is going to go to 4. So there's our first split at the 4, the marker of 4, and then the second split is going to be at position 7. And this is the same thing here. 4, position 5. That's why we're splitting it in those two sections. We could also do it 7, just to see what that looks like. Run. And you can see I now have 0, 1, 2, 3, 4, 5, 6, 7, 8. So we can split it in all kinds of different ways and create a different set of multiple arrays on here and split it all kinds of different ways. And before we get into the graphs and other miscellaneous stuff, let's go ahead and look at resizing the array. We'll go ahead and take this cell and set the cell as a markdown and run it. Give us a nice title there. And we'll do an array, an NP array of 1, 2, 3, and 4, 5, 6 here. And let's go ahead and just print. Let's go print a dot shape. And we'll go ahead and run that. Whoops, hit a wrong button there. Hit the comma instead of the dot. So we have a shape of 2, 3 here. And this is important to note because when we start resizing it, it's going to mess with different aspects of the shape. And so we'll go ahead and do a print. Scoop in for a blank line. There we go. Now let's do b equals np dot resize. We're going to resize A, and let's resize it with 3 by 2. And then we'll just go ahead and print B and print B period shape, not a comma. We'll run that. Oops, forgot the quotation marks around the end. We'll go ahead and run that, and let's just see what that looks like. So we have 1, 2, 3, 4, 5, 6, our original array, with a shape of 2, 3. And then we want to go ahead and resize it by 3, 2. And we end up with 1, 2, 3, 4, 5, 6, and we end up with a shape of 3, 2. That shouldn't be too much of a surprise. You know, we got 6 elements in there. We can resize it by 2, 3 was the original one, and then we're actually just reshaping it is how that kind of comes out as when you resize it like that. But what happens if we do something a little different? And let's go ahead and just take this whole thing and copy it down here so we can see what that looks like. And instead of doing 3, 2, remember last time I did the, to reshape it, I messed with the numbers and it gave me an error. Well, when you resize it, you don't have to match the numbers. They don't have to be the same dimensions. So we can, instead of going from a 2, 3 to a 3, 2, we can resize it to a 3, 3. So let's take a look and see how it handles that. And when we come down here to 3, 3, we end up with 1, 2, 3, 4, 5, 6, and it repeats 1, 2, 3. So it actually takes the data and just adds a whole other block in there based on the original data and repeating it. All right, now at this point, we've been looking at tons of numbers and moving stuff around. What we want to go ahead and do is get a little visual here, because that certainly you can picture all the different numbers on there, but let's look at histogram. Let's put this into a histogram. Let me go ahead and run that. And to do that, we're going to use the Matplotlib. So from Matplotlib, we're going to import pyplot as PLT. And that's usually the notation you see for pyplot. So if you ever see PLT in a code, it's probably pyplot in the Matplotlib. And then the guys in the back did a nice job, and gals too, guys and gals back there. Our team over at Simplilearn put together a nice array for me, 20, 87, 4, 40, 53, with a bunch of numbers. That way we had something to play with. And what we want to do is we want to do plot the histogram. Now remember, a histogram says how many times different numbers come in. And then we're going to put them in bins. And we have bins 0 to 20 to 40 to 60 to 80 to 100. You might, in here with the Matplotlib, they call them bins. You might hear the term buckets, or they put them in buckets. That's a really common term. And then we want to give it a title. So the way it works is you do your plt.hist for histogram, your plt title, and your plt show. And we're doing just a single array in here in the NumPy array of A. And let's go ahead and run this piece of code. Take it a moment to come out there. It says figure size, so it's generating the graph. And you can see we have, and let's just take a look at this. Let me go down a size. There we go. Okay, so now we can see we're taking a look at here. So between 0 and 20, we have 3 values. So we have a 20 here, we have a 4, and a 11, and a 15. 0, 1, 2, 3. It's actually 4 values, but they start at 0. So remember, we always count from 0 up. And from 20 to 40, we got 20. So it's 1, 42, 3, 4, 5, 6. And so you can see in the histogram, it shows that the most common numbers coming up is going to be between the 40 and 60 range, least common between the 80 and 100. This looks like an age demographics, is what this looks like to me. And you can see where they would have put it in the buckets of different age groups, which would be a nice way of looking at this. Histograms are so important and so powerful when you're doing demos and explaining your data. So being able to quickly put a histogram up that shows what's common and how it's trending is really important. And using that with a NumPy is really easy. And you know what, let's take the same data, and I want to show you why we do bins, or why we have buckets of data. I'm used to calling it buckets. Why we have bins. Let's do it instead of by 20, let's do it by tens and see what happens. And what happens when you do it by tens is you miss out on you can see a nice curve here on the first one, and on the second one it looks like a ladder going up and a plummet, a ladder going up and a plummet, and a ladder going down. So the first would be more indicative of an age group, and the second one would be what you would get if you divided incorrectly. You wouldn't see the natural trend of, I don't know what this would be, maybe how much food they eat. Hopefully not, because I'm in 50, so I'm right in the middle there, which means I eat a ton of food compared to everybody else. But it's some kind of demographic. Maybe it's mental, maybe it's knowledge, because we hit a certain point and then we start losing, our marbles start leaking out or something. So you start off knowing something, and then as you get older you grow more. But you can see here we lose that. You lose that continuity in the thing if you split the histogram into too many bins or too many buckets. And if you actually plotted this by the individual numbers, it would just be a bunch of dots on the graph and wouldn't mean a whole lot. And we've looked at graphs. Turns out there are a ton of useful functions in NumPy. I'm sure there's even new ones that aren't going to be in here. But let's just cover some important ones you really need to know about if you're using the NumPy framework. One of them is line space function. This is generating data. So you have a line space, we have 1, 3, 10, and when we do that, we end up with 10 numbers. So if you count them, there's 10 numbers. They're between 1 and 3, and they're evenly spaced. We get 1, 1.222. But these are all, there's a total of 10 here, and it's right between the 1 and 3 range. That can be, there's a lot of uses for that, but they're probably more obscure than a lot of the other common NumPy arrays set up. Then a real common one is to do summation. So we'll do summation where you do, in this case, we create a NumPy array of two different arrays, 1, 2, 3, or two different dimensions, 1, 2, 3, 3, 4, 5. And we're going to sum them up under axes 0, which is your columns. And if you remember correctly, columns is the 1 plus 3, 2 plus 4, 3 plus 5, so we have 3 columns. And if we change this, we'll just flip this to 1. We get 2 numbers. So we get 1, 2, 3 all added together, which equals 6, and 3 plus 4 plus 5, which equals 12. We'll set this back to 0. There we go, since we're looking at axis 0. And these probably could have been, some of these could be underneath our math section. Square root and standard deviation, 2 very important tools we use throughout the machine learning process and data science. And simply we take the NP array, we have again the 1, 2, 3, 4, 5, 6, 3, 4, 5. I don't know why I need to keep recreating it, I probably could have just kept it. But we can take the square root of A. So it goes through and it takes the square root of all the different terms in A. And we can also take the standard deviation, how much they deviate in value on there. And there's a rabble function. We can run that. And in p-array, it's x. We're going to do x equals, hey, we changed it from a to x. X equals rabble. And this sets it up as columns. So we have 1, 2, 3, 4, 5. This is all columns on here. Very similar to the flatten function. So they kind of look almost identical. But we also have the option of doing a rabble by column. And then another one is log. So you can do mathematical log on your array. In this case, we have 1, 2, 3. And we'll find the log base 10 for each of those 3 numbers. There's a couple of them. You can't just do any number here after log, but there is also log base 2. Log base 10 is pretty commonly used on here. We'll run that. There we go. Before we go, let's have a little fun. Let's do a little practice session here on some more challenging questions. So you start to think how this stuff fits together. Right now we just looked at all the basics and all the basic tools you have. So let's do some NumPy practice examples. And let's start by figuring out how do you plot, say, a sine wave in NumPy. What would that look like? And so in this project we wouldn't have to do this because I've already run these, but we'd want to go ahead and import our NumPy as NP and import our Matplotlib library pyplot as PLT. So we get our tools going here. And then we'll break it into two sections because we need our XY coordinates in here. So first off, let's create our X coordinates. And our X coordinates we're going to set to an A range. And we want this A range, since we're doing sine and cosine, it's going to be between 0 and 0.1. And then we use our NP, and we actually can look up NumPy stores pi. So you have the option of just pulling pi in there directly from NumPy. It has a few other variables that it stores in there that you can pull from there. But we have NumPy pi, and we generate a nice range here. And let's go ahead and run this. And just out of curiosity, let's see what X looks like. I always like to do that. So we have 0.1, 0.2, 0.3, 0.4. So we're going 0 to, in this case, 9.4, 3 times NumPy pi. Remember, pi is like 3 point something, something, something. So that makes sense. It should be about 9. And we're doing intervals of 0.1. So we create a nice range of data. And then we need to create our y variable. And so y is going to simply equal NP, or NumPy.sine of x. And then once we have our x and y, and if we print, let's go ahead and just print y. See how that, we'll do this. Let's do this so it looks print x, print y. So we basically have two arrays of data. So we have like our x-axis and our y-axis going on there. And this is simply a plt.plot because we're going to plot the points. And we'll do x comma y. And then we want to actually see the graph, so we'll do plot.show. And we'll go ahead and run that. And you see we get a nice sine wave. And here's our numbers 0 through 9. And here's our sine value, which oscillates between -1 and 1 like we'd expect it to. Then for the next challenge, let's create a 6x6 two-dimensional array and let 1 and 0 be placed alternatively across the diagonals. Oh, that's a little confusing. So let's think about that. We're going to create a 6x6 two-dimensional, so the shape is 6x6 two-dimensional array, and let 1 and 0 be placed alternatively across the diagonals. Now, if you remember from lesson 1, we can fill a whole NumPy array with zeros or ones or whatever. So we're going to do NP, create a NumPy zeros, and we're going to do a 6x6, and we'll go ahead and make sure it knows it's an integer, even though it's usually the default. And just real quick, let's take a look and see what that looks like. So if I run this, you can see I get 6x6 grid, so 6x6, 0, 0, 0, 0, 0. Now, if I understand this correctly, when they say 1s and 0 placed alternatively across the diagonals, they want the center diagonal, maybe that's going to stay 0 all the way down. And then the next diagonal will be 1s all the way across diagonally. And then the next one 0s, the next one 1s, the next one 0s, and so on. Hopefully you can see my mouse lit up there and highlighting it. So let's take a little piece of code here. And we'll do z1 colon colon 2 comma colon colon 2 equals 1. And wow, that's a mouthful right there. So let's go ahead and run this and see what that's doing. And so what we're doing is we're saying, hey, let's look at, in this case, row 1. There's 1. And then we're going to go every other row 2. So we're going to skip a row. So skip here, skip here, skip here. So we're going down this way. And we're going every other row going this way. It's hard to highlight columns. So you can see right here where we're not touching each row, like this row right here is not being touched. Okay, so we're going to start with row 1, and then we're going to skip a row and another one, and so we're going every 2 rows. And then in every 2 rows, we're looking at every 2 starting with the beginning. That's what this thing blank means. So we're going to start with the beginning, and we're going to look at all of them, but we're going to skip every 2. So starting with row 1, we look at all the rows, but we do it by 2 steps. So we go 1, skip 1, 1, skip 1, 1, skip 1, 1. If you left this out, it'd do every 1. This would just be 1s. In fact, let's see what this looks like. If I go like this and run it, you can see that I just get 1s. So this notation allows us to go down each row, row by row, and we're going to do every other row set up on there. And so if we're going to start with row 1, we also, Control Z, try that. There we go. We'll start with row 0. Again, we're going to go each row, step 2. So we'll start with row 0, and we'll go every other row. And this time we'll start with 1, column 1. And again, we go every other one going down. That's what that step 2 is. Skipping every other one. We're going to set that equal to 1. So let's see what that looks like. And you can see here we get our answer. We get 0, 1, 0, 0. But it has the 1s going in diagonals on every other diagonal and 0 on every other one. A little bit of a brain teaser, that one, trying to get that one to work out. So you can see how you can arrange your rows, and here's your step and your different axis on there. And then the next one is find the total number and locations of missing values in the array. The first challenge is to create some missing numbers. So let's create our array Z. We're going to do numpy.random.rand 10, 10. And before we do the second part, let me just take this second part out. And let's just see what that looks like. So let's run that. And there we go. So we have a 10 by 10 random array. It randomly is picking out numbers. And next, we want to go ahead and take our random integer size equals 5. And then we're going to do a random 10 size equals 5. So in the Z, we're going to select a number of random spaces here and set them equal to null value. And let's go ahead and run that so you can see what that looks like. And if we look at the array, we've created 1, 2, 3, 4. There should be a 5th one in here. My eyes may be failing me. So we've created a series of, because 0 to 5, 0, 1, 2, 3, 4. So we got 5, there are different null values on here. And this is kind of a neat notation to notice that we can generate random integers, size equals 5. So this generates 5 by 5 miniature grid inside of this to tell it where to put the nands at. So that's kind of a cool little thing you can do. And then we want to look up and see how many null values are in there. And this is simply just NP is nan of Z. Simple. So if it is nan, then we want to sum it up. So we're going to sum up all of the different null values on there. And let's do one more feature in here, which is really cool. Let's go ahead and print the indexes. So NP argware NP is nan of Z. So we're going to create our own another NP array. And let's run this, and we'll see here that it comes up with the 4 indexes. So we did count 4 of them up there. It tells you where they are, 1, 9, 2, 0, 4, 6, 5, 4. And then let's go ahead and run this again. Run, there we go. This time I got 5. That's what we get for random numbers. Another fun one that I always like to do, it's very similar because we have np is nanz.sum. So we're summing the number of nands. And we can get the indexes and you can reshape the indexes. But you can also just do, we'll do an INDS where np is nan of z. And let's just print that. Print INDS. Let's see what that looks like. And it's very similar. We have 013063863, but I've split it into 2 different arrays. So we have our x and our y kind of coordinates going there. And what I can now do is I can now do z INDS equals, and at this point you can also, instead of getting the sum, you can get the means or all the numbers and that kind of thing, or the average as it is. So that'd be one thing you could do, and you can pick out the average. That's very common in data science to get the average and just use that for a value. But we'll go ahead and just set it to 0, and then let's go ahead and print our z and run that. And you can see when we come down here, we have wherever there was a null value, it is now 0. And you can set this to whatever you want. This is another way to replace data or help clean data up, depending on what it is you're doing. So, wow, we covered a lot of stuff. So quick rehash going over everything. We went into there, we looked at array manipulation, changing the shape, how to switch that around. We even had the flatten down there, which remember we have another command lower that's similar. We could change the order by F. Remember F stands for Fortran, very strange connotation, but there's C and F. C is the standard, and F switches it to a different order. To be honest, I usually have to look it up because I almost never use F, but when you need it, you're like, oh my gosh, what was the other order? Just do a quick Google. So we talked about reshape, making sure that the dimensions are the same. You don't want to have like something that has 12 objects in it and reshape it to 11 and 5 because it doesn't work. It doesn't divide into 12. We can transpose, so we can switch them. So we can go from a 4x3 to a 3x4. Oops, I did that the other way around. 3x4 to 4x3. We covered reshaping the array. We did the roll the axes. You can do some weird things with swapping and rolling axes and transposing the numbers. We dug a little bit into the arithmetic. So we talked about adding, we talked about subtracting, multiplying, dividing. And at this point it's so important we just look up the NumPy mathematics. And you can see here they have just about everything. Your trigonometry, your hyperbolic functions, rounding, sums, products, differences. There is so many, all your different miscellaneous mathematical connotations. So, Google it, go to the main NumPy page and look at the different setups you can do on there. So we covered that, and we did slicing, how to break it apart. We did iterating over the array. We covered joining arrays and how to concatenate. Remember, concatenate just means add on to it. So in this case, how are you adding B onto A is how you read that. From Linux, you should catch the concatenate because that's used regularly there. Splitting the array, we talked about how to split the array in different ways. So you can split it in array of arrays, all kinds of different ways to split the array up. How to resize it. And remember, resize does not have to have the same shape, but if you resize it, it will take the data and begin at the beginning and add new rows on if the size is bigger. If it's smaller, it truncates it. It just cuts the end off. We looked at how to do a histogram and how to plot that. We mentioned buckets or bins, as they call them in PyPlot. And then we covered a lot of other useful functions in NumPy. We talked about the line space setup for doing numbers in a series. How to sum the axes up. Again, that's part of the mathematical formulas there that we looked at. There's a sum, there's also means and median. All of those you can compute in NumPy. And you can also do the square root and standard deviation. The ravel function, very similar to the flatten. To be honest, I almost always just use the flatten, but the ravel has its own kind of functionality that it does. And then we went into some NumPy practice examples. We challenged you to create a sine wave in NumPy and how to do that. We're kind of looking for that arange. Remember how we do the arange, and you can have your beginning value, your end value, which they did as 3 times pi, NumPy pi. And we're going to do intervals of 0.1. And then y just equals the NumPy sine of x. There's our math from the math page we were just looking at. Remember that? It's right at the top. And finally, we went down here. We had this kind of a little brain teaser, how to do diagonal zeros and ones, playing with the different connotations of the NumPy array. And then we did a random size, and we played a little bit with with the null values, playing with null values. If you're doing any data science, null values are like a headache. What do you do with them? Big sets of data, you get rid of them. Small sets of data, you have to factor something in there, like figure out the average or the median there, and then replace it with that. Pandas really is a core Python module you need for doing data science and data processing. There's so many other modules that come off of it. There actually sits kind of on NumPy, so if you've already had our NumPy array, hopefully you've already gone through the NumPy tutorial 1 and 2. So today we're going to cover what is Pandas. We'll discuss series. We'll discuss basic operations on series. And then we'll get into DataFrame itself, basic operations on the data frame, file-related operations on a data frame, visualization, and then some practice examples. Roll up our sleeves and get some coding underneath there. And let's start with just some real general, what is Pandas? Pandas is a tool for data processing which helps in data analysis. It provides functions and methods to efficiently manipulate large data sets. Now, this is a step down from, say, using Spark or Hadoop in big data. So we're not talking about big data here, but we are talking about Pandas, and there is some connections. There's like an interface going on with that, so there is availability, but you really should know your Pandas, because if you're working in big data, you'll know there's data frames. Well, Pandas is a data frame primarily. It has a couple different pieces we'll look at here. And if you've never worked with data frames before, a data frame is basically like an Excel spreadsheet. You have rows and columns. You can access your data either by the row or the column, and you have an index and different, that kind of setup. And we'll dig more into that as we get deeper into Pandas. But think of it as like a giant Excel spreadsheet that's optimized to run on larger data on your computer. And then I said it that it's a data frame. So the data structures in Pandas are series, one-dimensional arrays, and then we have data frame, two-dimensional array. And it really centers around the data frame. The series just happens to be part of that data frame. And here's a closer look at a Pandas series. Series is a one-dimensional array with labels. It can contain any data type, including integers, strings, floats, Python objects, and more. So it's very diverse. If you remember from NumPy we studied, they had to be all uniform. Not in Pandas. In Pandas we can do a lot more. And Pandas actually kind of sits on NumPy, so you really need to know both of those if you haven't done the NumPy tutorials. And you can see here we have our index 1, 2, 3, 4, 5, and then our data A, B, C, D, and E. Very straightforward. It's just two columns, and we have a nice index label and a column label for the data. And then a data frame is a two-dimensional data structure with labels. We can use labels to locate data. And you can see here we had, if we go back one, we had our index 1, 2, 3, 4, 5. So in each one of these series, they would share the same index over there, the row index. So you have your row index df.index, and then you have a column index df.columns. And this would look, like I said, this would be really familiar if you've done any work with spreadsheets, Excel. So it kind of resembles that. This does make it a lot easier to manipulate data and add columns, delete columns, move them around. Same thing with the rows. So you have a lot of control over all of this. Now, we're of course going to do this in our Jupyter notebook. You can use any of your Python editors, but I highly suggest if you haven't installed Jupyter and haven't worked with it, it is probably one of the best ways for easily displaying a project you're working on. I skip between a lot of different user interfaces or IDEs for editing my Python, and it's just simply jupyter.org, jupyter.org. And then I always let mine sit on Anaconda, anaconda.com. And just real quick, we'll open that up for you. Oops, offline mode. Don't show me that again. But you can see here that I have different tools that I can actually install in my Anaconda, including the Jupyter Notebook, which comes by default. And then I have access to the environments. And again, that's anaconda.com, named after the very large, one of the world's largest snakes, and then Jupyter Notebook. In this case, jupyter.org. And when we're in our, I'm going to go in here to our Jupyter Notebook, and we're going to go ahead and just do new and a Python 3. And this will open up a Python 3 untitled folder. So diving right in, let's go ahead and give this a title, Pandas Tutorial. And we'll go up to Cell, and we'll change the cell type to Markdown so it doesn't execute it as actual code. One of those wonderful tools when you have Jupyter Notebook so you can do demos with this. And let's go ahead and import Pandas. And usually people just call it PD. That has become such a standard in the industry. So we'll go ahead and run that. Now we have our Pandas has been imported into our Jupyter Notebook. And then, we can go ahead and let me do the Control Plus. Since it's Internet Explorer, I can enlarge it very easily so you have a nice pretty view. Oops, too big. There we go. And whenever you're working with a new module, it's good to check your version of the module. In Pandas, you just use the, in this case, pd.__version__. That's actually pretty common in most of our Python modules. There's different ways to look up the version, but that's one of the more common ones. And we'll go ahead and run that. We get 0.23.4. And if we go to the Pandas site, we see 0.23.4 is the latest release. And of course, a reminder that if you're going to your environment, you need to install it. So you'll need to do pip install pandas if you're using the pip installer. We'll go and close out of that. And the first thing we want to do is we're going to work with series. A lot of the stuff you do in series you can then do on the whole data set. We need to do what? Create one. We need to manipulate it, take pieces of it, so query it, delete, so you can delete different parts of it. So we want to do all those things with the series. And we'll start with the series, and then almost all the code, in fact all the code does transfer right into the actual data table. So we go from a series of a single list of one column, and then we'll take that and we'll transfer that over to the whole table. And we'll start by creating, there we go, creating a series from list. And let's just call this ARR equals, and we'll do 0, 1, 2, 3, 4. If you remember from our last one, we could easily do R equals range of 5, which would be 0 to 4. But we'll do R equals 0 to 4, and we'll call this S1, and we'll go PD, and series is capitalized. This one always throws me, is which letters do you capitalize on these modules? They're getting more and more uniform, but you got to watch that with Python. And we're just going to go ahead and do ARR. So we're just going to take this Python list and we're going to turn it into a series. And then because we're in Jupyter, we don't have to put the print statement. We can just put S1 and it'll print out this series for us. And let's go ahead and run that and take a look. And you'll see we have 2 rows of numbers. So the first one is the index. Now it automatically creates the index starting with 0 unless you tell it to do differently. So we get 0, index row 0 is 0, 1, 1, 2, 2, 3, 3, 4, 4. And because it's a series, it doesn't need a title for the column. There's only one column, so why title it? And this also lets you know that it's a data type of integer 64. So we print this out. This is our series, our basic series we've just created. And let's do a second series, PD, and we'll use the same data list. And let's go ahead and do order. We'll give it an order equals, let's do it this way. Let's go index equals order. And it helps if we actually give it an order. So we'll do order equals, and let's do 1, 2, 3, 4, 5. So instead of starting with 0, we're going to give it an order starting with 1. We're going to run that, and we'll go ahead and print it out down here, S2. And we'll see that we now have an index of 1, 2, 3, 4, 5, and that represents 0, 1, 2, 3, 4 in the series. And we're still data type integer 64. And very common as you're messing with NumPy arrays is we can import our NumPy as NP. Remember that from our NumPy tutorials. We can go ahead and create a NumPy out of random with the random numbers of 5. And let's just see what that n looks like, so we can see what our NumPy looks like. So we have some nice random float values here, 2.33, so on. And that's from our last tutorial, the NumPy tutorial 1 and 2. And instead of calling it order, let's call it index. And we're going to set our index equal to A, B, C, D, and E. I want to show you that the index doesn't have to be an integer, so it can be something very different here. And then let's go ahead and create we'll just use S2 again. And here's our NP for NumPy, series, capital S, and N is our NP for NumPy. PD for Pandas, there we go, switching my anachronisms. So we have PD.series of N, and we want to do our index equals our index we just created. And then let's go ahead and see what that looks like. S2 is to print it, and let's run that. And we can see here we have a nice series going on. A, B, C, D, and E for our indexes. So instead of it being 0, 1, 2, 3, or 4, we can make this index whatever we want. And you can see the numbers here going down that we randomly generated from the NumPy array. So we used NumPy to create our Pandas series right here. And so continuing on with creating our series, this one I use so often, we create a series from a dictionary. So we have our dictionary. In this case, we went ahead and did A of 1, B is 2, C of 3, D 4, E of 5. So each one of those is a key and then a value. And then we're going to use, let's use S3 equals PD for Pandas, series, and then we want to go ahead and just do D in here. Print out S3 here, and let's go ahead and run this. And you can see we got A is 1, B is 2, C is 3, D is 4, E is 5. And it's still of integer 64 because the actual data is 1, 2, 3, 4, 5, and it's all integer 64, type 64. And the last thing we want to do in the creating section of our series is to go ahead and modify the index, because we're going to start modifying all this data. So let's start with modifying the index of the series. And if you remember, let's do a print this time, S1. I'll go ahead and run this. And the reason I did print is because it only prints out the last variable. So if I put S1 up here and we're going to do another variable back down lower, it won't print the first one, just the last one. And we're going to go ahead and take S1, the index, and we're just going to set it equal to a new index. And obviously, the number of objects in our index has to equal the number of objects in our data. And then because it's the last variable, we can go ahead and just do an S1. And let's run that, and you can see how we went from 0 to 0, 0, 1, 2, 3, 4 as our index. We've now altered it to A, B, C, D, and E. So this would be much more readable, or might be representational of a larger database you're working with. So cool tools. We've covered creating a database based on our basic array, Python array. We've showed you how to reset the index. Then we showed you how to use a NumPy array. So you can put a NumPy array in there. It's all the same, pd.series, NumPy array, and then we can set the index on there. And the same thing with the dictionary. So it's very versatile how it pulls in data. And you can pull in data from different sources and different setups and create a new series very easily in the Pandas. And then we looked on changing your index. So now we have a new index on here. And then we want to go ahead and do some selection. Let's do some basic slicing, most common thing you'll probably do on here. And we'll just do S1. This notation should start to look really familiar. Again, this is going to put an output, so it doesn't change S1. This just selects it. So we might do A equals S1 and then print A. And you'll see that it just looks at the first three, 0, 1, 2. And we can do the same thing by not having the A in there. I'll go ahead and take that out, but it's just a reminder that it's not actually changing S1. It's just viewing S1. So simple slicing on here. And we can likewise do an append. Oops, before we do append, let's just do a quick kind of fun one. We'll do to -1. And you'll see it covers everything but the E. Of course, you can do -2 on this side. So another way to select it is to go how far from the end. And likewise, we can do a 2 here, a CDE to the end. So it starts at the second one. And another way we can do this is we can do a -2 over here. And that looks at just the last 2 in the slice. So you can see how easy it is to slice the data. And of course, there's no reason to do this, but you could select all of them if you wanted to view all of them on there. Oops, 32. There's not 32, so it's just going to show the first 3. There we go. And then we can also append. So I can take and, let's create another series and append one to it. And if you remember, we had S3. There's our S3. And we have our S1. We'll go ahead and do S1. And let's go ahead and do, let's call it S4 equals S1 append S3. So we're just going to combine those two into S4. And if we go ahead and print S4 on here, you'll now see that we have A, B, C, D, E, A, B, C, D, E, 0, 1, 2, 3, 1, 2, 3, 4, 5, because we started the data at 1. So very easy to append one series to the next. And if we're going to append one series to the next, we need to go ahead and drop or delete one. And drop is the key word for that. And let's just do E, or index E. And so if I run this, you'll see that it'll print it out, and A, B, C, D, there's no E. And remember, all these changes, if I type in S4 again, you'll see that S4 still has E in it. So this change does not affect the series unless you tell it to. So I'd have to do like S4 equals S4.drop E. And there's another way to do that, which we'll show you later on. Let me just cut this one out. There we go. All right, so we've covered all kinds of cool tools here. We have appending, we have slicing, we did all the creating stuff earlier. So you can see here on the setup how easy it is to manipulate the series. So next, what we want to get into is we want to get into operations that happen on the series. Let me go ahead and change this cell to Markdown. There we go, and run that. So series operations, what can we do with a series? And let's start by creating a couple arrays. We'll call it array 1, and we'll do 0 through 7, and array 2, 6 through 6, 7, 8, 9, 5. I don't know why we threw the 5 on the end. Let's go ahead and run those so those load up into Jupyter. And we'll do this a little backwards. We're going to do S5 equals a Pandas series of array 2. So I'm doing this in reverse. And then when we do S5, you'll see that we have 0 to 4. It automatically assigned the index 6, 7, 8, 9, 5 for our series. And let's go ahead and do the same, and we'll call this S6, and we'll set this equal to PD series for our first array. And if we do an S6 down here to print it out, we'll see something similar. I got 0 through 6, 0, 1, 2, 3, 4, 5, 7 for the data. So those are two series we just created, series 6, 5, and 6. And one of the first things we can do is we can add one series to the next. So I can do S5.add S6. And let's see what that generates. And just a quick thing, if you've never used Pandas, what do you think is going to happen with the fact that this only has 5 different values in it, and this one has 7 values? So let's see what that does. And we end up with 6, 8, 10, 12, 9, and it goes, oh, I can't add this, there's nothing there. So it gives us a null return. Very different than the NumPy that would have given you an error. This instead tells you there's no value here because we couldn't generate one. So we can easily add S5.add S6, and likewise we can do S5.sub for subtract S6, and we'll run that. And on the add, the subtract, and you guessed it, we're going to do multiply and divide next. Again, you can see there's null values where it can't subtract the two because there's no values there to subtract. We can also do S5 multiply, MUL. They're all 3 letters on these. That's one of the ways to remember how they figured out the code for this. So remember, these are all 3 letters, mul. We'll go ahead and run this, and you can see how they're multiplied together. And then we can also do the S5 div, 3 letters again, S6, and run that. And you'll see here, this goes to infinity because we have 0 in the wrong position. So it actually gives you a whole different answer here. That's important to notice. And then in the null values, because there's no data and it can't actually produce an answer off of missing data. And since we're in data science, let's do S6 median. So let's look up the median data, which is simply median. Sorry for those who are following the 3 letters, because median is not 3 letters. And you can see in S6 is 3.0. And let's do a print here. And we'll do median or average. S6. And let's print max, comma S6. And just like median, there's max value. And if we're going to have a max value, we should also have a minimum value. So let's pop in minimum. We'll go ahead and run this. And you're starting to see something that would be generated like, say, in R, where you're starting to get your different statistics. We have a median value of 3, max value of 7, and a minimum value of 0. And what it does when it hits these null values, if there is null values in there, because we could still do that, we could actually, you know what, let's go up here and do, let's pick this one where we multiplied. Let's go S7 equals, I'll go ahead and print the S7 just so I keep it nice and uniform, so I still have my S7 down there, and run it. And then I want to take the S7, because S7 now has null values and an infinity value, and let's see what happens. This is going to be interesting because I want to see what it does with infinity. And we end up with a median of 6, maximum of 27, and minimum of 0, which is correct. It drops those values. So when it gets to there and it doesn't know what to do with them, it just drops those values and then it computes it on the remaining data on there. So that's important to know when you're making these computations, you're looking at min and max and median, you're not going to know that there's null values unless you double check your data for the null values. That's a very important thing to note on there. So just a real quick review on there. We've created our PD series, and we've gone ahead and done addition, subtraction, multiplication, division. All of those are 3 letters, so sub, min, div, add. And then we looked at median, maximum, and minimum. So we're going to go ahead and jump into the next big topic, which is to create a data frame. So now we're going to go from series, and we're going to create a number of series and bundle them together to make a data frame. There we go, cell type, markdown. And we go ahead and run that. So we have a nice title on there. It's always good to have a good title. All right, so our first data frame, we'll jump in with some stuff that looks a little complicated, but we'll break it down. First, I'm going to create some dates. And you know what? Let's just go ahead and do this. I want you to see what that looks like, what I'm creating here. I've created a series of dates, PD date range, and we're going to use these for the index. Okay, so when you look at this, you'll see that it's just, basically it comes out kind of like a basic Python list or NumPy array, however you want to look at it, with our different dates going down. And we've generated 6 of them. And it's going to have whatever time it is right now on the thing for the date for the time. That's that time stamp right there. And then you'll see we have 11/19, 2008, 11/20, 11/19, and looking into the future there. So that's all this is generating a series of dates that we're going to use as our index. And this is a Pandas command, so we have a date range, which is nice. That's one of the tools hidden in there in the Pandas that you can use. And next we're going to use NumPy to go ahead and generate some random numbers. In this case we'll do the np.random.random in 6,4. You can look at this as rows and columns as we move it into the Pandas. And of course you could reshape this if you had those backwards on your data. But we want the 6 to match the rows, and we have 6 periods, so our indexes should match along with the rows on there. And then, you know, before we do the next one, let's go ahead and just print out our NumPy array so you can see what that looks like. Here we have it, 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6. 4 by 6. So it's a nice little setup on there. And since working with data frames can be very visual, let's give our columns, we have 4 columns, and we're going to give them names, A, B, C, and D. So now we have columns on there also. And then let's put this all together in a data frame, and we can actually, you know what, let's do this. Since I did it with everything else, let's go ahead and do columns. And you can see there's our columns on there. And we'll go ahead and do df1 equals pandas.dataframe. And note that the D and the F are capitalized. Series, it was just the S, and I always highlight this because you don't know how many times these things get retyped when you forget what's capitalized on there. It's a minor thing. You'll pick it up right away if you do a lot of it. And the first thing we want to do is we want to go ahead and take our NumPy array, because that's what we're going to create our data frame off of, is the NumPy array. And then we want our index equal to our dates. So there's our index in there. And then we also have columns equals columns. And then finally, let's see what that looks like. Now remember, we had all that different data that just looked like a jumble of data. We have our column names and everything else. Our NumPy array, kind of just a jumble array over there, 4 by 6. You can sort of read it. But look how nice this looks. I mean, this is, you come into a board meeting, you're working with your shareholders. This is pretty readable. This is, you know, this is our date. This is our A, B, C, D, whatever it is. Maybe each one of these dates has your leads, closures, lost leads, total dollar made, you know, whatever it is, if it's in a business. Maybe it's measurements on some scientific equipment, weather searching material, you know, where this is like high of the temperature, low of the day, humidity of the day, whatever it is. So you can see that we can really create a nice clear chart, and it looks just like a spreadsheet. You know, we have our rows, and we have our columns, and we have our data in there. Now this one I use all the time. If we're going to create, we can create it like you saw here with our NumPy array. Very easy to do that and reshape it. You can also create it with a dictionary array. So here we have some data, and let me just go down a notch so you can see all the data on there. We have an animal, in this case cat, cat, snake, dog, dog, cat, snake, cat, dog. We have the age, so we have an array of ages. We have the number of visits and the priority. Was it a high priority? Yes, no. And then we're going to take that, we're going to create some labels. We have A, B, C, D, E, F, G, H, I. And what I want you to notice on this is we have a title, animal, and then we have basically a Python list. And these lists, they don't necessarily have to be equal because we can have non-data, you know, np.nan, NumPy array, null value. But we want to go ahead and create labels that are equal to the number in the list. So A, the first cat, B, the second cat, C, the snake, D, the dog, and so on. So we'll go ahead and create our labels, which we're going to use as an index. And we'll call this df, let's do it this way. We'll call this df2 equals PD for pandas, data frame, and then we have our data, just like we did before, and then we have our index equals labels. And if we're going to go from there, let's go ahead and print it out so we can see what that looks like, df2. So let's go ahead and run that. And again, you have a nice, very clean chart to look at. We've gone from this mess of data here to what looks like a very organized spreadsheet, very visual and easy to read. Animal, age, visits, priority, and then A through J, cats, and all your different animals, so on and so on. And then when you do programming, a lot of times it's important to know what the data types are. So we can simply do df2 dtypes. And if we run that, we can see that our animal is an object because it's just a string, but it comes in as an object. Age is a float 64, integer 64, and then priority again is just an object. And exploring this one's very popular. Let's go df2 head, and if we print that out, the df2 head returns the first 5. And we can change this. You don't have to do 5. You might want to just look at the top 2. Maybe you want to look at, let's see, let's do 6. So maybe we want to look at just the top 6 in the database, in your data frame. And you can actually, this creates another data frame. So I could have a df3 equal to df2, and this now takes the df2 and just the first 6 values. So if we do df3, run, get the same answer. And if we do the head of the data, we can also do the tail. It's the same thing. df tail, you can look at the last, we'll just do the tail, which by default does 5, the last 5. And of course you can just look at the last 3 of those real quick just to see what's at the end of the data. And this is the tail. I love doing the tail of 1 because I'll have like the index or something like that, and it will just show me the last, whatever the last entry was. You know, looking at stock values, and I might want to look at just the last 5 days of the stock values. I can do that with the data frame tail. And some other key things to look up are the index. So we can do df2.index. And I want you to notice that this isn't a call function. So if I put the brackets on the end, it'll give me an error because index is not callable. It's just an object in there. So we do df2.index. There's also columns. So we can go ahead and let's print this. Remember, the first one's not going to show unless I print it, and then df2 columns. So now we can see that we have our indexes and we have our columns listed here, df2.columns, animal, age, visits, priority. It tells you what kind of object it is, or what kind of data type it is, and they're both object. And then finally df2.values. And again, there's no brackets on the end of df2.values because this is an actual object, it's not a callable function. So we'll go ahead and run that, and it just displays a nice array. A very easy way to convert this back to a NumPy array, basically. So before I go into the next section, let's just take a quick look at what we covered so far with the data frame. We came up here, we created our data frame. We did it from a NumPy array first, setting the columns and the index. The index setting it up is the same as when we set up the series, so that should look very familiar. So is the whole format, the NumPy array, the index dates, and the columns. And remember, in our NumPy array, we're looking at row, comma, column. So 6 rows, 4 columns is how that reads in the data frame. And we went ahead and also did that from a dictionary. In this case, animal was the column name with all the data underneath that column, and then age with that data, visits that data, priority that data. And then of course we added our labels in there for our index. So there's no difference in there, but it automatically pulled the column names. Important to know when you're dealing with a data frame and importing a data frame this way. And then we did looking up D-type. We looked at head and tail, looking at your data really quick. We also did index and columns and values. And note these don't have the brackets on the end. So the next thing we want to do is go ahead, since we're dealing with data science, is we want to go ahead and describe the data. So we have df2.describe to do that, and we're going to manipulate it in just a minute, but let's just see what this generates. And you can see right here we have age and visits. So looking at our data from up above, let me just go all the way up here. Animal, age, visits, priority. And it does a nice job generating your age versus visits, which has all the data. You have your count, your means, your standard deviation, your minimum value, 25% are in this group, 50%, 75%, and your maximum value. So this will look familiar as a data science setup with your describe for a quick look at your data frame data. So let's start manipulating this data frame and moving stuff around, and we'll start with transposing. And it is simply capital T for transpose. And when we run that, it flips the columns and the indexes. So now the indexes are all column names and the columns are all indexes, animal, age, visits, priority. So if we had come in here with our data shaped wrong, up above where we had a 4x6, we can quickly just swap it if we had it backwards. Not a big deal. And we can also sort our data, something that you can't deal, which is more difficult to do with a lot of other packages. In the data frame, it's really easy to do. Take our data frame df2, and we're going to sort underscore values by equals age. And so when we run this, you'll see the default is ascending. So we have 0.52, 2.53, and everything else is organized. So if you look at your indexes, they've been moved around because each index, it moves the whole row, not just the one piece of data is not being sorted. So a very quick way to sort by age our different data in the data frame. And in addition to sorting it, we can also slice the data frame. So I could do df2, and this should look familiar from earlier. We'll just do 1 to 3. So we're going to pull out, oops, it does help if I use a df instead of just d. And we're going to pull up just between 1 and 3. So we have not 0, which is A, but we have B, which is 2, or B, which is 1, and C, which is 2. So 1, 2, and then it does not include 3, which is the standard in Python. And we can even do something like this. We can combine them, which is always fun, because remember, this returns a data frame. So if I take df2 dot sort values, and we'll do by equals age. This is just kind of fun. And then I'm going to slice it. There we go. Double check my typing and run it. And now you should see FA, because FA are now 1 and 2 on there. So you can very quickly create a whole string on here which narrows it, that you can sort it, then slice it, and do all kinds of fun things with your data frame. We'll just go back to the original one. Run. There we go. And if we can slice it by row, we can also query the data frame. So we can do df2. And this is a little different because I'm going to create an array within an array. And in this case, we're going to look at, let's do age, comma, visits. So look at the different format in here. We have 1 to 3. So we've done this by slicing by an integer value. And then on here, I've done df2 age, comma, visits in an array. And when I run this, you can see that we get just these 2 columns on here. We get age and visits. So it's a quick way to select just 2 columns or select number of columns you're working with. And if you saw up there, we did the slicing. Almost identical to slice is iLocation, which uses the integer location 1, 3. There's a push in Pandas to move to this particular setup instead of doing just a regular slice. And that's because this can be confusing when we slice 1 to 3 and then we select age and visits. So there is a push to go ahead and move to an iLocation, which does the same thing. You can see here BC, it's the same as up above. There's also a copy command, so we can do df3 equals df2 copy. We're just going to create a straight copy of it. And of course, if we do df3, it'll be the same as a df2 on there. So df3 equals df2.copy. And then let's do df3.isNull. So we're looking for null values. And this will return a nice map, and you'll see that everything is false, except when you go up here under the cat or H, they had a null there. And so if we go to have a couple up here also underneath of, let's see, the dog. Okay, there's a bunch of nulls in here. There's D up here. So let's look at D down here, and you'll see false, true. There it is. There's our null value. So we can create a quick chart of null values. You can use this to do other things. We can leverage that null value to maybe take an average or something and fill those null spaces with data. And we can also modify the location. So here's our df3 location. And notice this is location, not iLocation. iLocation has I for integer. Location uses the, in this case, the variables on the left. And what we can do on here, and we'll go ahead and just set this equal to 1.5, and then let's pick a spot. Let's go back up here where we had, let's do F age, let's see, what were we looking at? Oh, here we go. Let's do F and age. And up here, F is set to age of 2.0. And we find out that that's incorrect data, so we go ahead and switch to df3 equal, and then we go ahead and print out our df3. And if we go to F and age, it is now 1.5. So we're just changing the value in the df3. And this is changing the actual data frame. Remember, a lot of our stuff we do a slice, and like it returns another data frame. This changes the actual data frame and that value in the data frame. So we've covered location, and iLocation is null. Making a copy, here's our iLocation, which is equivalent of a slice, and also selecting columns. So now we want to just take a little detour here, and let's look at DF3 means. And this is kind of nice because you can do this. You can either do this you can select a single column here, by the way. You can just add the column selection right here like we did before. So we could have age. Look up the mean, that just creates a series. If I run that, there's our age. But if I take that out, instead of selecting it, we can do the whole setup, and it has age and visits. So why doesn't it have priority or animal? Well, those are not integers, so it's really hard. They're non-numerical values. So what is the average? I guess you could do a histogram, which probably we'll look at that later on. But the only two things we can really look at is age and visits, and we have the average or the mean on the age is 3.375, and the mean on visits is 1.9. And let's do DF3 visits. We'll go ahead and still the visits again. And you remember all those different functions we looked at for a series? Well, we can do those here. We can do the sum. So if we run that, we'll see that these sum up to 19. We could also look up minimum. If you remember that from before, the minimum is 1, max. So all that functionality is here. I'll just go back to summing it up and adding it all together. So real quick, we've shown you how to take the series operations and put them into the data frame. And then we can actually, this is an interesting one, we can just do df3 sum, run, and you'll see the different summations on there. It just combines them. I like the way it just combines the strings on there for priority and animal. We've looked at is null. We've also looked at copying, along with the different slices which we talked about earlier. So let's talk about strings. Let's dive into the string setup on there. And let's go ahead and create a string series. String equals PD series. And we just put it right in there. We have A, C, D, AA, BA, CA, popped in a null value, cow and owl. I don't know why they picked cow and owl in the background. Someone must like those animals. And of course we can just do string. If we run that, you'll see, leave the R out, we'll get an error. But if we put it in there, you'll see that we have a simple series. 0A, 1C, 2D, and it automatically indexes it 0 to 8. And then we can go string dot lower. So when we're talking about our data frame, in this case, or our data series string, in this case, we use the string function str, and we're going to make it lower. And if we go ahead and put the brackets on there, and you'll see that we've gone from capital A, capital C, so on to ABC, and baka, CBA, cow, owl, they were all lowercase already. And of course, if you want to go lower, you can also do upper. We'll go ahead and run that. And you can see we now have ACD, AAA, baka. Everything's capitalized except for the null value, which is still null. Alright, so we looked at a few basic string. You can see that string functions upper and lower. We're going to jump into a very important topic. I'm even going to give it its own header on here because it's such an important topic. What do you do with missing values? Panda has some great tools for that, so we'll dive into those. We'll work with df4, and if you remember the df copy from above, we're just going to make a copy of df3. And let's just take a quick look at the data we're working with. Oops, df3, forgot the 3 on there. There we go. So here we have our cats, snakes, and dogs. Hopefully not all in the same container, because that would be just probably mean to all of them. So we made a copy. We're going to be working with df4. And the reason we made a copy is we want to go ahead and fill the data. And we just simply do fill NA, and then we're going to give it the value we want to put in there. We'll give it the value 4. So I can run in here, and you'll see now that df4 now has where the NA was, it's filled with the value of 4. Same thing down here. A lot of times we'll compute the mean first. So I might do a mean age equals df4, and then we want to go ahead and do age and dot mean, and then I'll do something like this, df4, I only want to select the age, and I want to fill that with the mean age. And I run in there, and you'll see that our df4 age now has the means in there. Just a quick way of showing you how you can combine these. Let me go back to our original one. There we go. And run that. And keeping with good practices, df5 equals df3.copy. And then we'll print our DF5, which should be the original one. And then on the DF5, we can now drop our missing data. I'm going to simply drop NA, and we're going to use how equals any. So I'm going to drop any row that has missing data in it. And you'll see we had D here with missing data and H. And then let's go ahead and see what DF5 looks like when we do that. There we go. And there it is. D is gone and so is H. So we create a new data frame off of this, missing those values. Now, if you have a lot of data, dropping values is a good way to take care of it because you don't miss some data. If you have not a whole lot of data, you're working with like the IRIS data set or something like that, or something small, you want to start trying to find a way to fill that data in so you don't lose your computational power of the data you got. So just a quick look at processing null values or missing values. You can fill them, usually with the means. Some people use medium or the mode. There's different ways you can fill it. One way is means. And we can also just drop those rows. Those are the two main things we do with missing data. Here we go. We're going to cover next. I so love data frames for this. File operations. It saved me so much time because they have so many different tools for bringing data in and saving data. So when we're looking at the data frame file operations, it's really streamlined. I don't know how many times I'll go on to different data downloads and they'll have Panda download standard on there just because it's so widely used. So let's start with the most common file is a CSV. So we have DF3 to CSV or animal. And let me just show you what the folder is going into. Right now I have some untitled and a few things in here, but nothing labeled animal. So we go ahead and run this. And this has now saved the animal to my hard drive. And you can now see the animal folder up here. And if I, let's do edit with a notepad. Oh, let's open it up with just a regular notepad. There we go. Or WordPad. If I open that up, you can see it's comma separated. Our titles, they don't have an index on the categories on the top. And the index, comma, and then all the different data is separated by commas. Standard CSV file on there. And if we're going to send it to CSV, and notice the format is .to_CSV, and it's just the name of the file we're sending it to. You can also put the complete path. By default, it's going to go whatever the active directory this program's running on. That's why those other folders are in there. So we have our DF3 to CSV, and then if we're going to put it in there, we want to also get it back out. And we'll call this one df_animal equals pd read_CSV. I always have to remember it's to_CSV and read_CSV. I always want to do like a capital in there and not the underscore. We're going in here again, it's the active directory. So if I now do print out my df animal, and let's just do the head. We only want to look at the first three lines. So if I go ahead and run this, we'll see the first three lines and they should match up here what we saved to our CSV. So very easy to save and import from our CSV files on here. And it turns out DF3 also has a to Excel. They actually have a lot of different formats, but old school Excel was real popular for so long, still is. We can go ahead and save it as animal.xlsx. We're going to call the sheet named sheet 1. And then I can also do df, we'll call it animal2, and this one's going to come from, and the same format on here. There we go. So we still have our animal XLSX, the sheet 1, that's where it's coming from. Index columns equals none. So we're going to suppress the indexing on the columns. NA values, and it'll just assign it's 0 on up on your indexes. So if it says index columns equals none, that's what it does. And then we've added null values because there's null values in here. And we want to just make sure that they're marked as NA. And we'll go ahead and just print out the animal2, there we go. And let's run that. Let's make this, let's just do the whole thing. So we'll go ahead and run that. And it probably doesn't help that I completely forgot the read. So animal2 equals pd.read Excel. There we go, Excel. So now we go ahead and run it. And what we expect is happening here. We have the same data frame on here. And if I flick back to my folder, you can now see that we have the animal. One of these is in Excel and one of these is a CSV on here. And so there's our two file types on there. And they have other formats. These are just the two most common ones used. And I don't know how many times I've had stuff from Excel I need to pull out. If you've ever played with Excel, it's a nightmare in the back end. because of the way they do the indexing. So this just makes it quick and easy to pull in an Excel spreadsheet. So we looked at two different ways to bring data in and save it to files. We've looked at all kinds of different ways of manipulating our data set and slicing it and creating it for our data frame. Let's get in there for your visualization. Always the big thing at the end, because one, it lets you check to see what you did, make sure it looks right. And then also, if you're going to show somebody else, it makes it very clear what's going on if they see something visual. So this is where a really important part of data science is. So let's go ahead and bring in our tools. We're going to do import NumPy as NP. We want to make sure we have our ampersand Matplotlib library in line. This just lets Jupyter know that we're going to print it on this page. If you're using a different IDE, you don't really necessarily need that, but this does help it displays correctly in Jupyter Notebook. And if you remember for earlier, we could create a, we're going to call it TS. We're going to create a pandas, which are cute, cuddly creatures, versus a pandem, short for pandemonium? No. So we have TS equals PD series, and we're just going to create a random setup of 50. We'll do an index. We'll set it equal to the pandas date range today. Periods equals 50, so the 50 should match. And I want you to notice something here. I did not import the Matplotlib library. Why? Because it's already in there. Pandas already has its built-in connection and interface with Matplotlib library, so you don't have to import it. And we'll go ahead and do TS equals TS dot cumulative sum. We're going to do the cumulative sum. So a little reformatting there, and we'll go ahead and plot it. And let's take a look at what that looks like. So we have a nice graph here. We have the dates on the bottom. We've set this up so we have a nice range between, in this case, -4 to, looks like about 2 maybe, or 1, -4 and 1. So what we've done here, we plotted a basic series, just a single row of data, and we've set indexes on there. But we can also do the whole data frame on there, and let's see what that looks like. So first, let's go ahead and create the data frame. We have here random numbers, so we're going to do 50 by 4, and then we'll go ahead and create columns A, B, X, and Y. Just because we can. Index is a ts.index on there, so we're going to use the same index as before, just to keep it nice and uniform. We've already generated the dates to go with it. And then we can do, just like we did with the series, we can also do with the data frame, df equals df cumulative sum. So we're going to sum the whole data frame. And then we'll do simply df plot. And let's put that in, and let's go ahead and run this. And look how easy and quick that was to generate a nice graph with all the different data on there. So we have our shared index, we have the shared columns, and then we have the different data from each one that we can easily look at and compare. So very quick way of displaying data. You can imagine if you were working in, I think I mentioned stock earlier because I've been doing some analysis of stock lately. So you'd have your date down here, and then you would have stock A, stock B, stock XY, whatever it is. And you can put them all on one chart and see how what they look like next to each other. And this isn't too far off from what some of those graphs look like, and this is just randomly generated. So stock has a lot of randomness in it, which is one of the reasons I actually play with it for doing some of my models for testing them out. Now, there are a lot of features in Pandas. So we're going to show you one more thing on here. There's some of the things, like I didn't go too deep. We looked at the top two for importing data from a CSV and from an Excel spreadsheet. Showed you how to quickly plot the data. There's more settings in there you can do. We're going to do one more thing down here, and this is kind of a fun one. Change this to a markdown and run that. So how would you remove repeated data using Pandas? And this is where you have a data set that comes in, and maybe it's feeding from one location, and instead of noting that it's repeated the date, like, let's go back to stocks. That's a good visual. We have the stocks from the 23rd. And it adds another row, and it's the same row. It's importing the 23rd again and again. So now you have that data repeated 3 times, and you need to go back and figure out how to get rid of it. How do you track that down? So let's start by creating a quick database, or data frame. Not a database. I keep saying database. It's a data frame. And we'll just make this data frame using our dictionary going in. This data frame only has one data series in it, which is fine. So if we do df to print it out, you'll see A, 1, 2, 2, 2, 2, 4, 4, 4, 5, 6, 7, and so on. And so how would you remove that? Well, there is a neat feature in data frames called shift, along with another feature that lets us select just certain information. And we'll go with the location function. Put that in brackets. Remember that from above, location. And then in the location, let me just spread this out a little bit so it's real easy to read. In fact, I'm going to go upscale on that since we're doing a little bit more complicated here. What you can see on this, on the location, is I have dfa.shift. So this is going to shift up 1 by default. You can actually change this to 2 or 3. You can even do a -1 and it shifts the other way. But it's going to shift up by 1 by default. And it's going to say if that does not equal df of a, then we want that. And if you look down here, we had 1, 2, 2, 2, 2, 2. When we run this logic on here and we do the shift, it now gets rid of all the duplicates. So we went from 1, 2, 2, 2, 2, 4, 4, 5, whatever it was. Here it is, 1, 2, 2, 2, 4, 4, 4, 5, 5, 5, 6, 6, 6, to 1, 2, 4, 5, 6, 7, 8. And you'll see on the index, it just deletes them out of there so the index stays the same. Obviously, you don't want the dates to change if you're working with an index dated setup. So it just deletes those duplicates out of there. This is just a quick way to introduce you to, 1, the fact that you can add logic gates into here. And 2, the iLocation allows you to use shift. So there's the shift function, and then the iLocation selects that based on true or false. Wow, so we've actually covered a lot today in Pandas. We've really covered into the basics of selecting your different series out of your column, out of your data frame, how to index rows, how to slice, how to plot. Hopefully you'll take this beyond that and start combining these different things, and you can create long strings and really explore your data, generate some nice graphs. If you're in Jupyter Notebook, it's a great demo to show others. And I didn't know this about Jupyter Notebook. You can do this in Jupyter Notebook, and then you can download. And I never really look too closely at all the downloads. But you can download it as an HTML and post it to your blog. So it's got a neat feature in there. But any of this is a really powerful tool. All of this is really powerful tools for doing your data science.
So as you can see, I'm using Jupyter Notebook for the Python. Okay, so here what I will do, I will go to new, and this Python 3. Okay, so here first I will rename it to Pandas for data analysis. Okay, then rename it. Okay, so already everyone know Pandas is a Python library that provides extensive means for data analysis, right? Data scientists often work with data sorted in the table formats like .csv, .tsv, or XLX. Okay, so Pandas makes it very convenient to load, process, and analyze such tabular data using SQL-like queries. Okay, so in conjunction with Matplotlib and Seaborn, Pandas provide a wide range of opportunities for the visual analysis. Okay, you can make charts and all, right? So the main data structure in Pandas are implemented with series and data frame classes. So now let me import NumPy first, okay, as np. Then I will write import Pandas as pd. Why I'm writing as np and as pd? Because I don't want to write Pandas and NumPy again and again and again. So I gave the short form, you can say. Okay, so here I will write just pd.set underscore option display dot precision. Okay, then I will write comma 2. Okay, where are it? Okay, fine. So we have imported Pandas and this NumPy library. So now what I will do, I will demonstrate the main method in action by analyzing a data set on the churn rate of telecom operator. I have one data set named telecom churn, okay, operator clients data set. So now let's first import it. Okay, so I will write here df equals to, df means data frame. You can give any name. Okay, df pd, as you can see here, pd means pandas dot read underscore csv, then telecom churn dot csv. So you can find this data set from the description box. Okay, in the description box below, right? Then I will write here df.head. What does this do, df.head? It will show you, the first 5 lines using the head method of the dataset. It will show you first 5 lines of the dataset head. And if you will use tail instead of head, you can see the last 5 rows of dataset. Okay, if I will write here df.tail, you can see the last 5 rows of the dataset. Fine. Yeah, so on our dataset we have state, account length, area code, international plan, voicemail, this. Okay, and the churn rate is false. Fine. So now what I will do, I will recall that each row correspond to one client, an instance, and the columns are the features of the instance. So now let's have a look at the data dimensionally, features, names, and the feature types. Okay, so how many columns and rows we have. Fine. So I will write here print df.shape. Okay, so now we have 3333 rows and 20 columns in our table, in our dataset. Okay, so now let's try printing on the column names using columns. Okay, so for that, what I will do, I will write here print. So these are all the functions used in Pandas. Okay, then df dot columns. Okay, so now you can see here we have 20 columns right here, 20 columns. Okay, so here state is one column, account and 3, 4, these are the all columns name, these columns name. Fine. So now let's use another function called info, which will give you some, it will give you some general information about the data frame. Okay, so here I will write print df.info. Okay, so yes, so now you can see class is pandas core frame data frame, then this much entries. Okay, 0 to this 3332. Okay, column name and the non-null values, non-null count is 0, and the data types you can see, this is object, this is int64 object, floating type. Okay, so there are 4-5 type of data sets here. Okay, bool is there, float is there, okay, int is there, and the memory usage you can see 498.1 plus KB. Okay, and then bool is 1, float 64 type is 8 columns, then int 64 8 columns, and object is 3, right? So here these bool, int 64, float 64, and object are the data types of features. Already I told you. So we can see that one feature is logical. Okay, that bool one is logical. Where is the bool? Yes, this one. Churn rate is logical. Okay, logical means true false, true false. Okay, and the 3 features are of the object type. You can see this state. These are the object, and the 16 features are numeric. Okay, float is also numeric plus variable, right? So with this same method, we can easily see if there are the missing values. So here are, none, because each columns contain 3333 observation. See, every column is same, and you can see null count is non-null. Okay, so here you can see we don't need any cleaning and that type of thing. Okay, so we can change the column type with the AS type method. There is one more method. So let's apply this method to the churn feature to convert into int64. Got it? So for that, what I will do, I will write df, then I will write churn. Please note that no spelling mistake while writing the column names. Okay, equals to df churn. Okay, C is capital, dot as type in 64. Fine. So now we have convert this bool to int 64 now. Okay. So now what I will do, I will use one more method. Okay, let me run it first. Okay, it's no issues. Now what I will do, I will write here df dot describe. Yeah. So now, so the describe method shows basic statistical characteristics of each numeric feature, int 64 and float 64. Okay. Count is there for the particular column, the mean, standard deviation, minimum value 25%, 50%. This is the max value. Okay. Okay, now you can see the churn 0 and 1 to 1. Okay. So, and the number of non-missing values, mean, standard deviation, range, median, everything is here. Using describe, you can just find it. Okay. For every column, it will give you. Okay. Count, how much count, and mean of this particular account length and the area code like this. So now, so in order to see the stat of non-numeric feature, so one has to explicitly indicate data types of interest in the include parameter. Okay, I will use the include parameter. So at first I will write df dot describe include equals to object comma bool. Okay. So now you can see the count is 333 and unique values are the 51 and the top is this and the frequency is this. Okay. So I am here seeing the stat of non-numeric features. Okay, like state, international plan and the voice plan like this. Fine. So for categorical data like type, object and the boolean type bool feature, we can use the value counts method. So now let's have a look for that also. So I will write df churn dot value counts. Okay. So this is some data, right? So now what I will do, so there are, okay, fine. So now what I will do here, I will normalize it. Churn dot value counts normalize equals to true. Okay. So we have 2850 users out of 3033 are loyal. Their churn value is 0. Okay. And to calculate fractions pass normalize is equals to 2, I have did that to the value count function. Okay. So here you can see 0 and the 1 value counts. Right. So now let's go for the sorting data. So what is sorting? So a data frame can be sorted by the values of one of the variables like columns. So for example, we can sort this table by total day charges using ascending or in descending, right? So now I will do here df. Okay, first let me write here sorting. Okay, df dot sort values by equals to total day charge ascending equals to false dot head. Dot head means I want to see the top 5 rows. Okay. So now what I did, total day charge. Okay, total day charge I have sorted in this. Ascending equals to false means I have sorted into the descending order. Okay, and the top 5 rows are this. Okay, 59 is the maximum, 59.64. Fine. So now, like, we can also sort by multiple tables, so in one go. Okay, so let me do it. df dot sort, same thing I have to write, values by equals to churn. Okay, let me write this. Yeah, churn, comma, then again total day charge, comma, ascending equals to true, comma, false. Then I want to see, okay, let me write the same dot at. Okay, first I will show you this 11111. Okay, then let me change it. See, it's sorted now. Fine. So these are the top 5 as per these two columns, churn and the total data charge column. Okay, so now we will perform some indexing and retrieving data. So a data frame can be indexed in a few different ways. Like, to get a single column, you can use data frame name. Okay, and so now let's use this to answer a question about the column alone. So let's take one question, like, what is the proportion of churned users in our data frame? Okay, proportion. Okay, df dot, we will do simply, we have to find the mean. I will write churn dot mean. That's it. Okay, so 14.5% is actually a quite bad for a company, such as a churn rate can make the company go bankrupt, right? So Boolean indexing with one column is also very convenient. So the syntax is, I will write here df, then again df churn equals to 1, then dot mean. Okay, so here what I am finding is what are the average values of numerical features for churn user. Okay, see, account length just ignore this warning. Okay, so account length is 102.66, area code is this, right? So now what I will do, I will find one more thing. So like, we will find how much time, like in average, do churn users spend on the phone during daytime. Okay, df then churn equals to 1, then total day in minutes. We have this column, right? I hope so. We have this column, total day minutes. Okay, fine. Yeah, dot mean. Okay, so how much time an average churn user spend on the phone during daytime is 206. Okay, almost 207. Okay, so now let's take one more question, like, what is the maximum length of international calls among loyal users? Okay, loyal user means where churn is 0, like who do not have the international plan. So here for that I will write df and df churn equals to 0, Here I will write and df, okay, I will, okay, international plan equals to no, because there is, see, you can see the international plan, no, yes, no, yes, no, okay, no, then total international minutes, okay, this, okay, for the confirmation let me copy it and paste, okay, no issues, dot maximum value, yeah, so 18.9, okay, so 18.9 is the maximum length of international calls among loyal user, whereas churn is 0 who do not have the international plan, okay. So indexing, data frame can be indexed by column name, I told you already, or the row name, or by the serial number, you can say, of a row. So there is one method, LOC, okay, method is used for the indexing by name, while iloc is another method for indexing by the number, okay. First I will show you df dot, here I will write indexing, df dot loc comma state, then area code, okay. So in this first case, we can say I gave the values of the rows with the index from 0 to 5, like inclusive, and the column labeled from the state to area code inclusive, okay. So this is how you can perform indexing, okay, using by name, okay. If you want indexing by the numbers, you have to use iloc instead of this loc. Iloc means location, okay, don't get confused. 5 comma 0 to 3, okay. See, you got the same almost, right? Yeah, this is 0 to 5, okay, and this is 0 to 3. 0 to 5 means 1 2 3 4 5, and 0 to 3 1 2 3, fine. Yeah, so what if we need the first or the last line of the data frame? So we can also do that. So here simply you have to write simple thing, df -1, okay, that's it. See, this is the last line, -1, last line, fine. So if you want to apply something to all the columns, so there is one more function which is apply. So how to do is df dot apply np dot max, okay, right. It gave me all the maximum values of the particular table, sorry, particular column, not table, okay. So this is how you can do this. So this apply method can also be used to apply a function to each row, I already told you. So to do this, you have to just specify the axis, or the lambda function are the very convenient in such scenarios. Like for example, let me give you one example, df, then df state, let's use the state, okay, then dot apply lambda state and state 0 equals to w, which is starting from w, okay. Then dot, I need only 5 rows, dot. Okay. So the state is starting from W. Here it is. Okay, top 5. Right. So yes. So there is one more function, map method, which is used to replace the values in a column by passing a dictionary or the form. Right. So map function. D equals to no okay, it is false, then yes is true, right? Then df international plan equals to df international plan dot map d. Okay, df dot head. Fine. Okay, there is some international plan. Okay, p is small, that is why I was saying please write it carefully. Yeah. Okay, so this is the map function. Okay, so wherever there is no or yes, okay, so I have mapped it to the true false, right? Okay, see here you can see international plan, yes no yes no yes no. I have marked yes to false and okay. Why different? Because the series is different. Okay, here I have performed different thing. The numbers, just check the number. Okay, 0 1 2 3 4, right? Df dot head. Let me write this. So now let's compare. Okay, why it's coming? Because I have already performed that thing. So we'll go to here, see no 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 yes yes. Now you can see here false 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 true true. So for no I gave false, and for the true, for the yes I gave true. Fine, this is the mapping. This is how you can do the mapping. Okay, so now let's do df equals to, same thing can be done using replace as well. There is one more function. Okay, let me give you the name, stack replace. Dot replace, then voicemail plan. Oh, sorry, my bad. Plan D. Okay. Fine now. Yes, then df dot. Okay, so what I took, voicemail plan, right? Same. See, true, true, false, false. Because here, if you will see, I have write D. D equals to this. Again, you have to write no to false and yes to true. The same I used here, D. No need to write again and again. Fine. So now let's see how to do grouping. Okay. So first, the GroupBy method divides the grouping columns by their values. Okay, first let me write this grouping. Okay. So here I will write columns to show equals to total day minutes, right? Comma total if minutes, comma total night, minutes. Okay, then df dot group by, then here I will write churn, then here I will write columns to show dot describe, percentile. Fine, where is it's empty? Fine. There is error. df.group by churn by. Can DataFrame describe got an unexpected keyword argument percentile? Okay. Fine. It will be percentiles. Yeah. So this is how you can do the group by with a churn. Okay. So what I did. So let me explain the steps. So first, the group by method divides the grouping columns by their value. Okay. Then they become a new index in the resulting data frame. Then column of interest are selected, column to show, this column to show. Okay, so if column to show is not included, all the non-group by classes will be included. Finally, one or several functions are applied to obtain the groups per selected column. So here what I did, we group the data according to their values of the churn variable and display stat of 3 columns in each group. Right, these 3 columns in each group. Same, count means standard deviation minimum 50%, max count means this. Okay, so this is how you can do grouping. Fine. So if you want to summarize the table, okay, suppose we want to see how observation in our sample are distributed in the context or 2 variable, churn and international band. So to do so, we can build the contingency table using the cross tab method. I will show you. Okay, so here I will write summary table. ed dot cross tab. Then I will write here DataFrame df churn comma df international plan. Okay, so this is the true false, the summary. Okay, we have this much true false 0 from the international plan, and for the one are this much. Okay, for one there are 346 and 137 true. Right, so this is how you can perform the summary table. Right, you can do for the more also. So now let's create the pivot table. Okay, so let's make the tables. Stack pivot tables. Okay, pivot tables. Fine. So I will add df dot pivot table. Okay, then I will write here. Sorry. Yes. So here I will write total day calls, comma, I will take 3 column total eve calls, comma, then total night calls, comma, then area code. Okay, comma, then aggregate function equals to mean. Okay, I'm using mean. Fine. So this is pivot, you got the area code and the mean of particular this thing. right? So data frame transformation. So let me explain you first this pivot table, okay, before moving forward. So so now we can see the most of the users are loyal and do not additional services, okay, international plan or the voice mail. So this will resemble pivot table to those familiar with Excel and non, of course. Okay, so here the values are the list of variables to calculate stat for, and the index, okay, a list of variables to group data by, okay, area code, okay, and the aggregate function is what stat we need to calculate for the groups. Like we can use sum, mean, minimum, maximum, okay, something else. Okay, so here I have used the mean, right? So now let's predict the telecom churn. Okay, so now let's see how the churn rate is related to the international plan feature. So we will do this using, cross tab contingency, already saw, and also through visual analysis with Seaborn. I've already told you with Matplotlib and the Seaborn, Pandas is crazy. Okay, so here I will write predicting telecom churn. Okay, so here I will write pd dot cross tab df churn, okay, C is capital, churn, comma, df international plan, comma, margin equals to true. Okay, sorry, my bad, it's margins. Yeah, okay, we got the pivot table here using cost tab. So I will import here, import Matplotlib for the charts. Matplotlib dot pyplot as plt. Then I will import Seaborn. Import. Just remember to install all these libraries. Okay, you can use pip install Seaborn and pip install NumPy, pip install Pandas before using it. Seaborn as SNS. Then for the graphic retina, I will use config inline backend dot figure format equals to retina. Okay, then here I will write SNS dot count plot, where x equals to x-axis I'm giving, okay, international plan, comma, let's set the hue equals to churn, then comma, data will be df. Okay, see, we have the counting of using international plan, and the hue is churn, okay, 0 and 1. Fine. So we can see that the international plan, the churn rate is much higher, which is an interesting observation. Perhaps the large and the poorly controlled expenses with international calls are very conflict. Okay, so now let's take a look to another important feature, which is customer service call. Let's also use to to make the summary table first. So for that I will do here pd dot cross tab df churn, comma, df customer service calls, comma, margins equals to true. Okay. Yes. So again, I have made the summary table for the customer service calls. So now what I will create SNS dot count plot x equals to customer service calls where hue is churn, then data equals to df churn. Yes. Okay, so this is how you can create the charts using Pandas and the Seaborn. Fine. So therefore predicting that the customer is not loyal, churn equals to 1 in the case of when the number of calls to the service center is greater than 3 and the international plan is added. Okay, so this is how you can do data analysis using Pandas. Okay.
If you categorize the steps to become a data analyst, these are the ones. Firstly, you need to focus on skills. Followed by that, you need to have a proper qualification. Then, test your skills by creating a personal project, an individual project. Followed by that, you must focus on building your own portfolio to describe your caliber to your recruiters. And then, target to the entry-level jobs or internships to get exposure to the real-world data problems. So these are the 5 important steps. Now let's begin with the step 1, that is skills. So skills are basically categorized into 6 steps: data cleaning, data analysis, data visualization, problem solving, soft skills, and domain knowledge. So these are the tools: Excel, MySQL, R programming language, Python programming language, some data visualization tools like Tableau, Power BI, and next comes the problem solving. So these are basically the soft skill parts. Problem solving skills, domain knowledge, the domain in which you're working, maybe a pharma domain, maybe a banking sector, maybe automobile domain, etc. And lastly, you need to be a good team player so that you can actively work along with the team and solve the problem collaboratively. Now let's move ahead and discuss each and every one of these in a bit more detail. Starting with Microsoft Excel. While advanced tools are prevalent, proficiency in Excel remains vital for data analysts. Excel versatility in data manipulation, visualization, and modeling is unmatched. It serves as a foundational tool for initial data exploration and basic analysis. Data management. Database management skill is indispensable for data analysts. As data volumes soar, efficient management and retrieval from databases is critical. Proficiency in database systems and querying languages like SQL ensures analysts can access and manipulate data seamlessly. Followed by that, we have statistical analysis. Statistical analysis allows analysts to uncover hidden trends, patterns, and correlationships within data, facilitating evidence-based decision making. It empowers analysts to identify the significance of findings, validate hypotheses, and make reliable predictions. Next, after that, we have programming languages. Proficiency in programming languages like Python is essential for data analysts. These languages enable data manipulation, advanced statistical analysis, and machine learning implementations. Next comes data storytelling, or also known as data visualizations. Data storytelling skill is paramount for data analysts. Data storytelling bridges the gap between data analysis and actionable insights, ensuring that the value of data is fully realized in a world where data-driven communication is central to business success. Data visualization skill is a cornerstone for data analysts. As data complexity grows, the ability to present insights clearly and persuasively is paramount. Next is managing your customers and problem solving. Managing all your customers' data and companies' relationships is paramount. Strong problem solving skills are important for data analysts. With complex data challenges and evolving analytical methodologies, analysts must excel in identifying issues, formulating hypotheses, and devising innovative solutions. In addition to the technical skills, data analysts in 2025 will require strong soft skills to excel in their roles. Here are the top ones. Data analysts must effectively communicate their findings to both technical and non-technical stakeholders. This includes presenting complex data in a clear and understandable manner. Next soft skill is teamwork and collaboration. Data analysts often work with multidisciplinary teams alongside data scientists, data engineers, business professionals. Collaborative skills are essential for sharing insights, brainstorming solutions, and working cohesively towards common goals. And last but not least, domain knowledge. Knowledge on domain in which you're currently working is really important. It might be a pharmaceutical domain, it can be an automobile domain, it can be banking sector, and much more. Unless you have a basic foundational domain knowledge, you cannot continue in that domain with accurate results. Now, the next step, which was about the qualification to become a data analyst. Master's courses, online courses, and boot camps provide strong, structured learning that helps you gain in-depth knowledge and specialized skills in data analysis. Master's programs offer comprehensive, academically rigorous training and often include research projects, making sure you're highly competitive in the job market. Online courses allow flexibility to learn at your own pace while covering essential topics, and boot camps offer immersive, hands-on training in a short period focusing on practical skills. All three paths enhance your credibility, keeping you updated on industry trends and make you more attractive to potential employers.
So as you can see, I'm using Jupyter Notebook for the Python. Okay, so here what I will do, I will go to new and the Python 3. Okay, so here first I will rename it to Pandas for data analysis. Okay, then rename it. Okay, so already everyone know Pandas is a Python library that provides extensive means for data analysis, right? Data scientists often work with data sorted in the table formats like .csv, .tsv, or XLX. Okay, so Pandas makes it very convenient to load, process, and analyze such tabular data using SQL-like queries. Okay, so in conjunction with Matplotlib and Seaborn, Pandas provide a wide range of opportunities for the visual analysis. Okay, you can make charts and all. Right. So the main data structure in Pandas are implemented with series and DataFrame classes. So now let me import NumPy first. Okay, as NP. Then I will write import Pandas as PD. Why I'm writing as NP and as PD? Because I don't want to write Pandas and NumPy again and again and again. So I gave the short form, you can say. Okay. So here I will write just pd dot set underscore option display dot precision. Okay, then I will write comma 2. Okay, where are it? Okay, fine. So we have imported Pandas and this NumPy library. So now what I will do, I will demonstrate the main method in action by analyzing a data set on the churn rate of telecom operator. I have one data set named telecom churn, okay, operator clients data set. So now let's first import it. Okay, so I will write here df equals to, df means data frame. You can give any name. Okay, df pd, as you can see here, pd means pandas dot read underscore csv, then telecom churn dot csv. So you can find this data set from the description box. Okay, in the description box below, right? Then I will write here df dot head. What does this do, df dot head? It will show you the first 5 lines using the head method of the data set. It will show you first 5 lines of the data set head. And if you will use tail instead of head, you can see the last 5 rows of data set. Okay, if I will write here df dot tail, you can see the last 5 rows of the data set. Fine. Yeah, so on our data set we have state, account length, area code, international plan, voicemail, this. Okay, and the churn rate is false. Fine. So now what I will do, I will recall that each row correspond to one client, an instance, and the columns are the features of the instance. So now let's have a look at the data dimensionally, features, names, and the feature types. Okay, so how many columns and rows we have? Fine. So I will write here print df dot shape. Okay. So now we have 3,333 rows and 20 columns in our table, in our data set. Okay. So now let's try printing on the column names using columns. Okay. So for that, what I will do, I will write here print. So these are all the functions used in Pandas. Okay. Then df dot columns. Okay. So now you can see here we have 20 columns right here, 20 columns. Okay. So here state is one column, account and 3, 4. These are the all columns name. These columns name. Fine. So now let's use another function called info, which will give you some, it will give you some general information about the data frame. Okay. So here I will write print df dot info. Okay. So yes. So now you can see class is pandas core frame data frame, then this much entries. Okay. 0 to this 3,332. Okay, column name and the non-null values. Non-null count is 0, and the data types you can see. This is object, this is int64, 64 object, floating type. Okay. So there are 4-5 type of data sets here. Okay, bool is there, float is there, okay, int is there, and the memory usage you can see 498.1 plus KB. Okay, and then bool is 1, float 64 type is 8 columns, then int 64 8 columns, and object is 3, right? So here these bool, int 64, float 64, and object are the data types of features. Already I told you. So we can see that one feature is logical. Okay, that bool one is logical. Where is the bool? Yes, this one. Churn rate is logical. Okay, logical means true, false, true, false. Okay, and the 3 features are of the object type. You can see this state. These are the object, and the 16 features are numeric. Okay, float is also numeric plus variable, right? So with this same method, we can easily see if there are the missing values. So here are, none, because each columns contain 3,333 observation. See, every column is same, and you can see null count is non-null. Okay, so here you can see we don't need any cleaning and that type of thing. Okay, so we can change the column type with the as type method. There is one more method. So let's apply this method to the churn feature to convert into int64. Got it? So for that, what I will do, I will write df, then I will write churn. Please note that no spelling mistake while writing the column names. Okay, equals to df churn. Okay, C is capital dot as type int64. Fine. So now we have convert this bool to int64 now. Okay, so now what I will do, I will use one more method. Okay, let me run it first. Okay, it's no issues. Now what I will do, I will write here df dot describe. Yeah. So now, the describe method shows basic statistical characteristics of each numeric feature, int64 and float 64. Okay. count is there for the particular column, the mean, standard deviation, minimum value 25%, 50%, this is the max value. Okay, now you can see the churn 0 and 1 to 1. Okay, so and the number of non-missing values, mean, standard deviation, range, median, everything is here. Using describe you can just find it. Okay, for every column it will give you, okay, count, how much count, and mean of this particular account length and the area code, like this. So now, so in order to see the stat of non-numeric feature, so one has to explicitly indicate data types of interest in the include parameter. Okay, I will use the include parameter. So at first I will write df.describe include equals to object comma bool. Okay, so now you can see the count is 333 and unique values are the 51 and the top is this and the frequency is this. Okay, so I am here seeing the stat of non-numeric features. Okay, like state, international plan, and the voice plan, like this. Fine. So for categorical data like type, object, and the Boolean type bool feature, we can use the value counts method. So now let's have a look for that also. So I will write df churn dot value counts. Okay, so this is some data, right? So now what I will do, so there are, okay, fine. So now what I will do here, I will normalize it. Churn dot value counts normalize equals to true. Okay, so we have 2850 users out of 3033 are loyal, their churn value is 0. Okay, and to calculate fractions pass normalized is equals to 2, I have did that to the value count function. Okay, so here you can see 0 and the 1 value counts, right? So now let's go for the sorting data. So what is sorting? So a data frame can be sorted by the values of one of the variables like columns. So for example, we can sort this table by total day charges using ascending or in descending, right? So now I will do here df. Okay, first let me write here sorting. Okay, df dot sort values by equals to total day charge ascending equals to false dot head. Dot head means I want to see the top 5 rows. Okay, so now what I did, total day charge. Okay, total day charge I have sorted in this. Ascending equals to false means I have sorted into the descending order. Okay, and the top 5 rows are this. Okay, 59 is the maximum, 59.64. Fine. So now, like, we can also sort by multiple tables, so in one go. Okay, so let me do it. df dot sort, same thing I have to write, values by equals to churn. Okay, this. Yeah, churn, comma, then again total day charge, comma, ascending equals to true, comma, false. Then I want to see, okay, let me write the same dot at. Okay, first I will show you this 11111. Okay, then let me change it. See, it's sorted now. Fine. So these are the top 5 as per these two columns, churn and the total data charge column. Okay, so now we will perform some indexing and retrieving data. So a data frame can be indexed in a few different ways. Like to get a single column, you can use data frame name. Okay, and so now let's use this to answer a question about the column alone. So let's take one question like, what is the proportion of churned users in our data frame? Okay, proportion. Okay, df dot, we will do simply, we have to find the mean. I will write churn dot mean. That's it. Okay, so 14.5% is actually a quite bad for a company, such as a churn rate can make the company go bankrupt, right? So Boolean indexing with one column is also very convenient. So the syntax is, I will write here df, then again df churn equals to 1, then dot mean. Okay, so here what I am finding is what are the average values of numerical features for churn user. Okay, see, account length just ignore this warning. Okay, so account length is 102.66, area code is this, right? So now what I will do, I will find one more thing. So like we will find how much time, like in average, do churn users spend on the phone during daytime. Okay, df then churn equals to 1, then total day in minutes. We have this column, right? I hope so. We have this column, total day minutes. Okay, fine. Yeah, dot mean. Okay, so how much time an average churn user spend on the phone during daytime is 206. Okay, almost 207. Okay, so now let's take one more question, like what is the maximum length of international calls among loyal users? Okay, loyal user means where churn is 0, like who do not have the international plan. So here for that I will write df and df churn equals to 0. Here I will write and df, okay, I will, okay, international plan equals to no, because there is, see, you can see the international plan, no, yes, no, yes, no. Okay, no, then total international minutes. Okay, this. Okay, for the confirmation, let me copy it and paste. Okay, no issues. Dot maximum value. Yeah, so 18.9. Okay, so 18.9 is the maximum length of international calls among loyal user, whereas churn is 0 who do not have the international plan. Okay, so indexing. Data frame can be indexed by column name, I told you already, or the row name, or by the serial number, you can say, of a row. So there is one method, LOC. Okay, method is used for the indexing by name, while iloc is another method for indexing by the number. Okay, first I will show you df dot, here I will write indexing, df dot loc comma state, then area code. Okay, so in this first case, we can say I gave the values of the rows with the index from 0 to 5, like inclusive, and the column labeled from the state to area code inclusive. Okay, so this is how you can perform indexing. Okay, using by name. Okay, if you want indexing by the numbers, you have to use iloc instead of this loc. Iloc means location. Okay, don't get confused. 5 comma 0 to 3. Okay, see, you got the same almost, right? Yeah, this is 0 to 5. Okay, and this is 0 to 3. 0 to 5 means 1 2 3 4 5, and 0 to 3 1 2 3. Fine. Yeah, so what if we need the first or the last line of the data frame? So we can also do that. So here simply you have to write simple thing, df -1. Okay, that's it. See, this is the last line, -1, last line. Fine. So if you want to apply something to all the columns, so there is one more function which is apply. So how to do is df dot apply np dot max. Okay, right, it gave me all the maximum values of the particular table, sorry, particular column, not table. Okay, so this is how you can do this. So this apply method can also be used to apply a function to each row, I already told you. So to do this, you have to just specify the axis, or the lambda function are the very convenient in such scenarios. Like for example, let me give you one example, df, then df state, let's use the state. Okay, then dot apply lambda state and state 0 equals to w, which is starting from w. Okay, then dot, I need only 5 rows, dot it. Okay, so the state is starting from w, here it is. Okay, top 5, right? So yes, so there is one more function, map method, which is used to replace the values in a column by passing a dictionary or the form, right? So map function d equals to no okay, it is false, then yes is true, right? Then df international plan equals to df international plan dot map d. Okay, df dot head. Fine. Okay, there is some international plan. Okay, p is small. That is why I was saying, please write it carefully. Yeah. Okay, so this is the map function. Okay, so wherever there is no or yes, okay, so I have mapped it to the true false, right? Okay, see here you can see international plan, yes no yes no yes no. I have marked yes to false. And okay, why different? Because the series is different. Okay, here I have performed different thing. The numbers, just check the number. Okay, 0 1 2 3 4, right? Df dot head. Let me write this. So now let's compare. Okay, why it's coming? Because I have already performed that thing. So we'll go to here. See, no 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 no, yes yes. Now you can see here false false false, true true. So for no I gave false, and for the true, for the yes I gave true. Fine, this is the mapping. This is how you can do the mapping. Okay, so now let's do df equals to, same thing can be done using replace as well. There is one more function. Okay, let me give you the name. Stack replace. Dot replace, then voicemail plan. Oh, sorry, my bad. Plan D. Okay. Fine now. Yes. Then df dot. Okay. So what I took, voicemail plan. Right? Same. See, true, true, false, false. Because here, if you will see, I have write D. D equals to this. Again, you have to write no to false and yes to true. The same I used here, D. No need to write again and again. Fine. So now let's see how to do grouping. Okay. So first, the group by method divides the grouping columns by their values. Okay. First, let me write this grouping. Okay. So here I will write columns to show equals to total day minutes, right? Comma total if minutes, comma total night minutes. Okay, then df dot group by, then here I will write Chan, then here I will write columns to show dot describe percentile. Fine, where is it's empty. Fine, where there is error, df dot group by Chan by. Can DataFrame describe got an unexpected keyword argument percentile? Okay. Fine. It will be percentiles. Yeah. So this is how you can do the group by with a churn. Okay. So what I did, so let me explain the steps. So first, the group by method divides the grouping columns by their value. Okay. Then they become a new index in the resulting data frame. Then column of interest are selected, column to show, this column to show. Okay, so if column to show is not included, all the non-group by classes will be included. Finally, one or several functions are applied to obtain the groups per selected column. So here what I did, we group the data according to their values of the churn variable and display stat of 3 columns in each group. Right, these 3 columns in each group. Same. Count means standard deviation minimum 50% max. Count means this. Okay. So this is how you can do grouping. Fine. So if you want to summarize the table, okay, suppose we want to see how observation in our sample are distributed in the context or two variable, churn and international plan. So to do so, we can build the contingency table using the cross tab method. I will show you. Okay. So here I will write summary table. ed dot cross tab. Then I will write here DataFrame df churn comma df international plan. Okay. So this is the true false, the summary. Okay, we have this much true, false, 0 from the international plan, and the 41 are this much. Okay, for one, there are 346 and 137 true. Right. So this is how you can perform the summary table. Right. You can do for the more also. So now let's create the pivot table. Okay. So let's make the tables. Stack pivot tables. Okay, pivot tables. Fine. So I will add df dot pivot table. Okay, then I will write here. Sorry. Yes. So here I will write total day calls, comma, I will take 3 column total eve calls, comma, then total night calls, comma, then area code. Okay, comma, then aggregate function equals to mean. Okay, I'm using mean. Fine. So this is pivot, you got the area code and the mean of particular this thing. Right. So data frame transformation. So let me explain you first this pivot table. Okay, before moving forward. So so now we can see the most of the users are loyal and do not additional services. Okay, international plan or the voicemail. So this will resemble pivot table to those familiar with Excel and non, of course. Okay, so here the values are the list of variables to calculate stat for, and the index. Okay, a list of variables to group data by. Okay, area code. Okay, and the aggregate function is what stat we need to calculate for the groups. Like we can use sum, mean, minimum, maximum, okay, something else. Okay, so here I have used the mean, right? So now let's predict the telecom churn. Okay, so now let's see how the churn rate is related to the international plan feature. So we will do this using cross tab contingency, already saw, and also through visual analysis with Seaborn. I've already told you with Matplotlib and the Seaborn, Pandas is crazy. Okay, so here I will write predicting telecom churn. Okay, so here I will write pd dot cross tab df churn. Okay, C is capital, churn, comma df international plan, comma margin equals to true. Okay, sorry, my bad, it's margins. Yeah, okay, we got the pivot table here using cost tab. So I will import here, import Matplotlib for the charts. Matplotlib dot pyplot as plt. Then I will import Seaborn. Just remember to install all these libraries. Okay, you can use pip install Seaborn and pip install NumPy, pip install Pandas before using it. Seaborn as SNS. Then for the graphic retina, I will use config inline backend dot figure format equals to retina. Okay, then here I will write SNS dot count plot, where x equals to x-axis I'm giving. Okay, international plan, comma, let's set the hue equals to churn, then comma data will be df. Okay, see, we have the counting of using international plan, and the hue is churn. Okay, 0 and 1. Fine. So we can see that the international plan, the churn rate is much higher, which is an interesting observation. Perhaps the large and the poorly controlled expenses with international calls are very conflict. Okay, so now let's take a look to another important feature, which is customer service call. Let's also use to to make the summary table first. So for that I will do here pd dot cross tab df churn, comma df customer service calls, comma margins equals to true. Okay, yes. So again I have made the summary table for the customer service calls. So now what I will create SNS dot count plot x equals to customer service calls, where hue is churn, then data equals to df churn. Yes. Okay, so this is how you can create the charts using Pandas and the Seaborn. Fine. So therefore predicting that the customer is not loyal, churn equals 1 in the case of when the number of calls to the service center is greater than 3 and the international plan is added. Okay, so this is how you can do data analysis using Pandas.
What are statistics in data science? Now, statistics is the science of collecting, analyzing, and interpreting data. By applying statistical methods, we can uncover patterns in the data and make informed decisions. Now, as we continue, you notice how these essential concepts will form the backbone of many data science practices. Let's explore the key functions of statistics in data science. First, statistics help summarize data using measures like mean, median, and variance. Next, it models uncertainty with probability and distributions, so we can better understand risk and variability in our data. It also tests hypotheses, such as when we use A/B testing to compare different outcomes. Statistics finds relationship through methods like regression and correlation, revealing how variables impact each other. And finally, all these tools enable data-driven decision-making, turning raw numbers into actionable insights. Now let's talk about why does statistics matter in data science. Statistics form the backbone of data science, providing the mathematical framework needed to make sense of data and draw reliable conclusions. Without statistics, it would be impossible to turn raw data into meaningful insights or make confident, evidence-based decisions. Now, let's have a look at the main branches of statistics: descriptive statistics and inferential statistics. So first, let's talk about the definition. Then we have got methods and measures. Now in the case of descriptive statistics, now let's have a look at the main branches of statistics. So basically there are two core branches: descriptive statistics and inferential statistics. Descriptive statistics summarizes and describes data using measures like mean, median, mode, range, and standard deviation. Its purpose is to organize and present data, typically with charts, graph, or summary tables. The scope of descriptive statistics is limited to the sample data itself. Now, on the other hand, inferential statistics makes inferences about populations based on samples. It uses methods like hypothesis testing, confidence intervals, and regression. The purpose here is to draw conclusions and make predictions with common examples including A/B testing and survey analysis. The scope of inferential statistics extends beyond the sample to the larger population. Understanding both these branches is essential for analyzing and interpreting data in any data science project. Now, let's take a closer look at the descriptive statistics, starting with measures of central tendency. The first measure here is mean, which is the average of all the values, simply calculated as the sum of all the data points divided by the total count. Next is the median, which represents the middle value when the data is sorted from lowest to highest. This is especially useful when dealing with skewed distributions. And finally, the mode is the most frequently occurring value in the data set, helping us identify common patterns or repeated outcomes. Let's continue our deep dive into descriptive statistics by looking at the measures of variability. First, we've got the range. This is simply the difference between the maximum and minimum value in a data set, showing us the spread of our data, which measures the average of the square differences from the mean. This tells us how much the values in our data set differ from the average. Closely related is the standard deviation, which is the square root of the variance. It gives us a more intuitive sense of how much the values typically deviate from the mean. And finally, we've got the interquartile range, or we say IQR. This shows us the range of the middle 50% of our data, helping us understand how data is distributed across the center and avoid the effect of outliers. Understanding these four measures allows us to summarize not just the center of our data, but how spread out and varied our data set is. Now, let's look at some practical applications of descriptive statistics. One major use is the data exploration and summarization, where we quickly get an overview and basic understanding of complex data sets, helping track performance and detect problems early in fields like manufacturing or operations. And finally, they are central to business reporting and dashboards, where concise summaries are essential for managers to review trends and make data-driven decisions. So in short, descriptive statistics help transform raw data into clear, actionable information across many business, scientific, and operational contexts. Let's explore the first type of data in statistics, qualitative or categorical data. This type of data includes descriptive information that cannot be measured numerically, such as categories or labels, and yes or no responses. These are all about qualities or characteristics rather than quantities. Qualitative data can be further divided into two types: nominal, where the categories have no specific order, and ordinal, where the categories do have an order or ranking. Recognizing and classifying qualitative data is very important, as it affects how information is analyzed and interpreted in statistics. Now let's discuss the second main type of data in statistics, which is quantitative or numerical data. This type of data includes information that can be measured and expressed with numbers, making it ideal for mathematical analysis. Quantitative data is further divided into two main categories. First, there is discrete data. These are countable values with specific fixed points, such as the number of students, cars sold, or website clicks. Second, there is continuous data, which includes infinite possible values within a given range. Examples of continuous data include height, weight, temperature, or time. Understanding the distinction between discrete and continuous data is very important, as it determines which statistical methods and visualizations will be most appropriate. Now let's dive into the fundamentals of probability. Probability measures the likelihood of an event occurring, and it's always expressed as a value between 0 and 1. Here are some key concepts. If the probability or P equals to 0, that means the event will never occur. If P is equals to 1, the event will always occur. And if P is equals to 0.5, the event has an equal chance of occurring or not occurring. It's truly a 50-50% scenario. Now, understanding these basic principles help us quantify uncertainty and make informed predictions about future outcomes. Now, let's look at the different types of probability. First, there's classical probability. This is based on equally likely outcomes, such as flipping a fair coin or rolling a balanced die. Next, empirical probability, which relies on observed frequency. It's calculated from actual data, such as the proportion of rainy days over the past month. Let's say, for example, the probability of it's raining today given that it's cloudy. Understanding these three types help us choose the right approach for different situations, whether we are predicting outcomes, analyzing data, or making decisions under uncertainty. Now, probability has a wide range of powerful applications in data science. First of all, it is used in predictive modeling and machine learning, where algorithms estimate future outcomes based on existing data. Probability also plays a key role in risk management and decision making, helping businesses and researchers evaluate the likelihood of different scenarios and plan accordingly. Conditional probability, calculating the chance of one event given that the another has occurred. This is crucial in fields like healthcare, fraud detection, and marketing analytics. And finally, probability is foundational in A/B testing and experimental design, allowing us to measure the effectiveness of new strategies or products. These applications show how probability enables smarter, evidence-driven progress in modern data science. Let's look at one of the most common probability distributions, the normal distribution. This distribution is famous for its bell-shaped symmetric curve, which shows that most values cluster around the mean, with fewer and fewer values appearing as you move away from the center. Now, many natural phenomena like heights, test scores, and measurement errors tend to follow this pattern, making the normal distribution a key concept in statistics. It's characterized by two main parameters, the mean, which determines the center of the curve, and the standard deviation, which controls its spread. Recognizing the distribution helps analysts make predictions, calculate probabilities, and apply statistical techniques to real-world data. Next, let's explore the binomial distribution, which is another common probability distribution. The binomial distribution is discrete and is used for situations with binary outcomes like success or failure. It is based on a fixed number of trials where each trial has a constant probability of success, such as flipping a coin a certain number of times or tracking pass-fail rates. Examples of binomial experiment includes coin flips and measuring how many students pass or fail a test. This distribution helps us model and analyze outcomes when only two possibilities exist in each trial. Now, let's focus on the Poisson distribution, another key type of probability distribution. The Poisson distribution is a discrete distribution specifically used to model rare events. It's particularly helpful for modeling events that occur independently over a fixed interval of time or space. For example, it predicts how many times an event, like a customer arriving on a website receiving a visit, might happen in a certain period. Typical examples include customer arrivals at a store, defect rates in manufacturing, or counts of website visits over a set period. This distribution is a great tool for understanding and predicting random independent events that don't happen very often but are important to track. It's a branch that allows us to make inferences, predictions, or generalizations about a larger population using sample data. Here are some key concepts. First is the population versus sample. The population represents the entire group we want to know about, while the sample is the subset we actually collect data from. Next concept is sampling distribution, which refers to the distribution of a statistic across multiple samples from the same population. Standard error measures how much the sample statistic is expected to vary due to random sampling. And finally, margin of error tells us how much we can expect our estimates to differ from the true population value. Together, these concepts form the foundation for drawing reliable insights from sample data in inferential statistics. Let's review some of the main techniques used in inferential statistics. First, we've got hypothesis testing. This method allows us to test claims or ideas about population parameters based on sample data, helping us determine if observed results are statistically significant and reliability of our estimate. Next are confidence intervals. These provide a range of likely values for a population parameter, giving us a sense of possible variation, reliability of our estimate. And lastly, regression analysis is used to model and analyze the relationships between variables, allowing us to make predictions, uncover trends, and understand how changes in one factor might affect another. Now, let's walk through the hypothesis testing process. The first step is to formulate hypothesis. Start with null hypothesis, represented as H0, which states that there is no effect or difference. Then, there's the alternative hypothesis, represented as H1, which suggests that an effect or difference does exist. Now, after setting up the hypothesis, the next step is to choose a significance level noted by alpha. Common choices for significance levels include 0.05, 5%, 0.01, 1%, 0.010, which is 10%. The significance level is important because it controls the likelihood of making a type 1 error, also known as false positive, and now each step in the process is critical for ensuring that statistical results are both meaningful and reliable. The next step is to collect and analyze sample data. Ensure the data is represented by choosing a good sample. Then calculate the appropriate and test statistic for your hypothesis test. Once that's done, it's time to make a decision. Compare the p-value to the chosen significance level alpha. Now, if the p-value is less than or equals to alpha, you reject the null hypothesis. If the p-value is greater than alpha, you fail to reject the null hypothesis. And finally, interpret your results. Draw your conclusions with respect to the context and problem at hand, always keeping the bigger picture in mind. Following these steps helps ensure your hypothesis test is robust, clear, and meaningful. Let's review the common types of hypothesis test used in statistics. The one sample test compares the mean of a sample to a known value, and the one sample Z test is used when the population standard deviation is known. Next, we have two sample test. The independent samples t-test compares to the means of two different groups, while paired samples t-test compares before and after measurements for the same subject. For categorical data test, the chi-square test checks for the independence or goodness of fit. And Fisher's exact test is useful for small sample sizes. And lastly, non-parametric tests such as the Mann-Whitney U-test and Wilcoxon-signed rank test serve as alternatives to the t-test when data doesn't meet certain parametric assumptions. Choosing the right hypothesis test depends on your data type and the specific question you want to answer. Let's explore the central limit theorem, or CLT, a foundation for inferential statistics. The central limit theorem states that as the sample size increases, the distribution of sample means approaches a normal distribution, even if the original data isn't normally distributed. This sample works for any population distribution, making it incredibly powerful. Now, for good results, the sample size should typically be 30 or more. What's interesting is the sample mean distribution, which will have the same mean as the population. The standard error, which measures variability by the sample mean, equals sigma divided by the square root of n, and this gets smaller as the sample size grows. And finally, the formula shown here, which is z is equals to x minus nu divided by sigma over the square root of n. Let's standardize and compare sample means. The CLT makes most parametric statistics possible and is the backbone for many statistical tests. Let's review the main types of regression analysis which are used to model and understand relationships between variables. First up is linear regression. This technique analyzes the relationship between a continuous variable and another variable, resulting in a straight line. It's commonly used in predicting sales or prices. Next is logistic regression. Unlike linear regression, this method is used for binary outcomes, helping estimate probabilities such as whether an email is spam or a patient has a disease. Moving to multiple regression, this allows us to account for the effect of several variables at once, modeling more complex relationships like determining house prices. Lastly, polynomial regression, which is used for non-linear relationships. The resulting curve, rather than a straight line, lets us capture growth trends and other patterns that aren't linear. Understanding these types of regression help analysts choose the right model for the data and business's problem at hand. Let's clarify the important differences between correlation and causation. Correlation is statistical measure of how two variables move together. Correlation values range from -10 to +1. But remember, correlation does not imply causation. On the other hand, causation means that one variable actually causes changes in another. Establishing causation requires controlled experimentation and is much stronger relationship than simple correlation. Always be careful when interpreting results. Just because two variables move together doesn't mean one caused the other. Let's look at some common problems with interpreting correlation and causation. First is the third variable problem, which happens when a hidden variable affects both variables in a question, leading to a misleading connection. There's also this directionality problem, where it's unclear which variable is causing others to change. But both are actually caused by a third variable, which is the hot weather. This demonstrates that correlation does not mean one variable causes the other, so always look for hidden factors before assuming causation. Let's talk about statistical errors, specifically type 1 and type 2 errors. Type 1 error, also called as false positive, occurs when we reject the true null hypothesis. In other words, we wrongly conclude there's an effect when there actually isn't. The probability of making this error is equal to the significance level alpha. For example, concluding a drug works when it actually doesn't. On the other hand, type 2 error is false negative, means failing to reject a false null hypothesis. That's when we miss a real effect or difference. The probability of type 2 error is beta. For example, missing the real effect of a drug and saying it doesn't work when it actually does. Understanding these errors is key for designing good experiments and interpreting statistical results properly. Let's look at 3 common sampling methods used in statistics. The first one is random sampling. Here, every individual in the population has an equal chance of being selected. Where every nth individual is chosen, random sampling is crucial for ensuring representative sample. Next is stratified sampling. The population is divided onto homogeneous subgroups or strata, and then a random sample is drawn from each group. This approach makes sure all the groups are represented in the sample. And finally, cluster sampling divides the population into clusters, often based on geography. Entire clusters are then randomly selected. It's cost effective and useful for large, spread out populations. Choosing the right method ensures the data truly represents the whole population and strengthens the study's conclusions. So guys, let's wrap up with some real-world applications of statistics. In business analytics, statistics are used for A/B testing to optimize websites, customer segmentation, and targeting, sales forecasting and demand planning, and quality control, and also process improvement. These techniques help businesses make smarter, data-driven decisions every day. Statistics play a vital role in healthcare and medicine as well. They are key for analyzing clinical trial results, conducting epidemiological studies, evaluating treatment, effectiveness, and identifying risk factors. By using these approaches, healthcare researchers and practitioners can improve patient outcomes in public health. From businesses to medicine, statistics transform raw information into actionable insights that create real impact. Statistics has a huge impact in technology, data science, and finance, and power recommender systems that personalize what users see. In finance, statistics help with risk assessment and management, optimizing investment portfolios, determining credit scores, and supporting market research and analysis. Now, these applications show how statistical techniques help make smarter decisions and solve complex challenges across high-impact industries. And that's a wrap-up on our journey to the world of statistics for data science.
So what is normal distribution? Normal distribution is a continuous probability density that has a probability density function which gives us a symmetrical bell curve. Now, data can be distributed or spread out in different ways, but there are many cases where the data tends to be around a central value with no bias to the left or right, which means that it doesn't show any particular spikes towards the left or the right, and it gets close to a normal distribution. Half of the data will fall on the left of the mean and the other half will fall on the right. Now let's take a look at a graph which shows the height distribution in a class. As you can see, the average height is in the middle and the data to the left of the average height represents the short people and the data to the right of it represents the taller people. The y-axis shows us the likelihood of any of these heights occurring. The average height has the most distribution, or it has the most number of cases in the class, and as the height decreases or increases, the number of people who have that height also decreases. This kind of a distribution is called a normal distribution, where the average or the mean is always the highest point and any other point after that or before that is significantly lower. The resulting data gives us a bell curve, and as you can see, there is no abrupt bias or spike in the data anywhere except for the average height. So this kind of a curve is called a bell curve, and it's usually seen in a normal distribution. The reason we call this a normal distribution is because the data is normally distributed, with the average being the highest and all the other data points having a lower likelihood. Now we came across two terms which are associated with normal distribution: continuous probability density and probability density function. What is continuous probability density? Continuous probability density is a probability distribution where the random variable x can take any given value. Because there are infinite values that x could assume, the probability of x taking on any specific value is 0. For example, let's say you have a continuous probability density for men's height. What is the probability that a man will have the exact height of 70 inches? It is impossible to find this out, because the probability of one man measuring exactly 70 inches is very low. It is more probable that he will measure around 70.1 inches or maybe 69.97 inches. And it doesn't stop there. The fact is that it's impossible to exactly measure any variable that's on a continuous scale, and because of this, it's impossible to figure out the probability of one exact measurement which is occurring in a continuous probability density. Next, we have the probability density function. It's nothing but a function or an expression which is used to define the range of values that a continuous random variable can take. An example of this would be to gauge the risk and reward of a stock. A probability density function is a statistical measure which is used to gauge the likelihood of a discrete value. A discrete variable can be measured exactly, while a continuous variable can have infinite values. However, for both continuous as well as discrete variables, we can define a function which gives us the range of values within which these variables will fall, and that function is known as the probability density function. Now let's take a look at standard deviation. What is standard deviation? Standard deviation is used to measure how the values in your data differ from one another, or how spread out your data is. A standard deviation is a statistic that measures the dispersion of a data set relative to its mean. The standard deviation is calculated as the square root of variance by determining each data point's deviation relative to the mean. If the data points are further from the mean, that means that there's a higher deviation within the data set, and then the data is said to be more spread out. This leads to a higher standard deviation too. Let's take an example of income in rural and urban areas. In rural areas, let's say such as farming areas, the income doesn't differ that much. More or less everyone earns the same. Because of this, our bell curve has a very low standard deviation and it has a very narrow peak. However, in urban areas, the wealth distribution is very uneven. Some people can have very high incomes and can be earning a lot, while other people can have very low incomes. Furthermore, the data distribution between these two income points is going to be more spread out, because there are a lot more people living there who work in various fields and who have various incomes. Because of this, our standard deviation is more spread out and our bell curve will also have a wider peak. Now, how can we find the standard deviation? Standard deviation is obtained by subtracting each data value from the mean and finding the squared average of these values. Let's look at how we can do this with the help of an example. These values correspond to the height of various dogs. We can find the mean by finding the average of all these values, which is nothing but adding all the values and dividing it by the total number of values. The mean that we get is 394. This means that the average height of a dog is 394 millimeters. To find the standard deviation, first we need to subtract the height from the mean. This will tell us how far from the mean our data points actually are. Next, we will square up all of these differences and add them up and again divide it by the total number of values that we have. This is called the variance. The variance that we get in this case is 21704. Finally, when we find the square root of this value, we will get the standard deviation. The standard deviation here is 147. The standard deviation will tell us how our data points differ from the average, and it gives us a basic value suggesting how spread out our data is from the very middle or from the mean. So when we plot these values, this value 147 will mean that a curve will have a width of 147 points around the mean. Now, what is the standard normal distribution? The standard normal distribution is a type of normal distribution that has a mean of 0 and a standard deviation of 1. This means that the normal distribution has its center at 0 and it has intervals which increase by 1. All normal distributions, like the standard normal distribution, are unimodal and symmetrically distributed with a bell-shaped curve. However, a normal distribution can take on any value as its mean and standard deviation. In the standard normal distribution, however, the mean and standard deviation are always fixed. When you standardize a normal distribution, the mean becomes 0 and the standard deviation becomes 1. This allows you to easily calculate the probability of certain values occurring in your distribution, or to compare data sets with different mean and standard deviations. The curve shows a standard normal distribution. As you can see, again, the data is centered at 0. This does not mean that the data necessarily starts at 0. This means that after standardizing, this point is where our mean will lie. In a standard normal distribution, the standard deviation is 1. So all the data points will increase or decrease in steps of 1. Let's better understand a standard normal distribution with the help of an example. Again, as you can see, the data is centered around 0, which is nothing but the mean. Let's again consider the weights of students in class 8th. The average weight here is around 50 kgs, and the data increases and decreases in steps of 5. The data over here in this curve is evenly distributed along these steps. This is what a standard normal distribution will look like. We already know that the mean of our data is 50, and because the data is increasing and decreasing in equal steps, we can just standardize it and take it to mean that the data is increasing and decreasing in steps of 1. This is what a standard normal distribution looks like, and when you have a data which looks like this, you can always standardize it and convert it into a standard normal distribution. Now, standard normal distribution has a couple of properties which makes calculation comparatively easy. The first one is that 68% of the values fall within the first standard deviation, which means that 68% of all data values on this curve will fall between the range of -1 to 1, or the first interval ranging from -1 to 1. The second property is that 95% of the rest of the values are within the second standard deviation, or from the second negative point to the second positive point. And finally, 99.7% of the values fall within the third standard deviation, or from the third negative point to the third positive point. This makes calculations on standard normal distribution fairly easy. You can compare scores on different distributions with different means and standard deviations. You can normalize scores for statistical decision making using standard normal distribution. You can find the probability of observations in a distribution which fall above or below a given value. And finally, you can find the probability that a mean significantly differs from a population mean. Now let's take a look at z-score. So what is a z-score? A z-score is used to tell us how far from the mean our data point actually is. It is calculated using the mean and standard deviation, so it can be said that the z-score is how many standard deviations below the mean our data is. Basically, by using the z-score, we can get an approximate location of where our data point lies on the graph with regards to the mean. Now the z-score is given by subtracting the data point from the mean and dividing it by standard deviation. This can also be written as x minus mu divided by sigma. Now, any normal distribution can be standardized by converting its values into z-scores. The z-score will tell you how many standard deviation from the mean each values lie. While data points are referred to as x in a normal distribution, they are called z or z-scores in the z distribution. A z-score is a standard score that will tell you how many standard deviations away from the mean an individual point will lie. A positive z-score will mean that your x value is greater than the mean, and a negative z-score will mean that your x value is less than the mean. A z-score of 0 will mean that your x value is equal to the mean. And again, to standardize a value from a normal distribution, all we have to do is convert it to a z-score by subtracting the mean from our individual value and dividing it by the standard deviation. Now let's see how we can find the z-score from data points with the help of a solved example. Let's do a case study. In this case study, we'll be taking the summary of daily travel time of a person who's commuting to and from work. All these values are in minutes, and using these values, we have to calculate the mean, the standard deviation, and the z-score. These values are as shown. As we can see, there are 13 values in total. Let's start by finding the mean. The mean is the average, and it can be gotten by adding all of these values and dividing it by the total number of values. This gives us a value of 38.6. The mean tells us the average of all our data points, which means on an average, he travels for 38.6 minutes to reach work. Next, let's subtract the individual values from our mean and calculate the variance and standard deviation. The values on the left give us the values that we get after subtracting it from the mean, and the variance can be calculated by squaring all of these values, adding up all of the squared values, and dividing it by the total number of values. At the end of the day, we get a variance of 140. To calculate the standard deviation, all we have to do is take a square root of the variance, which gives us a value of 11.8. Now, the mean signifies the average of our values, and we already know this. It gives us the average time which is taken to travel. But the standard deviation will tell us the average value of how much our data points differ from the mean. It tells us the deviation within our own data, and it tells us how far away on an average a point is from the mean. Now, the value that we get is 11.8, which means that on an average, a single data point is around 11.8 data points away from the mean. Now let's calculate the z-score. The z-score is given by subtracting individual data points from the mean and dividing it by the standard deviation. We know that we have a standard deviation of 11.8 and a mean of 38.6. Using these values, we can calculate the z-scores for individual x values. Now we know that a negative z-score means that our x value is lower than our mean. But what does the number 1.06 mean? This means that the z-score for 26 is 1.06 standard deviations away from the mean. The negative symbol here means that our x value is less than the mean. And by how less? 1.06 times the standard deviation. Now we know that the negative value of a z-score means that our x value is less than our mean. But what does the number 1.06 mean? This means that the z-score is 1.06 times the standard deviation less than the mean. The same thing can be said for the z-score of 33. It is 0.47 times the standard deviation less than the mean. The z-score of 65 is 2.23 times the standard deviation more than the mean. That means it has to be added to the mean. The reason that we know it's more than the mean is because this has a positive value. So this means that using z-scores, we can know where our data points fall relative to other points on the graph. The z-score will tell us how far away from the mean a point is in steps of our standard deviation.
Basics and terminology. The first one is outcome. Whenever we do an experiment like flipping a coin or rolling a dice, we get an outcome. For example, if we flip a coin, we get an outcome of heads or tails. And if we roll a die, we get an outcome of 1, 2, 3, 4, 5 or 6. Random experiment. A random experiment is any well-defined procedure that produces an observable outcome that could not be perfectly predicted in advance. A random experiment must be well-defined to eliminate any vagueness or surprise. It must produce a definite observable outcome so that you know what happened after the random experiment is run. Random events. Consider a simple example. Let us say that we toss a coin up in the air. What can happen when it gets back? It will either give a head or a tail. These two are known as outcome, and the occurrence of an outcome is an event. Thus, the event is the outcome of some phenomenon. The last one is sample space. A sample space is a collection or a set of possible outcomes of a random experiment. The sample space is represented using the symbol S. The subset of all possible outcomes of an experiment is called events, and a sample space may contain a number of outcomes that depends on the experiment. If it contains a finite number of outcomes, then it is known as a discrete or finite sample spaces. Now let's discuss what is random variable. A random variable is a numerical description of the outcome of a statistical experiment. A random variable that may assume only a finite number of values is said to be discrete. One that may assume any value in some interval on the real number line is said to be continuous. Let's see an example. Let x be a random variable defined as the sum of numbers when two dice are rolled. X can assume the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Notice there is no 1 here because the sum on the two dice can never be 1. Now that we know the basics, let's move on to binomial distribution. The binomial distribution is used when there are exactly two mutually exclusive outcomes of a trial. These outcomes are appropriately labeled success and failure. The binomial distribution is used to obtain the probability of observing x successes in n number of trials, with the probability of success on a single trial denoted by p. The binomial distribution assumes that p is fixed for all the trials. Here is a real-life example of a binomial distribution. Suppose you purchase a lottery ticket, then either you are going to win the lottery or not. In other words, the outcome will be either success or failure that can be proved through binomial distribution. There are 4 important conditions that needs to be fulfilled for an experiment to be a binomial experiment. The first one is there should be a fixed number of n trials carried out. The outcome of a given trial is only 2, that is either a success or a failure. The probability of success remains constant from trial to trial. It does not change from one trial to another. And the trials are independent. The outcome of a trial is not affected by the outcome of any other trial. To calculate the binomial coefficient, we use the formula which is NCR into p to the power r into 1 minus p to the power n minus r, where r is the number of success in n number of trials and p is the probability of success. 1 minus p denotes the probability of a failure. Now, let's use this formula to solve an example. Suppose a die is tossed 3 times. What is the probability of no 5 turning up, 1 5 and 3 5s turning up? To calculate the no 5 turning up, here r is equal to 0 and n is equal to 3. Substituting the value in the formula, we have 3c0 into 1 by 6 to the power 0 into 5 by 6 to the power 3, where 1 by 6 is the probability of success and 5 by 6 is the probability of failure. Calculating this equation, we'll get the value to be 0.5787. In a similar manner, to calculate the probability of 1 5 turning up, we'll replace r with 1 and n will be 3. So px1 will be equal to 3c1 into 1 by 6 to the power 1 into 5 by 6 to the power 2, which will come out to be 0.347. And for 3 5 turning up, we'll substitute r equal to 3 and the formula will remain the same and we'll get the value to be 0.0046. Now that we are done with the concepts of binomial probability distribution, here's a problem for you to solve. Post your answers in the comment section and let us know. A Poisson distribution is a probability distribution used in statistics to show how many times an event is likely to happen over a given period of time. To put it another way, it's a count distribution. Poisson distributions are frequently used to comprehend independent events at a constant rate over a given interval of time. The Poisson distribution was developed by French mathematician Simon Denis Poisson in 1837. A Poisson distribution is used in cases where the chances of any individual event being a success is very small. The number of defective pencils per box of a 6,000 pencil, the number of plane crashes in India in 1 year, or the number of printing mistakes in each page of a book. All of these examples can have use of Poisson distribution. The Poisson distribution can be used to calculate how likely it is that something will happen x number of times. A random variable x has a Poisson distribution with parameter lambda, and the formula for that is e to the power minus lambda into lambda to the power x divided by x factorial, where x can be the number of times the event is happening. The value of e is taken as 2.7182. Let's discuss some application of Poisson distribution. If you want to calculate the number of deaths per day or week due to rare disease in a hospital, you can use the Poisson distribution. In a similar manner, the count of bacteria per cc in blood or the number of computers infected with virus per week. The number of mishandled baggage per 1000 passengers can also have an application for Poisson distribution. Let's discuss one example to see how you can calculate the Poisson distribution. Suppose on an average, a cancer kills 5 people each year in India. What is the probability that one person is killed this year? We'll assume all these events are independent random events. So, by the formula, we have x is equal to 1 because we have to calculate the probability of one person that is killed this year. So p x equal to 1 will be equal to e to the power minus 5 into 5 to the power 1 divided by 1 factorial, which will come out to be 0.033, which will be near to 3.3%. So the probability that only one person is killed this year due to cancer is 3.3%. Now we have one question for you. Do try to answer in the comment section. Suppose the trains arrive at a railway station with an average arrival rate of 4 trains per hour. What is the probability exactly 6 trains will arrive in a 2-hour period? And here are our options. Please do let us know your answers in the comment section. Research and null hypothesis. The research hypothesis, which is also denoted by H1, says that the two variables are related in the population. The acceptance of the research hypothesis follows the rejection of the null hypothesis. The null hypothesis, H0, says that there is no association between the two variables and they are statistically independent. The null hypothesis has no bearing on the study's outcome unless it is rejected. Now let's define expected and observed frequencies. Expected frequencies are the value that we would get if the two tables were statistically independent. The expected values are calculated based on our null hypothesis. The observed frequencies are those frequencies that we gather ourselves from our observation. To calculate the expected frequency, we have a direct formula. We multiply the row total by the column total and divide the whole value by the total number of observations. Now let's move on to chi-square test. The chi-square test is a statistical procedure for determining the difference between observed and expected data. This test can also be used to determine whether categorical variables in our data are correlated. It helps to find out whether a difference between two categorical variables is due to chance or a relationship between them. The chi-square test requires no assumptions about the shape of the population distribution from which the sample is drawn. However, like all inferential techniques, they assume the random sampling. The chi-square test do have some limitations. Firstly, the chi-square test does not give much information about the strength of the relation or its significance in the population. The chi-square test is also sensitive to sample size. The calculated chi-square statistics is directly proportional to the size of the sample, which is independent of the strength of the relation between the variables. So, to calculate the chi-square statistics, we have a direct formula. The chi-square statistics, which is also denoted by x square, is equal to summation of expected frequencies minus observed frequencies whole square divided by expected frequencies. The chi-square test statistics follow 5 steps. First, we make assumptions about random sampling and state its research and null hypothesis. Then, we select the sampling distribution and specify the test statistics, and after that we compute the test statistics. The value we get is used to decide and interpret the results. Degree of freedom. The degree of freedom is a statistical calculation which represents the number of variables that can vary in a calculation. The degree of freedom can be calculated to ensure that the chi-square tests are statistically valid. These tests are frequently used to compare observed data with the data that would be expected to be obtained if a particular hypothesis were true. The formula to calculate degree of freedom is number of rows minus 1 multiplied by number of columns minus 1. So, after knowing the formula, we have a question for you. How many degree of freedom would a table with 3 rows and 2 columns would have? Post your answers in the comment section. Now that we have learned all the theoretical concepts regarding chi-square test, let's understand this more clearly with the help of an example. Let's say we want to know if the gender has anything to do with the handedness of the people. We have the data of 2,237 people in a simple random sample to find out if they are left-handed, right-handed or both. The results of the survey are shown in the table below. To see if the gender is linked to handedness, we perform a chi-square test. The first step is to define the null hypothesis. The null hypothesis says that the gender and handedness are independent to each other. The next step is to calculate the expected values. The expected value is calculated using the formula that is shown in the slide, which is row total into column total divided by the total number of observations. For example, the expected value of a right-handed man can be calculated by multiplying 1067 into 2004 divided by 2237, which comes out to be 956. In a similar manner, you can calculate the expected value for each of the cell. After calculating the expected value, we calculate the value of x square. X square is calculated by the following formula: observed frequency minus expected frequencies whole square divided by expected frequency. So, by putting the values in the formula, we get the x square value to be 12. Now, we got our x square, which is chi squared value, to be 12, and the degree of freedom is equal to 2, which is calculated by r minus 1 into c minus 1, where r and c were rows and columns respectively. The alpha value was assumed to be 0.05. We compare our chi square value with the critical values of the chi square distribution with the degree of freedom. So for degree of freedom 2 and alpha level 0.05, the value was 5.991, which was lower than our chi squared value. This states that handedness and gender are not very likely to be independent. Basics and terminology. The first one is outcome. Whenever we do an experiment like flipping a coin or rolling a dice, we get an outcome. For example, if we flip a coin, we get an outcome of heads or tails, and if we roll a die, we get an outcome of 1, 2, 3, 4, 5 or 6. Random experiment. A random experiment is any well-defined procedure that produces an observable outcome that could not be perfectly predicted in advance. A random experiment must be well-defined to eliminate any vagueness or surprise. It must produce a definite observable outcome so that you know what happened after the random experiment is run. Random events. Consider a simple example. Let us say that we toss a coin up in the air. What can happen when it gets back? It will either give a head or a tail. These two are known as outcome, and the occurrence of an outcome is an event. Thus, the event is the outcome of some phenomenon. The last one is sample space. A sample space is a collection or a set of possible outcomes of a random experiment. The sample space is represented using the symbol S. The subset of all possible outcomes of an experiment is called events, and a sample space may contain a number of outcomes that depends on the experiment. If it contains a finite number of outcomes, then it is known as a discrete or finite sample spaces. Now let's discuss what is random variable. A random variable is a numerical description of the outcome of a statistical experiment. A random variable that may assume only a finite number of values is said to be discrete. One that may assume any value in some interval on the real number line is said to be continuous. Let's see an example. Let x be a random variable defined as the sum of numbers when two dice are rolled. X can assume the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Notice there is no 1 here because the sum on the two dice can never be 1. Now that we know the basics, let's move on to binomial distribution. The binomial distribution is used when there are exactly two mutually exclusive outcomes of a trial. These outcomes are appropriately labeled success and failure. The binomial distribution is used to obtain the probability of observing x successes in n number of trials, with the probability of success on a single trial denoted by p. The binomial distribution assumes that p is fixed for all the trials. Here is a real-life example of a binomial distribution. Suppose you purchase a lottery ticket, then either you are going to win the lottery or not. In other words, the outcome will be either success or failure that can be proved through binomial distribution. There are four important conditions that needs to be fulfilled for an experiment to be a binomial experiment. The first one is there should be a fixed number of n trials carried out. The outcome of a given trial is only two, that is either a success or a failure. The probability of success remains constant from trial to trial. It does not change from one trial to another. And the trials are independent. The outcome of a trial is not affected by the outcome of any other trial. To calculate the binomial coefficient, we use the formula which is NCR into p to the power r into 1 minus p to the power n minus r, where r is the number of success in n number of trials and p is the probability of success. 1 minus p denotes the probability of a failure. Now, let's use this formula to solve an example. Suppose a die is tossed 3 times. What is the probability of no 5 turning up, 1 5 and 3 5s turning up? To calculate the no 5 turning up, here r is equal to 0 and n is equal to 3. Substituting the value in the formula, we have 3c0 into 1 by 6 to the power 0 into 5 by 6 to the power 3, where 1 by 6 is the probability of success and 5 by 6 is the probability of failure. Calculating this equation, we'll get the value to be 0.5787. In a similar manner, to calculate the probability of 1 5 turning up, we'll replace r with 1 and n will be 3. So px1 will be equal to 3c1 into 1 by 6 to the power 1 into 5 by 6 to the power 2, which will come out to be 0.347. And for 3 5 turning up, we'll substitute r equal to 3 and the formula will remain the same and we'll get the value to be 0.0046. Now that we are done with the concepts of binomial probability distribution, here's a problem for you to solve. Post your answers in the comment section and let us know. A Poisson distribution is a probability distribution used in statistics to show how many times an event is likely to happen over a given period of time. To put it another way, it's a count distribution. Poisson distributions are frequently used to comprehend independent event at a constant rate over a given interval of time. The Poisson distribution was developed by French mathematician Simon Denis Poisson in 1837. A Poisson distribution is used in cases where the chances of any individual event being a success is very small. The number of defective pencils per box of a 6,000 pencil, the number of plane crashes in India in 1 year, or the number of printing mistakes in each page of a book. All of these examples can have use of Poisson distribution. The Poisson distribution can be used to calculate how likely it is that something will happen x number of times. A random variable x has a Poisson distribution with parameter lambda, and the formula for that is e to the power minus lambda into lambda to the power x divided by x factorial, where x can be the number of times the event is happening. The value of e is taken as 2.7182. Let's discuss some application of Poisson distribution. If you want to calculate the number of deaths per day or week due to rare disease in a hospital, you can use the Poisson distribution. In a similar manner, the count of bacteria per cc in blood or the number of computers infected with virus per week. The number of mishandled baggage per 1000 passengers can also have an application for Poisson distribution. Let's discuss one example to see how you can calculate the Poisson distribution. Suppose on an average, a cancer kills 5 people each year in India. What is the probability that one person is killed this year? We'll assume all these events are independent random events. So, by the formula, we have x is equal to 1 because we have to calculate the probability of one person that is killed this year. So p x equal to 1 will be equal to e to the power minus 5 into 5 to the power 1 divided by 1 factorial, which will come out to be 0.033, which will be near to 3.3%. So the probability that only one person is killed this year due to cancer is 3.3%. Now we have one question for you. Do try to answer in the comment section. Suppose the trains arrive at a railway station with an average arrival rate of 4 trains per hour. What is the probability exactly 6 trains will arrive in a 2-hour period? And here are our options. Please do let us know your answers in the comment section. So, what is the central limit theorem? The central limit theorem is a statistical concept that states that the sample means of the distribution of a random variable will approach to a normal distribution if the sample sizes are large, respective of the shape of the original population distribution. We take the population and we take the sample out of them. Let's discuss the mean and standard deviation associated with it. Suppose we are sampling from a population with mean mu and a standard deviation sigma. Let x be the random variable representing the sample mean of n independently drawn observations. Then we can say that the mean of the sampling distribution of the sample means is equal to the population mean, which is mu x bar is equal to mu, where mu x bar represents the mean of the sample means and mu represents the population mean. On the other hand, the standard deviation of the sampling distribution will be equal to the population of the total standard deviation upon the under root of sample size. Let's understand this more clearly by taking a real world example. Suppose you are a regional manager of a pharmaceutical company in charge of 200 stores across the region, and you are in charge of weekly medicine restocking at all of them. You need to know how many cases to order weekly for each store in order to reduce the amount of inventory that expires. The plot on the right hand side shows the distribution of all the 200 stores and the average medicine cases required by each of the stores in a week. The red line represents the average cases required, which is equal to 34. You know, there has to be a better way to arrive at a reasonable answer that doesn't entail visiting every single store in your area and obtaining their weekly sales figure. You can apply the central limit theorem to this problem now that you understand the concept. We already knew the central limit theorem, when applied to real world problems, aids in balancing the time and cost of gathering the data required to draw the conclusions about the data. So here you can see the plot on the right hand side shows the distribution of sample means of the sufficiently large subsets taken from the population. Sample size greater than 30 will be sufficient enough to get the normal bell curve. The mean of all the samples taken from that population mean is equal to 34, which is equal to the sample mean of the subsets. If you plot the sample means, you will get a normal distribution which is a form of bell curve. If these samples meet the central limit theorem criteria, you can assume the distribution of the sample means can be approximated to the normal distribution. Now you know how to apply the central limit theorem in a real world problem. Let's discuss some assumptions behind the central limit theorem. The first one is the randomization condition. The data must be sampled at randomly and it must adhere to the randomization rule. The second one is the independence assumption. The sample value must be independent of each other. This means that the occurrence of one event has no influence on the next event. Usually, if we know that people or items were selected randomly, we can assume that the independence assumption is met. The third and the last one is the 10% condition. This states that when the sample is drawn without replacement, the sample size, which is n, should be no more than the 10% of the population. Let's now discuss some application of the central limit theorem. Political and election polling is a great example to show how you can use the central limit theorem. These post results are used to estimate the number of people who support a specific candidate. To calculate the confidence interval, which is shown on the news channel, the central limit theorem is very useful in this. One more place where you can use the central limit theorem is the census data. You use the central limit theorem to calculate the various population details such as family income, electricity, consumption, individual salaries, and so on. Now that we have a good understanding of the central limit theorem, its theories and application, let's see a demo in Python to understand it more clearly. Here we are on an online compiler. We'll discuss the CLT by taking a dice example. A dice has a different number on each side, ranging from 1 to 6. Each number has a 1 in 6 chances of appearing on a roll. Given all the equal likelihood, the dispersion of the numbers that come up from the dice roll is uniform. Let's start by importing some necessary libraries. We'll import the NumPy first. From numpy.random, we'll import the randit function, which will be used to generate the random integers. We'll also import the mean function from the NumPy. We'll set the seed to 1. Now we'll write the function to generate the random numbers. The randit function will generate a number ranging from 1 to 6. We have taken the 100 because the example will print the samples of 100 dice rows along with the mean. Print the rows and then we'll print the mean of the rows. So when you run this code, you'll get the following result. You see, we have the 100 numbers and the mean of this number is 3.38. Now we'll repeat the process 1000 times. This will give you the result of 1000 sample means. According to the CLT, the result of these sample means will be Gaussian. So we'll change this code from here. Means will be equal to mean of this random integers. We'll take from 1, 7, 100, and this will be for in range of 1000. Now we'll plot this distribution. We'll use the pyplot function. We'll get the graph as a histogram graph, so we'll plot it in that means and pyplot.show. Let's recheck our code. We have the random integer function, we have the seed. Okay, we have imported the mean. We have not imported the matplot library, so from matplot library we'll import pyplot. Now I think everything is in place, and let's try to run this code. Yep, you can see this graph is a histogram graph in the shape of a bell curve, and if you see closely, the mean is closely to 3.4.
So what is regression? Regression is nothing but a machine learning algorithm that helps us determine the relationship between two or more variables. It uses input or independent variables to find the value of the output or dependent variables. Regression is a prediction algorithm, which means that given some variables, we can predict the value of an output variable. The predicted value is not going to be from a set of values, but is going to be a unique value in itself. Now let's understand what exactly regression is with the help of a few independent input variables. In this case, the variables that we'll be looking at is rainwater, fertilizer, and seeds. When we pass these independent input variables through a regression model, we're going to get a predicted output. The output predicted is that a crop will germinate when all three of these components are put together in certain quantities. So with the help of regression, given raw input data, we can find out the dependent output variable that we'll get when all of these input variables are more or less combined. Regression is nothing but a statistical method which is used to determine the strength and character of the relationship between a dependent variable and a series of other variables. Now, using regression, if we have a set of data points, we can use a regression model to fit a line which passes through most of these data points and use it to predict the outcome for new data points. The line is fit using equation of a straight line or a polynomial equation. Now in this graph, consider that we have our dependent variable or the output y and our independent variable or the output x. For a certain value of our independent variable, we are going to get a certain value of our dependent variable or our output. Using the data given here, we can see how our output varies when our input varies. To predict the value of our outcome y, we're going to need to find a relationship between all of these data points. To do this, we're going to plot a straight line through it because, as you can see, all the data points lie more or less along a given straight line. Now, using the straight line, for any value of x, we can find the approximate value of y. So suppose you want to find the value of y at a point x, which is given here, say, then all you have to do is extend a line from this point onto our predicted model, which is this line here. And then we can see where this point on the line coincides with the y-axis and get the approximate value of the outcome. The equation of a straight line is given as y is equal to b0 plus b1x plus e, where b0 is a constant given by the y-intercept of our line, or basically where the line intersects on the y-axis. b1 is the slope of our line and x is the point for which we want to find the output. E in this case is nothing but an error correcting term. So this is basically how regression works, and this is how prediction takes place in our regression model. Next, we will explain the concept of the R-squared error to you. So what is R-squared error? R-squared error is nothing but an error measurement term which calculates how well our regression model fits the data. It determines the amount of variance in a model caused by the input variables. Now, R-squared is a statistical measure that represents the portion of variance for a dependent variable that's explained by an independent variable or variables in a regression model. R-squared is used to explain to what extent the variance of one variable affects the variance of a second variable. So, if the R-square of a model is 0.5, then approximately half of the observed variation can be explained by the model's inputs. In other words, an R-squared of 60% reveals that 60% of our data fits our regression model exactly. Now, in this case, in this graph, if we have a variance of 60%, it means that 60% of our data points fall exactly on our regression line. However, it is not always the case that a high R-squared is good for a regression model. The quality of the statistical measure depends on many factors, such as the nature of the variables employed in the model, the unit of measure of variables, and the applied data transformation. Thus, sometimes a high R-squared can indicate the problems with the regression model. A low R-squared figure is generally a bad sign for predictive models. Now, all this time we've been talking about variance in our model. What exactly is variance? Variance is nothing but a statistical term which determines how spread out our data is and tells us how many outliers are present in it. Basically, it's a measure of how far a set of numbers is spread out from their average value. Using variance, you can basically figure out where your data is centered and how spread it is from the mean, and also you can find out how many outliers it has. Now, how can you calculate the R-squared error? Let's start by considering the data that we have been given, as shown below. Now we can find the relationship between the input and the output variables by plotting a straight line or a regression model that passes through most of the data. To get the perfect fit for our model, we don't necessarily need to have the line passing through as many data points as possible. A true measure of a good model is that we reduce the error which is present in our model. Now, how do you find this error? The error present in our model is given by nothing but the distance between our predicted line and the data points which do not fall on the line. This is what you have to minimize. The distance between our data points and our line can be calculated by subtracting our data point from the point at which it coincides on our regression line. We square this just to get rid of any negative coefficients that may occur due to finding the difference between the 2 points. Now, to find the variance in our data, we're going to find the mean and subtract the data points from the mean. This will basically tell us how spread out our data point is from the average value. We can then square these differences and add up the result to get our total variance. This is also known as the sum of squares total, and using this we can find the total variance in our data. The mean is nothing but the average of our data, and using the mean we can find the center of our data. So this is exactly where our data is centered. This is the average value that occurs in our data. Now the variance is nothing but the distance of all of our data points from the mean. If we do this, we're basically going to find out how spread apart our data is from the average value, or how far all of our data points lie from each other. When we subtract the position of our data points from our mean and square it and add all of that up, we get something known as the sum of squares total. Now the R-squared error is the total variance in our input data. It can be obtained by dividing the SSR by the SST and subtracting the results from 1. So the R-squared error totally becomes 1 minus the sum of our squared errors divided by the sum of the squared difference between our data points and the mean. Now this value gives us the variance, and this is why we can say that R-squared is used to find the portion of variation in our data. Now, how can you implement R-squared error with Python? To calculate R-squared error with Python, we're going to look at the data which depicts the weather conditions which were present during World War II. And using the variables which are present in our data, we're going to create a model which predicts the daily weather forecast during World War II. And then we're going to use R-squared error to find the accuracy of our model. So this is our R-squared model. So we're going to start off by importing all of our necessary modules. We're going to use the model NumPy to perform numerical calculations on our database and arrays. And we're going to use Seaborn and Matplotlib to plot our data. So now we've managed to import all of our data sets. Let's also load our data by reading in the CSV file that it is stored as in the form of a data frame. So over here, as you can see, we've read in the CSV file into a variable called weather, and then after that we're changing weather into a Pandas data frame called climate. This is what our data frame finally looks like. So as you can see in our data frame, we have 5 rows because we're only looking at the top 5 rows, and we have 31 columns. So these are values which are not required and which are basically going to increase our error value. So let's drop them and get rid of them. Now let's also drop any empty values which may occur in the remaining columns of our data set and see what the final data set looks like. So this is our final data set. We have at the end, we're only left with max temperature, minimum temperature, and mean temperature. Now let's plot a count plot of our max temperature. A count plot is basically going to go through the entire max temperature column and figure out how many times every temperature value occurs. So it's going to figure out how many, it's going to count how many times 29.44444 has occurred, and it's going to plot that on this graph. And it is going to do that for every unique temperature value which is present in our column. So finally, this is the value that we get. So over here, as you can see, the majority of our temperature values are concentrated within this range. This means that these temperature values are the ones which occur most frequently. The other ones can be considered as outliers because they rarely are seen in our data, and they can further skew the output that we're going to get. Now let's do the same with minimum temperature. Let's plot a count plot for minimum temperature. So for the minimum temperature, we can see a very similar plot to the one that we got for a maximum temperature. Most of the values are concentrated around this region, but the outlier values here are way fewer. Now let's plot a regression plot between our maximum and our minimum temperature. So using the regression plot, we can plot a regression line for the two variables in our x and y axis. So this is our x axis and this is our y axis. This is basically going to plot a straight line which best fits the data that we are getting here. So over here, as you can see, this is a regression line. This thin blue line is a regression line which intersects our minimum temperature at a value which is between -30 and -40. And it passes through our entire data. So for a value of maximum temperature which is 0, using this we can predict the minimum temperature that would have occurred on the same day. So for 0, it will be somewhere around -10 degrees Celsius. So if we saw maximum temperature of 0 degrees on that day, we would have seen a minimum temperature of -10 on the same day. Now let's plot a heat map to see how these values are correlated with each other. So the correlation is basically used to find which values affect each other linearly, or which values when change will also affect the change in other values. So over here, as you can see, minimum temperature and maximum temperature have a correlation of 0.88, which means if minimum temperature changes, then the maximum temperature will also change to 0.88. Now the best correlation is obviously going to be between the mean temperatures and the minimum and maximum temperatures. The mean temperature is nothing but the average temperature value that we have. So this is basically going to lie in the middle of all of our temperature values, which is why we are going to have a better correlation for mean temperature. But minimum temperature and maximum temperature are also pretty well correlated with a correlation value of 0.88. This means that if our minimum temperature fluctuates, our maximum temperature will also fluctuate proportionately. Now let's separate our input and output values. We're gonna predict the maximum temperature given our minimum temperature. Here x is our input variable and y is our output variable. So now we're basically just gonna get all the important values in our x and y data sets. So after that, this is what our x and y data sets are gonna look like. Now let's split our data set into training and testing sets. The training set will be used to train our regression model, and the testing set will be used to predict how well our regression model is performing. The training data is the data which will be visible to our model, or the data which our model is allowed to have access to. Testing data will be data which the model has never seen before or which it doesn't have access to, and hence it will be made to work on completely new data to better test how well we've fitted to our data set. Now we can split our data set into training and testing sets by using the train test split functionality from our sklearn.model selection library. Now finally, from our scikit-learn library, let's import a linear regression model. We're going to initialize a linear regression model to a variable called regressor, and then we're going to fit a linear regression model to our training data set. So we finally got our trained linear regression model. Now let's use this model to perform predictions on our testing data set. So these are the values that we've gotten after running our linear regression model on our testing data set. Let's see how well we've performed. We are going to import the R2 score from our sklearn metric. Now the R2 score will directly perform R-squared error on our prediction and testing dataset and see how well our testing dataset matches our prediction dataset. So now we've gotten an R-squared error of 0.9345, which basically means that 93% of our output values are influenced by our input values. This also means that our model is 93% accurate and that approximately 93% of our observed variation can be explained by the model's inputs.
Let's start by defining what is mean squared error. Mean squared error measures the amount of error in a statistical model. It calculates the average squared difference between the observed and predicted values. In regression line, the mean squared error represents the average squared residual. As you can see in the graph, as the data points fall closer to the regression line, the model has a less error, decreasing the mean squared error. A model with less error produces more precise predictions. Now let's jump to our Excel workbook and discuss it with an example. Here we have a small table with the actual and predicted values. We'll start by finding the error between the actual and predicted value, which will be the difference between the actual minus predicted values. So here 10 minus 7 will become 3, 16 minus 14 will become 2, 13 minus 17 will become minus 4, 19 minus 20 becomes minus 1, and 7 minus 4 becomes 3. Now just calculate the total of the errors. While calculating the total, we'll treat this negative value as a positive value. So here the total of the errors will become 3 plus 2, 5 plus 4, 9, 1, 10 and 13. Then we'll calculate the square of the errors. So here 3 square will become 9, 2 square will become 4, 4 square will become 16, 1 square will become 1 and 3 square again is 9. And we'll do the total of the square errors. So this will become 9 plus 4, 13, 13 plus 1, 14, 14 plus 16, 30 and 39. To find the MSE, that is the mean squared error, we'll divide the total of the square error values with the total number of records. So here MSE will be equal to (39) divided by, and we have a total number of records, that is 5, which will be 7.8. Let's name this as model A. Now, for the comparison purpose, we'll create another model, that is model B. We'll have all the columns here. And we'll keep the actual values here same. We'll just change the predicted values. So let's take some random values. We'll keep this as 13, we'll take this as 20, we'll take this as 12, 18 and 3. Now to calculate the error, we'll subtract the predicted values from the actual values. So 10 minus 13 will become minus 3, 16 minus 20 will become minus 4, this will become 1, this will be 1 and this will be 4. Now to calculate the square error, we'll just square the error values. So this will be 9, this will be 16, this will be 1, this will be 1 and this will be 16. The total of all the square values will come out to be 43. Now to calculate the MSE, again we'll divide the total square values with the total number of records. So here this will be equal to 43 divided by 5, which will come out to be 8.6. If you observe here, the total of the errors in both model A and model B is same, that is 13. So which model to prefer? Since the mean squared error of model A is lesser than model B, we'll prefer model A because we are okay with a model that has small errors, but in model B, there are some significantly large errors. Suppose in this case 16 minus 20, that is minus 4, minus 3 and this here 4. So we do not want a model where the errors, large errors specifically, are more frequent. We can have a model with the small errors that will be okay. So we'll prefer model A over model B.
Now getting into probability theories. So during your school times or college time, you would have learnt about probability theory. What is probability theory? Yeah, as Vishal said, it is actually chance, the chance of getting. For example, if I toss a coin, okay, I'm tossing a coin and what is the probability of getting my head? It is actually 1 by 2. Only one time my head can occur. That is, as Amani said, it is 0.5. So that's what it is represent here. The number of favorable occurrence to the number of possible occurrence. So the number of possible occurrences, if I toss a coin, either I can get a head or a tail. So there are two possible occurrences. But when I toss a coin, only one can be the result. So either I'll get a head or else a tail. So it is divided by 1 by 2. If I'm talking about probability of getting a coin which is head, then I can tell it is 1 by 2, which has equal probability in terms of coin. For an example, if I'm rolling a dice, what is the probability that I get a number called 2? Dice generally has 6 faces. Yes, as Amani said, it is 1 by 6. So only one option can occur, either 2, 3, 4 or 5 or 6. Any one of these numbers can occur, but there are actually 6 spaces. So the probability is 1 by 6. So that's what we're going to look here. And in another way, now for an example, let us look at a case study. Okay. So in this particular case study, I have 100 coins. Okay. I'm going to toss 100 coins. Sorry, I'm going to toss 10 coins. So I have 10 coins and I'm going to toss 10 coins simultaneously. Okay, this is the process. And how many times it is possible to get a head? So if I'm tossing 10 coins, what is the probability of getting no hits? What is the probability of getting one head? What is the probability of getting two hits? And this is actually the thing that I'm going to choose. Yeah, as I'm going to say, it is 0.5 into 10, but I'm going to repeat the process for 100 times. So first time I'm going to toss 10 coins parallelly, okay, and I'm going to record how many times head had occurred. And the second time also I'm going to toss 100. And the second time also I'm going to toss 10 coins simultaneously, and I'm going to record how many times head had occurred. Okay, I'm repeating this process 100 times. If you're looking at this frequency, see, so what they actually made a survey. So they had tossed 10 coins and they had repeated this experiment 100 times. So don't get confused. So I'll just tell, okay, I'm tossing 10 coins simultaneously, and I'm going to do this operations 100 times. Okay, 100 times I'm going to repeat the same process. So first time I'll toss 10 coins. Second time also I'll toss 10 coins. The same way I'm tossing the 10 coins 100 times. Okay, and I had recorded the frequency. So I just see that only in this 100 times, only one time I found that no heads turned up. Okay, all the 10 coins were showing me tail. That frequency is only one. And 2 times it showed only one head and 9 tails. And 3 times it showed 2 heads and 8 tails. Okay, this is actually the number of heads which had occurred. So here, just tell me which is the maximum frequency, which is the number which had maximum times which had occurred. On looking at this frequency, this is actually, if you're adding all these things, it comes to 100. 100 times the experiment is done. In only one experiment, I found that all my 10 coins are tail. And in only 2 experiments, I find that only one head turned up and the rest 9 coins are tail. Okay, as Matthew said, 5 heads 30 times. So in 30 experiments, I find that 5 times I get head and 5 tails I find. So this is having maximum frequency. So according to us, if I toss a coin, if I toss 10 coins simultaneously, the optimum probability, the maximum probability that I get is 5. 5 times 5 heads will occur and 5 tails would occur. That is the maximum occurrence that is here. So that's what we're going to see here. And this would give you the relative frequency for every flips. For an example, if I ask you a question, what is the probability of getting 0 head when I'm tossing 10 coins? What would be your answer? If I toss 10 coins, all the 10 coins are tail. I'm not getting not even a single head. What is the probability? It is 0.001. This relative frequency would tell you what is the probability. This is nothing but 1 divided by 100. Because in 100 experiments, only one time this scenario had occurred. So 1 divided by 100 is 0.01. 2 divided by 100 is 0.02. Because if you're adding up all this frequency, it comes to 100. So individual value divided by 100. And 30 divided by 100 would be 0.3. Clear? If I'm asking a question, what is the probability of getting 5 heads when I'm flipping 10 coins? What is the probability? What is the probability that I get 5 heads in this particular scenario? It is actually 0.3. 0.3 would be the probability. So for 5 times head, 0.3 is the probability. And what is your expected value? So before I toss a coin, okay, we are not talking about this experiment. In a general way, I am asking a question, okay. I am tossing 10 coins simultaneously. What is the probability for me to get head? What would be your answer? Amani said 5. On what basis you said 5? This is actually your expected value, right? You didn't do any experiment, but you are arriving at a particular value. You guess that, okay, whenever I toss 10 coins simultaneously, at least 5 times I can get head. At least 5 coins will turn up head. That's your expected value. That's where this expected value is calculated. So the method to calculate your expected value is nothing but 0 into your frequency. So into your relative frequency. So if you're multiplying 0.01 into 0, it becomes 0. Your relative frequency into the number of heads. So this is 0.02 into 1, it becomes 0.02. 0.03 into 2, it becomes 0.06. And if you are adding up all these values together, 5.14. Yeah. So 5.14 is the expected value. So according to our analysis, initially before doing this experiment, what was our expected value? If I toss 10 coins, 5 is the thing that I'm going to get 5 times. I assume that at least 5 heads would turn up. Even after looking at the expected value, now we are guessing that it is 5.14, so it is closely near to 5. So 5 times head can turn up. That's how the probability works. Okay. And if I'm asking the probability of individual things to occur, for an example, if I ask you a question, what is the probability of 7 times head occurring when I flip 10 coins? What would be your answer? Your answer would be 0.12, right? This is the probability. Clear about probabilities and expected values? Expected is nothing but your assumption. So initially you would have some assumption. What is that overall assumption that it gives, and what is the maximum number which is occurring? This is all about probability distribution. So generally, if you know the probability, it sometimes help you in knowing some business process. For an example, in the same phases, just connect it with customer getting into your company and getting a particular product. Okay, so initially on a particular day, 10 customers are getting into your shop and they're getting chocolate coffee. And in the same way, what is the probability that tomorrow, if there are 10 customers, how many customers would, if I want to check the probability that 5 customers are getting hot coffee, I can derive from this probability values. That's what you can also relate the same example with some of the business cases, and you can do it. Okay, this is about probability distribution. And if you're looking at in our slide also this will be represented. So this is the same way, like they took another example, how many units sold on the first day, like here are different days. For 10 days 0 units sold, for 55 days only 1 unit had sold, for 150 days 2 units has sold. The same example they had given for another business case. So sales data for AC sold in last 300 days. In last 300 days, how many AC is getting sold? So in last 300 days, only 10 days, I found that 10 days there is no sale. In 55 days, I found only 1 unit sold. In 150 days, I found 2 units sold. So this is actually the frequency which is mentioned, and here the probabilities are calculated correspondingly, and which is being plotted. Here you can see at an average level how many units are sold. At an average level 3 units are sold. This would be your expected value, right? Clear everyone? The same thing in terms of business example they had given. Just go through this example and it is also the same process. Next, coming to binomial distribution. So because we will not much get into the statistical part or a mathematical part, so what will is, because some people are from business background and some people are from maths background, so what I'll do is I'll try to put all these things in a simpler way. So that's the reason I created another slide, because generally on looking at a complete slide, it is difficult for you to understand the stats concept. So that's why I had also created some additional slides to represent all these examples. Okay. So for an example, what is binomial distribution? Okay, as Akansha said, it is 2 values. So whenever you have 2 situations like probability of success or failure or the event happening or not happening, in those sort of situations, only if you have, if your values are like, if you have a fixed number of trial and if you have the trials of independent of each other, then you can go for a binomial distribution, and it has only 2 options, either a success or else a failure. So in those sort of situations, you can go for a binomial distribution. So only one probability of success and the other things would be a failure. So what I'll do is I'll also show the slide that I had created. For an example, binomial distribution, let's not get much into a technical part. Okay. Suppose a die is tossed 5 times. So how many sides a die has? It has 6 sides. And what is the probability of success there? What is the probability of success in a dice? It is 1 by 6. And what is the probability of failure? It is actually 5 by 6. Yeah. So in this case, what I'm going to do is, what is the probability of getting exactly 2 4s? So if I roll a dice and if I'm doing the same process 5 times, what is the probability of getting exactly 2 4s? In this case, it becomes easier. So one thing is you can do, okay, as Amani said, 1 by 36. I'm just, yes, 1 by 36 when you are accounting 5 times. For a single die, it would be 1 by 6, right? Yeah, yeah, that is option. And Sandhya, you were telling 2 by 5. How it is 2 by 5? What is 2 by 5? because 2 4s, yeah, it cannot be related in that way. So I'll just tell you how to do this process. This is the process. You are clear about one die phases, right? What is the probability? It is 1 by 6, and just make sure that this I'll be taking in terms of formulas, and I'll also tell you how to do this in Excel in an easier way. First, I'll tell you the formula how to do this process. Okay, the formula to do this is binomial distribution is, the formula is NCR, N would be capital NCR, P to the power of R into Q to the power of N minus R. This is the formula. This probably you would have learnt in your colleges or school. So here, let me explain. Once I'll put it in a formula basis, and I'll do this process, and again I'll explain you how this is happening in terms of tool very easily. So what is exactly N here? How many times we had repeated this process? What is N? This is the formula to calculate binomial distribution. So it is 5. 5 times I had repeated the process. So 5, the combination of, what is R here? How many times 4 should occur? It is 2. So it is 2. And what is P is nothing but the probability of success. What is the probability of success when you are rolling a dice? It is 1 by 6. Yeah. So if you are dividing 1 by 6 in calculator, what is the value? 1 by 6 to the power of, what is R here? It is 2. And in the same way, what is the probability of failure? Q is nothing but your probability of failure. It is 5 by 6. If your success is 1 by 6, it is minus of your success rate. So it is 5 by 6. To the power of, what is N? What is N here? 5. 5 minus 2. So can someone tell me what is 5c to the power of 5 combination of 2? What is 5 combination of 2? What is the value of, someone said it is 3, but basically we will also do 5c to the power of 2. What you will do is, I will also tell you what is the formula for this. This is nothing but n factorial divided by r factorial into n minus r factorial. I'll just put this formula just for your understanding. This is nothing but n factorial. So if you want to calculate manually by hands also you can do it. N factorial divided by r factorial into n minus r, the whole factorial. Okay, and if you are substituting in this formula, what is the answer that you get? 5c2. What is n factorial here? 5 factorial is nothing but 5 into 4 into 3 into 1. Yeah, 5 into 4 into 1 divided by. So only for this I am just giving a detailed explanation. And what is r factorial? What is r factorial here? Okay, I think everyone had did this process. Everyone had given the answer 10. But just for the first process, I will do this. This is actually 2 factorial. 2 factorial into n minus 2 is nothing but 5 minus 2 is 3. 3 factorial. So 3 factorial would be 3 into 2. Right? So this is actually 3 into 2, it gets cancelled, and 2 will cancel by 2. So this is actually 10. So 10 would be the result of 5c2. Instead of 5c2, now we can substitute 10. Okay. 10 into what is the result? 1.6, 1 by 6 into 1 by 6 to the power of 2. What is it? What is the result? Yeah, here 1 by 6 would be 0.167. 0.167 to the power of 2 into the failure would be 0.833 to the power of 5 minus 2 is actually 3. And if you are solving this, you would get a result of 0.161, right? This is the probability that you would get. This is the result that you would get using formula. In the same way, if I am doing the same process in Excel, let me see how much time it is. And now what is the probability? So if I ask you a question, what is the probability? What is the probability for me to get exactly 2 4s when I toss 5 times the dice? What is the probability? It is 0.161. The same thing you can do very easily in terms of Excel. So just open your Excel. Here just type what is the operation that we are going to do? What is the distribution that we are going to do now? We are going to do binomial distribution. So just type binomial, you will get binomial distribution option. So in this binomial distribution, you can see the number to specify here. What is the number that we are going to take here? How many times 4 should occur? So the number of time exactly 4 should occur is 2 times. And what is the number of trials? It is 5. And what is the probability of success? What is the probability of success? It is 1 by 6. Okay, I'm putting 1 by 6. And cumulative. Cumulative is something very important to understand. So now we are going to do a point probability. So in terms of point probability, you have to select false as your option. I'll tell you what is cumulative probability and what is point probability. So now we are able to see the result, right? What is the result? Even when manually calculating 0.161, it is 0.16075. It can be accounted as 0.161. It is equal, right? It becomes very simple in terms of Excel. Now in the same way, if I am asking you, okay, Sandhya, repeat again. So what I'll do is, I'll do the same process again. Binomial distribution. Okay, what is this number of S? Number of S represents that how many times that your number should occur. So in our case, exactly 4 times the number should occur, right? I'll show you the question once more. Suppose a die is tossed 5 times. What is the probability of getting exactly 2 4s? So what is the number that you're expecting? Exactly 2 4s. That's what I had mentioned here as 2. First number is actually I'm mentioning I want 2 exact 4s. And how many trials I had made? How many times I had made the trial? 5 times I had made the trial. And what is the probability of getting a success in a dice? 1 by 6. So I'm giving 1 by 6 here. And it is very easy in Excel because it throws you what are all the parameters to pass. And cumulative, here I'll talk about point probability. Then I'll talk about cumulative probability as well. So first I'll talk about point probability, which is exactly 4. Okay. So here I want only on this particular point, what is the probability? So I'll select my operation as false. Okay. I'm clicking it, I'm closing it, I'm clicking enter. So I get the probability value. Clear? Clear, Sandhya? Clear about this process? Okay. Now, what the question that I had framed is exactly 2 numbers. What exactly 2 4s? So what I did is, and also, so the first question what I did is exactly 2 times the number 4 should occur. This is what I did. So here what I can do is the probability of x is equal to 4. This is the x is equal to 2 times it should occur. In the same way, if I want to find less than or equal to 2, p of x less than or equal to 2. In this case, what would be my value? What should be my value? So I should calculate the probability of 0, because if it is less than or equal to 2, I should calculate the probability of 0, I should calculate the probability of 1, probability of 2, right? In this situation. In this case, if I take only one probability, that is sufficient. This is called point probability. Because I am doing this operation for only one particular value, which is a pointed value. I want to know exactly 2 4 to occur. But what if I have a question, okay, at least 2 times it occurred. So in that case, what you will do is p of x less than or equal to 2. Here what you want to know is, you want to know the probability of 0 times occurring, and you want to know the probability of 1 time the value getting occurred, and you want to know the probability of 2 times the value get occurred. Clear? This is what you have to do. So first what I'll do is, I'll take a, now instead of false, instead of this particular false, if I give true, the cumulative actually happens. If I give true here, this is actually cumulative distribution. So this is actually the probability of 0, 1 and 2 gets added. So what is the probability of 0, 1 and 2 all together for less than or equal to 2? What is the probability? In another way, what I'll do is just copy this. So first time 0 times it is occurring. Okay, what is the value? 0.40. And now I'll just put the value here as 1. Only one time the value is occurring. Okay. And now I'll put the probability of 2 times the value get occurred. Okay. Now if I add all these things, this is for what? The probability of x is equal to 0. 0. This is actually the probability of x equal to 1. And this is actually the probability of x is equal to 2. This is, all these points are individual probability, right? This is point probability. What is the chance of 0 time occurring? What is the probability of 1 time occurring? What is the probability of 2 time occurring? This is exactly 0, this is the value. Exactly 1, this would be the probability. Exactly 2, this is the probability. So what if I want x less than or equal to 2? What I should do? These are all like point probabilities I had found. Now if I want to calculate the total, I have to sum it up. Yeah. If I sum all these 3 values, what is the value that I get? 0.964506, which is nothing but if you are mentioning as true, the accumulation happened. If you are mentioning as false, the point probability happens. Now is it clear for everyone? One thing is you can take point probability of all the points and you can add, or else directly with the last value you can divide, you can mention your cumulative as true. Then automatically the accumulation happens. Is it clear everyone? Now is it clear for everyone with this example? This is how the binomial distribution works. Either you can calculate point probability and you can add, or else you can mention your accumulation as true. If you are mentioning accumulation as false, it is point probability. If it is true, then it is a cumulative probability. Okay. Next I'll get into the other distribution. So in the same way, that's what as I gave you an example here they had given. So now can someone tell me with this particular problem, don't see the answer. Okay. Just tell me what is the probability of updating. First tell me what is the probability of obtaining exactly 45 heads in 100 tosses of a coin. Can someone tell me for exactly 45? First tell me exactly 45. Then tell me the cumulative probability. So for doing this process, what are all the factors that I should consider? Exactly 45 times. I want to know exactly 45 times how it is occurring. I'll also copy this question. In this question, what is the formula that I should put here? What is the, instead of obtaining fewer hits, first consider exactly 45 hits. First the question is, just tell me the point probability of exactly 45 hits. Okay, 0.048. So I'll also check it once. Okay, so equal to binomial distribution. What is the number of parameters that we are fixing? Exactly 45, right? And number of trials, we had made 100 trials. And what is the probability of success here? In tossing a coin, it is 0.5. Yeah, 1/2 or 0.5, anything is okay. And what is the parameter that I should mention for point probability? False or true? I should mention false. Yeah, I mentioned false. This is 0.048. And in the same way, if I want to find what is the probability of less than or equal to 45 or fewer heads of 45, then what I'll do is I can make it true here. I will get a cumulative option. Okay, fine. So this has a probability of heads occurring less than or equal to 45. Clear everyone? 18% chance.
So now let's dive into the definition of the probability distribution function. What is probability distribution function? A function which defines the relationship between a random variable and its probability such that you can find the probability of the variable using the function is called a probability density function. In simple words, probability density is the relationship between an observation and the probability. Some outcomes of a random variable will have low probability density and other outcomes will have a very high probability density. Basically, the probability of a variable x happening or occurring will vary, and it can sometimes take on a lower value or it can take on a way higher value. The overall shape of the probability density is referred to as probability distribution, and the calculation of probabilities for specific outcomes of a random variable is performed by a probability density function, or PDF for short. Now consider a variable x with a PDF of f of x. This is what your probability density function will look like. There might be a point where the probability of x occurring is very high. Hence, your probability distribution function, or f of x, will also be very high. At other points, the distribution or the probability of x happening or occurring is going to be very low. Hence, your f of x is also going to have a very small value. Basically, given the random sample of a variable, we might want to know things like the shape of the probability distribution. This here is something called a normal distribution, where your probability distribution function takes on a bell shape. However, this is not the probability density function that might always occur. There are different probability distribution functions, and all of their graphs look very different from each other. Knowing the probability distribution for a random variable can help you calculate movements of the distribution like the mean and variance, but it can also be useful for other more general considerations like determining whether an observation is unlikely or very unlikely and might be an outlier or an anomaly. Like, consider this graph itself. In this graph, these points over here, which have very less probability distribution, are outliers, which means that the chance of them occurring is very low. And basically, this is not something that you're going to see in your regular scenario for your variable x. Now let's consider 2 points a and b, which are values that our variable x can take. P of A and P of B just represent the probability of A and the probability of B, which can be found out by drawing a straight line and coinciding it with our graphs. The area under the graph over here, which is going to give you your probability of this region occurring, can be written as probability of A less than equal to x, which is the probability that we're searching for here, less than equal to probability of B. What does this mean exactly? This means that this area is always going to be greater than or equal to the probability of A, but less than or equal to the probability of B. This gives us the narrow region of the probability which is present over here. And doing this, we can find the probability of occurrence for any value of x. Suppose you want to find the probability of B happening. For a probability distribution function, the probability of B happening is not simply this point here, but the entire area of the graph which is taking place before this point itself. So if you want to find the probability between these regions, you're going to have to find the entire area and not simply the probability at one point. Now, so far we've been talking about different types of variables, which is discrete random variables and continuous variables. What exactly do these mean? A variable which can only take a value within a certain range is called a discrete random variable. The value is usually within a certain distance of another finite value. An example of this would be the sum of two dices. Basically, values which are well defined are called discrete values, and a variable which has well-defined values will be called a discrete random variable. This variable can only take values which fall within a certain set of values. Let's say you roll a dice. The dice can only give you specific outcomes which range from 1 to 6. This is what you would call a discrete output. On the other hand, a continuous random variable can take on infinite different values within a range of values. For example, the height of a student. The height of a student is not fixed. Even if the height is 1.7 meters, in reality, the height can be 1.77 or 1.765 or 1.789. The exact height is very hard to determine because it's not easy for us to find the precise value of the height of a student. So basically, the height can take on an infinite different range of values. When we're trying to define the values that a continuous random variable can take, we usually say it in the form of a range of values, which means that the value can fall in that range and can take on any value in that range. It's not like a discrete random variable where you can define definitive values. Now let's understand a probability density function with the help of a graph. Consider the graph below, which shows the rainfall distribution in an year in a city. The x-axis has the rainfall in inches, or the amount of rain that we're getting, and the y-axis has the probability density function of getting that amount of rain. The probability of some amount of rainfall is obtained by finding the area of the curve to the left of it. So let's say we have a point 3. If we want to find the probability of 3 inches of rainfall occurring, we would have to find the area of the curve which falls to the left of 3. When we draw a line from 3 which intercepts the graph and further extend it onto the y-axis, we get a value of 0.5. Simply put, this means that the probability of 3 inches of rainfall occurring is going to be lesser than or equal to 0.5. The exact probability can be found out by finding the area of the curve, which falls to the left of 3. How do we find the probability distribution function? The first step is to summarize your density with the help of a histogram. The first step in a density estimation is to create a histogram of the observations in the random sample. Now, what is a histogram? A histogram is a plot which involves first grouping the observation into bins and counting the number of events that fall in each bin. The counts or frequency of observation in each bins are then plotted as a bar graph with the bins on the x-axis and the frequency on the y-axis. The choice of the number of bins is important as it controls the coarseness of the distribution and in turn how well the density of the observation is plotted. It is a good idea to experiment with different bin sizes for a given data sample to get multiple perspectives or views on the same data. At the same time, the number of bins is important as it determines how many bars the histogram will have and their widths. This will change not only the shape of the graph, but also how the graph is read. This will also determine how a density is plotted. Now, let's see how we can summarize our density with histograms using Python. First, let's import all of our necessary modules which we're going to require. We're going to require Matplotlib to plot graphs. We're going to need the normal random function so that we can get a normal distribution. We're going to import mean and standard deviation from NumPy to use on our graphs. We're also going to normalize our data, so we're going to import the norm function from SciPy. We finished importing all of our necessary modules. Now let's generate a sample which has a size of 1000 and it's going to be a normal distribution. And we're going to also plot this with the help of a histogram in bins of 10. So as you can see here, you get a normal distribution, which is nothing but a almost bell-shaped curve. And we have 10 bins here, which are centered at 0 and which extend from -3 to 3. How will our graph look if we change the number of bins though? Let's run it and see. So you still have a normal distribution, but it's not as well defined. Because of how less the number of bins are, you lose a majority of the data which will contribute to your normal distribution. It doesn't look like a proper normal distribution, but it looks more like a discrete data at this point. Now let's take a look at the next step of finding our probability distribution function. The next step is called parametric density estimation. What exactly is parametric density estimation? The probability density function is of many types. The shape of your histogram will help you determine what type of a function it is. We can also calculate the parameters associated with the function to get our density. Now, different probability distribution functions will have different graphs which will have different shapes and which will also have different parameters like mean, standard deviation, etc. associated with them. Using these parameters, we can find important points of our data. Hence, it's very important for us to recognize what type of a distribution it is. Common distributions will occur again and again in different and sometimes unexpected domains. Getting familiar with common probability distributions will help you identify a distribution from a histogram, and once identified, you can attempt to estimate the density of the random variable with a chosen probability distribution. This can be achieved by estimating the parameters of the distribution from a random sample of data. Now, an example of this would be a normal distribution which has two main parameters, the mean and standard deviation. Given these two parameters, we will now know the probability distribution function. These parameters can be estimated from data by calculating the sample mean and sample standard deviation. This entire process is known as parametric density estimation, and it includes identifying your probability distribution function and getting the parameters which are associated with it. Now, once we have estimated the density, we can check if it's a good fit. This can be done in three different ways. One is plotting the density of the function and comparing the shape to the histogram. The next is sampling the density function and comparing the generated sample to the real sample. And the last one is using a statistical test to confirm if the data fits the distribution. Now over here, as you can see, all we've done is taken our data and plotted the density function on top of our histogram, and we've compared the shape. So the density function that we're actually considering here is a normal distribution. And from this graph, we can see that it's almost an exact fit to our histogram. Now let's see how we can perform parametric density estimation using Python. To begin with, let's generate a random sample of 1000 observations from a normal distribution with a mean of 50, which is determined by the LOC parameter, and a standard deviation of 5, which is determined by the scale parameter. Now, just to show you what the distribution looks like, we're going to plot it in the form of a histogram. So this is what the histogram looks like. But this is just to give you a basic idea of our data and what it looks like once plotted. But let's assume that we don't know the probability distribution and we don't know what it looks like as a histogram, and we don't know that it's normal. So now if we just assume that it's normal, we can calculate the parameters of the distribution, specifically the mean and the standard deviation. We would not expect the mean and standard deviation to be 50 and 5 exactly, given the small sample size and the noise in the sampling data. So because of this noise and the small sample size, we have a mean of almost 50 and a standard deviation of a little more than 5. Now let's define the distribution as normal. So now using this, we've defined a normal distribution. We've used the norm method of the SciPy library, and we're doing this with the mean and the standard deviation that we've obtained from our samples. So up until now, we're just assuming that it's a normal distribution, and because of that, the parameters that we've calculated is the mean and standard deviation. And using the calculated mean and standard deviation, we've gotten a normal distribution. And up until now, again, keep in mind, we do not know for certain that it is a normal distribution. So far, all we have is this data. So the next thing that we're going to do is fit the distribution with these parameters. and then sample the probabilities for a distribution for a range of values in our domain, which in this case is 30 and 70. So all we're doing is we're calculating probabilities for a range of outcomes, and in this case we've taken 30 and 70 as our domain. So these are the probability distribution values for the normal distribution that we've defined over here, and this is basically gonna give you the outline of your normal distribution. These are the points at which your normal distribution will be plotted. Now what we're basically going to do is we're going to plot our histograms using the samples that we've already generated along with the values and probabilities of the normal function that we defined over here. So as you can see, it's almost a complete fit. The normal distribution that we have here is made using the mean and the standard deviation of our actual samples. The reason we took mean and standard deviation was because we assumed it was a normal distribution, and the parameters associated with the normal distribution are mean and standard deviation. Using the mean and standard deviation, we got the normal distribution. We calculated probabilities for this normal distribution using a random domain of 30 and 70. And we plotted the probabilities and the values on top of our histogram to see if the normal distribution was a fit to our histogram. If it was not a fit, you would have to go and do the same procedure with other common probability density functions until you found a function which was a proper fit to your histogram. Now let's move on to the final step, which is used in the calculation of our PDF. This final step is called non-parametric density estimation, and it's only used when the shape of a histogram doesn't match a common probability density function, or it cannot be made to fit one. In this case, we will calculate the density using all samples in our data using certain algorithms. This is only done when a data sample does not resemble a common probability distribution, or it cannot be easily made to fit the distribution. And this is often the case when the data has two peaks. This is also called a bimodal distribution, or it has many peaks, which is also called a multimodal distribution. In this case, the parametric density estimation will not be feasible, and alternative methods can be used that do not use a common distribution. Instead, you will use an algorithm which is used to approximate the probability distribution of the data without a predefined distribution, which is also referred to as a non-parametric method because we're not using any predefined parameters. The distribution will still have parameters, but these are not controllable in the same way as a simple probability distribution. For example, a non-parametric method might estimate the density using all observations in a random sample, in effect making all observations in the sample parameters. Now consider this graph which has two peaks. This is not a normal distribution or any other sort of distribution that we are familiar with. So for this, we're not going to use a parametric estimation method, but we're just going to calculate the parameters for every single sample point in this. Perhaps the most common non-parametric approach for estimating the probability density function of a continuous random variable is called kernel smoothing or kernel density estimation, or KDE for short. Kernel density estimation is a non-parametric method for using a dataset to estimate probabilities for new points. It uses a mathematical function and smoothing probabilities, so the sum of the resultant probabilities is always 1. Now in this case, a kernel is a mathematical function that returns a probability for a given value of a random variable. The kernel effectively smooths or interpolates the probabilities across a range of outcomes for a random variable such that the sum of probabilities always equals 1, a requirement of well-behaved probabilities. You also have a parameter called the smoothing parameter, which controls the scope or the window of observations from the data samples that contributes to estimating the probability for a given sample. As such, the kernel density estimation is sometimes referred to as your Poisson-Rosenbalt window. Now at the end you also have a basis function, which is a function which is chosen to control the contribution of samples in the data set towards estimating the probability of a new point. This is only done to make sure that you're not learning from a lot of noise and that you're not using a lot of the outliers. Again, let's see how we can perform non-parametric density estimation with the help of Python. So first we'll start by importing all the necessary modules along with the kernel density estimation, which can be imported from sklearn. Now let's create a bimodule distribution by combining two different samples, sample 1 and sample 2. Sample 1 has 300 examples with a mean of 20 and a standard deviation of 5, while sample 2 has 700 examples with a mean of 40 and a standard deviation of 5. We're then going to use hstack to merge both of them together to get a final sample. The means that we've chosen, which is 20 and 40, are chosen close together to ensure that the distributions overlap in the combined sample. So this is what our distribution is. Let's just plot it so you get a basic idea of what our graph looks like. So this is what our graph looks like. Now we already know that none of the various different probability distribution functions fit these graphs. So now we're going to perform non-parametric estimations. So to perform non-parametric estimations, we're going to use the scikit-learn machine learning library, which provides the kernel density class that implements kernel density estimation. First, the class is constructed with the desired bandwidth or window size of 2. And your basis function, which in this case is a Gaussian function. It's a good idea to at least test different configurations to your data. And in this case, we're only going to try a bandwidth of 2 and a Gaussian kernel. But usually there are multiple different kernels that you can that you can play around with, and you can also tweak your bandwidth to exactly fit the distribution that you have. Now let's run this. So now we've gotten our kernel density estimation. Now we can evaluate how well the density estimates matches our data by calculating probabilities for a range of observations and comparing shapes to the histogram, just like we did for the parametric case before. So again, we're gonna just calculate different probabilities using the kernel density function, and we're just gonna plot it on top of a histogram to see how well the kernel density function is estimating for our data. So these are the probabilities that we've gotten finally with the kernel density estimation, and now we're going to plot it on top of our histograms. So as you can see, it's almost a complete fit. It's just left out some of these outlier values, which again are ranging very high, but overall we have a pretty good fit. The only problem is it's not very smooth, and you can again try tweaking the bandwidth to different values. So let's just in this case try tweaking it to 3 and see how well it runs. Okay, so now we've gotten new probabilities, and let's run it on top of our bandwidth. So again, using a bandwidth of 3, you can see that we're fitting our data even better, and we're again ignoring a lot of the outliers which are out there. So this is going to give us a better estimation. So let's come to the first topic at hand. What is cumulative distribution function? The cumulative distribution function is used to describe the probability distribution of random variables. It can be used to describe the probability for a discrete, continuous, or mixed variable. Basically, the cumulative distribution function, or the CDF, of a random variable is just another method to describe the distribution of random variables. The only advantage of CDF is that it can be defined for any kind of a random variable, be it discrete, continuous, or mixed. Let's consider the curve which is shown in the figure. Over here, we can see that we're plotting a random variable x against its probability density function f of x. The graph is plotted between two variables a and b. And as we can see, the probability density function for them is a constant line which extends between these 2 points. The probability density function for the graph shown is nothing but the inverse of b minus a. Now we know why we need a cumulative distribution function. But what exactly is a cumulative distribution function? In layman terms, the cumulative distribution function can be defined as the probability that a random variable isn't greater than a given value. In a random trial, the outcome of a random variable will be less than or equal to any specified value of x as a function of x itself. When plotted in a graph in which the horizontal axis is a variable x and the vertical axis ranges from 0 to 1. The cumulative distribution function of a random variable that is evaluated at point C will take a value less than or equal to the value of C. In basic simple terms, if I'm evaluating the cumulative distribution function for a random point, let's say C over here, the cumulative distribution function that we get will always be a value which is lesser than this value. And why is that? To first understand this, you should know that the cumulative distribution function is calculated by finding the total probability density function for a given value. So consider the point C. When we draw a line from C, it intersects the curve at a certain point. To find the cumulative distribution function, you have to find the total of the probability density function up until this point. Or basically, you have to find the total of the probability density function for the rectangle which is formed between A and C. This can be done by summing up all of the probability density functions. But what happens when you have a large number of probability density function? In that case, all you have to do is integrate the probability density function over the limits or the points that it is being calculated between. Now let's get back to the problem at hand. Over here, you can see that we have this rectangle, and if we basically find the area of the curve which falls to the left-hand side of C, or the entire area of this rectangle, we will have the cumulative distribution function. Now for a rectangle, we all know that the area is nothing but the length into the breadth of the rectangle itself. So for this, we can see that the breadth of the rectangle is nothing but the distance between these 2 points, A and C, which is C subtracted from A. As for the height of the rectangle will be the point at which it intercepts the probability density function on the y-axis. For now, because we're not taking a certain value, let's just assume that value to be f of x itself. So at the end of the day, the probability of x being lesser than or equal to c, or the total probability of x being lesser than or equal to c, is nothing but c minus a into f of x. F of x is nothing but 1 divided by b minus a, as seen in the previous slide. Hence, the total probability or the cumulative distribution function for this graph becomes c minus a divided by b minus a. In general, the formula for cumulative distribution function is the cumulative or the total sum of the probability density function over the interval that it is being calculated over. To find the sum of smaller points, all you have to do is integrate that function. In this case, you'll be integrating the PDF. So the cumulative distribution function for a point x calculated over the probability density function p of x, which is lesser than the value of x, is nothing but the total sum of that entire probability density function. This can also be represented in the form of integration as an integration of the PDF. So we already know in the previous slide that the PDF was represented as f of x. So when we integrate f of x over the values that we have to calculate the cumulative distribution function, in this case between the values of a and b, that's when we get the total distribution function or the cumulative distribution function. Now, up until this point, we've talked about various different terms such as the probability density function and mixed variables, discrete variables, etc. But what do these terms mean? So first, let's take a look at the probability density function, a function which basically defines the relationship between a random variable and its probability is called a probability density function. It shows the relationship between a random variable and the probability such that on solving that function, we get the probability distribution for that random variable. A probability density function of a continuous random variable is a function whose value at any given point in the sample space can be interpreted as providing a relative likelihood that the value of the random variable would equal that sample. Next, we've also been talking about various types of random variables. One of them is a continuous random variable. So what is a continuous random variable? A continuous random variable is one which can take off infinite different values within a range of values. For example, rainfall in a month. Basically speaking, a continuous random variable is a random variable where the data can take infinitely many values. For example, the amount of rainfall received in a month. So let's say every day we get a certain amount of rainfall. So consider a day where we got a rainfall of 1.7 centimeters. In this case, the value 1.7 is not exact. In some areas, the rainfall might have been 1.68, while in others it might be 1.71 or 1.70001. In this case, the random variable can take on an infinite different amount of values which are falling within the same range of 1.7. This is called a continuous random value because there's no definitive value. When we plot a graph of all the different values that the variable can take, we get a continuous curve and not multiple different scattered data points. Another type of a random variable is a discrete random variable. A discrete random variable is the very opposite of a continuous random variable. This variable can take a definitive value within a certain range, and the values are usually within a certain distance or a certain range from each another. For example, consider the example of rolling a dice. When you roll a die, there are 6 definitive values that you can get: 1, 2, 3, 4, 5, and 6. When I roll a die and I say that I got the value of 2, I don't mean that I got 1.999 or 1.98 or 2.30. I mean that I got a definitive value of 2. In simple words, a discrete random variable is a variable whose value can be obtained by counting. It has a countable number of possible values, and the number of values that it can take are finite. Next, we come to mixed random variables. A random variable which can take on both discrete and continuous values is called a mixed random variable. The range of values which fall under this random variable are a mixture of discrete and continuous random variables. For example, take a look at this graph. Starting from 0 and extending up unto 0.5, this variable can take on infinite number of values between this range up until the value for y of 1 by 4. After this, it can take on only one value up until infinity, which is the constant value of 1. So in this region, as we can see, we can plot multiple different values for the same variable. So in this region, ranging from 0.5 on the x-axis and 1 by 4 on the y-axis, the random variable behaves as a continuous random variable. And after this point, ranging up unto infinity, it has a definitive value of 1, and hence it behaves as a discrete random variable. So this random variable can be said to be a mixed random variable. Now let's come up to the case study. In this case study, we will be working with the iris data set. The iris data set is a dataset which contains information about 3 different species of iris flowers. Each different species has 50 data points assigned to it, and the species included in the dataset are Iris setosa, Iris versicolor, and Iris virginica. For each flower, which constitutes a sample in our dataset, the length and the width of the sepals and petals is measured in centimeters, and these are the features that we'll be working with. Now, based on the combination of these 4 features, it becomes easy to classify the different flowers and to figure out which type of flower it is. It is usually used for classification models. So this is what your iris dataset looks like. It has 50 different rows or 50 different data points and 5 columns. The column values describe the sepal length, the sepal width, the petal length, and the petal width. It also has a separate column which details the species that each of these samples belong to. Now, depending on these 4 features, these are the features that we'll be working with, you're supposed to differentiate between the 3 different species of iris flowers. And as you can see, these features are quite little different from each other. For setosa, in fact, the sepal length ranges around the value of 5, whereas for virginica, it ranges more around the values of 6, 6.5. So based on these values, you can differentiate between these 3 different flowers. Now, before we start finding the CDF of this dataset, we first have to find the probability density function by using the different features and plotting the histograms. What is a histogram, first of all? A histogram is an accurate graphical representation of distribution of numerical data. It is an estimate of the probability distribution of a continuous variable. To construct a histogram, the first step is to bin the range of values, that is, divide the entire range of values into a series of intervals and then count how many values fall into each interval, and then plot those values in the form of rectangles. The bins are usually consecutive and non-overlapping intervals. Now, because our ultimate aim is to be able to correctly identify the species of iris flowers given its features, the first question that we have to ask ourselves is which among the 4 features is more useful than other variables in order to distinguish between the species of iris flowers. To answer this question, we first plot the probability density function with each feature as a variable on the x-axis and its histogram and corresponding kernel density plot on the y-axis. So as you can see, when we do that, these are the graphs that we get. The first density plot that we see here plots the sepal length values. So in this graph, as you can see, the sepal length for the 3 flowers, setosa, versicolor, and virginica, have a significant overlap between each other. A huge amount of the data for setosa, versicolor, and virginica overlap, and even their distribution graphs, as you can see here represented by these curves, have a major overlap. Versicolor is almost entirely taken over by setosa and virginica. Because of this, it wouldn't be a good idea to consider sepal length as a distinctive feature. Now, coming to sepal width, we can again see that there's a lot of overlap. A lot more than the overlap in sepal length itself. The spread of data is also very high. In sepal length, the data values were ranging from around 4 to around 8, which is around 4 data points. But over here, they range from 1.5 all the way to 5, which is a slightly higher value as compared to sepal length. So it becomes clear after seeing these graphs that we cannot distinguish between our flowers based on the sepal length and the sepal width itself. Next, we come on to the petal length graph. In the graph of petal length, as you can see, most of the different features are very distinctive from each other. There's not much overlap. The only overlap that you can see is between versicolor and virginica, and even that is significantly lower than that of the sepal length and sepal width. Furthermore, the PDF distributions over here also take on a bell shape. This kind of a probability distribution is called a normal distribution. So it will become easier to calculate the CDF for these, as the PDF for the petal length is very well defined. Now over here, as you can see, the setosa species is well separated from versicolor and virginica. The density of the petal width also looks pretty good. The overlap between these three flowers is very less, but again there's a little bit of overlap over here between setosa and versicolor, and obviously you can see the overlap here between versicolor and virginica. The PDF distribution is also not very well defined, and the normal curve is not smooth in this case. After looking at these graphs, it becomes evident that if we have to choose one feature for classification, we will be picking petal length to distinguish between the species. On the other hand, if you're going to select two features, then you might as well choose the petal length and the petal width, because these again have the least amount of overlap. Next, we have to find the CDF of our data set using the petal length feature. Again, this can be done by integrating over the PDF or by finding the cumulative sum of the PDF values. When we do this, the below graph is observed. The bell-shaped curves in this graph represent the probability density function, and the exponential curves represent the CDF. The CDF is nothing but the cumulative sum or the integration obtained after PDF. So this graph is obtained by adding every single value on our PDF graph. After looking at this, there are three main conclusions that can be drawn. From the graph that we see, it is evident that 100% of the setosa flower species have a petal length which is less than 1.9. How do we conclude this? As you can see, the CDF for the setosa flower falls just short of 2. We can take, after extending this value onto the x-axis, we get the value of 1.9. And anything below this value will fall under this curve and will definitely belong to the setosa species. Now coming on to versicolor and virginica. For versicolor, we can see that the range is from just after 3 to a little after 5. So we can say that petal length, which lies between 3.2 and 5, has a good chance of being versicolor. A chance of 95% in fact. Where is that 5% of uncertainty coming from? Again, as you can observe from this graph, there's a slight amount of virginica which overlaps with versicolor below the petal length of 5 centimeters. So because of this, we have a slight amount of uncertainty which comes into the equation. Now looking at the CDF for virginica, we can see that anything which is above 5 has a very good chance of being virginica. A 90% chance in fact. Where are we losing that 10% of accuracy? This is because some of the petal lengths of the virginica flower falls below 5. Also, there's a little bit of overlap above the value of 5 with versicolor. Because of this, the accuracy for virginica is further reduced. But at the end of the day, we can say with confidence that majority of the flowers which have petal lengths of greater than 5 have a 90% chance of being the virginica flower. Now let's take a look at how we can find the cumulative distribution function with the help of Python. So before we start with finding our CDF, we first have to import necessary modules into our Python program. The first module that we'll be working with is the Pandas library. The Pandas library is used to deal with data sets and modify them at ease. Next, we'll be working with two libraries which are used for plotting data and making graphs, Seaborn and Matplotlib. And finally, we'll also be working with the NumPy library, which is used to perform numerical computations on our data sets. So let's run this and import our libraries. Next, let's read the pre-downloaded data set into our program. This is done with the help of pandas.readcsv, which is going to read in a file which consists of comma-separated values and structure them in the form of a data set. So again, as you can see, this is our iris data set. It has 4 features: sepal length, sepal width, petal length, and petal width, which are used to differentiate between 3 different species of flowers. And it has 150 data points ranging from 0 to 149, with each flower being allocated 50 data points. Let's perform exploratory data analysis on our iris data set. First, Let's find the mean and the median of the iris dataset. Now for all the species, the respective values of mean and median of all the features present in the dataset are found to be pretty close. So as you can see here, sepal length for the 3 different species of flowers that we're going to be considering are pretty close to one another. The setosa has a mean sepal length of 5 and versicolor has a mean sepal length of 5.936. Virginica is even closer to versicolor with a mean sepal length of 6.5. And this is the trend that you can see in every single feature of our dataset. This indicates that the data is nearly symmetrically distributed with very less presence of outliers. Let's see how spread out our data is. Now let's see how spread out our data is, or how wide the range that it falls between is, by finding the standard deviation. Again, the standard deviation for various different features of our data set is found to be a very small value. All of the standard deviation values are comparable to each other for all the features. This means that our data isn't spread out very far and further shows how few outliers are present in our data. Now let's find the violent plots for the different features which are present in our data set. What is a violent plot? A violent plot shows the distribution of data across several levels of one or more categorical variables, in our case flower species. It plots the distribution such that they can be compared. The violent plot also shows the kernel density estimation of the underlying distribution. So once we're done plotting the violent plots, here are some conclusions that you can draw from them. The violent plot for the sepal length has a huge range of values. It ranges from 4 to 6, and also there are a lot more outliers present in this graph, as can be seen from how wide our violent plots are. The same can be said for sepal length. The range of values is even higher for all 3 different flowers, and the outliers are even more as they're wider also. Now coming to a petal length, we can see that the range of values that the various petal lengths fall under are very small. Further, the outliers are also not a lot, with setosa having the most outliers in this case. Versicolor and virginica have relatively fewer outliers. Another thing that will strike you over here for the petal length feature as compared to the sepal length and the sepal width feature is that in this case, there's a lot of overlap in the range where these values fall under. So as you can see for setosa, it overlaps significantly with a vast amount of the versicolor species data. And the same can be said for virginica. The same is also observed in the sepal width feature. But in petal length, all of the 3 different species have very distinctive ranges of values. Now coming to petal width, we can see that again the range of values is very short and there's not a lot of overlap, but it's significantly more as compared to that of the petal lengths. Also, the outliers for different species in petal width are greater than that compared to the petal length, as can be seen from how much more spread out this data is widthwise. Now let's also plot pair plots for our iris data set. A pair plot basically allows us to see both distributions of single variables and relationship between 2 variables. Now in our case, we have 4 features: sepal length, sepal width, petal length, and petal width in our iris dataset. In this case, we will have 6 unique plots which plot 2 different features against each other. The pairs are going to be sepal length versus sepal width, sepal length versus petal length, sepal length versus petal width, sepal width versus the petal length, the sepal width versus the petal width, and the petal length versus the petal width. Now along the diagonals, the plots basically showcase our histogram data These are univariate graphs which basically plot one single variable, like in this case sepal length, over here sepal width, over here petal length, and over here petal width. These histograms allow us to see the probability distribution of a single variable, while these scatter plots allow us to see the probability distribution of various features. Now again, looking at these various pair plots, we can come to different observations and conclusions. The first one being that petal length and petal width are the most useful features to identify various different flower types. As you can see here, the data falls between different ranges as compared to the other graphs, where there's a lot of overlap in the ranges that the data falls within. Over here in this graph, we've literally separated the Setosa species of flowers from the rest of the data, as it's all concentrated between a certain range and has no overlap in the x-axis or the y-axis with the rest of the data. For versicolor and virginica, the data overlap is very small, but we can find lines and if-else conditions to help build a simple model to differentiate between these two flower types. Also, there's not a lot of data overlap in the y-axis along with the x-axis for all of the three different flower species. The same cannot be said for any of the other plots that we've plotted. Over here in this graph, there's a lot of overlap between versicolor and virginica, and even Setosa has an overlap along the y-axis with the other two flowers. So using this, we can conclude that if you were to find the CDF using two different features, petal length and petal width would be the best two features to plot against one another to help classify our flowers. Now let's find the probability density function of our data. So again, we're going to be plotting the various different features in the form of histograms. And over here, as explained before, we see the least overlap in our petal length feature, and this is evidently the best feature that we can use to differentiate between our different flowers. Now let's find the CDF of our data by using the petal length feature. First, let's isolate the data that we have available on the different types of flowers into three different arrays and lists. Next, we know that the area under the plot of the PDF over an interval represents a probability of occurrence of random variable in that interval. In our analysis, petal length is the random variable. Mathematically speaking, CDF is an integral of PDF over the range of values that a continuous random variable takes. The CDF of a random variable evaluated at any point x gives the probability that a random variable will have a value less than or equal to x. So now we're going to be plotting the PDF and the CDF for the iris setosa, versicolor and virginica flowers for comparative analysis of the petal lengths on the same graph. To find the PDF, we first take the counts feature and the bin edges of a histogram. The counts feature is going to tell us how many values are present in every single histogram bar. To find the PDF, all we have to do is take every single data value and divide it by the total number of data values. This is going to give us a continuous graph of the PDF. The CDF is nothing but the cumulative summation of the PDF. This can be done by using the numpy.cumSum function on the PDF. Following this, all we do is plot the PDF and the CDF for various different flowers together on the same graph so that it becomes easier to compare them. Let's run this and see what we finally get. So finally, this is the graph that we get. As said again, we can see from this graph that 100% of the Setosa flower species fall below 1.9 and 95% of the versicolor flower species have petal lengths less than 5 but greater than 3.2, while about 10% of the virginica flowers will have petal lengths less than 5. So at the end of the day, we can say that the accuracy for finding our virginica flowers is going to be around 90%. Thus, by using the cumulative distribution plots, we get a better picture and robust understanding of distribution, leading to formation of simple univariate classification models.
What is a random experiment? Let's say that you roll a fair die and there are 6 possible outcomes. You can get a number from 1 to 6, but it is impossible to accurately predict the outcome. In mathematical theory, we consider only those experiments or observations for which we know the set of possible outcomes. Also, it is important that predicting a particular outcome is impossible. Such an experiment, where we know the set of all the possible results but find it impossible to predict any one particular execution, is a random experiment. Even if a random experiment is repeated under identical conditions, the outcomes or results will fluctuate randomly. Sample space and events. The sample space associated with a random experiment is the set of all the possible outcomes. Suppose you roll a die. So the sample space for a single throw of die will be 1, 2, 3, 4, 5 and 6. An event is a subset of the sample space, or you can say it is an outcome of a random experiment. Getting a heads when we toss a coin is an event. Now we will discuss about the multiplication rule in probability. The multiplication rule says that when two events are independent, the probability of both occurring simultaneously is given by probability of A intersection B will be equal to probability of A into probability of B. Let's understand this with the help of an example. If a coin is tossed twice, what will be the probability of getting two heads? So, in a single throw, the probability of getting a head is 1 by 2, that is 0.5. So, the probability of getting the two heads in both the coins will be 0.5 into 0.5, which is equal to 0.25. Let's look at another example. Suppose a coin is flipped and a die is rolled at the same time. So, what will be the probability of getting a head on the coin and 4 on the dice? So, the probability of getting a head, as discussed in the previous example, will be equal to 0.5. And the probability of getting a 4 on a single throw of die will be 1 by 6, since there are 6 sample space and 1 favorable outcome. So, the probability of getting a head on a coin and 4 on a die will be equal to 0.5 into 0.16, which will come out to be 0.80. Now let's move on to dependent events. Two events are said to be dependent if the outcome of the first event affects the outcome of the second event so that the probability is changed. Let's understand this with the help of an example. Suppose you have a deck of cards. The probability of drawing a card from a deck of cards is 1 by 52. Now, if you do not replace the card, the probability of drawing another card changes to 1 by 51. Another example of it can be parking at a no parking zone and getting a ticket. When you park at a no parking zone, the probability of getting a ticket increases. There is a multiplication rule associated with the dependent events. It says that when the two events are dependent, the probability of both occurring is given by this formula, which is P A intersection B is equal to probability of A into probability of B slash A. The slash reads the probability that B occurs given that A has already occurred. Let's look at an example. 3 cards are drawn from a deck and are not replaced. What will be the probability of getting 3 jacks? So in this case, the probability of getting a jack out of 52 cards in the first draw will be 4 by 52. Now after we have drawn the first card, there are 51 cards left. The probability of getting a jack in a second and third draw will be 3 by 51 and 2 by 50 respectively. So according to the formula, the probability of getting the 3 jacks will be P 0.76 into 0.058 into 0.04, which will come out to be 0.00176. Now that we know all the basic concepts in probability theory, we'll move on to conditional probability. Let A and B be the two events associated with a random experiment. Then the probability of A's occurrence under the condition that B has already occurred is called the conditional probability. It is denoted by PA slash B. Thus, we have PA slash B is equal to PA intersection B divided by P of B. PA slash B is read as probability of occurrence of A given that B has already occurred. Similarly, B slash A can be called as probability of occurrence of B given that A has already occurred. Let's look at an example. In the recent study, it was found that the probability of a randomly selected student is a girl is 0.51 and is a girl and plays sports is 0.10. So if the student is a female, what is the probability that she plays sports? In this case, the probability that a student is female and plays sport is 0.1 and the probability that a student is female is 0.51. So the probability that a student plays a sport given that she is a female will be 0.1 divided by 0.51, which will come out to be 0.1961. Now we are done with all the theories related to conditional probability. We'll move on to the demo in Excel. Let's look at this problem statement. Suppose there are a group of 100 buyers, out of which 70 purchased football and 40 purchased hockey. However, there are 20 buyers who purchased both football and hockey. Determine the probability that a randomly chosen buyer has purchased football, given that he also purchased hockey. So, this is a clear example of a conditional probability. Let's fill in this table. So, the probability of purchasing a football is 0.70 and that of hockey is 0.40. It is also given that there are 20 buyers who have purchased both football and hockey. So, 0.20 is the probability of PA intersection B. Now, if you remember the formula of the conditional probability, the A slash B is equal to PA intersection B divided by P of B, where PA intersection B is the probability of occurrence of both A and B. PB is the probability of occurrence of B. So we have all the values, let's fit in. So this will be equal to, this is cell E7. So we'll divide the cell E7 by cell E6, which will come out to be 0.5. So the probability that a randomly chosen buyer has purchased football, given that he also purchased hockey, is 0.5. What is probability? Probability is the branch of mathematics concerning numerical descriptions of how likely an event is to occur, or how likely it is that a proposition is true. The probability of an event is a number between 0 and 1, where roughly speaking, 0 indicates the impossibility of the event and 1 indicates certainty. The higher the probability of an event, the more likely is that the event will occur. Let's look at an example. A simple example is the tossing of a fair unbiased coin. Since the coin is fair, the outcome, that is heads and the tails, are both equally probable. The probability of heads equals the probability of the tails, and since no other outcomes are possible, the probability of either heads or tails can be said to be 1 by 2, which is also 50%. The probability of an event can be calculated by number of ways it can happen divided by the total number of outcomes. Now that we know about the probability, let's see if you can answer this question. What is the probability of drawing a jack and a queen consecutively from a deck of 52 cards without replacement? Here are your options. Post your answers in the comment section and let us know. Now let's move on to conditional probability. Let A and B be the two events associated with a random experiment. Then the probability of A's occurrence under the condition that B has already occurred and probability of B is not equal to 0 is called the conditional probability. It is denoted by PA slash B. Thus, we can say that PA slash B is equal to PA intersection B divided by P of B, where PA slash B is the probability of occurrence of A given that B has already occurred, and PB is the probability of occurrence of B. To know more about conditional probability, you can check our previous video which is specifically on conditional probability. Now let's move on to Bayes' theorem. The Bayes' theorem is a mathematical formula for calculating conditional probability in probability and statistics. In other words, it is used to figure out how likely an event is associated on its proximity to another. Bayes' law or Bayes' rule are the other names of this theorem. The formula for the Bayes' theorem can be written in a variety of ways. The most common version is P A slash B is equal to P of B slash A into P of A divided by P of B, where P A slash B is the conditional probability of event A occurring given that B is true, and P A and B of B are the probabilities of A and B occurring independently of one another. Let's solve a problem using the Bayes' theorem to understand it better. There is a cricket match tomorrow, and in recent years it has rained only 5 days each year. Unfortunately, the meteorologist has predicted the rain for tomorrow. Now, when it rains, the meteorologist correctly forecasts rain 90% of the time, and when it doesn't rain, he incorrectly forecasts rain 10% of the time. Let's calculate what is the probability that it will rain on the match day. So, the two sample spaces here are the events that it rains and it does not rain. Additionally, a third event is also there that meteorologist predicts the rain. So the notation for these events appear below.
event A1 is equal to it rains on the match day, event A2 that it does not rain on the match day, and event B is the meteorologist predicting the rain. Now in terms of probability, we know the following. Probability of A1 is 5 by 365 that it rains 5 days in a year, which will come out to be 0.0136. PA2 is 360 by 365, that is no days for 360 days in a year, which will come out to be 0.986. PB/A1 is 0.9. This signifies when it rains, the meteorologist predicts the rain 90% of the time. In a similar manner, PB/A2 is 0.1, that it does not rain, the meteorologist predicts the rain 10% of the time. Combining all this, we can calculate PA1/B, that is the probability it will rain on the given match day, given a forecast of rain by meteorologist. The answer can be determined using the Bayes theorem as shown below. So here's the formula of the Bayes theorem, and putting all the values that we have calculated in the previous slide, the probability that it will rain on the match day given a forecast of the rain by meteorologist will come out to be 0.111, which will be equal to 11.11%. So there's an 11% chance that it will rain on the match day given that the meteorologist has predicted the rain. I hope this example is clear to you.
So we're looking at our different systems, our different model. We have supervised versus unsupervised versus reinforcement learning. And with the supervised learning, that is probably the most controlled environment. We have a lot of different supervised learning models, whether it's linear regression, neural networks, there's all kinds of things in between, decision trees. The data provided is labeled data with output values specified. And this is important because when we talk about supervised learning, you already know the answer for all this information. You already know the picture has a motorcycle in it. So you're supervised learning. You already know that the outcome for tomorrow, for going back a week, you're looking at stock, you can already have like the graph of what the next day looks like. So you have an answer for it. And you have labeled data which is used, you have an external supervision, and solves problems by mapping labeled input to known output. So very controlled. Unsupervised learning, and unsupervised learning is really interesting because it's now taking part in many other models. They start with, you can actually insert an unsupervised learning model in almost either supervised or reinforcement learning as part of the system, which is really cool. Data provided is unlabeled data. The outputs are not specified. Machine makes its own predictions. Used to solve association with clustering problems. Unlabeled data is used. No supervision. Solves problems by understanding patterns and discovering output. So you can look at this and you can think some of these things go with each other. They belong together. So it's looking for what connects in different ways. And there's a lot of different algorithms that look at this. When you start getting into those, there's some really cool images that come up of what unsupervised learning is. How it can pick out, say, the area of a donut. One model will see the area of the donut, and the other one will divide it into 3 sections based on its location versus what's next to it. So there's a lot of stuff that goes in with unsupervised learning. And then we're looking at reinforcement learning. Probably the biggest industry in today's market in machine learning, or growing market. It's very infant stage as far as how it works and what it's going to be capable of. The machine learns from its environment using rewards and errors. Used to solve reward-based problems. No predefined data is used. No supervision. Follows trial and error problem solving approach. So again, we have a random, at first you start with a random, I try this, it works, and this is my reward. Doesn't work very well maybe, or maybe it doesn't even get you where you're trying to get it to do, and you get your reward back, and then it looks at that and says, well, let's try something else, and it starts to play with these different things, finding the best route. So let's take a look at important terms in today's reinforcement model. And this has become pretty standardized over the last few years, so these are really good to know. We have the agent. Agent is the model that is being trained via reinforcement learning. So this is your actual entity that has, however you're doing it, whether you're using a neural network or a Q table or whatever, combination thereof. This is the actual agent that you're using. This is the model. And you have your environment. The training situation that the model must optimize to is called its environment. And you can see here, I guess we have a robot who's trying to get a chest full of gems or whatever, and that's the output. And then you have your action. This is all possible steps that can be taken by the model, and it picks one action. And you can see here that it's picked 3 different routes to get to the chest of diamonds and gems. We have a state, the current position condition returned by the model. And you could look at this if you're playing like a video game. This is the screen you're looking at. So when you go back here, the environment is a whole game board. So if you're playing one of those Mobius games, you might have the whole game board going on, but then you have your current position. Where are you on that game board? What's around that? What's around you? If you were talking about a robot, the environment might be moving around the yard, where it is in the yard and what it can see, what input it has in that location. That would be the current position condition returned by the model. And then the reward. To help the model move in the right direction, it is rewarded. Points are given to it to appraise some kind of action. So, yeah, you did good, or if didn't do as good, trying to maximize the reward and have the best reward possible. And then policy. Policy determines how an agent will behave at any time. It acts as a mapping between action and present state. This is part of the model. What is your action that you're going to take? What's the policy you're using to have an output from your agent? One of the reasons they separate policy as its own entity is that you usually have a prediction of different options, and then the policy, well, how am I going to pick the best? Based on those predictions, I'm going to guess at different options, and we'll actually weigh those options in and find the best option we think will work. So it's a little tricky, but the policy thing is actually pretty cool how it works. Let's go ahead and take a look at a reinforcement learning example. And just in looking at this, we're going to take a look, consider what a dog that we want to train. So the dog would be like the agent. So you have your puppy or whatever. And then your environment is going to be the whole house or whatever it is where you're training them. And then you have an action. We want to teach the dog to fetch. So action equals fetching. And then we have a little biscuit, so we can get the dog to perform various actions by offering incentives such as a dog biscuit as a reward. The dog will follow a policy to maximize this reward, and hence will follow every command and might even learn new actions like begging by itself. So you have, so we start off with fetching. It goes, oh, I get a biscuit for that. It tries something else, and you get a handshake or begging or something like that. And it goes, oh, this is also reward based. And so it kind of explores things to find out what will bring it as biscuit. And that's very much like how a reinforced model goes. Is it looks for different rewards. How do I find? Can I try different things and find a reward that works? The dog also will want to run around and play and explore its environment. This quality of model is called exploration. So there's a little randomness going on in exploration. And it explores new parts of the house. Climbing on the sofa doesn't get a reward. In fact, it usually gets kicked off the sofa. So let's talk a little bit about Markov's decision process. Markov's decision process is a reinforcement learning policy used to map a current state to an action where the agent continuously interacts with the environment to produce new solutions and receive rewards. And you'll see here's all of our different vocabulary we just went over. We have a reward, our state, our agent, our environment, and our action. And so even though the environment kind of contains everything, that you really, when you're actually writing the program, your environment's going to put out a reward and state that goes into the agent. The agent then looks at this state, or it looks at the reward usually first, and it says, okay, I got rewarded for whatever I just did, or I didn't get rewarded. And then it looks at the state, and then it comes back, and if you remember from policy, the policy comes in, and then we have a reward. The policy is that part that's connected at the bottom. And so it looks at that policy and it says, hey, what's a good action that will probably be similar to what I did, or sometimes they're completely random, but what's a good action that's going to bring me a different reward? So taking the time to just understand these different pieces as they go is pretty important in most of the models today. And so a lot of them actually have templates based on this that you can pull in and start using. Pretty straightforward as far as once you start seeing how it works, you can see your environment says, hey, this is the agent did this. If you're a character in a game, this happened, and it shoots out a reward in a state. The agent looks at the reward, looks at the new state, and then takes a little guess and says, I'm going to try this action. And then that action goes back into the environment. It affects the environment. The environment then changes depending on what the action was. And then it has a new state and a new reward that goes back to the agent. So in the diagram shown, we need to find the shortest path between node A and D. Each path has a reward associated with it, and the path with a maximum reward is what we want to choose. The nodes A, B, C, D denote the nodes to travel from node A to B is an action. Reward is the cost of each path, and policy is each path taken. And you can see here A can go to B, or A can go to C right off the bat, or it can go right to D. And if you explored all three of these, you would find that A going to D was a 0 reward, A going to C and D would generate a different reward, or you could go A, C, B, D. There's a lot of options here. And so when we start looking at this diagram, you start to realize that even though today's reinforced learning models do really good at finding an answer, they end up trying almost all the different directions you see. And so they take up a lot of work or a lot of processing time for reinforcement learning. They're right now in their infant stage, and they're really good at solving simple problems. And we'll take a look at one of those in just a minute in a tic-tac-toe game. But you can see here, once it's gone through these and it's explored, it's going to find the A, C, D is the best reward. It gets a full 30 points for it. So let's go ahead and take a look at a reinforcement learning demo. In this demo, we're going to use reinforcement learning to make a tic-tac-toe game. You'll be playing this game against the machine learning model. And we'll go ahead, we're doing it in Python. So let's go ahead and go through, not always, I actually have a lot of Python tools. Let's go through Anaconda, which will open up a Jupyter notebook. It seems like a lot of steps, but it's worth it to keep all my stuff separate, and it also has a nice display when you're in the Jupyter notebook for doing Python. So here's our Anaconda navigator. I open up the notebook, which is going to take me to a web page. And I've gone in here and created a new Python folder. In this case, I've already done it and enabled it to change the name to tic-tac-toe. And then for this example, we're going to go ahead and import a couple things. We're going to import NumPy as NP. We'll go ahead and import pickle. NumPy, of course, is our number array. And then pickle is just a nice way sometimes for storing different information, different states that we're going to go through on here. And so we're going to create a class called state. We're going to start with that. And there's a lot of lines of code to this class that we're going to put in here. Don't let that scare you too much. There's not as much here. It looks like there's going to be a lot here, but there really is just a lot of setup going on in our class state. And so we have up here, we're going to initialize it. We have our board. It's a tic-tac-toe board, so we're only dealing with 9 spots on the board. We have player 1, player 2 is end. We're going to create a board hash. We'll look at that in just a minute. We're just going to store some information in there. Symbol of player equals 1. So there's a few things going on as far as the initialization. Then something simple, we're just going to get the hash of the board. We're going to get the information from the board on there, which is columns and rows. We want to know when a winner occurs. So if you get 3 in a row, that's what this whole section here is for. Let me go ahead and scroll up a little bit. And you can get a copy of this code if you send a note over to Simplilearn. We'll send you over this particular file, and you can play with it yourself and see how it's put together. I don't want to spend a huge amount of time on this because this is just some real general Python coding. But you can see here we're just going through all the rows, and you add them together, and if it equals 3 in a row, same thing with columns. Diagonal, so you got to check the diagonal. That's what all this stuff does here, is it just goes through the different areas. Actually, let me go ahead and put, there we go. And then it comes down here and we do our sum, and it says true, -3 just says did somebody win, or is it a tie? So you got to add up all the numbers on there anyway, just in case they're all filled up. And next we also need to know available positions. These are ones that no one's ever used before. This way when you try something, or the computer tries something, it's not going to give it an illegal move. That's what the available positions is doing. Then we want to update our state. And so you have your position going in. We're just sending in the position that you just chose. And you'll see there's a little user interface we put in there. You can pick the row and column in there. And again, I mean, this is a lot of code. So really it's kind of a thing you'd want to go through and play with a little bit and just read through it, get a copy of it. A great way to understand how this works. And here is a given reward. So we're going to give a reward, result equals self winner. This is one of the hearts of what's going on here, is we have a result self.winner. So if there's a winner, then we have a result. If the result equals 1, here's our feedback. If it doesn't equal 1, then it gets a 0. So it only gets a reward in this particular case if it wins. And that's important to know because different systems of reinforced learning do rewarding a lot differently depending on what you're trying to do. This is a very simple example with a 3x3 board. Imagine if you're playing a video game, certainly you only have so many actions, but your environment is huge. You have a lot going on in the environment. And suddenly a reward system like this is going to be just, it's going to have to change a little bit. It's going to have different rewards and different setup. And there's all kinds of advanced ways to do that as far as weighing, you add weights to it. And so they can add the weights up depending on where the reward comes in. So it might be that you actually get a reward. In this case, you get the reward at the end of the game. And I'm spending just a little bit of time on this because this is an important thing to note. But there's different ways to add up those rewards. It might have, like if you take a certain path, the first reward is going to be weighed a little bit less than the last reward because the last reward is actually winning the game or scoring or whatever it is. So this reward system gets really complicated in some of the more advanced setups. In this case, though, you can see right here that they give a 0.1 and a 0.5 reward just for picking the right value and something that's actually valid instead of picking an invalid value. So rewards, again, that's like key. It's huge. How do you feed the rewards back in? Then we have a board reset. That's pretty straightforward. It just goes back and resets the board to the beginning because it's going to try out all these different things while it's learning. It's going to do it by trial and error, so you have to keep resetting it. And then, of course, there's the play. We want to go ahead and play rounds equals 100. Depends on what you want to do on here. You can set this different. You can obviously set that to higher level. But this is just going to go through, and you'll see in here that we have player 1 and player 2. This is the computer playing itself. One of the more powerful ways to learn to play a game, or even learn something that isn't a game, is to have two of these models that are basically trying to beat each other. And so they keep explore new things. This one works for this one, so this one tries new things. It beats this. We've seen this in chess. I think was a big one where they had the two players in chess with reinforcement learning. It was one of the ways they trained one of the top computer chess playing algorithms. So this is just what this is. It's going to choose an action. It's going to try something, and the more it tries stuff, the more we're going to record the hash. We actually have a board hash where you self get the hash set up on here where it stores all the information. And then once you get to a win, one of them wins, it gets the reward. Then we go back and reset and try again. And then kind of the fun part we actually get down here is we're going to play with a human. So we'll get a chance to come in here and see what that looks like when you put your own information in. And then it just comes in here and does the same thing it did above. It gives it a reward for its things, or sees if it wins or ties, looks at available positions, all that kind of fun stuff. And then finally we want to show the board. So it's going to print the board out each time. Really, as an integration, is not that exciting. What's exciting in here is, one, looking at this reward system. Whoops, play one more up. The reward system is really the heart of this. How do you reward the different setup? And the other one is when it's playing, it's got to take an action. And so what it chooses for an action is also the heart of reinforcement learning. How do we choose that action? And those are really key to right now where reinforcement learning is in today's technology, is figuring this out. How do we reward it, and how do we guess the next best action? So we have our environment, and you can see the environment is or the state, which is kind of like what's going on. We're going to return the state depending on what happens. And we want to go ahead and create our agent, in this case our player. So each one is, let me go and grab that. And so we look at a class player. This is where a lot of the magic is really going on, is how is this player figuring out how to maneuver around the board, and then the board of course returns a state that it can look at and a reward. So we want to take a look at this. We have name, self-state. This is class player. And when we say class player, we're not talking about a human player. We're talking about just the computer players. And this is kind of interesting. So remember I told you, depending on what you're doing, there's going to be a decay gamma, explore rate. These are what I'm talking about, is how do we train it? As you try different moves, it gets to the end. The first move is important, but it's not as important as the last one. And so you could say that the last one has the heaviest weight, and then as you get there, the first one, let's see, the first move gives you a 5 reward, the second gives you a 2 reward, and the third one gives you a 10 reward, because that's the final ending. You got it. The 10's going to count more than the first step. And here's our, we're going to get the board information coming in, and then choose an action. This was the second part that I was talking about that was so important. So once you have your training going on, we have to do a little randomness, and you can see right here is our NP random uniform. So it's picking out a random number. Take a random action. This is going to just pick which row and which column it is. And so choosing the action, this one you can see we're just doing random states, choice, length of positions, action position, and then it skips in there and takes a look at the board for P in positions. And it's actually storing the different boards each time you go through, so it has a record of what it did, so it can properly weigh the values. And this simply just appends a hash state. What's the last state? Append it to the to our states on here. Here's our feedback reward. So the reward comes in, and it's going to take a look at this and say, is it none? What is the reward? And here is that formula. Remember I was telling you about up here that was important because it has decay gamma times the reward. This is where, as it goes through each step, and this is really important. This is kind of the heart of this, of what I was talking about earlier. You have step 1, and this might have a reward of 2. You have step 2. I probably should have done ABC. This has a step 3, step 4, and so on until you get to step N. And this might have a reward of 10. So reward of 10. We're going to add that, but we're not adding, let's say this one right here, let's say this reward here right before 10 was, let's say it's also 10. That just makes the math easy. So we had 10 and 10. We had 10, this is 10 and 10n, whatever it is, but it's 0.9. So instead of putting a full 10 here, we only do 9. That's 0.9 times 10. And so this formula, as far as the decay times the reward minus the cell state value, it basically adds in, it says here's 1, or here's 2, I'm sorry, I should have done this ABC, it would have been easier. So the first move goes in here and it puts 2 in here. Then we have our self setup on here. You can see how this gets pretty complicated in the math, but this is really the key, is how do we train our states? And we want the final state, the win, to get the most points. If you win, you get most points. And the first step gets the least amount of points. So you're really training this almost in reverse. You're training it from the last place where you have, like it says, okay, this is now where I need to sum up my rewards, and I want to sum them up going in reverse, and I want to find the answer in reverse. Kind of an interesting play on the mind when you're trying to figure this stuff out. And of course we want to go ahead and reset the board down here and save the policy, load policy. These are the different things that are going in between the agent and the state to figure out what's going on. Let's go ahead and load that up. And then finally we want to go ahead and create a human player. And the human player is going to be a little different in that you choose an action, row and column. Here's your action. If action in positions, meaning positions that are available, you return the action. If not, it just keeps asking you until you get an action that actually works. And then we're going to go ahead and append to the hash state, which we don't need to worry about because it returns the action up here. And feed forward. Again, this is because it's a human. At the end of the game, backpropagate and update state values. This part isn't being done because it's not programming the model. The model is getting its own rewards. So we've gone ahead and loaded this in here. So here's all our pieces, and the first thing we want to do is set up P1 player 1, P2 player 2, and then we're going to send our players to our state. So now it has P1, P2, and it's going to play, 50,000 rounds. Now we can probably do a lot less than this, and it's not going to get the full results. In fact, you know what? Let's go ahead and just do 5, just to play with it, because I want to show you something here. Oops, somewhere in there I forgot to load something. There we go. I must have forgot to run this. Run. Oops, forgot a reference there for the board, rows and columns, 3 by 3. There's actually in the state, it references that. We can just tack it on the end. It was supposed to be at the beginning. So now I've only set this up with, let's see, where are we going here? I've only set this up to train 5 times. And the reason I did that is we're going to come in and actually play it, and then I'm going to change that, and we can see how it differs on there. There we go, and it didn't even make it through a run, and we're going to go ahead and save the policy. So now we have our player 1 and our player 2 policy. The way we set it up, it has 2 separate policies loaded up in there. And then we're going to come in here and we're going to do player 1 is going to be the computer, experience rate 0, load policy 1, human player human, and we're going to go ahead and play this. Now remember, I only went through it just 1 round of training, in fact minimal training, and so it puts an X there, and I'm going to go ahead and do row 0, column 1. And you can see this is very basic on here, and so I put in my 0, and then I'm going to go 0, block it, 0, 0, and you can see right here it let me win. Just like that, I was able to win. 0, 2, and woo, human wins. So I only trained it 5 times. We're going to run this again, and this time, instead of 5, let's do 5,000 or 50,000. I think that's what the guys in the back had. And this takes a while to train it. This is where reinforcement learning really falls apart. Look how simple this game is. We're talking about a 3 by 3 set of columns. And so for me to train it on this, I could do a Q table which would go much quicker. You could build a quick Q table with almost all the different options on there, and you would probably get the same result much quicker. We're just using this as an example. So when we look at reinforcement learning, you need to be very careful what you apply it to. It sounds like a good deal until you do like a large neural network where you're doing, you set the neural network to a learning increment of 1, so every time it goes through it learns, and then you do your action, so you pick from the learning setup, and you actually try actions on the learning setup until you get what you think is going to be the best action. So you actually feed what you think is right back through the neural network. There's a whole layer there, which is really fun to play with. And then it has an output. Well, think of all those processes. I mean, that is just a huge amount of work it's going to do. Let's go ahead and skip ahead here. Give it a moment. It's going to take a minute or two to go ahead and run. Now, to train it, we went ahead and let it run, and it took a while. This took, I got a pretty powerful processor, and it took about 5 minutes plus to run it. And we'll go ahead and run our player setup on here. Oops, it brought in the last, whoops, it brought in the last round. So give me just a moment to redo the policy save. There we go. I forgot to save the policy back in there. And then go ahead and run our player again. So we've saved the policy, and then we want to go ahead and load the policy for P1 as a computer. And we can see the computer's gone in the bottom right corner. I'm going to go ahead and go 1, 1, which is the center. And it's gone right up the top, and if you have ever played tic-tac-toe, you know the computer has me. But we'll go ahead and play it out. Row 0, column 2. There it is, and then it's gone here, and so I'm going to go ahead and go row 0, 1, 2, no, 0, 1, there we go, and column 0. That's where I wanted. Oh, and it says, okay, your action, there we go, boom. So you can see here, we've got a, didn't catch the win on this, it said tie. Kind of funny that it didn't catch the win on there. But if we play this a bunch of times, you'll find that it's going to win more and more. The more we train it, the more the reinforcement happens. This lengthy training process is really the stopper on reinforcement learning. As this changes, reinforcement learning will be one of the more powerful packages evolving over the next decade or two. In fact, I would even go as far as to say it is the most important machine learning tool and artificial intelligence tool out there, as it learns not only a simple tic-tac-toe board, but we start learning environments. And the environment would be like in language. If you're translating a language or something from one language to the other, so much of it is lost if you don't know the context it's in, what's the environments it's in. And so being able to attach environment and context and all those things together is going to require reinforcement learning to do. So again, if you want to get a copy of the tic-tac-toe board, it's kind of fun to play with. Run it, you can test it out, you can do test it for different values. You can switch from P1 computer where we loaded the policy 1 to load the policy 2 and just see how it varies. There's all kinds of things you can do on there.
Supervised learning uses labeled data to train machine learning models. Labeled data means that the output is already known to you. The model just needs to map the inputs to the outputs. An example of supervised learning can be to train a machine that identifies the image of an animal. Below you can see we have our trained model that identifies the picture of a cat. Unsupervised learning uses unlabeled data to train machines. Unlabeled data means there is no fixed output variable. The model learns from the data, discovers patterns and features in the data, and returns the output. Here is an example of an unsupervised learning technique that uses the images of vehicles to classify if it's a bus or a truck. So the model learns by identifying the parts of a vehicle, such as the length and width of the vehicle, the front and rear end covers, roof hoods, the types of wheels used, etc. Based on these features, the model classifies if the vehicle is a bus or a truck. Reinforcement learning trains a machine to take suitable actions and maximize reward in a particular situation. It uses an agent and an environment to produce actions and rewards. The agent has a start and an end state, but there might be different paths for reaching the end state, like a maze. In this learning technique, there is no predefined target variable. An example of reinforcement learning is to train a machine that can identify the shape of an object given a list of different objects such as square, triangle, rectangle, or a circle. In the example shown, the model tries to predict the shape of the object, which is a square here. Now, let's look at the different machine learning algorithms that come under these learning techniques. Some of the commonly used supervised learning algorithms are linear regression, logistic regression, support vector machines, k-nearest neighbors, decision tree, random forest, and naive Bayes. Examples of unsupervised learning algorithms are k-means clustering, hierarchical clustering, DB-scan, principal component analysis, and others. Choosing the right algorithm depends on the type of problem you are trying to solve. Some of the important reinforcement learning algorithms are Q-learning, Monte Carlo, SARSA, and Deep Q network. Now let's look at the approach in which these machine learning techniques work. So supervised learning takes labeled inputs and maps it to known outputs, which means you already know the target variable. Unsupervised learning finds patterns and understands the trends in the data to discover the output. So the model tries to label the data based on the features of the input data. While reinforcement learning follows trial and error method to get the desired solution. After accomplishing a task, the agent receives an award. An example could be to train a dog to catch the ball. If the dog learns to catch a ball, you give it a reward such as a biscuit. Now, let's discuss the training process for each of these learning methods. So supervised learning methods need external supervision to train machine learning models, and hence the name supervised. They need guidance and additional information to return the result. Unsupervised learning techniques do not need any supervision to train models. They learn on their own and predict the output. Similarly, reinforcement learning methods do not need any supervision to train machine learning models. And with that, let's focus on the types of problems that can be solved using these three types of machine learning techniques. So supervised learning is generally used for classification and regression problems. We'll see the examples in the next slide. And unsupervised learning is used for clustering and association problems, while reinforcement learning is reward based, so for every task or for every step completed, there will be a reward received by the agent. And if the task is not achieved correctly, there will be some penalty used. Now, let's look at a few applications of supervised, unsupervised, and reinforcement learning. As we saw earlier, supervised learning are used to solve classification and regression problems. For example, you can predict the weather for a particular day based on humidity, precipitation, wind speed, and pressure values. You can use supervised learning algorithms to forecast sales for the next month or the next quarter for different products. Similarly, you can use it for stock price analysis or identifying if a cancer cell is malignant or benign. Now, talking about the applications of unsupervised learning, we have customer segmentation. So based on customer behavior, likes, dislikes, and interests, you can segment and cluster similar customers into a group.
What is NLP? Natural language processing, NLP, constitutes a sector of artificial intelligence focused on textual and speech data. This technology enables machines to comprehend, scrutinize, and handle human language, extract valuable information in the process. Now, let's understand who is an NLP engineer. A natural language processing engineer, or NLP engineer, is a professional responsible for crafting and constructing computer systems that can process, assess, and produce human-like language. NLP branches out into numerous captivating domains, including semantic analysis, sentiment analysis, face recognition, machine translation, and speech recognition. Now, the reach of NLP extends across a diverse spectrum of applications, notably featuring virtual assistants, chatbots, sentiment analysis, customer service interactions, and language translation. The task of NLP engineers involves erecting these innovative applications and seamlessly embedding them into existing frameworks. Now, the average salary of an NLP engineer is 10 lakhs per annum in India. In US, the annual wage of NLP engineers is about $120,000 per annum. Now, let us understand the skills required to become an NLP engineer. Becoming a natural language processing engineer entails the acquisition of a diverse set of skills and knowledge. Some of these encompass the first one as Python programming, mastery of at least one programming language such as Python, Java, or C++, coupled with solid grasp of data structures, algorithms, and the principles of software engineering is important. Next is grasp of machine learning. Building a strong foundation in machine learning algorithms encompassing both supervised and unsupervised learning is important. Familiarity with advanced techniques like convolutional neural networks, or also known as CNNs, and recurrent neural networks, also known as RNNs, is vital. The third one being NLP techniques. Cultivating a deep understanding of NLP techniques, which encompasses facets like text preprocessing, syntactic and semantic analysis, and the intricate domain of sentiment analysis. Fourth one is NLP libraries and frameworks. Navigate easily through the NLP libraries and frameworks such as the Natural Language Toolkit or NLTK, Spacey, Stanford Core NLP, and Genesim, harnessing their capabilities to streamline your NLP endeavors. The fifth one is data science acumen. Developing a sound grasp of data science principles encompassing facets such as data visualization, statistical analysis, and the art of data manipulation is important. Armed with this multifaceted skill set, you will be primed to embark on a journey as an accomplished NLP engineer who is ready to navigate the complexities of natural language and contribute to the exciting world of NLP innovations. Now, the important point of today's session, that is the roadmap to become an NLP engineer. Here is a comprehensive professional strategy or trajectory for those aspiring to become adept natural language processing engineers. The first one is educational foundation. Embark on your journey by pursuing a degree in a pertinent field such as computer science, linguistics, or artificial intelligence. Many accomplished NLP engineers hold advanced degrees, either a master's or a PhD in these domains. Next one is internship or entry-level ventures. Consider immersing yourself in practical experience through internships or entry-level positions within the industry. These opportunities not only equip you with hands-on expertise, but also aid in constructing a robust portfolio. Moreover, they facilitate the establishment of valuable professional connections. Next is skills and knowledge acquisition. Develop a comprehensive grasp of the essential proficiencies requisites for an NLP engineer. This encompasses programming prowess, machine learning acumen, NLP techniques, familiarity with pertinent libraries and frameworks, proficiency in data science, and the owning of communication and teamwork competencies. Next is portfolio development. Curate a diverse portfolio teeming with projects that illuminate your capabilities and expertise. Projects like a sophisticated chatbot, a sentiment analysis tool, or a language model can substantiate your aptitude for solving real-world NLP challenges and validate your skill set for potential employers. Now, the next one, networking endeavors. Engage in conferences, meetups, and industry events to forge connections with fellow NLP professionals. This affords opportunities to remain abreast of the latest developments in the field and exposes you to an array of NLP applications. Next is specialization consideration. Ponder the prospect of specializing in a specific NLP realm, be it machine translation, speech recognition, or conversational agents. This specialization not only differentiates you in the job market, but also enables you to attain expertise within a particular niche. In summation, the path towards becoming an NLP engineer entails a fusion of educational attainment, hands-on experience, and the mastery of an eclectic array of skills and knowledge domains. Now, we will discuss the applications of NLP. Natural language processing boasts an extensive array of applications extending well beyond the following 10 examples. We have chatbots, intelligent replies on chatbot platform, which is email or LinkedIn, virtual assistants in customer care services, spelling check, and grammar correction.
In India, the salary ranges from 2.5 million rupees to 5 million rupees. However, in US, the salary ranges between $60,000 to $90,000 per year. Entry-level NLP engineers typically have background in computer science engineering or a related field and have some experience with NLP, but may not have yet worked on large-scale enterprise projects. Moving towards mid-level NLP engineers. These engineers earn 5 million to 8 million rupees per year. However, in United States, they earn between $90,000 to $120,000 per year. Mid-level NLP engineers have few years of experience working on NLP projects and are typically comfortable working on both technical and business-related aspects of NLP projects.
They may have some leadership responsibilities and are often responsible for ensuring that NLP projects are completed on time and to spec. Next, we have is senior level NLP engineers. These engineers earn up to 8 million rupees to 15 million rupees in India per year. However, in United States, they earn between $120,000 to $165,000 per year. Senior level NLP engineers have extensive experience working on enterprise level NLP projects and are often considered authorities in NLP technologies, methods, and tools. They may serve as subject matter experts, lead teams of engineers and other NLP professionals, and be responsible for ensuring the long term success of NLP projects.
So let's start with the data science interview questions and answers. And the number one problem we would be facing is real world problem solving. And the question one is handling missing data in predictive modeling. So imagine you have given a data set where 30% of the data for a key predictive variable is missing. This variable is crucial for a predictive model. How would you handle this situation to ensure the integrity and performance of your model? And please describe your approach step by step. So starting with the answer, you can start with handling missing data set is a common challenge in data science, and it's important to address it carefully to maintain the accuracy of your model. And here's how you could approach this situation. The number one point could be identify the missing data. So first you need to understand where the missing values are in your data set. You can do this by using a simple code in Python with libraries like Pandas. For example, you can use the data.isNull.sum function that will show you the count of missing values in each column. Then you can analyze the pattern, determine if there's a pattern to the missing data. Is it random or is it missing for a reason? This can affect your approach. If the data is missing at random, the methods you use might be different than if the data is missing systematically. So choosing a method for imputation. Let's see the next method, that is choosing a method for imputation. So if the missing data is numeric, you might replace missing values with the mean or median of that column. This is simple and effective, but can be used primarily when the data is missing completely at random. Then comes model-based imputation. Sometimes you can use other variables in the data to predict missing values using a regression model. This can be more accurate, but is also more complex. Then we'll use the k-nearest neighbors KN algorithm. But before that, we have a code snippet here that could be used for the implementation of imputation. You could use Python or R. And now moving on, we'll see the k-nearest neighbors algorithm. So this method predicts the missing values based on how closely related the data points are to each other. So after imputation, it's crucial to check how your changes have affected the overall dataset and model performance. Sometimes filling in too many missing values can introduce bias. And then we have visualization. To help understand before and after the imputation, you could visualize the distribution of the variable using histograms or box plots. This helps in seeing how the imputation has changed the statistical properties of the data. And by following these steps, you can handle missing data thoughtfully and maintain the integrity of your predictive model. Now moving to the question number 2, that is based on evaluating model overfitting. So the question is, you have developed a predictive model, but you suspect it might be overfitting the training data. How would you test and address the issue? Please explain your steps and the techniques you would use. So you could start the answer by explaining what is overfitting. So overfitting is a common problem where model performs well on training data but poorly on unseen data, indicating it's too closely fitted to the training data's specific details and noise. So now we'll see a step-by-step guide on how to address this. The number one step is cross-validation. So one effective way to test for overfitting is by using cross-validation technique. Cross-validation involves splitting your training data into multiple smaller sets, that is faults, and then training a model on some of these sets and validating it on the others. So this helps you understand if the model's good performance is consistent across different subsets of data. For example, in Python, you can use the cross_value_score function from sklearn.model_selection. So this is the code, and this is the code snippet of Python that you can use for the cross-validation. And here we are importing from sklearn, that is the module, and we are importing cross_val_score. And here we have used the cross_val_score function, and then we have printed the average cross-validation score. And the next step we will do is running cross-validation model. So this is your predictive model that you have already built using scikit-learn. And here's the X train. These are the X input features of your training data, and Y train, these are the output labels of training data. So we are running cross validation model here. This is your predictive model that you have already built using scikit-learn. So X train here, that means these are the input features of your training data. And Y train here means these are the output labels of training data. And CV equal to 5. This parameter tells the function to split the data into 5 parts, that is false, and the model is trained on 4 of these parts, and the remaining part is used for testing. So this process rotates until each part has been used for testing once. And the printing results, that is score.mean. So this calculates the average of the scores obtained from each cross validation fold. This average score gives you an idea of how well your model is likely to perform on unseen data. A consistent score across different folds suggests your model is generalizing well rather than overfitting to the training data. So now moving to the next point, that is training versus validation error. So plot the training and validation errors as a function of training epochs or complexity of the model. A model that overfits will show a low error on training data and a high error on validation data as it trains further. Then we have pruning the model. If you confirm that the model is overfitting, consider simplifying it. This might mean reducing the number of parameters by selecting fewer features, using regularization techniques like lasso or ridge, or choosing a less complex model. After this step, we will move to regularization technique step. So these techniques add a penalty to the loss function used to train the model, which can discourage complex models that overfit. Then we have common methods that include L1, that is lasso, and L2, ridge regularization. And here's how you can add L2 regularization in Python. So this is the code snippet here. And what we have done here is we are creating the ridge model, and we have applied alpha equal to 1.0. So this parameter controls the strength of the regularization. A higher alpha value increases the regularization effect, which helps reduce model complexity and combat overfitting. The alpha value can be tuned to find the optimal balance between bias and variance. And now coming for the fitting the model. So model.fit, and in that we have X train and Y train that trains the ridge model on the training data. It adjusts the weight of the feature in X train to predict the Y train while also considering the regularization term. This helps prevent the model from fitting too closely to the noisy aspects of the training data. And then we are re-evaluating the model. After making adjustments, it's important to re-evaluate the model again using the same cross-validation technique to see if the issue of overfitting has improved. And then we have visualization. To help illustrate overfitting, you could create a plot showing the training and validation errors over the number of epochs or model complexity. So by using these techniques, you can identify if a model is overfitting and take steps to correct it, ensuring it performs well not only on the training data but also on new unseen data. So now moving to the next question, that is question number 3, and it is based on real-time data stream processing. And the question is, you are tasked with building a model to predict stock prices in real time. The data comes in every second and you need to update your predictions accordingly. Describe how you would set up your system to handle this type of data effectively, and what tools and techniques would you use and why. So you could start answering this question with handling real-time data. So handling real-time data, especially for something as volatile and fast-paced as stock prices, requires a robust system that can process and analyze data quickly and accurately. So here's how you could approach this. We will set up such a system and we will have some steps. So starting with the steps. So the first step is choosing the right tools. The right tool would be Apache Kafka. So this is a popular tool for handling real-time data that streams because it allows you to publish and subscribe to streams of records, that is data. And it can handle high throughput with low latency. Kafka acts as a buffer and manages the flow of data, ensuring that your system doesn't get overwhelmed. And you can also use Apache Spark. Especially Spark streaming is excellent for processing the data. It can process data in real time and perform complex operations like windowing, grouping data into chunks of a specified time period, and aggregating, that is summarizing data. So you can modify it and perform the predicting of stock prices. And then the step is data processing pipeline. And the first step comes here is ingestion. Data first enters the system, typically through Kafka, which collects data sent from the stock market. And then we do the processing. So Spark streaming takes over here. Here you can apply transformations and run your predictive models on the data. For example, you might calculate moving averages or other indicators that feed into your stock price prediction model. And then comes the output. Finally, the predictions are outputted. This could be to a dashboard for traders, an automated trading system, or even stored for further analysis. And then we develop the model. Now comes the model development. You would likely use a machine learning model that can update quickly and incorporate new data as it arrives. Models such as ARIMA for time series forecasting or more complex machine learning models like recurrent neural networks (RNNs) can be suitable. The model should be retrained or fine-tuned periodically with new data to ensure it stays accurate. Now we'll come to scalability and reliability. So ensure your system can scale as data volume increases. This might mean adding more servers or optimizing your data processing code. Implement monitoring to catch any issues early, like delays in data processing or model performance drops. And now we'll see the step, that is visualization and monitoring. Consider setting up a real-time dashboard that shows key metrics like prediction accuracy and processing time. This helps in quickly spotting when something goes wrong. By setting up your system with these tools and strategies, you can effectively handle the challenge of predicting stock prices in real time. So now we will move to the next question, that is question number 4, and this will be based on scalable data analytics. So we have covered 2 questions that were a bit code-based questions, and now we'll see other questions that would be based on scalable data analytics, or they might be on different areas. And with the 13th question, we will start again with the coding ones. So moving with the question 4, that is based on scalable data analytics. And the question is, given a scenario where your organization suddenly needs to scale its data analysis capabilities due to an influx of data that would be 10 times the normal volume, how would you handle this situation to ensure your data analytics processes remain efficient and accurate? What technologies would you consider and what steps would you take? So you can start answering this question with, handling a sudden increase in data volume requires a strategic approach to scaling your analytics infrastructure without compromising on efficiency or accuracy. So we'll see some steps from that you could effectively manage this scenario. That you would start answering the interviewer that we can start by evaluating the current infrastructure's ability to handle increased loads. This includes assessing your databases, servers, and analytical tools to identify potential bottlenecks or limitations. Then you could move to next step, that would be choosing scalable technologies. To manage the increased data volume, consider leveraging cloud-based solutions such as Amazon Web Services, Google Cloud Platform, or Microsoft Azure. These platforms offer scalable resources which can be adjusted accordingly to the data load, ensuring you only pay for what you use. Integrate big data technologies like Apache Hadoop for distributed storage and Apache Spark for fast data processing. These tools are designed to handle massive volumes of data efficiently and can scale up to meet standard increased demands. Now we'll move to the next step, that would be optimizing data processing. So implement data partitioning and indexing strategies to improve the efficiency of data queries. This will help in managing large data sets by breaking them into smaller, manageable chunks and speeding up search operations. And use real-time data processing frameworks like Apache Kafka or Apache Flink, which can handle high throughput and provide timely insights from large data streams. And the next step would be automation and monitoring. Automate routine data processing tasks to reduce the manual effort and speed up the analysis. This can be done through scripting or using workflow automation tools. Set up comprehensive monitoring systems to track the performance of your data processes. Tools like Prometheus for system monitoring and Grafana for analytics and monitoring dashboards are useful here. They help ensure that the system is running smoothly and alert you to potential issues before they become critical. And the next step will be regular evaluation and scaling. Continuously evaluate the performance of analytics infrastructure. As your data grows, keep adjusting and scaling your resources to maintain optimal performance. Plan for periodic reviews of your technology stack and infrastructure to ensure they remain aligned with your data needs and organizational goals. By following these steps, you can ensure that your data analytics processes are prepared to handle sudden surges in data volume effectively, maintaining the integrity and speed of insights. So this was all for the question 4. Now moving to the question 5, and this is based on integrating machine learning models into production. And the question is, you have developed a machine learning model that performs well in testing environment. Now you need to integrate it into your production environment where it will be used in real-time applications. What steps would you take to ensure the successful deployment and operations of the model in production? So we'll start answering this by successfully deploying a machine learning model into production involves several critical steps to ensure it performs as well in real-time operations as it does in testing. So you would have a clear pathway to make the interviewer understand. We will start with the pathway with the first step, that would be model validation. So before moving anything into production, revalidate your model's performance using a separate validation dataset. This helps confirm that the model generalizes well to new, unseen data. The next step will be preparing the production environment. Ensure that the production environment is ready to handle the model. This includes setting up the necessary hardware and software, ensuring that it can handle the expected load, and that all dependencies are correctly installed and configured. Then the next step comes, that is model wrapping. Wrap your model in an API, that is application programming interface, making it accessible to other parts of your software infrastructure. Frameworks like Flask for Python can be used to create a simple web server that listens for data inputs and provides model outputs. Then comes the next step, that is deployment strategies. Consider using containerization tools like Docker, which can help encapsulate your model and its environment, ensuring that it works uniformly across different development and production settings. And then we'll use deployment strategies like blue-green deployment or canary releases to minimize downtime and reduce the risk of introducing a faulty model into production. And then comes the next step, that is monitoring and logging. Implement logging and monitoring to track the model's performance and health in real time. Tools like Prometheus for monitoring and ELK, Elasticsearch, Logstash, Kibana for logging help in quickly identifying and diagnosing issues in production. And then comes the next step, that is performance tuning. Monitor the model's performance over time. If the model's performance degrades, or if new data shows different patterns, you may need to retrain or fine-tune the model to maintain accuracy. And after this step, there's a step for feedback loop. Set a feedback loop where predictions and outcomes can be compared. This feedback is crucial for continuously improving the model and catching any drift in data or changes in external conditions that affect the model. And after this comes a last step, that is legal and compliance checks. Ensure all the data used by the model in production complies with privacy laws and regulations. This is crucial for maintaining trust and legality, especially when handling sensitive information. So by carefully planning and executing these steps, you can smoothly transition your machine learning model from a testing environment to a fully functional component of a production system. So this was all about the question number 5. Now moving to the question number 6, that would be based on data-driven decision making. And the question is, your company wants to shift towards more data-driven decision making. You have been tasked with developing a strategy to implement this. What steps would you take to ensure that the data at all levels of the organization is utilized effectively to make informed decisions? And what challenges might you face and how would you address them? So you can start answering this by implementing a data-driven decision-making strategy that will require a comprehensive approach to ensure that reliable data is accessible and effectively used across all levels of the organization. And now we can develop and deploy this strategy, and similarly you could tell this strategy to the interviewer. So the number 1 step will be assessing current data infrastructure. Start by evaluating the existing data infrastructure to understand what data is available, how it is stored, and how it is currently used. This assessment will help identify gaps in data collection, storage, and access that need to be addressed. Now we'll move to the next step, that is developing a data governance framework. Implement a data governance framework that defines who can access data, how it can be used, and who is responsible for maintaining its quality. This framework ensures data integrity and security, which are critical for making reliable decisions. Now we'll move to the next step, that is training and empowerment. So train employees at all levels on the importance of data-driven decision making and provide them with the tools and knowledge necessary to analyze and interpret data. This might include training sessions, workshops, and ongoing support to ensure everyone can use data effectively. Now moving to the next step, that is implementing analytical tools. So deploy user-friendly analytical tools that can integrate seamlessly into the daily workflows of employees. Tools like Tableau, Microsoft Power BI, or even advanced Excel techniques can provide powerful data analysis capabilities without requiring extensive technical knowledge. After this, we'll move to the step that would be creating a centralized data platform. Develop a centralized data platform where all organizational data can be accessed and analyzed. This platform should be scalable and secure, providing a single source of truth for the organization. And then we have the promoting a data-driven culture. So foster a culture that values data-driven decision making. Encourage experimentation and learning from data-driven initiatives. Celebrate successes and learn from failures to continually improve the use of data-driven in decision making. And there would be some challenges and solutions for that. So one major challenge we know here is resistance to change, as some employees may prefer traditional decision-making methods. So address this by demonstrating the tangible benefits of data-driven decisions through pilot projects and success stories. So data silos can also hinder effective data use, promote cross-department collaboration, and integrate disparate data sources to overcome this challenge. After that, you can monitor and do continuous improvement. So by systematically implementing these steps, you can transform your organization into one that leverages data at all levels to make informed and effective decisions. And after answering in these steps, you could make the interviewer have a truth and a faith in you that you could make these models. Now move to the next question, that is question number 7, and that is based on handling large data set. And the question is, your project involves analyzing extremely large data sets, potentially exceeding terabytes in size. What strategies would you use to manage and analyze such large data sets effectively? Describe the tools and techniques you might employ. And you could start this with answering that working with large data sets, especially those in terabyte range, presents unique challenges in terms of storage, processing, and analysis. So we'll have a structured approach to handle these challenges effectively. We'll start with the data storage, that would be use distributed file systems. Consider using a distributed file systems like Hadoop Distributed File System, HDFS, or Amazon S3. These systems are designed to store vast amounts of data across many servers, offering high availability and fault tolerance. And then comes the next step, that is data processing. Leverage big data processing frameworks. Tools like Apache Spark are ideal for processing large data sets because they handle distributed computing effectively. Spark can perform data processing tasks much faster than traditional disk-based processing due to its in-memory computing capabilities. And next, we could start with efficient data sampling. So there are many sampling techniques that we can use. So when the data set is too large to handle, even with powerful tools, consider using data sampling techniques to reduce the size to a manageable level without losing significant insights. Ensure that the sample represents the whole data set accurately. And then comes optimization of data queries. Indexing and partitioning. Optimize your data queries by implementing indexing and partitioning. This can drastically reduce the time it takes to perform queries by limiting the amounts of data scanned. And then we can do scalable analytics. And then we'll move to the next step, that is scalable analytics. And in that, we could start with the parallel computing. Use parallel computing capabilities of frameworks like Spark or Dask to analyze data across multiple nodes. This helps in scaling up your analytics operations to handle large data sets effectively. And now we'll move to the cloud-based analytical tools. So consider using cloud services like Google BigQuery or AWS Redshift, which are designed to handle massive data sets and complex analytics with ease. And after this step, we'll move to data cleaning and pre-processing. Here we will automate pre-processing tasks. We'll use automated tools to clean and pre-process data. This includes handling missing values, normalizing data, and removing duplicates, which can be particularly challenging with large data set. And after this step, we'll move to the step that will visualize large data set. So we'll use specialized tools. That tools could be Tableau or Power BI that can handle large data set by aggregating data and using efficient back-end technologies. For more detailed exploration, tools like Plotly or Bouquet can be used as they offer capabilities to interactively visualize large volumes of data. And after that, there would be a step for regular maintenance and updates. That could be continuously monitoring the data quality. As new data comes in, you can continuously monitor its quality. And after this step, you could integrate all these strategies and tools into your workflow, and you can effectively manage and extract valuable insights from extremely large data sets, thereby supporting robust data-driven decision making. And you could answer the whole strategy to the interviewer. Now moving to the question number 8, that is based on optimizing machine learning models. And the question is, during model development, you have noticed that your machine learning model is underperforming. What steps would you take to diagnose the problem and optimize the model's performance? What techniques and tools would you use? So you can answer this by starting with the optimizing. And optimizing a machine learning model that is underperforming involves several steps to diagnose and improve its accuracy and efficiency. And here we will have structured approach to tackle this issue. and you could start this with the number one step, that is diagnosing the problem. Evaluate model metrics. Start by thoroughly evaluating the performance metrics of a model. For classification task, look at accuracy, precision, recall, and the F1 score. For regression task, consider R squared, mean squared error, that is MSE, and mean absolute error, that is MA. And then you can move to the next step. That is, use plots like ROC curves for classification models and residual plots for regression to visually assess where the model is going wrong. After that, we'll move to the next step, that is data quality and quantity check. Inspect the data. That is, sometimes the quality and quantity of data can be the root cause of poor model performance. Ensure the data is clean, well pre-processed, and sufficient. Look for issues like missing values, outliers, or imbalanced classes. And after this, we'll move to the feature engineering step, that would be experiment with creating new features or transforming existing ones to provide better predictive power. And then we have the next step, that is model tuning and configuration. After feature engineering, we'll move to the next step, that is model tuning and configuration. So hyperparameter tuning. Use techniques like grid search or random search to find the optimal settings for your model's parameters. Tools like scikit-learn's grid search CV or randomized search CV can automate this process. And there's a cross-validation that would implement cross-validation to ensure that the model's performance is consistent across different subsets of the dataset. And then we have the next step, that is trying different models. So experiment with algorithms here. If initial models are underperforming, try different algorithms that might be better suited for the problem. For instance, if you started with linear regression and it's not performing well, consider more complex models like random forest or gradient boosting machines. And after this, we have ensemble methods that we can use techniques like bagging, boosting, or stacking to combine the predictions of multiple models to improve overall performance. After this step, we have feature selection that includes reduce dimensionality. Use techniques like principal component analysis, that is PCA, to reduce the number of features, which might help in improving model performance by removing noise and redundancy. And then we have select important features. So use model-based technique to identify and keep only the most important features that impact the outcome. And then comes the last step, that is regular updates and retraining. So here you can monitor and update, that could be continuously monitoring the model's performance over time. As new data becomes available, update and retrain the model to adapt to any changes in underlying patterns. And after that, you could have a consultation and collaboration work with the other teams. And by methodically addressing each of these areas, you can diagnose why your machine learning model is underperforming and can take steps to optimize its accuracy and efficiency. So this was all about question number 8. So let's start with the question number 9, and this is based on handling unstructured data. So the question is, you are given a large amount of unstructured data, including text, images, and videos. What strategies would you use to manage and analyze this type of data effectively? Describe the tools and techniques you might employ. So you can start answering this question by describing that dealing with unstructured data can be challenging due to its lack of predefined format or structure. However, with the right strategies and tools, you can effectively manage and analyze it to extract valuable insights, and there will be an approach how you can do that. So we will discuss the approach here, and starting with the steps. So the number one step will be data categorization and organization. So the number one step in this step will be sorting and tagging. We will begin by categorizing the data into types, that will be text, images, or videos. Use tagging to add metadata, which helps in organizing the data and makes it easier to access and analyze later. Then, and after that, particularly for text data, we'll use natural language processing, NLP. We will employ NLP techniques to extract useful information from text. Tools like NLTK, Spacey, or even more advanced models like BERT can help you perform tasks such as sentiment analysis, entity recognition, and topic modeling. After that, we will do text indexing. We can use Elasticsearch or Apache Solr to index large volumes of text. These tools provide powerful search capabilities and can handle complex queries efficiently. And after that, we'll move to image data. And to structure image data, we'll use image processing. We'll use libraries like OpenCV for basic image processing tasks such as filtering and transformations. For more advanced image analysis, consider deep learning models using frameworks like TensorFlow or PyTorch. And then we'll feature extraction. Apply techniques to extract features from images. such as edges, textures, or key points, which can be used for further analysis or machine learning. And then we'll come to video data. And here we'll do video processing, and we'll use the tools like FMPEG that can be used for basic video processing tasks such as format conversion or extracting frames. For analyzing video content, look at machine learning models that can classify or recognize activities in the video. And after this, we'll move to temporal analysis. For videos, temporal components are important. Techniques like sequence modeling or recurrent neural networks, RNNs, can be useful to analyze sequences of frames for activities or events. And then we'll move to data storage and management. Here we'll use the given volume and complexity of unstructured data and use big data platforms like Hadoop or cloud services like AWS S3 for storage. These platforms can scale up to handle large data sizes and provide the necessary infrastructure to store and retrieve unstructured data efficiently. And then we have visualization and reporting. Custom dashboards that we'll create here. We will develop custom dashboards using tools like Tableau or Power BI, which can integrate different data types and provide a unified view of the analyzed data. And after that, we will do data summarization. Tools that provide summarization capabilities can help in considering large volumes of unstructured data into more manageable and interpretable forms. And after that, we will leverage these strategies and tools and can effectively manage, analyze, and derive insights from unstructured data, which can be crucial for making informed decisions in various applications. And this is the path that you can explore and explain to the interviewer if this question has been asked. Now moving to the question number 10, and that will be based on scaling AI solutions in enterprise. And the question is, your company wants to scale its AI operations from a few initial pilot projects to enterprise-wide implementation. What are the key considerations and steps you would take to ensure the successful scaling of AI solutions across the organization? And what challenges might you face and how would you address them? So you can start answering this question with the scaling AI solutions. You could answer him that scaling AI solutions across an enterprise requires careful planning and strategic implementation to ensure success and alignment with business objectives. And there should be a strategic approach to implement this. So starting with the approach, and the number one step will be strategic alignment. So identify business objectives. Start by identifying the business objectives that the AI solutions are intended to support. This ensures that the AI initiatives are aligned with the company's strategic goals and can demonstrate clear business value. And then comes the stakeholder engagement. So engage stakeholders from various departments early in the process to gather input and build support. This helps in understanding diverse needs and ensures broader acceptance of the AI solutions. And after that comes the infrastructure and technology. So there's an option that is assess and upgrade infrastructure. Evaluate whether your current IT infrastructure can support the expanded use of AI. You might need to upgrade hardware, invest in cloud solutions, or adopt technologies that facilitate AI processing and data handling. And after that, we have standardization of tools. Standardize the tools and platforms used for AI development to ensure compatibility and ease of maintenance across the organizations. And after that, we'll move to data management. So robust data governance, that is to implement a strong data governance framework to manage enterprise data effectively. This includes policies for data quality, security, and compliance, especially important when scaling AI solutions that rely on vast amounts of data. And after that, we will come to data accessibility. So ensure that data is accessible across the organization, but also secure against unauthorized access. This involves setting up secure data lakes or warehouses that centralize data while allowing controlled access. And then we come to the next step, that is talent and training. So build AI competency, that is develop in-house AI expertise through training programs and hiring. So this builds the necessary skills within the organization to develop, manage, and scale AI solutions. And after that, you can also perform cross-functional AI teams. That could be forming cross-functional teams that include data scientists, IT professionals, and domain experts. So this fosters collaboration and ensures that AI solutions are developed with a comprehensive understanding. And after forming these collaborative teams, we'll move to scalable deployment models. So pilot test and phased rollout. Before a full-scale rollout, conduct pilot tests to gauge the AI solution effectiveness and integration capabilities. Based on feedback, adjust, and then gradually deploy the solutions across the organization. And then we have modular and flexible design. So design AI systems to be modular and scalable, allowing for adjustments and expansions as needs and then we'll monitor and do the continuous improvement. So there will be performance metrics that would establish metrics to regularly assess the performance of AI systems. We will monitor these systems to ensure they met expected outcomes and adapt as necessary. And after that, we have next step, that is addressing challenges. So there could be cultural resistance, that there could be employees that would be resisting to the changes, but we have to address this through continuous education and by showcasing successful AI use cases within the organizations. And by carefully considering these aspects and methodically implementing steps, you can successfully scale AI solutions across your enterprise, driving significant business value and innovation. And that's all for question number 10. Now we'll move to question number 11, and that is based on ethical considerations in data science. So the question is, in your data science projects, how do you ensure that ethical considerations are addressed? Describe the steps you take to identify and mitigate ethical risk in your projects. What frameworks or guidelines do you follow? So you could start answering this question with ethical considerations, that they're crucial in data science to ensure that the solutions and analyses do not advertently cause harm or bias. Here's how you can ensure that. So there are some steps and we will discuss those steps, starting with the number 1, that is educate on ethical standards. So stay informed about the ethical standards in data science, such as fairness, accountability, transparency, and privacy. Organizations like the Data Science Association and the ACM have codes of ethics that we refer to as guidelines. And then we have ethical risk assessment. Identify potential ethical issues. That would be at the beginning of each project, conduct a thorough assessment to identify any potential ethical risk, such as biases in data or impact on vulnerable groups. This involves reviewing the source of data, the methodologies used for data collection, and the intended use of the data analytics results. And then we have stakeholder analysis. Engage with stakeholders to understand the diverse perspectives and potential impact of the project. This helps in identifying ethical issues that may not be apparent from a purely technical standpoint. And then we'll move to mitigation strategies. Implementing bias mitigation techniques, we will use statistical and machine learning techniques to detect and mitigate biases in data. This might involve techniques like resampling, reweighing, or using algorithms designed to be fair. And then we have privacy preserving methods. Employ methods such as data anonymization, encryption, or differential privacy to protect individual privacy when analyzing sensitive data. Then we have other methods, that is transparency and explainability. There we have model explainability, and after that coming to documentation and reporting. So we have to maintain thorough documentation of data sources, model decisions, and methodologies. And then we have continuous monitoring and feedback. There you have to monitor outcomes and the feedback mechanism should be applied. And then we have the panels, that is collaboration and advisory panels. There we have ethical review boards. So for complex projects, setting up or consulting with an ethical review board can provide oversight and diverse perspectives on the ethical implications of project methodologies. So by proactively addressing ethical considerations through these steps, you can ensure that your data science projects uphold high ethical standards and positively contribute to society while minimizing harm. So this was all about question 11. Now moving to question number 12, that is based on time series forecasting for business decisions. So the question number 12 is, you are tasked with forecasting monthly sales for a retail company using time series data from the past 5 years. What steps would you take to prepare and analyze this data to make accurate forecast? What specific tools or techniques would you use and why? So we can start answering this by time series forecasting. And we could address them that it's a powerful tool for predicting future events based on past data, especially in business context like retail sales. So we will have a structured approach here, and we'll start with data collection and cleaning. First, we will gather data and ensure that you have collected all relevant data, including monthly sale figures from the past 5 years, and also considering including external factors that might affect sales, such as economic indicators, holidays, and promotional activities. And then we'll proceed to clean data. We'll check for and handle any inconsistencies or missing values. And then we have data visualization. Here we will plot the data. We'll use plotting libraries like Matplotlib or Seaborn in Python to visualize the data. This will help in identifying patterns, trends, and seasonality. And then we have decomposition of data. So there's a seasonal decomposition, and we'll use statistical techniques to decompose the data into trend, seasonally, and residuals. So this can be accomplished with tools like the seasonal decompose function from the stats models library in Python. and we'll understand these components separately and can improve the accuracy of our forecast. And then the next step is model selection and forecasting. So there are two models, that is ARIMA and SARIMA models. So we have to choose appropriate forecasting models based on data's characteristics. For instance, ARIMA, that is autoregressive integrated moving average. It is effective for non-season data, while SARIMA, that is seasonal ARIMA, that is suitable for data with seasonal patterns. And after choosing the model, we'll move to cross-validation. We will implement time series specific cross-validation techniques like time-based splitting to evaluate model performance. And this will ensure your model generalizes well on unseen data. And then we have model fitting and diagnostics. We will fit the model, that is by using the Cynimax class from stat models that will fit your model to the data. And then we will carefully select parameters based on AIC, that is Archaic Information Criterion, that scores or thorough grid research technique. And then we can do the diagnostics and forecast and validation. And after forecast validation, we'll move to iterative improvement. So there's a feedback loop that should be mandatory, and there should be a regular update for the model with new sales data and refining the model as needed. So this continuous improvement cycle helps adapt to changing patterns in sales data. And by following these steps and using these tools, you can create robust forecasts that help the retail company plan better and make informed decisions. So this was all about question number 12. Now moving to question number 13, that is based on customer segmentation using machine learning. So the question is, you are given a data set containing demographic and purchasing behavior data for a group of customers. Your task is to segment these customers into distinct groups based on similarities in their purchasing behavior and demographics. So what steps would you take to perform this segmentation, and can you provide a sample Python code snippet to illustrate the initial stages of data handling and model application? So we can start this by explaining customer segmentation, that it's a powerful approach to tailor marketing strategies and improve customer service by identifying distinct groups based on their behavior and characteristics. And here also we have a detailed approach for this task. So we'll start with number one step, that would be data exploration and pre-processing. So there will be initial exploration, that is beginning by examining the data set to understand the features available such as age, income, purchase frequency, etc. Then we'll look for missing values or anomalies and decide how to handle them. That could be using imputation. And then we'll move to feature engineering. We will create new features that might be useful for segmentation, such as customer lifetime value or average transaction amount. We will also use normalization, that is normalize the data to ensure that one feature doesn't disproportionately influence the model due to its scale. We'll use standard scaling or min-max scaling as appropriate. So then we'll come to the next step, that is choosing the segmentation technique. And here we have k-means clustering. So this is a popular method for customer segmentation. Here we will decide on the number of clusters by using techniques like the elbow method or silhouette analysis to determine the optimal cluster count. And then we have model implementation. And in that we will use data preparation, and we'll prepare the data by selecting the relevant features and applying any final transformations. And then we have model fitting. We'll fit the k-means clustering model to the data and evaluate and interpret analyzing clusters. And after analyzing clusters, we'll move to the next step, that is strategic insights. We'll provide actionable insights based on cluster characteristics such as targeted marketing strategies for each segment. And then we have iterative refinement, that is feedback incorporation, and we'll use business feedback to refine the segmentation. If additional data becomes available, incorporate it to enhance the model. And now we'll see the sample Python code. So for this, first we'll import the libraries and modules. As you can see on the screen, we have imported Pandas, random forest classifier, train test split, standard scaler, classification report. And after that, we'll load the data. And for that, we have used the Pandas to read the data, that is read underscore SSV. And after that, we are processing the data, that is data pre-processing. We are handling missing values and using the forward fill or FIL to fill missing values in the data set. And then we are featuring scaling, that is normalizing the selected features, that is feature 1, feature 2 and feature 3 using standard scaler. And then we'll move to the next step, that is data splitting. We'll split the data set into training and testing sets. So that test size equal to 0.2 parameters specifies that 20% of the data will be used for testing. And then we'll train the model we'll initialize and train a random forest classifier with 100 trees and a random state for reproducibility. And then we'll evaluate the model. We'll make predictions on the test set, that is x underscore test, using the trained model, and print a classification report showing precision, recall, F1 score, and support for each class. So this code demonstrates the process of loading, pre-processing, training, and evaluating a machine learning model, that is random forest classifier, for predicting equipment failures in a manufacturing plant. The use of techniques such as data pre-processing and splitting along with the random forest classifier highlights a standard flow for building predictive maintenance models. So this was all about the question number 13. So now moving to the question number 14, that is based on predictive customer churn. And the question is, you are tasked with developing a model to predict which customers are likely to churn from a subscription service. So what steps will you take to build this model, and can you provide a sample Python code to illustrate the data preparation and model training process? So we'll start answering this question about depicting what is predicting customer churn. So predicting customer churn is crucial for businesses to implement retention strategies proactively, and we'll have a detailed approach for building a predictive model for this purpose, starting with data collection and exploration. And in this, we will collect data, and after that, we will perform the exploratory data analysis, that is EDA. We will perform an initial analysis to understand patterns and trends. And then we have feature engineering. We will create new features and derive new features that might influence churn, such as change in usage pattern or service upgrades. And then we'll handle the missing values if we found any. And then we'll encode categorical variables. We'll use techniques like one-hot encoding or label encoding for categorical variables. And then we have scale features to normalize or standardize numerical features to ensure they contribute equally to the model's performance. And then we'll select the model, that is, we'll choose the appropriate model and start with for the knowing handling binary classification task. That could be with logistic regression, random forest, or gradient boosting machines. And after selecting the model, we'll train the model and evaluate it. So fit your model on the training data, and after that, evaluate the model using appropriate metrics like accuracy, precision, recall, F1 score, and ROC to gauge its performance. And then we'll optimize the model using hyperparameter tuning. We'll optimize the model parameter using grid search or random search to improve performance. And then we have feature importance, that is, analyze and rank features by their importance in predicting churn to refine the model further. And then the last step is deployment and monitoring. We'll deploy the model. Once validated, deploy the model into a production environment where it can predict real-time churn. So after deploying the model, regularly monitor the model to ensure it remains effective over time as new data comes in. So now we'll see the sample Python code for this example. So starting with the importing of libraries, we will import Pandas, NumPy, Scikit-learn, sklearn, TensorFlow, and the TensorFlow keras and callbacks. And after importing the modules, we'll start with data loading. We'll load the dataset from a CSV file named equipment_data.csv, and that too with the Pandas data frame. And after that, we'll do the data pre-processing. We'll handle missing values, and for that, we'll use forward fill to fill missing values in the dataset. And then we have feature scaling that will normalize the selected features, that is feature 1, feature 2, feature 3 using standard scaler. And after that, we'll use the data splitting. We'll split the dataset into training and testing sets, and the test size will be equal to 0.2. And this parameter specifies that 20% of the data will be used for testing. And after that, we'll start with building the model. First, we'll see sequential model that initializes a sequential model technique. And then we have dense layers that adds 2 dense layers with 64 units and ReLU activation function. Then we have dropout layers that adds 2 dropout layers with a dropout rate of 0.5 to reduce overfitting. After that, we'll do the model compilation. We'll compile the model using the Adam optimizer and binary cross entropy loss function for binary classification. And there will be an early stopping that will define an early stopping callback to stop training when the validation loss metric has stopped improving after 3 epochs. And after training the model, we will evaluate the model, and evaluating the model on the test data and print the loss and accuracy metrics. So this code demonstrates the process of loading, pre-processing, building, compiling, training, and evaluating a deep learning model using TensorFlow and keras for predicting equipment failures in a manufacturing plant. So the use of techniques such as data preprocessing, dropout, regularization, and early stopping helps in building a robust deep learning model for predictive maintenance. So that's all with question number 14. Now we'll start with question number 15, that is based on deep learning in NLP. And your question is, you are tasked with developing a sentiment analysis model using deep learning to understand customer opinions from reviews. So what steps would you take to build this model, and can you provide a sample Python code snippet to illustrate how you would pre-process data and train a simple deep learning model? So we'll start answering this with sentiment analysis. That sentiment analysis using deep learning allows businesses to gauge customer sentiment from text data like reviews or comments effectively. And we'll have a detailed approach for building a sentiment analysis model. We'll start with data collection and cleaning. We will collect the data, gather a substantial data set of text reviews and their associated sentiments, typically labeled as positive, negative, or neutral. And then we'll clean the data, pre-process the data by removing noise such as HTML tags, special characters, and stop words. And we'll normalize the text by converting it to lowercase. And then we have text pre-processing. We'll convert text into tokens, words, or phrases. And then we have vectorization that transforms tokens into numerical format using techniques like word embeddings or TF-IDF, that is term frequency in words document frequency. And then we'll use the padding. And then we have the option of model selection. We'll choose a model architecture based on a basic approach and use a RNN or more advanced architecture like LSTM, that is long short term memory, or GRU, that is gated recurrent units, which are effective for sequence data like text. And then we have model training. We'll compile the model, define the model architecture, and compile it with the loss function suited for classification like categorical, cross entropy, and an optimizer like Adam. And then we'll train the model, we'll fit the model on our pre-processed data. We'll evaluate and optimize it. Evaluating model performance, here use the metrics such as accuracy, precision, recall, and F1 score to assess the model. And then we have hyperparameter tuning. We'll optimize the model by adjusting parameters like learning rate, number of layers, and units per layer. And then coming to deployment. We'll deploy the model and integrate the model into the existing review processing pipeline so it can automatically classify new reviews. So let's see the sample Python code, and we'll have a basic approach for that. Here we'll import NumPy, TensorFlow, sequential, embedding LSTM, dense dropout. So embedding converts positive integers, that is indexes, into dense vectors of fixed size. And LSTM, that is long short term memory layer, that is used for learning dependencies in sequence data. And then we have dense, that is a regularly densed connected NN layer. And then we will import pad underscore sequences. And after that we have the data set and the sample text data representing customer reviews that will store in variable text. And then we have labels that has binary labels indicating sentiment, 1 for positive, 0 for negative. And now we'll start with the pre-processing of data. Here we have declared that tokenizer. We will initialize a tokenizer that will help only the top 1000 most frequent words. And then we have fit underscore on underscore text, that is update the internal vocabulary based on the list of text. It essentially creates a dictionary of word to index pairs. And then we have text to sequences that will transform each text in text to a sequence of integers. And then we have pad sequences that will ensure all sequences have the same length by padding shorter sequences with zeros up to the maximum length. And then we'll start building the model. Here we have sequential model that will set up a linear stack of layers. And then we have embedding layer that will map each word index to an embedding vector of size 64. So the input length is set to 10, that is the length of the input sequences. Then we'll start with LSTM layers. So 2 LSTM layers are added. The first one returns sequences to allow the next LSTM layer to process these sequences. And after that we have the dropout layer that applies dropout with a rate of 0.5 of the first LSTM layer to reduce overfitting. And after that we'll come to dense layer that has output of a single scalar that represents the predicted sentiment and using sigmoid activation to output a probability. And now we'll start with model compilation and training. So we'll configure the model for training and we'll use binary cross entropy as the loss function that is suitable for binary classification, and the Adam optimizer and tracks constantly accuracy as a metric. And then we have the fit that trains the model for a specified number of epochs, that is iterations or the entire data set. And then we'll predict the model, that is after training, the model can predict the sentiment of the reviews in the data set. This is useful for checking how the model performs on the training data itself. So this breakdown explains each step of the coding process, detailing how the data is prepared and how the model is configured. And then we'll compile it and use for training and prediction. So its detailed explanation should help in understanding how to implement a simple LSTM model for sentiment analysis in TensorFlow. Now moving to the question number 16. So let's start with question number 16, that is based on anomaly detection in transaction data. So the question is, you are tasked with identifying unusual transactions in a company's financial data that might suggest fraudulent activity. So what steps would you take to develop an anomaly detection model, and can you provide a sample Python code snippet to illustrate how you would pre-process the data and apply an anomaly detection technique? So we'll start answering this with anomaly detection technique. That is, anomaly detection is essential for preventing fraud by identifying transactions that deviate significantly from typical patterns. And now we'll see the structured approach to building an anomaly detection model for transaction data. We'll start with data collection and cleaning, and we'll collect all the compiling transaction data, which should include details like transaction amount, time, user ID, and transaction type. Then we'll move to feature engineering and develop features that capture the essence of transactions, such as time of day and the day of the week. And then we have data normalization. We'll use scaling techniques such as min-max scaling or standardization to ensure that the model is perfectly normalized. And then we have choosing the anomaly detection technique. So here we have to choose the technique which is effective for high dimensional data sets and works for isolating anomalies instead of profiling normal data points. After choosing the anomaly technique, we'll train anomaly identification. We'll fit the chosen model to the data, and the anomalies that would have been chosen will be those transactions that the model identifies. And after this, we come to the last step, that is review and action. Here we have manual review, that is transactions flagged as potential anomalies should be reviewed manually to confirm fraudulent activity. And then we have continuous improvement. That is, we can regularly update the model with the new data and feedback from the review process to improve accuracy. And now moving to the prediction, that is after training the model, we can predict the sentiment of the reviews in the dataset. And this is useful for checking how the model performs on the training data itself. Now we'll see the Python code to see how you can set up this model for anomaly detection. We'll start by importing the libraries and module, and after that we'll load and prepare data. That is, we'll load transaction data from a CSV file into the Pandas data frame. And after that, we'll convert the transaction time column to date time format, which allows the extraction of additional time-based features. And after that, we'll perform feature engineering that will extract the hour of the day from the transaction time column. This feature can be important as transactions occurring at unusual hours may be indicative of fraud. And then we'll move to the normalization of data. This will apply standard scaling to the amount and hour of the day feature. This normalization process involves subtracting the mean and dividing by the standard deviation for each feature, ensuring that the feature contribute equally to the analysis and improving the performance of many machine learning algorithms. And after that, we'll start with anomaly detection with isolation forest. That's a technique. We will initialize an isolation forest model with 100 trees, that is n estimators equal to 100, setting the proportions of outliers, that is concatenation, to 1% of the data. So this parameter is crucial as it influences the threshold of marking an observation as an anomaly. Then we'll fit the model to the scaled amount and hour of the day data and predict the anomaly status for each transaction. And then we'll start with filter and display anomalies. We'll filter out transactions identified as anomalies, that is anomaly equal to -1. We'll display these transactions which can be reviewed manually to determine if they represent actual fraudulent activity. So this code snippet provides a systematic approach to detecting anomalies in transaction data, leveraging the isolation forest algorithm's ability to handle complex and high dimensional data set effectively. So the pre-processing steps ensure that the data is appropriately formatted and normalized for optional model performance. So this was all about question number 16. Now moving to question number 17, and that is based on integrating machine learning models into web applications. And your question is, you have developed a machine learning model to predict real estate prices based on various features like location, size, and amenities. How would you integrate this model into a web application to allow users to get real-time price predictions? Can you provide a sample Python code snippet to illustrate how you would prepare the model for integration and handle user requests? So starting with the approach, that is integrating a machine learning model into a web application, this will involve several steps to ensure the model is accessible and perform well in a live environment. So here's how you can approach this task. We could divide into steps and we'll start with number one step, that is model preparation. We'll finalize and save the model. So once your model is trained and validated, save it using a format that can be easily loaded into a web application. So Python's pickle module or TensorFlow's save model format are commonly used for this purpose. Then we can use web application backend setup. For this, select a suitable web framework. So Flask is popularly known for its simplicity and effectiveness in integrating Python-based machine learning models. And after that, we'll develop the API. After developing the API within your Flask app, that you can receive user inputs for model features, load the model, make prediction, and return the result. And after this, we'll develop the UI. We'll design a user-friendly interface. We'll create a simple and intuitive UI that lets users input the feature like location, size, and submit them for prediction. And after that, we'll move to the deployment phase. We'll use a cloud platform like Heroku, AWS, or Google Cloud to deploy your Flask application. And then we have the maintenance and updates. We'll monitor and update regularly for the performance and use the model as needed based on user feedback. So now moving to the Python code and see how this model can be created. So here we'll start importing the libraries and module, and we are using Flask, Pickle, and JSONify. And we will start with app initialization. We'll initialize a new Flask web application. That would be a special variable which gives Python files a unique name to differentiate between them when they are imported into other scripts. And after that, we'll load the model. So loading a pre-trained machine learning model from the file system. So this model is assumed to be saved in the same directory as this script. So the model is loaded in RB mode, which stands for read binary. And after that, we'll move to API route and prediction function. So we will define an API endpoint at predict that listens for post request. This is the URL that the front end of the web application will call to send data to the backend. And after that, we'll start with predicting the function. And here we have extract features that retrieves data sent into the JSON format from the post request. That is request.get_JSON, and the force we have set it as true here. And forcefully formats the request data into JSON, ensuring compatibility. And then we'll extract the relevant features, that is location, size, and amenities from the JSON object and store them in a list as expected by the model. And after preparing the features, we'll make the prediction. We'll use the loaded model to make a prediction based on the provided feature. And then we have the return prediction method. Here we will convert the prediction result into JSON format using JSONify and send it back to the client, and this will ensure that the response can be easily handled by the client application. So this was all about the question number 17. Now moving to the question number 18, that is based on analyzing. And now we'll move to the question number 18, that is based on analyzing geospatial data. And your question is, you are tasked with analyzing geospatial data to help a city improve its public transportation system. The data includes GPS coordinates of bus stops, ridership numbers, and traffic patterns. What steps would you take to analyze this data, and can you provide a sample Python code snippet to illustrate how you might visualize bus stop location and ridership? So you can start answering this question, that geospatial data analysis can provide critical insights into how effectively a public transportation system serves its city and guide improvements. And there's a detailed approach for this, and we can start with data preparation. And in this, we will do data collection and data cleaning. And after this step, we will move to the next step, that is exploratory data analysis. And in this, we will have statistical summary, we will generate descriptive statistics, and then we have correlation analysis. And after moving that, we have geospatial visualization, that is mapping bus stop. We will plot the locations of bus stop on a map to visually assess their distribution across the city. And after that, we have heat maps that will create ridership data to identify hotspots and areas with potential service gaps. And after geospatial visualization, we'll move with spatial analysis. We have proximity analysis that will analyze the proximity of bus stop to key areas like commercial centers or residential areas. And now moving to the fifth step, that is optimization and recommendation. So we'll have a route optimization that will suggest modifications to route based on traffic patterns and ridership demand, and the policy recommendations that will provide actionable recommendations for improving bus frequencies. Now moving to the sample Python code where we can define this model and use it accordingly. And here we will start importing the libraries and modules, and here we will start with importing GeoPandas and Matplotlib.pyplot. And after importing, we'll start with data loading. So we will declare a variable bus underscore stops and load the bus stops data from a shapefile. So shapefiles are popular geospatial vector data formats for geographic information system software. And then we have the ridership that will load ridership data from a CSV file which includes columns for longitude, latitude, and ridership levels. And after that, we'll create geodata frame that will convert the ridership data frame into a geodata frame. And this step involves creating a geometry column from the longitude and latitude columns. And then we have the plotting one. Here we will plot the graphs that would be figures and axes and create a figure for the single subplot with a specified size that is 10 cross 10 inches. And then we have city underscore map.plot. It is assumed that there is a base map of the city loaded as a geodata frame named city map. This is plotted first with the light gray color to serve as a background for the other layers. So this was all about question number 18. Now moving to question number 19, that is based on predictive maintenance using machine learning. And the question is, you are tasked with developing a predictive maintenance system for a manufacturing plant that relies heavily on automated machinery. So the data available includes machine operational parameters, maintenance history, and failure incidents. What steps would you take to develop a predictive model, and can you provide a sample Python code? So you can start with predictive maintenance that is essential in manufacturing as it helps prevent equipment failures, reducing downtime and maintenance cost. And here you would have a detailed approach or predictive model for this, starting with data collection and integration. Then you can do EDA, that is exploratory data analysis, and then we can perform feature engineering and then move to data pre-processing task, and then the selection model and training. And after that, we have model evaluation and deployment technique that we can do for the model using appropriate metrics such as precision, recall, and F1 score. So this was all about question number 19. So now move to question number 20, that is based on personalization using machine learning. And your question is, you are tasked with developing a machine learning model to personalize content recommendations for users on a media streaming platform. The data available includes user demographic details, viewing history, and ratings. So what steps would you take to build a model for personalized recommendations? And can you provide a sample Python code for that? So you can start answering this with creating a personalized recommendation systems. This would be essential for engaging users by providing content that is relevant to their interest. And there will be a systematic approach for personalized content recommendation. We'll start with data collection and integration. And after that, we'll perform EDA, that is exploratory data analysis. And then we have feature engineering. In this, we'll interact features, and the temporal features will include time-based features to capture trends and seasonality in viewing behavior. And then we'll select the model, that is by collaborative filtering and hybrid models. And then we'll train the model and validation and implement and monitor them.
And with that, we have come to the end of our course. If you have any doubts or questions, ask them in the comment section below. Our team of experts will reply to you as soon as possible. Thank you and keep learning with Simplilearn.